So for significant figures, it's related very much to uncertainty. And I love this this drawing, this picture here of Keanu Reeves. You know, you're supposed to round something to 4 sig figs. What do we mean by this? I think a lot of people spend too much time worrying about, you know, how many significant figures to use. A good rule of thumb is to actually use the least good one. So what I mean by that is if you've been given a whole bunch of different values. So this has to do with making measurements. So let's just say, or, you know, using values on, you know, on exams. So let's just say you have different choices. You have like 2.0 is one of the values you're given, and maybe like 17.458, and maybe you're given like, yeah, just these two, for example. Let's just say these are the two numbers you used in an equation in order to actually solve something. Then what you would do is when you're finished with your answer, if you got an answer that had a whole bunch of different digits like this one right here, like this 17.458, you would actually use only 2 right here. So you'd only use these 2 right here. You'd have something point something else. That's the main thing really to worry about as far as significant figures go. Just use the least good one. I think that's sort of a good rule of thumb here. So what do I mean by significant figures and uncertainty? When you're actually making a physical measurement, so let's just say you measure like the length of my, I don't know, this right here, whatever this is. Let's just say it's the length of, I don't know, an eraser or something like that. When you make a physical measurement, that means that you're going to measure it with something, some device, and that means there's going to be some uncertainty on the actual measurement. In other words, you don't know it exactly. You might say it's like 5.8 centimeters, but it's not exactly. It's plus or minus a little bit. So this plus or minus implies the sort of shaky nature of measurement. So for example, I just want to focus on one thing, especially for the IB physics here, is usually the uncertainty is just one non-zero number. So what do I mean by that? I mean that, you know, later on when I show you, you know, in videos how to actually calculate uncertainties, you might end up calculating something with a whole bunch of digits. So for example, let's say you get something that says like plus or minus 0.052 like I have here. This implies that you're so certain about your uncertainty, so which is a little bit weird and counterintuitive. So what I like to tell you is for this one here, what I would probably do is think about this and say, okay, you just need one non-zero number. So in this case right here, I would just need the 0.05. So that would mean I would have to actually round this right here. My uncertainty itself, I need to make it, I'm only allowed one non-zero number. I'm allowed zeros to the left, I'm allowed zeros to the right, but usually that's how we write uncertainty. So in this case right here, I would write 0.05, and I would think about rounding. Do I have to round that number up or down? In this case, I don't. So do you see, the first thing I always check for is, does the student have one non-zero number? So in this case right here, yep, good. So that's a properly written uncertainty. Let's say you did another calculation and you got this like plus or minus 15.29. What do you do there? You're only allowed one non-zero number. So what I would say is you'll probably have to round on this to tens digits, so to speak. And that means I would either make it 10 or maybe 20. And it depends how you like to do your conventions here, but most people will say that a 5 afterwards will make it round up. So in this case right here, you'd end up with plus or minus 20, whatever these units are. And the reason I know this is okay is because, see, I've only got one non-zero number. What I like to tell students, we go more detail like this. I say, make a non-zero number sandwich. So if there's a whole bunch of, things in between like this right here, you would do this. That would be sort of for the significant figures. But I wouldn't worry too much about it. The key thing as far as your exams go is knowing how it is to actually write these uncertainties. So first of all, make your uncertainty a non-zero number. Next, once you know the uncertainty is a non-zero number, it's the uncertainty that drives how many significant figures you should use, not the other way around. So I'll give you a few examples. So let's just say here, I just wrote out a couple here. So let's just say we have, let's say you did a measurement and you actually measured through some device or something like that, some length, let's just say, is 2.128427 meters. You measured it somehow super accurately according to your little device that you used. But your uncertainty is 0.001 meters, let's just say. So first of all, you need to check, I want to write down this value. And let's just say I want to write down the length. Let's just say I want to say, all right, the length is going to be, this number, this 2 point whatever. Don't just say this plus or minus 0.001 and say you're done. Because you see, there's a problem now with how many significant figures you're allowed to use. Or in this case, I like to think of it as how many digits you can use, how many numbers you can use to represent this. You're always allowed to use you're always allowed to use scientific notation. So what I would do here, for example, is look, okay, first of all, is my uncertainty one non-zero number? Yes, it is. Now, do you notice that it's the third digit after the decimal? See that? After the decimal, it's 1, 2, 3. So that means, remember I showed you before here, it's the uncertainty that tells you how many significant figures to use. So in this case right here, I'm allowed 3 after the decimal. So I have to round here. So what that means is I can say my value is L equals 2.128. I have to stop there. I would round up or down. In this case here, I just leave it. Plus or minus 0.001 meters. Let's just say this could be a measurement. And this actually could be my answer. This could be my final answer. I could say, all right, that's it. Because if you're checking if someone did it right, you first check, is it one non-zero number? Yes. Are you rounding on the same digits? In other words, 3 after the decimal, 3 after the decimal? Then you got it. Let's look at the other one here. Let's say you make a measurement of force, and somehow you measure it or you calculate it. You know, when you're actually using your calculator, you actually type it all in, and you end up with a number of 259.4, right? Because that's a measured thing you can get. But your uncertainty is supposed to be plus or minus 10. So what do you do? This is for newtons. Again, you don't just say plus or minus 10 right here, right? You don't actually say just that, right? You can't just say that. You have to write it properly. So what I would do is I would say F equals, and think about this, 10, that's rounding in the sort of tens digit. So that means I have to round here, you know, because this is 259. So that means I would have to round here. So I write my 2, and my 5, however, though, will round up. Do you see that? Because the 9 makes it actually round up. So that means it becomes that 6. And I'm only allowed a 2 and a 6. I can't use any other numbers to represent it. The rest of it just has to become zeros. In this case here, it's just going to be 0. Now, I don't say 0.000, something like that. I'm not allowed that many digits. So I just say 260 plus or minus 10 newtons, and I'm good to go. So this right here could be my answer. So I hope this explains it. It's a really, really simple concept, but a lot of people mess it up. And just so you know, this shows up, this is immensely important for paper 3. Because the first part of paper 3, you have to do a lot of this sort of calculations, and it really helps to be able to understand how to actually represent your answer. These definitions of accuracy, precision, and error become really important, especially on paper 3. In the first part of paper 3 especially. You know, in the first part, it's called section A, where you've got all these questions about the prescribed experiments. So in this, those definitions, especially about error, become really important. And I like this Star Wars reference here about, you know, only the Imperial Stormtroopers are so precise. I mean, these definitions themselves aren't actually that difficult, but you need to know them really well in order to actually succeed in your exams. So let's look at the word accurate. The word accurate, what we mean is a small systematic error. And I'm going to explain the word systematic error as well. But it means they're close to the real value, the quote-unquote real value. So what do I mean by that? Let me see if I can do, just paste something here. Yeah, good. So let's just say you're doing, I mean, this is the old trope. Everybody uses archery as an example, but it actually works. So let's just say I'm doing a whole bunch of archery here, and I want to see something that's accurate. So a small systematic error. That means they're close to the real value. So in this case right here, let's see something then that is, let's see, I'll try to draw on it here. So let me say something right here that is, let's just say like this here. So really close to the real value. So this one right here, for example, if I shot a whole bunch of arrows right here, do you notice they're close to the real value? In other words, in this case, they're close to the center or whatever they're supposed to be. So they're pretty close to this right here. So we could say these are accurate. Now, I'm just going to show you the contrast just so we can actually compare these words. We've got the word after that called precise. And there what it means, there's a small random error. And what I mean by that, they're close to each other. So what I'm going to try to do again is paste something here. Yeah, there we go. Do another one. So I'll show you something else then that's small random error. Do you know, by the way, I'm going to define them a little bit clearer too. I'm just going to start with this. So let's do something then as a small random error. Let's say I shot a whole bunch of them, but they're all really close to each other. Maybe they're all right here. Whole bunch of them. They all hit right over here. In this case here, you could say these are here are precise. Now these words accurate and precise, something can be accurate and precise, it can be accurate and not precise, and so on. So now take a look at this. So again, precise means close to each other. They're grouped close together. They don't necessarily have to be where they need to be. So in this case, these are precise, but you could say they're not accurate. Do you know how you can say that? Because if they are accurate, they'd also be close to the center. In this case here, they're accurate because they're close to the center. And it depends on if you want to consider this close to each other or not. Then, it's a bit of a dodgy definition. In this case right here, you could say, but not precise, because you could say that, well, they're not totally close to each other. Again, it just depends what you mean by close, doesn't it? So maybe we'll go into these definitions a little bit more detail. So systematic error. What do we mean by a systematic error? It means that everything is off by a certain amount. So in this example back here, I said there's a small systematic error. In other words, things weren't off by very much. Whereas over here, can you see you're trying to shoot the center of the target, but instead you're way off all the time. So in this case right here, everything is off by a certain amount. And what I mean by that is that, more experiments, they won't help. You probably need to recalibrate your experiment. And an example of that could be, let's see here if I can get a little pen going here. So let's just say you're doing an example of something like Hooke's law, if you know that one, where you have a whole bunch of data points here. So let's just say I have some things here. I'll draw some error bars here. So I have one here and I have another one here. Let's just say, so I'm just drawing myself some data points with some error bars. Like this right here. And if I draw a line of best fit through this bad boy, let's see here what I would get. Let's see if I can draw that. That would be something like this, right? Not exactly, but something like that. So if you take a look at this, you can say, all right, so there's my points, there's my uncertainty, so my error bars on those points. But if you know about Hooke's law, at 0, this would be like a spring. If you've got a spring and you attach some weights to it or some masses to it, as the spring extends, that'll be the force on it. So the force on it, as it increases, the extension will increase. So in this case, that's what this would be a graph of. And I hope it makes sense that at 0 displacement, it should be for 0 force. So in other words, this thing, you're expecting it to pass through 0, 0, but it's not. So in this case right here, can you see that right here? Whoa, I didn't mean to do that. Don't mess it up there, Mitch. There we go, like this. This one right here, do you see we're off by that same amount? We're always off. So we're off by this amount. So this means we have a systematic error. In other words, every value you did is off. It's sort of messed up by the same amount. So if you just repeated it a lot, it wouldn't change. You'd still just be off by the same amount. You need to recalibrate. You need to maybe remeasure things in order to fix it. By contrast, a random error, this is where the data points don't match the others. So maybe I'll do an example of that here. So I'll just show you some data points here. So let's just say I'm drawing some data points. So here's a data point, let's just say, and here's another data point here. I'm just drawing some data points with some error bars here. And then I have a point that's over here. Let's just say something like this. I'm drawing it poorly, of course. But do you see that? I mean, if I drew a whole bunch of data points like this here, you'd see that, most of them match, and most of them seem to follow this dotted line, or this line, right? Most of them seem to match. But there's this one weirdo point here. There's one that just doesn't really fit. That is your random error. That one right there is the one that's messing everything up. You probably made a mistake. Probably. Or just something weird happened. In this case, more experiments will help. You see that? Because if you do this, more experiments are going to help because you're going to reduce your random errors. So for systematic errors, more experiments don't help. You need to recalibrate. But if you have random errors, more experiments will actually help. And then I have an example. Oh no, wait, not an example yet. Really important, actually. Yeah, I'm really glad I checked this. Line of best fit. Oh my God, this is so important. Does it need to be a straight line? In other words, if you're looking at something like, you've got some sort of graph. It doesn't matter what it's a graph of, right? It could be, I don't know, potential difference versus the current, let's just say. And you would expect to be a straight line, maybe, but I don't know. Maybe you get data points that do, something like this right here. And maybe then, I don't know, maybe it does something different. Maybe it's something like this. So the question is, does it have to be a straight line? And maybe I have another point maybe up here like this right here. Well, not quite like this, but maybe way up here like this. There we go. So the question is, does it have to be a straight line? No. So that's the answer for sure. It's no. It just has to fit through the error bars. That's the key thing. In other words, if I was trying to draw a straight line through this right here to make it pass through all the error bars, I probably can't. Because at the bottom right down here, all the way up to the top right here, I probably can't make it pass through all the error bars. So if that's the case, you can actually state it's not a linear fit. You know, this right here, for example, is something that's going to be a curve. That might be my line of best fit. So lines of best fit do not have to be straight. They just have to pass. This is the key thing. They need to pass through the error bars. That is the key stipulation here. This is what has to happen. They gotta pass through the error bars. As long as they do, it can be whatever curve you need. Now I have an example. So let's just say we're given an archery target and you're given this right here. And you might say, do you have, because before I define these as accurate versus precise, let's see, this was, for example, a question very, very recently on an exam on a paper 1. This for SL and HL. And the question had been asking, what kind of uncertainties do you have here? So try to think about, do you have random uncertainties? Do you have systematic? Do you have neither? Or do you have both? Think carefully about them now. So instead of accurate and precise, you got to think about them as random versus systematic. First of all, I can say, so here's the answer. The answer is, let's see. First of all, we have systematic errors. Do you know why we have those? That's because they're off from the center. Do you notice? Like they're not at the center. They're off a little bit, aren't they? So we have systematic. How about random? Do we have random errors here? I would say yes, we have random errors because they're also not so close to each other. Do you notice they're a little bit spread out? Had they been all tightly grouped, then you could say there's very little random errors. So in this case, I would say, yeah, you have plenty of systematic errors and you have plenty of random errors as well. In order to calculate uncertainties, it's not as simple as it looks. That's the thing I really wanted to show you today. So if you're going to actually try to calculate them, you need to understand a little bit about how to work with these uncertainties. I'll give you a really, really simple, dumb example, and I'll show you how to use it in 2 different methods, and after that, I'll show you a real example from an exam. So let's just say you're doing a measurement. So you're measuring a distance here. And you're measuring your distance, let's just say is, so I'll just maybe rewrite it like this. Maybe it's a bit easier here. So I'll say, so your distance is 10 meters, but your uncertainty on your distance is plus or minus 1 meter. And you have the time is 5.0 seconds, but the uncertainty on your time is 0.2 seconds. I think it's maybe clearer to have it written big like this. Okay, so first of all, it's a good idea to double check that your uncertainties are correct. Is it one non-zero number? Yep, good. And do the digits match? Are you rounding on the sort of ones digit? Yeah. And here it's one non-zero number as well, the 0.2, and they're both being rounded. They're both sort of, you get 1 digit after the decimal for both of them. So that looks okay. There's nothing sort of weird about this. You're measuring distance and a time, and you want to know the speed. Now, if you remember just simple dumb equations for speed, speed is just distance over time, right? Or displacement over time if you want velocity. Okay, so then you can say, all right, then fine. I mean, speed then is just d over t, so that's just 10 over 5. So that's just 2, right? It's just 2 meters per second, right? But is it? Here's the problem. In this kind of example, if they're giving you uncertainties, you're fully expected to figure out plus or minus what do you do here. So how do you actually do this? And remember what I showed you before. If you've done this like this, remember it's the uncertainties that then drive the number of significant figures you're allowed to use here. So we don't know if we need to go 2 or 2.0 or 2.00 or 2.000 or I don't know. So let's just see what we get. So I'm going to show you 2 different methods to do this. So the first method is called the largest smallest method, or at least that's what I like to call it. What I mean by that is it's a really, really simple, by the way, I just cut and paste the same example just so we have all the numbers there. So the largest smallest value method is just that. Just try to find out what's the biggest value you could possibly have with your uncertainty. Not with your uncertainty, I mean for each of your values. And I think I'll explain this. In context, it's going to make more sense. So for example, let's just take a look at this right here and see what we do here. So if we have a distance, just think about this here. So we have a distance here. Maybe I'll draw in light blue here. So the distance that I'm measuring is actually, like I said, it's 10 meters plus or minus 1 meter. That means it could be as small as, think about this, 10 minus 1. So it could be as small as 9 meters, but it could be as large as 11 meters. just like your time, right? Your time is 5.0 seconds, and it's plus or minus 0.2. So that means your time could be as, let's see, as small as 5 minus 0.2, which is 4.8 seconds. And it could be as high as 5 plus 0.2, which is 5.2 seconds. This is sort of your range of values for d and for t for your time. So if you think about it, if you're looking at a velocity, or a speed, sorry. So this is right here is the equation you're looking for, right? You're looking for speed. Let's just say, so the speed then is distance over time. How do you get the biggest value? So I'm trying to find out basically largest v, and I want to get the smallest v. So I'm trying to see like which different things, like what's the absolute largest I can get, what's the absolute smallest I can get. To get the largest value of v, think about it, I want the so that means so largest distance here. So in this case right here, I would use 11. And I would divide that by, let's see here, in this case right here, because it's a denominator, you want the denominator to be the smallest value, because the smallest, a big number divided by a small number is the biggest thing you can get. In this case, I want the smallest time. So in this case right here, I would use the 4.8. And I just use my trusty calculator with that, right? So I'm using an TI-84, but some people use the Inspire or the Casio. There's different choices, but I'll just use my simple little TI-84 here. So if I do this right here, I get an answer of 2.2916, let's just say, meters per second. And if I want the smallest value of v, I do the opposite. So there I'm going to use the smallest value of d on the top. So in this case here, I'm going to use 9 meters. By the way, this is in seconds. I'm going to use the largest value of time on the bottom. So I'm going to use 5.2 seconds. So that means there I get 9 over 5.2. So there I get, notice these are calculated values. There's lots of digits here. I don't really know where to stop. I'll just stop at like 4-ish because I probably don't need to go much further than that. Meters per second. So do you see I've got these two values? I've got the largest value and I've got the smallest value. So how do I actually deal with this? That's where I use this sort of magic equation here. This equation I need to use is this, right? That the uncertainty, this is the one here I'm going to use. So the uncertainty is going to be the largest minus the smallest, and it's going to be half of that. So in this case right here then, the uncertainty, and I'm going to write it as delta, because that's what we use. We use delta v in this case here, uncertainty on the speed. Delta v in this case here is going to be the largest, which is 2.2916, minus the smallest, which is 1.73077. You can use lots of decimals if you want, doesn't matter. All that divided by 2. I'm going to do that on my calculator. So 2.2916 minus the 1.73077, divide that by 2, and I get an answer of this. I get delta V equals 0.280415, let's just say, something like that. So first of all, what do you do with this? Do you remember I was showing you before? Your uncertainty on V needs to have just one non-zero number. So I'm going to take my answer for delta V here, and I'm going to make it delta V equals, let's see, I'm only allowed one non-zero number. So I'm going to have to round right here. And the 2.8 becomes the 8 forces this number to go up. So in this case, it's just going to be 0.3. So now I'm finally ready to have my conclusion here, which is that the speed then is going to be grand total here of, let's see now, it was, what did we say it was? Well, it's 10 divided by 5, so that's 2. So in this case, it's going to be 2.0 plus or minus 0.3 meters per second. This is going to be my final answer. So do you notice what happened here, right? This is it. I'm done. So what happened is I calculated the delta V, the uncertainty on the speed. I forced it to be one non-zero number. And then from there, I can tell how to round because I can only use 1 after the decimal. That means I'm only allowed 1 after the decimal here. So that's how you can do it. Now the other method uses the equations. So these are the equations from your data booklet, and you can actually look these up. They look just like this on your data booklet, this one and this one. So I just want to show you those ones. So for example, what this tells you is if you're measuring, so this just tells, the notation looks a bit weird, and not many people know to look for this, but if you look at your data booklet, it's actually there. This is there for you. So what you can do then is you can take a look and say, okay, the uncertainty on a value. given that you have something plus another thing. In this case, A plus B, or it could be A minus B. I hate the way they wrote it because it looks like it's A plus or minus, as in if B is the uncertainty. I don't mean that. I mean like if Y equals A plus B, then the uncertainty on A and the uncertainty on B, you just add them together, you get the uncertainty on your total value. Hope that makes sense, because if you actually take, I don't know, let's just say you're taking a length like this, you take another length like this, the uncertainty on both those lengths, just add the uncertainties and it should make sense. Also, if you're subtracting, so that's why if it's A plus B, or if it's Y equals A minus B, the uncertainty, this delta Y, is going to be the same thing. You just add the uncertainties, whether you're adding or subtracting the values. This one, however, looks a bit more complicated, but it's totally doable. This says that Y equals AB over C. What this means is if you're multiplying or dividing, or even both, you can be multiplying and dividing in an equation. Here they show you, like, you have Y equals something times another thing divided by another thing. They tell you that the uncertainty on your Y, it's not quite just isolated for uncertainty. Do you notice it's delta Y over Y? In other words, the uncertainty divided by its own original value is going to be equal to the uncertainty on the first thing divided by itself, plus the uncertainty on the second thing divided by that thing, plus the uncertainty on C divided by C. So in this case, I'm going to show you the example that we had. It was just V equals D over T, wasn't it? So do you see we have an equation just like this? So we can apply this method here, and you'll see this method is much faster. So if I want this, then I know that delta V over V, because I'm going to use this second method here. I'm going to use that one. So if I want, that's because I have something divided by another thing. So I'm doing dividing and multiplying here, or multiplying. So in this case, what do I do here? I know that delta V over V, because I'm using this function here, I'm using this delta Y over Y, in this case delta V over V, is just going to equal to the uncertainty on distance divided by itself, so divided by the distance, plus the uncertainty on the time divided by the time, and that's it. So in this case here I can figure it out, right? So the uncertainty on V divided by V is going to be, let's see, what's the uncertainty on the distance? It's 1 meter. See, that's over there, it's 1. Divided by 10, because that's the original distance, plus the uncertainty on the time, which is 0.2, divided by 5. That wasn't so hard, was it? By the way, keep in mind, you also know your V, actually, so I should probably, I'll just leave it. So therefore, keep in mind, I have V, don't I? So I have 1 over 10 plus 0.2 over 5. But I also, if I want just delta V, I have to multiply this V. I have to put it to the other side. So I'm going to multiply it here. And what's the V value? What's the speed? Remember, it's 10 over 5, which is 2. So this is why I get the actual uncertainty here. We're going to call it later, we're going to call it the absolute uncertainty. That's what I have here. The absolute uncertainty on this is going to be 1 over 10, which is 0.1, plus 0.2 over 5, all that times 2. So in this case right here, I get, hey, good news, I end up with 0.28. Hey, isn't that what I had before? So that's why I'm going to end up with, look at the example I had before. Remember I had that delta V was 0.3? I get the same thing here. Look, my delta V, let's just look at it here. So my delta V then is going to be, well, I can't use 2 digits. I'm only allowed 1 digit to use it, and 1 non-zero number. So in this case, this has to be 0.3 meters per second. Therefore, my final answer then is V equals, remember it's 2, and again I know to round it to put 1 decimal after, one value after the decimal. So in this case I'm going to say 2.0 plus or minus 0.3 meters per second. Aha! That's how we do it. And I have an example for you, another one, just to make sure it makes sense. So this is the final answer here. So if we do another example, so here you measure, this is something like, well, this is something from an exam here. So you measure the length of a cube. In this case, so remember what a cube looks like. Cube looks like this, right? It's going to be a nice cubic, well, I'm a lousy artist, but we'll see here. This is a cube. And we have the length of a cube to be 2 meters. So this is 2 meters here, but so is this, because it's a cube, right? It's got the same length, width, height. And we know the uncertainty is 0.001. So we know that L is 2.00 plus or minus 0.00, 0.01 meters. This is what we know. We want the volume. And how do you find the volume? There's a couple ways of looking at it. I mean, there's another equation on your data booklet, actually, that has it like what to do if there's a power here. You're just supposed to put the power in front. But I'll show you that that's going to be we're just sort of going to know what to do here. You'll see what we do here. So what we're going to do, we're going to get an equation for the volume. The volume, maybe I'll write a volume just so you know, it's going to be the length times the length times the length, or length cubed, right? But in this, I'm just going to split it up just so you can see it more obviously. I'm going to use this rule number 2 here. This y equals AB over C is just delta y over y plus delta of all the things divided by themselves here and add them together. In this case right here then, that means I'm going to say delta V over V, delta volume over volume, is going to be equal to then just delta L over L plus delta L over L, because I've got it again, and again delta L over L. That might get kind of annoying, right? So that's why what you can say instead is you can say that equals 3 times delta L over L. And this is actually the equation you're supposed to get to. That's another equation on your data booklet. It says, in this case right here, you know, if we're going to do this, we could say it's L cubed. And you could say what happens is the 3 comes in front. So basically that's just sort of the same rule happening here. So 3 times delta L over L. Because we have it this plus this plus this. So in this case right here, then we have delta volume, remember, over the volume. It's going to be 3 times the uncertainty on the length, which is 0.01, divided by the length itself, which is 2. And I have it times 3 right here. So in this case right here, we can figure it out. Oh, and we have the volume itself. We actually have to figure out that because we want delta volume by itself. We want the absolute uncertainty. So the uncertainty on the volume is going to be just this right here. So this is 3 times, well, that's 0.03. Let's see. I just multiplies that, right? So 3 times 0.01, all that divided by 2. And I'm going to say that thing right here. So that's 0.15, sorry, 0.015. But remember, I got to multiply that. Here I had delta volume over the volume. So that means I have to multiply by the actual volume. The volume, of course, is going to be 2 times 2 times 2, which is 8. Because that's actually the volume. The volume is actually 8. So then I do this number right here times 8. And I get delta volume is going to be 0.12. And remember, you're only allowed one non-zero number. So in this case here, I'm going to state then that the uncertainty on the volume is going to be 0.1. In this case, meters cubed. So what do I do with that? I have my final answer. Now I'm ready. I can then state that the volume is going to equal 8, because that's what L times L times L is, right? 2 times 2 times 2 is 8. And I know how many figures to put in. I know how many values after the decimal I'm allowed. Because my uncertainty is 0.1 meters cubed, then I know that I'm only allowed 1 after the decimal, so that means I know to force it to be this. This is your final answer. So see, you can solve exam questions too. They might seem annoying, and once you've done a lot of them, you'll see you're a lot quicker at them. I just wanted to show you all the steps. Absolute, fractional, and percentage uncertainty, again, are really important for paper 3. So in order to do this, we have to understand sort of a measurement. So in this case right here, we're going to be using this example of measuring just something. That thing you measure, that could be a distance, it could be a force, it could be whatever. In this case here, I'm just going to call it a thing A. Now that thing A has some sort of associated uncertainty with it when you actually measure it, right? You're going to have A, but you're not going to be exactly sure what its value is, right? You could be a little bit uncertain. So that's why I'm going to put an A plus or minus, you know, some sort of, I don't know whatever this uncertainty is. It could be like 0.1 or whatever. So this is what I mean here. So you're going to have some value plus or minus whatever that uncertainty was. So the definition then of absolute uncertainty, it's super easy. The absolute uncertainty is just plus or minus delta A. In other words, the absolute uncertainty, it's the actual value of your uncertainty. So if you're measuring a distance of like 2.0 meters, then the uncertainty would be like 0.1 meters. So it's an actual literal value. Whereas the fractional uncertainty, hopefully that'll tell you a lot more about it, right? Fractional implies a fraction, duh. So in order to do that, you can actually figure it out. The fractional uncertainty will simply be the uncertainty on your measurement A, and you're going to divide it by A itself. So that's how you're going to find the fractional uncertainty. Now the percentage uncertainty is just like the fractional uncertainty, except you multiply by 100. That's it. So in this case here we have delta A over A, and we have that times 100. And that's how we find the percentage uncertainty. Now you might be wondering, okay, well, when do I need these? Actually, I mean, very often, if you're actually going to be measuring something, you're going to need to know the absolute uncertainty. But a good trick is to actually use the percentage uncertainty. And this is something I'm gonna try to show you here. So I have a nice trick for you here. First of all, I mean, these kind of questions, a lot of people don't know what they're doing. That's why I like this. I have no idea what they're doing. And you know that meme probably, right? So a nice trick is that if you have things multiplied or divided, and when I say things, that could be really a lot of different things. Okay, oops, I realize it's sort of off the screen. Let me just fix it here. So if you have things that are multiplied or divided, let's see here if we can fix it. There, nice. Then what you end up doing is you can add up all the uncertainties on whatever value you are measuring. So in this case, if you're measuring a distance and a time, let's just say, and you want to find the velocity, even though the velocity is the distance divided by time, or displacement divided by time, if we're going to be really accurate about it, then what you can do, you can just find the percent uncertainties for each of them. You can find the percent uncertainty for distance, the percent uncertainty for time, and even though the way you calculate velocity is by doing the distance divided by time, it sounds complicated, but if you have things multiplied or divided, which in this example I'm telling you, you do, then all you have to do is just add up the percent uncertainties and you'll get the uncertainty on the total value. And I think to make it make more sense, I'm going to use that actual example there. So here we go. We have an actual example here. So what's the percent and absolute uncertainty on the speed? So here we have a distance of 10 meters plus or minus 1 meter. And we have a time of 5.0 seconds plus or minus 0.2 seconds. So to find the percent uncertainty, that might be a good one to start with, right? So let's do the percent uncertainty. The way we're going to find that, we're going to remember that equation, right? That we first have to do the fractional uncertainties on each. So let's do the fractional uncertainty on distance. So for distance, we have the fractional uncertainty is going to be delta D over D, which in this case, the uncertainty on D is just 1, and the actual value of distance is 10. So in this case right here, remember, right now I'm actually finding the fractional uncertainty, which gives me 0.1. Now to do the percent uncertainty, remember I have to take that and multiply it by 100. So what I do, I move my decimal over by 2, and I end up with a percent uncertainty of 10% on the distance only. We can do the same thing for time. For the time, we have delta T over T. I'm doing the fractional uncertainty on the time, and it's 0.2 divided by 5. And I do that, what do I get? I get 0.04, don't I? I think so. Yeah. 0.04 times 100, of course, to get the percent, and end up with 4%. All right. Now, how does this help me? Well, I want to find the velocity. The speed. And the speed itself, remember, is given by this equation, right? V equals d over t. The speed is the distance over the time. But remember that little trick I showed you, that to find the uncertainty on the total value, all you have to do is just use both of these right here, and you can just add them together. So 10% plus 4% is 14%. So you have a 14% uncertainty on your speed. Your speed has a plus or minus 14%. So we're done that first one. What's the percent uncertainty? Done. We got it. Now to do the absolute uncertainty, you could work it all out with that equation. You know, do delta D over D plus delta T over T and multiply that by V. You could absolutely do it that way. See, absolute, huh? But instead, let's just use this percent uncertainty. If we know that the... we know the percent uncertainty, so that's actually really good. We know that the value, let's see, the velocity, the speed, is going to be just 10 divided by 5, right? Hope you know that. It's going to be 10 divided by 5, which is just equal to 2. We don't know, though, how many decimals to put, right? But we know it's 2 meters per second. So here's the thing. To find the absolute uncertainty, we can just use the percent uncertainty. We know that our value is going to be 2 plus or minus 14% of 2. So all you have to do then is multiply with your trusty calculator. I'm going to do 2 times 0.14, and I get an answer of, I don't know if you can see it, but it's 0.28. So I end up with the uncertainty, so delta V in this case right here is going to be 0.28 meters per second. But do you remember what you have to do? Your uncertainty has to have one non-zero number. So in this case, I'm going to change it then to make it delta V is 0.3 meters per second. This is my uncertainty on the speed, the absolute uncertainty. If I really wanted to write everything correctly, I would have written it like this, right? That the speed is actually 2.0, because now I know I'm only allowed 1 after the decimal, plus or minus 0.3 meters per second. So this is sort of how I would write the speed. I hope that makes some sense, at least. So for calculating these right here, really important for paper 3, really, really important. Linearization is not exactly something that you need formally for the IB diploma, especially for physics. However, it's implied. You need this a lot. So you won't really find this in a book, I don't think, like exactly called linearization, but this skill is really important. So that's why I thought it warranted its own video here. So this idea of linearization really hinges upon this word linear, and linear means line. So what I'm going to do is really focus on lines here. So do you remember the equation for a straight line? Remember this from math. It goes y equals mx plus, now some people use b, some people use c, it doesn't matter. So this is the equation of a straight line. So if I actually want to graph that, let's see if I can do it nicely here or not. I'll just try here like this. So if I want to do a graph of it, let's just see here, so like this and like this. I have to do it again here. Let's just say, so something like this right here. If I actually wanted to do a graph of this, right, x and y, then do you remember how these go? What features are there? I mean, the y and the x have to remain y's and x's. The m is just a number in front of the x. And whatever that number is, and keep in mind, I know you're probably wondering, like, what? I know this. Watch carefully. I'm going to remind you of this, and I'm going to do some sneaky things that are actually going to end up being linear graphs, okay? So bear with me in case you think this is too easy. I agree, this is supposed to be really easy, this part right here. So remember this junk, whatever is in front of the x, no matter what it is, it can be a bunch of stuff, complicated equation, but whatever junk is in front of the x, that is your gradient. Some people call it your slope. Same, right? So gradient. And remember what b is? B, or whatever this is, you're adding or subtracting to your x's, that is your y-intercept. So in this case right here, then the general sort of graph then would look like, I don't know, maybe something like that. So this could be something where, the y-intercept right here, this right here would be b. So whatever that value is here, that'd be b. And this slope, remember how we found the slope? The slope would be, slope or gradient, right? Gradient and slope are the same thing. So slope, which is equal to the gradient. In this case here, that'll just equal m. And do you remember how to find it? When you do delta y over delta x, or sort of people call it rise over run. There's a lot of ways of seeing it. Now that, of course, seems probably too easy, and I love this little meme here. So here is your line graph. A lot of people use this one image here, and they don't really attribute it to the proper source, but I guess I didn't hear either, but I'll tell you about it. It's actually from a blog called Hyperbole and a Half. It's a blog that's brilliant, absolutely brilliant. So let's do an example here with springs, with Hooke's law. If you know about springs and Hooke's law, maybe you don't. I hope you know about it. So this one here, imagine I have a spring here, and I attach to that spring some sort of mass here. And of course, as I add more and more mass, the spring extension itself, it'll extend even more. So I could see that the extension is related to the mass that's been added. So you might then end up doing a whole bunch of different values, right? You could actually, have different values in a table of the force, the applied force, which is related to the mass, right? Mass times acceleration due to gravity. So the force would be in newtons. And you would also have related to that the extension. So x, that could be like the displacement. And Hooke's law goes like this, that F equals kx. It's technically got a negative. It tells you about the force is in opposite direction to the extension. I'm going to ignore the negative for right now. I'm just going to say F is kx. Now keep in mind then what this means. So you have a whole bunch of values here of F versus x. And you have uncertainties on them, sure. The key thing though to remember here is that what would you need to graph against what to get k? See, very often on exams, especially on paper 3 now, they're going to be asking you to somehow determine some sort of value. And it won't necessarily be k, so don't memorize this, but I want you to learn how to deal with this and how to look at this in the right way. It may not seem so obvious, but can you see that this one right here, I can see this as a linear graph? Can you see it? This one right here, this could be my y. My x, hey, that's actually kind of nice. X could literally be x. That means whatever junk is in front of the x, remember, that's going to be the slope. And that means that whatever I'm adding here, in this case here it's 0, that would be the y-intercept. So what this tells you then is really cleverly, you can already know what the graph is going to look like. You could actually sit there and know that, okay, well, if I graphed, in this case right here, let's see here, the force in newtons versus the extension or the displacement in meters, then what would the graph look like? You know what it's going to look like already. Look, it's going to be a straight line graph that passes through the origin, so it's going to pass through here, and it's going to have a slope of something. I don't know what, whatever. Whatever that slope is, let's just see. Oops, I can't seem to draw a nice straight line. Maybe I'll do it this way instead. Draw a line. Let's see if it works here like this. I suppose technically it could go in the negatives, but you can't have negative extension. Well, I guess you can. You just go up above. But let's just leave the positive for now. So this right here would be the graph. And if you're really clever about it, then you could use that graph to tell you, oh, I know, I'll find the slope of that graph because that slope will literally equal k. And what will its units be? The slope's units will be, well, remember, slope is rise over run. It's y over x. So in this case right here, it'll be newtons per meter. Okay, so it'll be in newtons per meter. So this right here is how we can linearize this. I'm going to give you another example. It's with the pendulum. I love this one here. So how often does one make jokes about IB physics with pendulums? Periodically. Ha ha. That's actually because I had a video a while back that I did actually about a cat, and you could actually hold the cat up and actually make the cat be a pendulum. So it's called Pendulum Cat. You can look it up on YouTube. But what I want to show you is that there is a pendulum equation. There's actually one you get. It's in your data booklet, and it goes like this. Maybe I'll put it in green. There's a pendulum equation. It goes T equals 2 pi times square root of L over G. And this is the equation for a pendulum. Okay, so you don't have to memorize it. You can look it up. But this particular equation is really important because what it tells you is that if you were measuring a bunch of values, so let's say you're taking data and you knew the period and you were manipulating the length. So those are the two things you'd be changing, the period and the length. The period is in seconds and the length would be in meters. And you have different values of period and length, right? So you manipulate the length, you change the length of the pendulum. In this case of pendulum cat, you're having different cats of different lengths, I guess, technically. You let them, operate as a pendulum, and you measure the time it takes to do one full motion. That's one period here, in seconds. Now, if you were to graph T versus L right now, okay, so I'll just be a little bit lazy. I won't use nice straight lines. I'll just graph L in meters, and I'll graph T here on the top here. What would the graph look like? If you look at this, T versus L, well, the 2 pi, and by the way, G is just acceleration due to gravity, so you can kind of ignore that for now. The way the graph is going to look, it's going to look like y equals square root of x, won't it? Because it's got T equals just square root of your x value. Remember what square root of x value looks like, or graph looks like? It does this. So here's the problem. Using this graph, how am I going to linearize it? How am I going to take the slope of this graph to find G? I can't really. I mean, you could do individual values of T and L, but that's not the best way at all. The best way is to use a linear graph. So this is not helpful. So rather, a better thing to do is to actually manipulate this equation. I don't like the square root. So what am I going to do? I'm actually going to square both sides. So I'm going to square both sides. I'm going to say T squared equals, let's see, 2 squared is 4. Pi squared is just pi squared. And square root of L over G, that's just L. And I'm going to do over G over here instead of over here, just so it looks a little bit prettier. Because look carefully. It doesn't look like it, but this is actually linearized. Look at this. This junk right here can be Y. This right here can be my X. If that's the case, whatever crap here is in front of it, that's the slope or the gradient. So that means if I was to do a graph now, let's just actually draw it here. So if I was to do a graph this time of L in meters, versus T squared, so that would be in seconds squared. If I was to graph this, I know it's going to be a linear graph and the y-intercept is 0. So that means it's going to pass through the 0, 0. It's going to be some graph that's going to go like this. And I know furthermore that the slope of this graph is going to equal 4 pi squared over g, which means I can actually literally then find the slope of that graph. And if I did that, can you see I can manipulate this? I can use that graph then to find g, because I can just rearrange this, right? Cross multiply, as people call it. G goes over here and the slope goes down there, so it's going to be 4 pi squared over the slope. That will be your answer. That is how you will actually use a graph of t squared versus L. And just that graph then, you know it's going to give you a straight line because you're smart, you know about linearization. And you know then that the g is actually going to be found literally by the slope. In this case, the slope is going to be 4 pi squared over the slope. That's going to be what g is. So you could actually find the acceleration due to gravity. Isn't that cool? Uniformly accelerated motion is one of the most basic things that you need to know from physics. And I don't mean basic as in easy. I mean basic as in base. As in a lot of things really hinge upon this, especially an understanding of it. So I'd like to maybe go a little bit by contrast and talk about what happens when you're not accelerating. So see, if you're actually not accelerating, then it becomes really, really easy. Okay, if you're not accelerating, you have nice, easy equations of motion. In this case right here, your speed or your velocity will just be equal to your distance or displacement divided by t here. So it'll be s over t. Some people call it distance over time. That's also fine. Right, so something like this in seconds, and this is in meters. In this case right here, super, super easy. Okay, if not accelerating, really, really easy. I love this picture here, accelerate to attack speed. So there are 4 equations of motion. You really need to know these ones right here. You don't have to know them by heart because they're on your data booklet, but you do need to know how to use them. There's one extra one that's really important, I think, as well, so I'm going to actually put it down here. It's sort of a general definition of acceleration. If you're accelerating, it's your change in velocity versus time. Technically, it's a vector, so I'm going to be really careful here and actually go like this. So this right here is your acceleration is technically the change in velocity over a change in time. That is sort of a key thing in physics. So maybe we'll talk about this. If you're accelerating, remember, it means your speed is actually changing with time. What that means, imagine if you're driving in your car. If you're going at a constant velocity, if your velocity is constant, then you're not accelerating. Right? That's maybe we should say v equals constant. So if your velocity is constant, you're not accelerating. So what that means, and you could still be in motion, right? Because you're not accelerating doesn't mean you have to be stopped. You could still be moving, right? You could be in your car going at 100 kilometers an hour. So if you're driving at a constant 100 kilometers an hour, think about your speedometer. Or if you have digital one, then, you know. But the numbers will actually just remain the same. You'll be just at 100. You're not changing. Therefore, you're not accelerating. If you are accelerating, that means your velocity is changing. Do you see it came from that literal definition here? That acceleration is a change in velocity. So anytime your speed or velocity is changing, you've got some sort of acceleration here. Now, there are these 4 main equations of motion, which you don't have to memorize, but they go v equals u plus at. You've got s equals ut plus half at squared. You've got v squared is u squared plus 2as. You got the other one here with s equals v plus u times t over 2. It's important to make sure you know what all these different letters mean. So that's why I'm going to add to them here. So remember that s is your displacement. I always thought that was strange that they call it displacement, right? Why do they call s displacement? You'd think it should be called d, right? But s is displacement, and that's in meters. Actually, there's a reason. I mean, there's a lot of reasons why, but it just seems silly, I think, to an IB student at least. Like, what is it? Displacement? But I mean, if you think about if you're doing calculus with all this stuff, like with derivatives, we use the symbols d, dx, and things like that. Then it gets really confusing. So that's why, okay, displacement is fine with an s. Initial velocity or initial speed. We'll use these as a vector ones actually. So this will be good. So technically, I suppose they should all have little vector symbols on top of them here. So should this and this and this. These are all vectors. You know the difference between vectors and scalars. See, time is a scalar, so you don't have to worry about it. But this is technically how it should go here. So if we do this, the initial velocity is going to be measured in, you know what velocity is? It's a rate of change of position. So in this case, remember velocity is change in displacement over time. That's how you can define velocity. And if you define it that way, then you can say, look at the units of this thing. Look, it's like a slope, isn't it? In fact, if you have a graph of displacement versus time, right? Displacement is in meters, time is in seconds. You have a graph of displacement versus time, which, I don't know, maybe it does something like this. The velocity is just going to be, let's see, delta s, delta t. That's the slope of the tangent. So what that tells you then, for example, right up here, can you see the tangent line right here be flat? That tells you then that the speed right here, or the velocity right here, is going to be 0 because the slope is 0 right here. Over here, speed is positive. Over here, speed is negative. So let's go into this units then. If the velocity is dependent on the displacement, the units of displacement are meters, units of time are seconds, so that's why it says meters per second. I'm just trying to show you where everything came from. Like I said, it's a basic because it's a base. Final velocity, same thing. Because remember, if you're going to accelerate, you're changing your velocity. So what does it start off at and what does it finish at? That's u and v. Acceleration is literally this thing right here you're talking about here. It's this change in v versus t. And again, look at the units. Doesn't v have units of meters per second? Right, we just talked about it right here. Right? V has units of meters per second, and you're dividing by seconds. So it's meters per second. That's why it's meters per second squared. That's why I write it like that, meters per second squared. Time, of course, is in seconds. We're going to say s, but I like to put seconds. So these are these main equations that you need. These are the different letters, different variables you're going to be using. Now, there's a nice little trick here for solving lots of acceleration equations. I like to call it UVAT. Some people call it SUVAT. It doesn't matter. But basically, you should use this sort of trick here. At least I think it's a good way to do it. If you're not super good at this, it's a good trick. What I like to do is, this basically tells you your shopping list. So what I would do is I would, split up. I would actually write down, what do I know? Do I know what U is? Do I know V? Do I know A, S, and T? If I don't know something, I put a question mark. If it's the thing I want, I put a star. I'm really careful with pluses and minuses if it goes up or down or whatever. And I always make sure that the only things that go in here are in proper units. In other words, if they're being sneaky and they gave you something in centimeters, let's just say, make sure you convert that to meters. So in my own rules, at least, that's how I deal with this. And maybe let's actually do an example. So here you're driving in your car. Oh, by the way, I like this. Decelerate, because you're going to be talking about decelerating. I like to decelerate to regurgitate the celery you just ate. So you're driving in your car and you're going 21 meters per second. Just the notation is a bit weird, but basically your initial speed, remember, initially you're going this. So that means u now is 21 meters per second. You slam on the brakes. What that means is you slow down, don't you? You decelerate at 3.2 meters per second squared. So acceleration is 3.2 meters per second squared. But you got to watch out here. If you're decelerating, let's just assume you're going to the right. Let's just maybe assume that. So we'll draw our little situation here. So here's your car. I'm a really lousy artist, as you can see. So your car is initially going with some speed 21 meters per second. And what happens, of course, at some point, you're going to be stopped, won't you? So at some point, oh god, my drawing got even worse. My speed is 0. So to do this, think about this. What's the direction of my acceleration? My acceleration has to have an opposite sign to the speed. Because you see, if the speed is going to the right, then you need to define your acceleration as to the left. So I'm going to put a negative in front of it. Just because the acceleration, otherwise the acceleration would be positive 3.2. That means you'd be starting at 21 meters per second. And you'd accelerate, like, you'd actually, put on the gas. And you'd end up going way faster. And that's not the situation here. So somehow you have to account for it. I like to just make my initial speeds in the positive direction, and anything that acts opposite to that, I just throw a negative in front. So how long does it take for you to stop? How long? That implies a time. So this is what we're looking for here. So what I'd like to do then is just show you that whole UVAS thing, or SUVAT, or whatever you like to do here. I just put in what I know and what I don't know. This helps me to pick which equation I should use. So U, the initial speed, is easy. It's 21. It's meters per second, so it works. V, the final speed, think about it, you stopped. So there, V is 0. So that's why this is 0 here. Acceleration in this case is negative 3.2 because, again, you're acting in the opposite direction. If you didn't do this, you couldn't have V here be 0. Your displacement, I don't really know it, and I don't really care. I'm going to put a question mark, like don't know, don't care. And T, oh, that's what I want. I put a star by that. So what this does, this is like my shopping list. This tells me what to do. Look carefully here. I've got my time. And what I want to do is I want to solve for time. In order to do that, then what I should do is find an equation that doesn't have S in it, but that has time in it. So I need an equation with no S's, but that has T. Let's see if we can find one here from these. Do I have an equation that has no S's? Well, that means it only has to be the first one here. V equals u plus at. If you're going to solve it, you should always write down which equation you're using. So I'll say v equals u plus at. That shows your examiner you know what you're doing. Then you actually just put in the numbers. So let's just see if we can figure it out here. So I would say then that, well, I can solve for t. I can get t by itself. Remember, v is 0. That's really easy. So let's see, I have negative u equals at, because I moved my u over. And then to get t, then I have negative u over a. So in this case here, the time is going to be negative u, which is 21 meters per second, over a, which is, remember I called it negative 3.2. So see, it works out. The time isn't negative. If you're really careful with this stuff, units will always work out. In this case here, you get 21 over 3.2, which is, what's that? I'm using my trusty calculator here. I get an answer of t equals 6.5625. What kind of digits should I be using? Do you notice I have 2 numbers here to represent this and 2 numbers to represent this? So I have to do the same. So I will state then that my time is going to be 6 point, in this case I'll round 1 after. So it'll be 6.6 seconds. See? We can solve. Here's another example of how to use uniformly accelerated motion. So here I have a situation where I'm pushed off a 325 meter high cliff. So not good, I guess, for me. So here's the cliff here. Here's me. Not good. Here we go. Not happy. So what happens is this height right here is 325 meters. And the question is, how fast will I be going when I hit the ground? And that how fast, that's an implication of speed. I like this picture. It's obviously photoshopped. It looks awesome. So if you actually have this, you want to figure out how fast you're going to be going right before you hit the ground. Right? You're going to go sort of splat right here, or in the water in this case. Yeah, how do you find your speed? So all you have to do is use, again, this idea about UVAST, this idea that, put in what you know and be really careful with signs, with positives or negatives, and everything's going to be just fine. Because you're accelerating, because you're going to have gravity who's going to be accelerating you. In this case, your initial speed, it's implied that it's 0 because you're not told you're running or anything. I think it's a vertical situation. In this case, your initial speed will be 0. V, your final speed, we don't know. In fact, it's what we want. So I'm going to put a star by that one. The acceleration, in this case, there's only gravity acting on you. It's the only force acting on you. So because of that, acceleration is going to be the gravity that you know, 9.81. However, this can be really important. If you just put in a positive 9.81, that's going to imply you accelerate upwards. You don't, you accelerate downwards. So it's really important here, if you're going to consider up being positive, then down has to be negative. So in this case, that has to be a negative. Displacement. How far do you actually travel? In vertical situation, it's really easy. You start off at that height of 325 and you end up going down to 0, right? How far then have you displaced from your start to your finish? You've displaced by 325 meters downwards. Time, we don't know. We don't know how long it takes for you to do this. It could have been the question. And this could we don't know and hopefully don't care. So what I'm going to try to do now is find an equation that has a v in it that doesn't have t. You see, I don't want t in it because if I have t, I have to find it. So look for an equation that has v with no t. Let's see if we can find one. So go back to here. We'll look for an equation with v in it, no t. That one has a t, that one has a t, that one does. But this one right here doesn't. See, so v squared equals u squared plus 2as. So I put that in, and I make sure I tell the person who's the examiner that I know what I'm doing by actually writing this equation. Remember, it goes v squared, equals u squared plus 2as. So let's put in what we know now. U is 0, so that's gone. We want v, which is great. So if we actually want to do this, then it's going to be pretty straightforward, I think. We want to get v on its own. That means I have to take the square root of 2as. Keep in mind, though, technically, when you do a square root, it's a plus or minus, isn't it? Because there's 2 different answers that you square them could give you that positive value. So in this case, we've got to do plus or minus square root of 2as. Let's put in the numbers. So we have square root of 2, plus or minus, square root of 2 times negative 9.81 times s, which is 325. Again, negative. Good news, the negative and the negative cancel out. You get a positive, which is great because you're not allowed to have a negative in the square root. Well, you can, you just get some wacky results. You get things in non-real numbers, which is maybe a bit tough. So I'm actually figuring this out now on my calculator, and I get a value of v equals plus or minus 79.85 with lots and lots of digits. First of all, how many numbers can I use? I'm allowed to use 3 digits. So that means I'm going to use 3. So I'm going to say my V is equal to 79 point, we could say 8 or we could say 9. Maybe we'll just say 9 meters per second. But really, really careful. If you want to know this, I mean, this is technically your speed. If you want to know your velocity, it's technically negative because you're actually going downwards. So just keep that in mind. It's a little interesting little caveat here. But this is your speed. You're going about 80 meters per second, which is actually really fast if you think about it. What's that? That's like 280 something kilometers per hour, I think. So really pretty fast. So I hope this example helps just to make it make a little bit more sense again for how to use uniformly accelerated motion. When we look at motion in 2 dimensions, what we mean by this is projectile motion. I like this picture here that I have. It looks like a unicorn. It's like projectile vomiting some rainbows. But I mean, this is what projectile motion looks like, right? It's something that goes up and sort of goes down again. That's because you can really break up its motion into 2 dimensions, right? That's why it's called, oddly enough, motion in 2D. So what I mean by this, the really important thing when you deal with these kind of questions, they don't show up all that often, but when they do, they're pretty sneaky unless you really know what you're doing. So components of the velocity. What I mean by this is if you're given a velocity. So in this case right here, maybe you're told that the velocity is called v. And if you're looking at that velocity v, it's at some angle theta above the horizontal. Then you can consider this as 2 different vectors. Since velocity is a vector, you could consider it as 2 different vectors added together. So that's why I've redrawn it like this. And this is actually kind of how it looks in your data booklet. Did you know you don't have to memorize how to deal with this stuff? It's actually there. A lot of people just forget to look. They write it with an A and they put an AX and an AY, but same, right? So in this case right here, if I'm looking at my V here, my V vector, it can be written as the sum of 2 other vectors. In this case, this vector plus this vector equals that vector. So in this case right here, you could say Vx and you could say Vy. And what's really important in 2-dimensional motion is splitting it up into its components. What I mean by that is the different parts. There's a velocity in the x direction that's going straight across, and there's a velocity in the y direction which is going straight up. It's related to the angle, and you can do your sort of right angle trigonometry tricks, SOHCAHTOA, some people call it. Otherwise, here it is. It's Vy is V sine theta, and Vx is V cos theta. The way I remember it is that to me, sine kind of sounds like y. It doesn't, but it kind of does. It has the I sound at the end of the sine, y. Well, it doesn't really work, but there you go. That's how I remember it. So the important key thing is this. In the horizontal direction, in other words, in the Vx, in the x direction here, that's horizontal. It's really, really nice and easy. It's not accelerating because it goes at a constant speed in whatever it's doing here. So it's super easy. What I mean by super easy, that means that your speed then will just be equal to, or in this case, you could even say the velocity, will just be equal to your displacement divided by time. Velocity is distance over time. Which is in meters, and that's in seconds. So that is super easy, but it's really important because almost half the time you're just needing, you're needing this at some point. You got to remember, in the horizontal direction, no acceleration, so it's super easy. You just use your equation of non-accelerated motion, of constant velocity. But in the vertical direction, it does accelerate. That's because you can consider this thing, and let's say you're being, something is being launched up at an angle. You can consider it as it's going a constant speed in that direction, over the ground, but it's the equivalent of being thrown straight up because there's a straight up component. So because of that straight up component, that has gravity acting on it downwards. So its speed is going to change, won't it? Its velocity will change, so it will be accelerating. Because of that, we have to use the equations for accelerated motion. Remember those 4 equations, right? So then you'll have to use this sort of UVAST stuff, and you'll have to figure out what to do. So I've got an example for you, and it's one that starts off okay, and then it gets really gross, and I just want to show you a really gross example so you know how to deal with it. So you're launched off a cliff that's 100 meters high, so maybe I'll try to draw it here. So here we go, maybe I'll do it in blue here. So I've got a cliff right here, and it's 100 meters high. And you're launched off it at a speed of 50 meters per second, but at an angle of 30 degrees above the horizontal. What that means then is you're being launched like this. And this here's 30 degrees here, and your speed here is 50. 50 meters per second. This is what's happening. And if you're not sure about the path that you're going to follow, I'll trace it for you. It's going to be a parabola. That means you're going to go something like this. You're going to hit the ground. Now, some people think these here are really, really complicated questions, but if you see it in the right way, they can be really easy. So here, what is your maximum height above the ground? You're like, oh God, how do I deal with that, right? I mean, then you might actually want to be doing like what the unicorn is doing. You want to throw up. Maybe rainbows, I don't know. So if you're doing this, your maximum height above the ground, that's right here. Your maximum height here, that's this value right here. You want to find out what's this height. And that sounds really complicated, doesn't it? I think the key thing here, first of all, is to break it up into components. Remember I showed you right here to break it up into these different pieces? So let's do that with the velocity here. So we'll do that with our velocity. So in this case here we have our velocity, which goes up like this. It's at 50 meters per second. That means we have a Vx and we have a Vy here. And if I'm going to do these, then I have to write out Vx. And Vx is going to be V cos, in this case right here, theta, which is 30 degrees. So V cos theta. Remember to have your calculator in degree mode. And this is V sine 30. Let's actually figure them out on the calculator. I'm going to use the TI-84, but you could use whatever you like. I'm going to make sure my mode is in degree mode. Yes. I like there's a South Park meme, you know, it says if you forget to turn your calculator into, if you forget to put your calculator from degree mode, you're going to have a rad time. Because you have to get radians. In this case, I do cosine of 30. I multiply that by 50, and I get an answer of 43.3 meters per second. That's enough decimals. And the other one then is sine of 30. I do that times 50, and I get an answer of, what did I get? 25 meters per second. All right, I'm going to need these numbers. So what's your maximum height above the ground? If I look at this then, the max height above the ground, we can deal with UVAST and try to figure out what happens at max height. This is going to be the key thing. At maximum height, what can you tell me about the horizontal speed? Nothing. It's going to be constant, isn't it? It's constant at 43.3. Its horizontal speed is always going to be 43.3 meters per second as it goes along here. But its maximum height, it's going to be doing all sorts of crazy stuff, right? Maximum height, though, something very special happens with the speed in the vertical component. Okay, so here we're going to be considering things in the vertical world. We don't care about horizontal, we just care about vertical. In the vertical world, it is accelerating. So because of that, our maximum height then, think about carefully. What happens right when it's at its maximum height? Vertically speaking, it stops. Of course, horizontally, it's still moving. But vertically speaking, it goes up, it stops, and it drops down again. So from that then, V is 0. That's the key here. Your final speed is 0 at maximum height. That's the key. Your initial speed is, let's see, in the vertical direction, in the Y direction. Maybe I'll put a little Y here for it. These are all in the Y direction here. There's no component needed for time. So Uy is going to be 25. Positive 25 because you're going up. Acceleration is going to be 9.81 because gravity is accelerating you downwards. And because it's downwards, I have to throw a negative on it. And then I want to solve for S. So can you think of any equations, by the way, I don't know T. So can you think of any equations that don't have T in them, that have an S in it? And if you look carefully at your different equations, you should be able to find one that goes V squared equals U squared plus 2AS. If I'm going to use that equation then, look at what happens here. V cancels out. Well, not cancels out, it's 0. So then I have U squared. Well, I want to solve for S, don't I? So I'm going to get S equals, let's see, it's going to be minus U squared, because I'm going to move the U squared over. I'm going to divide that by 2A. So in this case, it's going to be minus, 25 squared. And it's minus outside the bracket. So I do 25 squared, then I do a minus. Divide that by 2 times A, and A is negative 9.81. Good news, then the negatives are going to cancel out. You're going to get a positive answer, which is good. You should go up. If it was a negative, that means you go down. So I'm just going to do this. So 25 squared, I take that answer, I divide that by 2 times 9.81, and I end up with an answer of, my displacement is 31.855 meters. And then you might say, okay, so I'm allowed how many digits for this? Oh, I wrote this kind of poorly here, but let's just say it was, we'll just do it to the nearest, well, I guess we only get 2 digits to do it. So we'll use 2 digits. So we'll say that means S is 32 meters, right? Is this the answer? Nope, not quite. This is needed. It's not quite there. Think about it. That is your height above where you took off. But there's still the height of the cliff. That's a sneaky part about this question here. So actually your final answer is going to be, your displacement will actually be 32 plus 100. So that'll be 132 meters. If you're only going to use 2 decimals, I guess you should say it's 130, because you're only allowed 2 decimals here, but let's just say it's 132 meters. So that is a pretty good example, I think. To do the second part of this question, for how far away from the base of the cliff will you land, I think it helps to just sort of redraw it again, just to make sure it's more clear. So here we go, and you're going up in the air, and you're sort of landing down here. So the value you're looking for how far away from the base of the cliff, what you're really looking for here is this distance right here. And that's a displacement, we're going to call it S, and it's in the X direction, so we'll label it SX. And remember now, in the horizontal direction, things are really easy. It doesn't accelerate, it goes at a constant speed. This constant horizontal value of 43.3 meters per second all the time. How far will it go? Well, do you remember your equation for horizontal motion? It's super easy, right? It's just Vx is just Sx over t. It's not accelerating, it's just velocity distance over time. So in this case, if I wanted Sx then, I could just solve for that, right? I'm putting all the subscripts just to keep them straight here. So if I want Sx by itself, then I have to make sure that I put t on the top, so then I get Vx times t, and that's all I need. So you got to think, oh, well, is that it? Yeah, is that it? That's easy. I know Vx. Vx is 43.3, so I know that value. But I don't know t. Here's the problem. Here's the sneaky part. This is why it's actually a sneaky question. We actually don't know the t value. So this is the problem. We're stuck. In the horizontal direction, we can't do any more. But that means in the vertical direction instead, maybe we can get some help there. So what I'm going to do is I'm going to look now in the vertical. Because although in the x direction, in the x component, you're going at a constant speed, in the vertical direction, you're of course going up and then back down again. Which means when you land right down here, your vertical velocity is going to be something very different, right? So we don't know what's going to happen. We just know the initial vertical velocity is 25. So let's look at this in the vertical world. Maybe I'll write this UVAST again. And what I'll do, of course, is put subscripts everywhere just to make sure we keep this so we know what's going on here. We've got y's everywhere here. So uy, the initial y velocity, we know that is 25, and it's positive 25. The final y velocity is not 0 like we did before. That was for the maximum height. That was the case. But what happens is when it lands, it's going down. And it's going down really fast. It's going to be some big negative value, a lot bigger than 25. So we don't know what it is. We know the acceleration was 9.81 meters per second squared, and we know it's negative because it acts downwards. What I like is for this displacement, it's really easy to figure out. For displacement, you just have to think about where do you start and where do you finish. Although you go way up and do all these crazy things, as far as your vertical displacement though, it's really simple. You start off at 100 meters. Sure, you go up above it, but all we care about for displacement is the final result. You end up, in the end, at 100 meters below where you started. So that's why that just makes it negative 100. And t, that's what we want. We want the time. So then we have to think about what's one of the equations of motion that has t in it that doesn't have a v in it. If you look it up, you'll actually see there's this one. It goes, how does it go? It goes S equals ut plus 1/2 at squared. And if that's the case, I'm just going to try to see if I can delete that little one right here. I didn't like my plus being so high up. There we go. So if we use this equation, I mean, we can do this. The only problem is nothing cancels out. You're used to things canceling out, it becomes a lot easier. This one here, nothing cancels out. That's what makes this one harder. So S, let's put that in. We get negative 100 equals u times t. U, which is 25 in the vertical, yes, so 25 times t, plus we have 1/2 of a, which is negative 9.81, times t squared. This is a quadratic equation I have to solve. And you could be expected to solve this in paper 2. This could be that hard. Let's maybe figure it out here. We'll put all the t's on one side. So 1/2 of negative 9.81, what's that? That's negative 4.905 t squared. We have plus 25t. And we have the minus 100. I'm going to move it over so I get a plus 100. and I'm basically setting it equal to 0. If that's the case, then I can use my trusty calculator, which you probably have as well. There's lots of ways of finding zeros of quadratics. You could graph it and find the zeros. You could ask your calculator function to help you, and I'm actually going to do that right now. So I'm going to put it in. I have to put in the A and the B and the C terms. And I end up with 7 seconds. That's my answer for the time. Now I can put it all together though, can't I? Because now that I know the time, then I can put it together and say, fine, the x component then of the displacement is going to be here. I'm just going to maybe separate them just so we don't get too confused here. There we go. Different question altogether. We use this Sx equals 43.3 in this case right here, times 7.7 seconds. And if we do that, we have meters, we have seconds here. No, we have meters per second times seconds. That ends up with meters, so that's good. The units work out. Oops. So I have 43.3 times 7.7, and end up with 333 meters. And I'm, if I'm only allowed 2 digits, then I'll say fine, it's 330 meters. Say good enough. That'll be my final answer. Phew, pretty tough, but you can still do it. I want to show you a good trick for accelerated motion and looking at graphs of accelerated motion. These are really common things. First of all, I just want to show you this one. I like the velociraptor. It's just, it's almost like it's a velocity, so it's a distance over time. I like this one here too, that don't be and this is the third derivative of position with respect to time. The second derivative of position and time is acceleration. Turns out we have something in physics that's the third derivative. It's actually called jerk. So that's why it's don't be a jerk. So to do this accelerated motion and graphing, I'm going to use an example of rolling a can of soup up an incline. So what I mean by that is, let's just imagine then I have my trusty can of soup here. See, my name is last name is Campbell, so of course I would use a Campbell soup can. But what I would end up doing then is I would have this incline here, and what I would do, I would take this little can of soup, I'd start it here, and I'd sort of roll it up the hill. And I'd have a little detector right here that can actually say the displacement. It's a little sonic ranger, so it tells you the distance from the beginning. So that's the displacement. So, it would say at the beginning, obviously the distance from the start is 0. At some time, it goes up to the top somewhere, and after that it stops, and then it comes back down again. So what I want to do is show you then what these graphs then of displacement versus time should look like. This will be time in seconds, and this will be displacement, in this case right here in meters. But I'm also going to graph velocity versus time here, which is in meters per second versus time. And I'm also going to graph acceleration. I'm going to put these graphs underneath each other for a reason. You'll see that in a second here. You'll see why this is awesome what I'm doing here. So what I'm going to do then is just consider what's going on with the motion of this thing right here. So if we think about the motion at the very, very beginning, it starts off with no displacement, right? So that means it should be right here, no displacement. At time t equals 0, displacement should be 0. At some point, it's some maximum height above the ground. So I don't know, maybe it's something here. And at some point, then it comes back down again. So that means at some time, it's probably symmetric, so it's probably over here. And if you think about what shape it should have, it should be a nice, smooth curve. So some sort of parabola here. That should be the displacement versus time. Now the graph of velocity versus time, remember now, how do you get from displacement to velocity to acceleration? The nice little trick I want to show you is this one right here. So whenever you go down in graph, so in this case, that's what we're doing. You start off with a graph of displacement and you go down to velocity. This down and up only makes sense if you consider these three graphs one on top of each other like this. Like this is first, this is second, this is third. But if you're going down, what you do is this. So I'll say down, I'll say that means gradient. It's technically in the calculus terms, it's supposed to be the derivative. And just like I'm going to say up, it's going to be the area under the curve, which in math terms, that's called the integral. Right? So area under the curve is up, down is the gradient. This is the trick. Because if you think of it this way, then you can actually work it out, right? You can say, all right, Let's look at this first graph right here. If I want to go from displacement to velocity, then I'm going down. So what that means, I have to take the gradient. So what I do is I think about the gradient here at this point. Gradient of a tangent line of that graph right there, it's going to be some straight line that goes like that. And that line has a positive slope. I don't know what its value is. It's some positive number here. It's some positive thing. Right here in the middle, lined up right here at the middle, something very special happens. The tangent line is flat. Can you see that? It's exactly flat. If the tangent line is flat, that means the slope of the tangent is 0. Right? Because slope is rise over run. It doesn't rise or go down. It doesn't go up or down. So that means its slope is 0. That means the value of the velocity then is 0. Because the slope of this graph is 0, it means the value of the velocity graph is 0 here. And over here, the slope of the tangent line is some negative value. And it's probably the same as this. So this is negative, and whatever this was up high, this will be negative. And if I did it right, it should look like a straight line. Should be a straight line. It also should make sense if you think about math. This is a quadratic. It's an x squared. Take the derivative of an x squared. It gives you a linear function. It gives you an x. See, that should work. And furthermore, if I want to take a velocity graph and go down again, I do the derivative of that. So in this case right here, think about the derivative of this graph right here at this point. It's some negative value, right? Look at the slope of the tangent right here. Isn't it also some negative value and some same negative slope? And over here, the slope is also the same negative value. So in this case, it'd be some negative constant value. I hope that'll make sense too. When you take the derivative of like a, I don't know, 2x, the derivative will just be 2. In this case, if you do the derivative of this thing right here, if you do this right, you can actually end up extracting out of this the acceleration due to gravity. You can actually get that as negative 9.81 if you calibrate it properly. Isn't that a cool trick? Now, if you want to go up, then you just have to take the area under the curve. So that means if you're starting with a velocity curve, or starting with a velocity, and you're asked for something about displacement, then you can think, displacement is above velocity. So I'm going up, so I'll take the area under the curve. So in this case, I would take the area of this triangle here, let's just say. And that's how you can do it. So let's maybe look at an example. Put this all in perspective here. This is quite common, especially on paper 1. They love these kind of questions here. So, but also it could show up on paper 2 as well. So this kind of graph right here, let's just say it's a graph like this, and it goes like that. So we have some sort of function, and we have a velocity versus time here. Velocity versus time. We want the acceleration. Think about this. Acceleration, how is it related to velocity again? Go back to this little trick. You're given velocity. If you want acceleration, you're going down, aren't you? If you go down, you take the gradient. That's how you know to take the gradient of this graph. So at 2 seconds, let's see. Oops, something here got a little bit messed up here. Let me just see if I can grab these and move them. These should be like this. There we go. So if we do this then, I'm going to do this here at 2 seconds. Then it should look something like, see the gradient right here? If I drew a tangent line right here at 2 seconds, can you see that right here? It would look like this. It would be something flat, wouldn't it? And a gradient at 2 seconds, at t equals 2 seconds, the gradient is 0. So my acceleration is 0 as well. Is it 0 meters per second squared or just 0? Isn't that awesome? So you can actually deal with really, really kind of weird looking things, and you can totally do them. Maybe I'll just get this here. Oh no. I was trying to do something clever, but I guess I'm not that clever. I don't know. There we go. Took that one. I don't know. You know what? Forget it. I'll just leave it. Not worth the trouble. So I want to find the distance traveled. And again, I'm given a velocity graph. So think about it. If I want the distance traveled from velocity, think about it. Distance is up. That's a displacement, right? Displacement is a measure of distance. So if I want the distance traveled, I go up. Therefore, I have to take the area under the curve. So in this case, I'm going to need the area. So maybe I'll do this in a different color here. So I'll take the, so distance, distance equals the area under the curve. So here's the problem. I need to consider what's the area then under the curve in the first 3 seconds. And maybe it helps to split this up into 2 pieces. Can you see I'm going to have to take the area underneath this thing right here, and I'm going to have to take the area underneath this thing right here as well. I'll need that one. So maybe I'll say area of the triangle. Let's figure out that area. That area is, let's see, it's base times height divided by 2, isn't it? So the base is 1. The height is 5. And I divide that by 2. So I end up with 5 divided by 2, which is 2.5. Think about the units for this too. Area is length times width, right? Or in this case here, it's meters per second times seconds. If you think about that, meters per second with a second on the top, the seconds cancel out. You just get meters. Good news, that's a unit of distance. So even the units work out. I need the area of the sort of square part. You need to be really careful. The length is not 3. It goes from 1 to 3. So the distance from 1 to 3 is actually 2. And I multiply that by the height, which is 5. And it's a nice square, so just 2 times 5 suffices, right? I only divided by 2 here because I had to have a triangle. So here I have a square, so it's just this, which is 10 meters. So what's the total area then? So the distance traveled then is just 10 plus 2.5. So that equals 12.5 meters. Awesome! That's how you solve this. Forces and Newton's laws are usually something that people have seen a lot of times, but an understanding of it is still really important on your exams. So I really like that may the mass times acceleration be with you, because I hope you know that's why it's force, especially with these days of Star Wars movies coming out some more. So let's talk a little bit about free body diagrams. I think that's maybe something really important. You want to add up all the vectors to figure out the net force. And I put in F with a little subscript net. So for example, I mean this. It just doesn't turn out all that nicely with the way I wrote it. So it's like this, F with little subscript net. What that means, that's the result of adding all the different vectors up. So let's just say, there's a force acting on me this way, and there's a force acting on me also this way. If the two forces are equal and opposite, I am getting a force one way, I am getting a force the other way, and yet if they're equal and opposite, let's say they're both 2 newtons, so 2 newton that way, 2 newton that way, the end result is going to be 0 in this case. So therefore, the F net equals 0. And if net equals 0, here's what happens. It's really, really important that you understand this. There's no acceleration. This is the key thing here. Whoops, I can't even spell apparently. Oh God, really bad at writing here today. Acceleration. This is the key thing here. If there's no net force, there's no acceleration. You can still be in motion. This is the key thing. So let's just say I have this force this way, this force this way. I mean, yeah, I have no acceleration. That's because in this case, I'm still. But what if I was, driving in my car? I might have a forward force caused by the engine, from the sort of thrust or the sort of the forward action of the engine. But I might also have, the backwards result of all the friction. And if the net force is 0, it just means the vectors are canceling out. You can have it canceling out up and down as well. For example, right now as I speak to you, I'm sitting in a chair and my bum is actually having a force going downwards because of gravity. But the chair is also giving me an upwards force. It's called the normal force, or the reaction force. And this one is exactly equal to my downwards force. Therefore, I'm not accelerating up or down, right? I'm not like flying down or up or whatever. So just keep in mind, you could still be moving and have no acceleration. Just means constant motion, or you could be 0. This is an example. I saw this show up on an exam before, on a paper 1 actually. So for example, 3 different forces. So here, let's just say you get different forces. So 2 newtons, 7 newtons, 4 newtons, and they act on you. And here you're not told which way they act, which means, you might have the 2 newton this way. You could have the 7 newton, going that way, for example. Then you can have, the 4 newton maybe acting that way, let's just say. If that was the case, then what's the maximum? Let's just say that was 4. Let's just say I added up these ones, just the way I drew it. I would have 2 plus 4. They're both in sort of one direction, so that gives me 6 in one direction. I have 7 in the other direction, so 7 minus 6. I end up with a result of 1 newton, that way in this case, or 1 newton to the right. In this example here, we have 2 newtons, 7 newtons, and 4 newtons. What's the maximum resultant force you could have? Well, in this case, the maximum you could have is if you had them each on top of each other. In other words, you had the 2 newtons, then the 7 newtons, let's just say, and then the 4 newtons. It doesn't matter which order you do them, right? As long as you add up all 3 of the vectors in the same direction, that's the maximum you can have, right? This plus this plus this. In this case here, 7 plus 2 is 9. 9 plus 4 is 13, so that would be the maximum force you could have. Keep in mind, do you see it could be anything else though? Do you see in this case, I was able to make it 1 newton by going 7 to the left and 2 to the right and 4 to the right. So all these different combinations are possible. Just depends how you arrange them. Let's go maybe quickly through equilibrium. So equilibrium is what happens when the resultant force is zero. Just what I showed you before. So if the resultant force is zero, you are in equilibrium, but you can still be moving. An example of that, like I said, with a car, well, we could also do the same idea with a plane, for example. So right now, this plane right here has an upwards force, probably due to lift, has a downwards force due to its weight, so we could say gravity. It's going to have a forward force, we call that thrust. We often call that, at least in aviation. And it'll have a backwards force, we call that one F drag. And if it is not accelerating, it means the lift force and the gravity force are equal and opposite, they're cancelled out. And the forward thrust and the backwards drag caused by air resistance, because it's going through the air, they're all cancelling each other out. Now that doesn't mean your plane falls out of the sky, right? It just means you're not accelerating. Okay, so we'll say that again. So no acceleration. That was the key thing here. This is important, like, when you're in an airplane, for example, and they tell you at some point after you reach cruising altitude and they say, everybody's free to move around the cabin. That's usually when there's no more extra forces on you. So there's no more unbalanced forces, you could say. So that's why then it's safe to just walk around inside the airplane. But when you're taking off, for example, you can have more thrust and drag. So, you're really feeling an acceleration. They don't want people walking around. Then people can fall and get hurt and all that. Newton's first law. This is just one way of writing it, but an object at rest tends to stay at rest. An object in motion tends to stay in motion. Whoops, I actually wrote this kind of wrong, didn't I? Yeah, I'll have to take that out here. I'm going to remove this piece right here, actually. I'm just going to say object in motion tends to stay in motion as well, right? I just realized I had made a mistake. That's okay. Object in motion tends to stay in motion. That's the key one there too. Now, what I mean by this, it sounds really simple, and yet you really need to understand this to answer some of the exam questions. So, for example, if you're at rest, you're going to stay at rest unless you're acted on by an external unbalanced force. In other words, that unbalanced force, that's this F net. This is the unbalanced force. So if there is a net force, then you will cause this object that was at rest to not be at rest. Or just like if you have an object in motion, like that airplane, if you apply an unbalanced force, so in other words, if there is a net force, then it will change its motion in some way. This becomes very important for all sorts of examples, like a cyclist, for example. Can you imagine if you're biking and you're about to strike this, big obstacle here? As soon as you reach that obstacle here, here's your bike, right? So, there's your bike. After you hit it, and you go flying. Now, why do you go flying? That's because you and the bike initially were going in one direction, but what happens is when you hit this thing, the bike stops suddenly, but because you are a separate physics object, you are a separate object, you weren't tied to your bike. Therefore, when the bike stops, you're an object in motion, so you tend to stay in motion. So you're going to go in a linear, you're going to try to just keep going straight. Obviously, gravity then gets you. So that's why you keep going flying. This example here from Seinfeld about a ketchup bottle. Did you know actually that there is an efficient way to actually get the ketchup out of a ketchup bottle? If you try to hit the ketchup bottle from the top like that, that's really stupid. It turns out you're not using Newton's first law correctly. One of the best ways, imagine this is your ketchup bottle. Imagine my pen here is a ketchup bottle, okay? Put it at a roughly 45-degree angle. And what you should do is you should get the ketchup and the bottle, both of them going in one direction. So for example, let's just say you bring them down this way and bring your hand there to stop it suddenly. So if you go bang, you stop it. You're basically doing what the bike did. Imagine this, the bottle and the ketchup are two separate physics objects. And as you stop the bottle stops suddenly, but the ketchup wants to keep going. So if you just go bang, bang like this right here, usually the ketchup comes out right away. 45-degree angle, go bang like this, does it. Although, of course, a lot of ketchup bottles now are just squeezed ones, so who cares? Seatbelts, really important as well. That's why you want to be strapped into your car. Again, imagine this. You're driving in your car. You and the car are separate physics objects if you're not tied together. If the car runs into something and you hit something, the car stops suddenly. You keep going. So it's not like you fly through the window, it's that the car stops, you just keep going and the window happens to be in your way. That's why, bad things happen. So you do want to be strapped into your car. You want to be part of the physics. We have Newton's second law. That's a really important one. That one has some equations for it in your data booklet. We've got F equals ma. That's the more famous way of writing it. But there's actually a better way. There's a more complete way. This is a force. This is a vector. Force is a vector. Acceleration is a vector. Most people know F equals ma. They like that dumb joke with the Star Wars, right? May the force, which is mass times acceleration, be with you. So if we do this right here, we've also got another version that says that force is also the change in momentum over time. So P is momentum in kilogram meter per second. T is the time. F is the force. And we also have A is acceleration, and M is the mass. So we have an example here. So let's just say I'm pulled by the way, I really wanted to point this out. Really important. This right here is F net. In other words, this is your unbalanced force. This one here is really, really important. So here in this example, I have that I'm pulled by a velociraptor. So in this case, maybe like this, it's a ridiculous situation, but there we go. I just drew a little man here like this. You can see I'm not an artist. But the raptor's force on me is 52 newtons to the right. We're going to assume it's not on an angle. We'll make it really nice and simple, okay? So the force on me is 52 newtons to the right. But there's a friction force, right? Because I'm dragging on the ground, there's a friction force. In this case, it's going to act opposite to the motion. In this case, it's going to be 12 newtons acting on me to the left. Friction always opposes the motion, so I'll draw a shorter looking one, because it's supposed to be less. You could do it to scale, of course, but I'm being really sloppy here. Basically, I'm given the mass. You're told that I'm at rest. How long will it take me to travel 1 kilometer? So in other words, I'm still right here, and away I go. It's not exactly, this example is a little bit poor, because if I was initially at rest, I wouldn't have any friction force acting on me, but let's just calculate these. This will be to do with friction, and then you can actually calculate with the dynamic and static friction. But we're going to be a lot simpler here. We'll just ignore the dynamic and static friction components and just figure out this net result here. So in this case here, I have to figure out my net force. What happens when I add up my two vectors? If I add my 52 newtons vector to the right with the 12 newton vector to the left, I add them up. In this case, I have to subtract that one. So 52 minus 12, what's that? That should be 30, isn't it? Nope, sorry, 40. 40 newtons. And which way is it acting? It's to the right. So because of that, now that's my F net. So now I know that F net is going to be equal to ma. So that's going to tell me my acceleration. So now I know my acceleration is going to be F net over m. So in this case here, my net force is going to be 40 newtons. Yup, 40 newtons divided by my mass, which is 75 kilograms. Let me just work that out. So let me see here. So I've got 40 over 75. I've got my acceleration, which is 0.533 meters per second squared. This is my acceleration. I'm going to need this. Now, if I'm initially at rest, how long does it take to travel some distance? This is just an acceleration problem. This isn't so bad at all. So what I'm going to do then is just to deal with it as that. So acceleration. So I'm going to do U, V, A, S, T. It's in 1D, so it's super easy. There's no two dimensions to worry about. My initial speed is going to be 0. My final speed, I don't know it. I know my acceleration now is 0.533. My displacement, I know that. It's 1,000 meters. And my time, that's what I need to know. I need to know how long does it take me to travel 1 kilometer, accelerating at a constant acceleration of this. So if I look at this right here, then I need to take an equation, has a t in it, that doesn't have any v's in it. And let's see if I can figure out which one to do. So can you remember which equations that you have from your data booklet? Can you remember, or maybe look it up? Because you can actually do it. You'll see that, which one should I use? I should use S equals ut plus half at squared. I think that'll work because I don't have a v. That'll work. And u is 0. That makes it really nice and easy. So now I have, I want to solve for t. So I can take my 2 and multiply it by the s. So I can say 2s equals 2s over a. That equals t squared. So that means t is going to be plus or minus the square root of this. So I just need to put those numbers in. So I have 2 times my displacement, which is 1,000. All that divided by 0.533. Take the square root of that. I'll do that on my trusty old calculator here. Let's see if I can do it. So it's 2,000 divided by 0.533. Take that, square root it, and I get that the time is about 61.256 seconds. Then I need to think about how many digits can I use. I can use 2 digits to write it. So I'll just say t equals, in this case, just 61. Oops, maybe I'll write it over here so you can see better. So I'll say t equals 61 seconds. There we go. We've solved it. Now, Newton's third law is really nice and straightforward. Every action has an equal and opposite reaction. You just got to think about which is your action and reaction pair. What this means is if let's say you're standing on a skateboard by a wall and you push to the left onto the wall, what happens? The wall technically pushes back. That's why you push to the left and you actually end up going to the right, don't you? Just like jumping. Think about it carefully. How do you jump? I mean, I have a 4-year-old daughter. She doesn't think about jumping. She just knows how to do it, right? She doesn't know physics. She doesn't care. She already knows how to jump, doesn't she? Don't you? To jump, you have to push your legs down. Isn't that kind of weird? Think about it. You push your legs down, but that's because you know, without thinking about it, Newton's third law. If you push down against the earth, technically the earth will push up against you. That's why you'll jump. Same with a rocket. I love this Photoshop of a cat. It's like he's farting or something, but this is how it works in space, right? If you're going to eject a bunch of gases out of a rocket one way, then Newton's third law says that you will get a opposite reaction. You get a force to that way. That's how come you can actually have a rocket and actually have its engine work in space when there's no air. Some people originally thought, because there's nothing in space, you won't be able to have propulsion. You won't be able to move around in space. But Newton's third law says, oh, absolutely. It's the key thing for moving around in space. Throw something one way, you go the other way. So all you got to do in a spaceship, throw a bunch of stuff one way and you go that way. It's really simple. For friction, I really like this picture here with the terminal velocity. So it's terminal velociraptor, a question of your gravity in your air, right? It talks about, it's related to friction, at least. And I like this one here, which is an old trope from, do you remember this show? Whose Line Is It Anyway? It used to be with a British host, and they had it with Drew Carey later. I like this, welcome to physics, where the situations are made up and friction doesn't matter. In this case, friction will matter. So friction is a force that opposes the motion. It opposes the motion usually with a loss of energy in the term of heat. You can actually feel that, this sort of dumb example, but it really works, right? You just rub your hands really a lot. You notice they actually get really hot. So, I mean, that is friction. So let's just say I have this example here where some sort of dinosaur here or something is pulling on me. If this is the case, if I want to draw the different forces acting on me, I would have my force, due to my weight, an upwards force. I'd have a reaction force. We can call it R if you want for reaction force. Some people call that the normal force. Fine, same. So the reaction force and the weight. But I would also be feeling some sort of force applied here by this dinosaur, and I would also have some sort of force of friction. And if these two forces, the force applied and the friction force, are not equal, then I'm going to accelerate. So then I'll start moving. So there's this whole idea about this friction force and what actually happens with it. So this R is the reaction force. It's measured in newtons. It's also called the normal force. We have W as the weight. That's also in newtons. We have the friction force, which is in newtons. And this is the key thing, is that F, the friction force, and the reaction force, so the normal force, they're proportional. What that means is you have a bigger force of friction when you have a bigger reaction force. And it turns out they're related to each other by this relation here, that the slope of this, or the gradient of this, will be mu. Mu is a symbol we use for the coefficient of friction. Now, we have a general equation then. If you look at this, this is linearized, which means we can say F of friction is going to equal to some constant mu times R. If you look, see, this is the Y, this is the X, and that means this right here is the slope or the gradient. So it's going to look something like this. Okay? But we can get a little bit more specific because it depends on if you're moving or if you're not moving. So that's the next little page here. So if you're not moving, we call it static friction. So there we say that your force of friction, remember I said everywhere else that force of friction is equal to mu R, right? And it depends on what kind of mu we have, what kind of friction we're looking at. So the little subscript S means static, means not moving. So what it tells you is your force of friction is less than this. That means that this thing isn't moving. So like if you were trying to drag on the ground and I was just trying to pull a little bit, if I'm not pulling enough, it's not going to move. That's at that moment, I've got that force of friction is less than this value. However, if I can pull enough, then all of a sudden my force of friction, becomes, such that these two right here are equal to each other. When they're exactly equal, then it can just start moving. So that's that static friction coefficient. And once you are moving, then we can talk about dynamic friction coefficient. And that's why we use this mu d for dynamic. Okay, so that's the key thing is still thing is that's static coefficient of friction. This right here is moving, so it's dynamic. So that's why we put this subscript S and D. So let's take a look then if we can do a real example. And all of a sudden it starts off kind of okay looking, and then I've got an example that looks really horrible. So we'll deal with it. So you have an object. It's originally sitting on a horizontal board. So maybe I'll try to draw that. But then that board is raised up slowly, so that it makes an angle with the horizontal. So let's just say I draw that. So I could draw some sort of random board like this. Oh, that was a good straight line. There we go. That's theta. And this is my object. Doesn't matter what. World's most boring example because it's an object here, right? So I keep raising it until the this object starts to slide. So this could be like me just sitting there, and all of a sudden you just raise it. Oh, I fall down. You ever seen the old movie Titanic, for example? That happened to the people on it, sadly. But I mean, this happens with anything. It raises up, and eventually it's going to start sliding. Same thing with snow and avalanches, actually. So I mean, a lot of things relate exactly to this. So if we were to look at this, we need to know the normal reaction force, N. We could call it N, or we can call it R. I mean, some people call it N or R. It doesn't matter, right? And that's the problem with the IB. They use a lot of different notations sometimes. So this is one of these questions. I really want to show you this because it's really important to be able to break all this up into components here. So let's just say we look at this one. I'm going to take this, and right from this one, I have a downwards force. Huh? And this downwards force, I should call it maybe the weight. So I'll call it the weight maybe. But we know how that one's going to be related in a second here. We'll see. Now I've got this force right here, and that is actually this normal force here. That's this normal force, or you can say the reaction force. I can call it N or I can call it R. That is always perpendicular to the surface. So in this case, this surface is up at a weird angle. There it is. This is one of those you might be cringing. Oh God, what do I do? Oh yeah, we're going to have to break it up into components. So what I'm going to do is say this. I mean, this thing isn't flying upwards or downwards. I mean, it's not flying off the surface. It's sliding, but it's certainly not flying off the surface. So that means I know that I can make a vector that goes sort of down, and I can also make a vector that goes across. I'm going to break it up. And did you know, if you're really careful through geometry, this is also that same angle theta? Did you know that? This angle that you lifted up is the same as that angle that goes like that. This is one of these typical questions that a lot of people really struggle with. That's why I want to show you how to deal with it. So I've redrawn it like this now. We can also figure out a little step from what each of these things is, because we do know something about this. We know that the weight is going to be equal to something to do with theta, isn't it? I mean, we know it's the mass times gravity, but the problem is we don't know exactly what to do with it, right? So here's the thing. This thing right here is going to be related to the angle. In this case right here, it's going to be, and we have the mass times the force of gravity. So this is how it's going to work. The weight is always mass times force of gravity. So in this case, it's going to be mg. That'll be this piece down here. That straight down piece. That's mg right here. That's this force here. That's this weight. So weight is mg. Okay, so that's this one right here. However, how do I figure out the rest of these ones? Like, what's this piece and what's this piece? I need to figure those out. So I'm going to do this maybe in a different color. Look a little bit weird, but we can do this. So if this is mg, then this one right here, if you use your right angle triangle, SOHCAHTOA, you'll see that this one right here is the sine. That's because this one here is opposite to it like this. So I always remember that. So this tells me it's a sine. This one then will be mg sine theta. This one over here then will be mg cos theta. You can take your time and try to figure it out. If you use SOHCAHTOA, you'll get that. So now here's the issue then going on. What am I looking for? In this case right here, I have, first of all, I want the normal reaction force. Do you notice, by the way, that this one that's going up, this normal force going sort of up and left, it's exactly counteracted by this mg cos theta here. So actually this is really easy. My normal force is just equal to this mg cos theta, this one going down that way. It's exactly in that same plane. So I can just say it's mg cos theta. Nice, that was actually not so bad. I mean, it's drawing this is the hard part. Once you get used to these drawings, you'll see you can solve these. Find the coefficient of static friction. How do I do that? Well, I know that when I just have it start to slide, then I know that my static friction force, you could say, is, how should I say it? Yeah, I can say my force of static friction. I can call it Fs, S for static. I can say that just when it starts to move, that static friction force is going to be just counteracting. Remember, friction is always acting opposite to the motion. So if this thing right here is sliding down that way, the friction force is going to act that way. The static friction force is going to be that way. And this force right here, do you see which force that is going down that way? Do you see it's this arrow right here? It says mg sine theta. That's the one that's going down that hill. So this is the mg sine theta. And this is this Fs, this static friction force. And just when it's about to start sliding, those two forces are equal. So just at that moment, then I know that that Fs, that static friction force, is going to be exactly equal to that mg sine theta going down the hill. Right? But do you remember the equation for static friction? Static friction says that, let's see, the Fs in this case would be mu s times the reaction force. So I know, so I'll say, but I know my static friction force is equal to the static coefficient of friction here times the normal force, which in this case they called it N. Fine, we'll call it N then. So good news. Do we know what N is? We sure do. Do you see this? This is actually really awesome. We actually know what N is. N is this. So we shove it into here. So that means then that we can say that, maybe I'll do it in a different color now. That means I can say that Fs equals mu s times N, which is mg cos theta, right? That's from this piece. But we said it also equals mg sine theta. So now I have mg cos theta times mg sine theta. What do I do there? Do you notice the mg's can cancel out? So now I have mu s equals, let's see, I can do sine theta. Do you know I can divide by cosine? Because I have sine and I have cosine over here multiplied by the mu. So because of that I can divide by cos. And do you remember what sine over cos is? It's tangent. So phew, we actually figured it out. So this question is not very easy at all. And yet, once you get used to solving these kinds of questions, especially breaking it up in these component pieces, being really good at finding that mg cos theta, that mg sine theta, that is so important. So I would really recommend you learn how to do that. When we're speaking about work, energy, and power, I'm going to start off actually with work itself. I like this, I actually saw this on a t-shirt once, you know, physicists do it with energy. I get it, because we do everything with energy, and then it sounds a little bit naughty. Anyway, work itself. Let's actually look at this. This is an equation you get on your data booklet, so it's really important. And it goes like this. It goes work equals Fs cos theta. Now, F is the force that's applied. S is the displacement, so that's in meters. And work itself, that is actually a scalar. That means it's not a vector. It doesn't need direction. It's just a number. And the theta, that's the angle between the force and the displacement. So this is the really key thing right here. This is so important. Maybe I'll put a rectangle around it and say this is your work equation. Now there's something called the work energy theorem, and it really says that work is energy. And that's actually pretty obvious, I hope, because work is measured in joules, and so is energy. So work is a form of energy. So if you're going to do work on something or have work done against something, it means someone's expending energy or sort of giving energy somewhere. Work is really interesting because you can say that, you know, the work done, for example, if I'm going to hold my calculator here. I take my calculator and I hold it right now like this. Right now there's an applied force going upwards, right? And right now there's no displacement, so of course no work. If I displace it upwards, like this, do you see that my displacement is upwards? My applied force is upwards? So that means my angle between the two, theta, is 0. And if cosine of 0, that's actually just 1. So that's why in this case I have work done. I do work done against gravity. However, look at this special case. What if I take this calculator here and I walk with it? Let's say I walk to the side. Think carefully. The applied force to keep it from falling is still up. I know you think I have to apply a sideways force, but not really. I can be at constant motion. So what if I displace it sideways, but I apply a force upwards? Yes, I take this calculator and I walk that way. Have I done any work against gravity? No. And the reason not is because the angle between my applied force, in this case this way, and my displacement, in this case this way, the angle between them is 90 degrees. Cos of 90 is 0. Therefore, there's no work done. So it's a little bit of a sneaky one with work done, but the angle is important if they're 90 degrees to each other or 0 degrees to each other. Then we've got energy. I'm going fast because these are just mainly definitions. They're still important, but most people know them. So kinetic energy, that's the energy related to moving objects. We can say E with the subscript K. And you're given this in your data booklet. It says it's half mv squared. Most people know this, don't they? So that's that one there. That's energy. However, we have potential energy. I mean, most people know this one down here, right? Most people know that the potential energy, EP, we could say. Most people know that the potential energy, this is the simplistic version at least, is just mgh. That's the mass times the acceleration due to gravity times the height. That one becomes a lot less important when you talk about gravitation and later on, later topics. When you look at all this stuff, especially if you do HL. And then you have gravitational potential energy. You basically define it, and this is just a special case of the general things. But in this case, just talking about Earth, fine, you can use mgh. Then you have an equation for the potential energy of a spring. So you might need that at some point. So we'll put EP, and it's half K delta X squared, I think. Let me just make sure that's the case. I don't want to get it wrong. Yeah, that's it. So this is the case. So this one here is what you need for a spring. Remember what K is. K is a spring constant. X is just a displacement from equilibrium. Now we have a total energy, and that one is actually really important as well. But the good news, it's super easy. Right? Total energy is just ET, we'll just say. It's just the sum of the kinetic and the potential energy in this case. So that would be the total energy here. And it's usually conserved, which means the total energy is constant. And that sometimes you can use that to solve questions. Oops, I've made this a lot worse, haven't I? I made it look I was trying to make it look prettier, but I made it look worse. There we go. I'll just leave it like that. So that I think is really important, that the fact that energy is conserved is really key here. So what that means is that you can use energy. If you can find the total energy somewhere in the reaction or whatever is going on, then you know the total energy everywhere. You often use it for special cases like where the kinetic is 0, then you know the potential energy tells you the total energy because 0 plus potential is the total. Whereas by contrast, when it's the opposite, when there's no potential and it's all kinetic at some point in the motion, then you can have it where the kinetic then tells you the total energy. For example, for the equations for simple harmonic motion for HL students, they have that. That's how you can find the total energy of this spring. You just find it from the maximum kinetic energy, because at max kinetic energy, potential energy is 0. But just so you can see, total energy is still really important in a lot of different topics. Power. Now we use this word for power. Oh, by the way, sorry, I didn't really mention. Energy is measured in joules. I don't think I mentioned that anywhere, so I should probably put that here. Energy is mentioned in is measured in joules. Let's put that in there. That's really important here. So measure in joules. Important. Now we have power. We use the letter P for power, capital P, by the way. And actually, the main equation you're actually supposed to use is this one. That the power is FV. So that's power, that's force times the velocity. By the way, did I define everything here? Okay, good. So your power is your force times the velocity. Where the force is measured in, let's think about this. What will we measure force in? Hope you know, it's in newtons. Velocity is measured in meters per second squared. But power is a funny unit. It's called watts. That's why it's a really dumb joke, like, what's the unit of power? I guess you see that pun. So yeah, the power is measured in watts. That's a really important one. So I'm just going to draw a little thing around this. So this is the one. If you want the power, multiply the force times the velocity, and you get the power in watts. However, I think there's an even more important equation. It's really worth knowing, okay? So I'm going to put this in like big stars here. Whoop. See, I'm going to put it maybe in red. Here we go. Another equation that's I think even more important. Power is energy over time, which is measured in joules, isn't it? Energy, and time is measured in seconds. You could also say then, because of the work energy theorem from before, you could say it's the work done. Work in joules over time in seconds. And this equation comes in so much to help and save the day. This equation shows up in pretty much any topic, especially in topic 5 when you're talking about circuits. You can do things like this where you need this. You especially need it in topic 8 where you talk about power generation. So it's another version. It's still measured in watts, but it's also in joules per second. So this is how you convert from like something that looks really crazy with like electronic stuff. You know, like you say, oh, maybe, I don't know, you have a motor that lifts something up and it takes it this much time to lift it up. Then they say, using that, what's the current? You're like, what? How do I go from sort of topic 2, sort of mechanics, to sort of topic 5, sort of things related to electricity? So if that's the case, I mean, this is really important here, okay? So what you can do then with this equation, this allows you to mix and match between things because energy can be in any form. So if you can find the energy or you know something about the time, then you can get the power. And from the power, you can get other things. So this is a really key, really important equation for you. For momentum and impulse, I really like this picture here. Why science teachers should not be given playground duty. You ever seen those little sort of the metal spheres, you know, so they go like bang, bang, bang. That has to do with conservation of momentum. That would be awesome if you did that. I don't know why I laugh at that. Maybe I have kids. I could just imagine that. They'd be laughing their butts off, that's for sure. So we have something called momentum. And it seems like a really strange thing. I mean, we understand mass, I think, right? Most people get mass. And mass is something that's measured in kilograms. I'll put the units here. And velocity is measured in meters per second. That's something we can measure. Now, a lot of people think, why do we have momentum? Well, it turns out momentum is a really weird sounding thing, but it's really useful. First of all, the equation for momentum goes like this. P equals mv. That's the equation you get. This is the vector, and that's a vector. Super important. And yet, a lot of people think it's really strange. So what I mean by that is, I mean, this is in your data booklet, by the way. So this thing called momentum, let's look at the units for it, by the way. You don't have to memorize them. Let's look. Momentum is, let's see, what's mass measured in again? Oh yeah, kilograms. So that's why it's measured in kilograms. And then velocity, which is meters per second. So that's why it's a kilogram meters per second. That's the units for momentum. Seems like a strange thing, like an arbitrary thing. But it turns out in a lot of times in physics, or even in general science, you're trying to find some quantities that are conserved. And when I say conserved, I mean same before as after. Now, mass is often conserved, but not quite, right? It turns out, you know, E equals mc squared. Mass goes missing and gets turned into energy and weird stuff there. Velocity isn't necessarily conserved from before to after. Somebody figured out that if you multiply mass and velocity, just that product of mass and velocity, that thing we call momentum, that thing that's kind of arbitrary, that is conserved. So that's what we use. This is the reason why it's a useful unit, okay? Because momentum itself on its own doesn't really mean much to us. It's a product of mass and velocity. Yes, so what? Well, the reason why it's important is because of this idea here that it's conserved, which means the momentum before, like the total momentum before, will equal the total momentum after. And you use this to make predictions. You can use this to solve all sorts of crazy problems. So this is the main idea behind momentum conservation. So I'm going to give you an example here. I just went skiing recently, so that's why I was thinking about this. But I mean, it's very much set up like an IB question. I just changed the skier and snowboarder, but I mean, the idea is an IB idea here. They definitely do this. So let's just split everything. I like to split the question into two here. So we have a skier. Mass of the skier is 55 kilograms, and they run into a snowboarder of 70 kilograms. They have an inelastic collision. Do you know what inelastic means? Inelastic means they don't bounce. In other words, they stick together. Okay? They stick together. That's the important thing here. Inelastic means they stick together. Now, what's their final velocity after the collision, assuming no friction? And we're given that the skier, remember S means skier, is 20 meters per second east, and we have the snowboarder going 30 meters per second west. So I think maybe it helps to draw something here. So let's just try to draw this. I'm not a good artist, so I'm just going to say this is going to be the skier. And it's going to be M skier is 55 kilograms. And I have V skier is, what was it again? It was 20. So 20 meters per second. And I'll draw east being that way, just to the right. Now I'm going to draw the snowboarder. This is the snowboarder over here. They're going to the left, by the way. We're going to say the mass of the snowboarder is 70 kilograms. I'm just lining everything up just so it's going to be a lot easier to deal with. And the velocity of the snowboarder is 30 meters per second. Now what's really important then is, again, if you want to figure out what happens, I mean, in the end here, they stick together. We have this person and we have the skier here. Right? They're stuck together somehow. So maybe there's sort of tangle and they're angry with each other. Now we don't know necessarily which direction they're going to be going. We're going to have to figure that out. But we want to know their final velocity. And a good way to do that is, again, to calculate what is the thing that's conserved. And obviously you should know it since it's a video about momentum. Duh, he's probably going to use a momentum example. But this is an example where we need momentum. So let's actually find it here. So I'll try to solve for momentum here. I'll say, we'll do them in the same colors maybe. So I have momentum of the skier. Well, the momentum is just mass times velocity. So it's just 55 times 20. So that's 110 with an extra zero there. Kilogram meters per second. And that is in the direction of the travel. So that's that way. But now we also have the P of the snowboarder. The momentum of the snowboarder. Let's figure that out. That is 70 times 30. Which is 21 with two extra zeros. So this is this number here. Have I done? Yeah. Kilogram meters per second. But this is that way. It's left. Now, it helps to figure out what's the total momentum then. Total momentum. I'll see P total. It's just going to be the momentum of the snowboarder plus the momentum of the skier. In this case, then I have to do 2100 and 1100, and they're opposite directions. So I know the one that's going to win is the snowboarder. So 2100 minus 1100, that's going to give me 1000. So what I'm going to do then with that number 1000, I have to keep in mind which direction it is. So that gives me a direction to the left. And this is the only thing that's allowed to cross that line. What I mean by that line is going to define before the collision and after the collision. So that way, the only thing that can cross this line, the only thing that's useful, the only thing that's conserved is this total momentum. So now I know that this total momentum is also equal to this same number right here. So now I know that. So maybe I'll write it in a totally different color now. Now I know then that P total is equal to 1000 here as well. I even know the direction. It's to the left. Or west, sorry, west. So what happens here? Well, they're both stuck together. Well, now I know they're both going that way. And what I can do is figure out, well, I know the momentum equals the mass times the velocity. But I know that they're together, so it's going to be m1 plus m2. So in other words, it's going to be 55 plus 70, all that times the final velocity, which I don't know. Remember, I'm actually trying to find that. So I'm going to actually take a look at that and try to do it all here. I can actually put in for PT here. I've got 1000. So that's going to equal, because that's my total momentum. I know that 1000 equals this plus this times V. So that means that 1000 divided by 55 plus 70, that's going to equal V. So I'm going to get out my trusty calculator here and see if I can solve this. So I've got 55, what do I have to do? I have to do 1000 over, what was that, 125? I end up with 8. So my velocity then is 8 meters per second, and it's left. So in other words, it's west. That's what's going to happen. That's going to be the total velocity, or sorry, the velocity of both of them together. So that's how you can use this to solve things. Now comes something really important, which is impulse. Something that a lot of students, I think, really struggle with. You have an equation for it. You're actually told impulse, this is in your data booklet, impulse equals, how does it go? It goes F delta t equals, is it m delta v, or do they give you delta p? I think they just say delta p. You have to know that it's that. Here we go. This is the impulse equation. You get this in your data booklet. It looks just like this. So what does this mean? Well, impulse then is a change in momentum. That's the key thing. Okay, so impulse is a change in momentum. Oops, oh no. I need to have my pen out. There you go. It's a change in momentum. So if the momentum changes, then there's been an impulse. Now the important thing is this force and delta t. So what I'm going to do is I'm going to draw myself a graph of F and delta t. An impulse is really like a kick or a push or something like this. So I imagine it like, if I kicked, I don't know, a ball, then I would impart a force on that ball in a short amount of time. See that? So therefore, you can calculate then what the impulse is. So the way the impulse works is, this graph might be actually a weird shape. It might do some strange shape, like, I don't know, it's a common one that they like to use in the IB, like that. Like a nice sort of shape like this. And the question is, like, how do I find the impulse from just this one graph? And that brings up what I think is maybe one of the most useful things I'm going to show you, maybe in this whole course, is what to do if you're stuck and you have a graph. So this is an example here. This shows up all over the place. I use this trick pretty much everywhere. Whenever I'm not sure what to do, I just do this, and it almost always saves the day. So here's what you do. When you're stuck and you have a graph, so let's say I'm looking at a graph. I don't know what this is, okay? It doesn't even matter what it is. It could be any sort of shape. It can be anything. We have this thing called y, whatever that is, and it's got units of y. Like, I don't know what, whatever units. We have some thing x, and it's got units of x. So this could be like force, in this case. Force, which has units of newtons, and delta t, which has units of seconds, for example. Then you can figure out what to do here. So if you're not sure what to do with a graph, there's only three things you could really do with it. You could either read a value directly. So what I mean by that is, let's say you take an x thing, you go up here, then you go over there and get the y value, or vice versa. Take the y value, read it down, go to the x. You can either read the value directly, or you could be using the gradient. If you use the gradient of something, remember that means you have to take a tangent line and then you actually find the gradient of that line. The units of gradient, keep this in mind, the units of gradient will have, because remember how gradient goes? Gradient is, isn't it rise over run? So isn't that equal to delta y over delta x? Like, you have to say, take some sort of, like, let's say it was this right here. I would take some sort of gradient right here. Then I would find out, what was the delta y, what was the delta x? I could measure that. Well, I could do it right here if I was wondering something right here. I could take the gradient, but keep in mind what units it'll have. The units it'll have will be units of y divided by units of x. So it'll have those units. In this case, if I did the gradient of this bad boy over here, I would have, let's see, newtons per second. So in that case, it would be newtons per second. That's one other option. And the last option is you could take the area under the curve. So what I mean by that is you might actually, I don't know, maybe from here to here, maybe take the area under the curve right here. So the area is going to have units of, because of course you do length times width, right? You do, I should do area equals x times y, which in this case right here, then you can say that the area then will have units of whatever x was times whatever y was. In other words, these units, y times x. It'll have those units. So I basically look at the units to tell me what to do. So if I'm looking for a question and I'm they'll often give you a hint in the IB about what kind of things you're looking for. I just take a guess and see, does this get me closer to what I need or farther? So in this case, look at this carefully then. If I've got impulses F times delta t, multiplying a thing times a thing, is that a reading a value directly, gradient, or area under the curve? Hope you can see area under the curve is multiplying, isn't it? So you can then state with this that the impulse, because it's equal to F delta t, that's this thing times this thing, you could then say it's the area under the curve of F versus t. And what units will it have? You could say that impulse's units will be, let's see, newtons times seconds. So you can say impulse will have units of newton seconds. You could also say it has kilogram meters per second, but this is another unit. So you can also say that impulse has units of this. This is really important. So I hope this is going to really help you out to decode some of this strange stuff. In thermal physics, there's a lot of really important definitions you need to have. So I want to start with just these main three here. These are the ones I think the most important, you could say. So first of all, we have the word heat. And heat's the transfer of energy between a system and its surroundings. So we use a letter for heat. We actually use a very particular way of writing it. We write Q. Q is heat. So that's actually one thing that's actually pretty important here. I just want to make sure I have the right size pen here. So Q, that's the heat, and it's measured in joules. So this is the key thing here, okay? So Q is the heat, it's measured in joules. Then we have temperature. This is the most important one. It's used by far the most. So temperature is the average kinetic energy of the molecules. So you have to imagine inside of a gas, you have all these little molecules moving around. And because they're moving, they have an associated kinetic energy. Remember, kinetic energy is EK is half mv squared. So because they all have an associated kinetic energy, more energy means more temperature. Now obviously we write T as the temperature. Right, we write it with the letter T, which is good at least. And we use different units for temperature. We use degrees Celsius or we use Kelvin. We don't really use Fahrenheit. It's pretty much just Americans who use that. But so we have kinetic energy is related to half mv squared. And the key thing here then is going to be the fact that since kinetic energy relates to mass and speed, squared of course, and the mass doesn't really change within the molecules, at least. The molecules themselves have the same mass, but they might have a different speed. So really, because the kinetic energy is proportional to the speed squared, really you can say this, you can say that a larger, I just want to try to give you sort of an important thing here, the larger velocity. So if these particles are moving faster, that implies a larger EK, right? Larger velocity means larger kinetic energy. Therefore, maybe I'll write this in a different color even, maybe in red. You can say faster particles. This is the sort of really simplistic versions, but you'll see why. Faster particles means hotter, right? Because as they move faster, then the actual gas gets hotter. And that's really straightforward how it works. So the slower they go, the cooler it is. The faster they go, the hotter it is. And you might ask, hey, what happens if the particles technically stop? Well, that's actually when you're at absolute zero. That's 0 degrees Kelvin. By definition, is when there's no more motion, when V is equal to 0. Now we have something called internal energy as well. That one is useful a lot for HL especially. But we have U, which is the letter we use for that. We call it internal energy. And it's just the total kinetic plus potential energy. So because it's an energy, it's also measured in joules. And we could therefore say that U is equal to, you could say EK plus EP. You could say that. That's the total kinetic and total potential energy of all the different particles in that box, so to speak. Because here we're going to be talking about sort of ideal gases and this idea that all these little molecules are all sort of stuck in a box and they're all moving around in different directions. But this is really it. There's not actually much more to it than that. Specific heat capacity is something that causes students a lot of problems, but I really think it could be actually quite easy. I really like this meme here, this Doge, this many temperature, wow, such hot. Did you know they actually tried to create a Bitcoin currency called Doge coins? That's awesome. So let's talk about specific heat capacity. So it's formally defined as the energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Kelvin. So what this really means, I mean, this doesn't really make much sense to a lot of people, right? But think about it, it comes from a definition. And the definition is going to be this, this is the definition, sorry, but there's an equation for it. I think that's going to help. Remember, heat is a form of energy, so that's why we're going to use Q, because Q is heat. And it's going to be given by mc delta T. That's the equation we're going to need. So this is like the main equation here for specific heat capacity. And this is found in your data booklet, so you don't have to worry. So then we can define things, right? We can define, okay, well, what's the heat? The heat itself then is going to be measured in joules. Mass is measured in kilograms. Change in temperature will be in degrees Celsius, or it can be in Kelvin. And specific heat capacity then is this weird c. It's not the speed of light, by the way. Well, later on we have a c as the speed of light. In this case, in thermal physics, it's the specific heat capacity. What it is, it's a property of all materials. So different materials have different resistance, so to speak, to raising its temperature. So if you think about it, how much energy do you need to raise something's temperature? That is its specific heat capacity. So that means if something has a high specific heat capacity, it means you need a lot of energy to change its temperature. Some things are really, really easy to change their temperature, right? Some things are really good conductors of thermal energy. So as soon as you add a little bit of, energy to them, they get really hot really fast. So specific heat capacity, let's think about the units for it. If you want to get C by itself, let's just maybe do it off to the side. If you want to get C by itself, you'd end up with Q over M delta T, wouldn't you? See, because you get C, you'd have to divide by M, divide by delta T. If that's the case, what are the units of Q? That's joules. Mass is on the bottom, that means it's kilograms to the -1. And you got delta T, so that means it's degrees Celsius, -1. There you go. Now the trick to solving these questions is going to be to remember that heat gained equals heat lost. So what I mean by that is you can write yourself some sort of equation like Q gained, let's just say. So Q gained, and you can say Q lost. This is going to be the key thing here. So that way what you can do then, I'm just going to see if I can fix this here. What this means is you can set up an equation for each side of what's going on. So you can think, is somebody losing energy and someone gaining energy? And all the ones that are losing energy, put them on one side for Q lost. All the things that are gaining energy, put them on Q gained. Then just do a Q equals MC delta T equation for all of them. This is sort of the way to do it. So what I'm going to do is show you a really nice, really gross example, but you can totally solve this. This actually was found on a paper too, so this is why I have it here. So you pour 200 grams of tea at 95 degrees Celsius into a 150 gram glass cup, and that's initially at 25 degrees Celsius. What's the equilibrium temperature of the cup and the tea? And you're told the specific heat capacity of the tea. It's the same value as water, because tea is pretty much water. That's why they put that in there. And the glass is 840. So see, it's got a lower specific heat capacity, which means it doesn't take that much energy to raise its temperature. That means it's really easy to make it hotter. So the glass is part of the situation here. I think it maybe helps to draw things a little bit. So I'm going to try to draw, I guess, a cup. I'll try to draw that. Let's see if I can draw. Okay. Yeah, that's an all right cup, I guess. And now we've got some tea being poured in, don't we? So we've got tea being poured in. Now think about this. Which one is hotter? Which one is colder? Can you see you've got the tea that's really, really hot? So because the tea is hot, and we've got the cup right here, right? And we're assuming the cup is empty. The cup didn't have to be empty. It could have had water in it too at that temperature, right? Because you would assume that the cup and that water are already at equilibrium. But right now we have them not at equilibrium, right? Right now we've got the cup. Whoops, actually I probably shouldn't do that because it's not there yet. It's just like this. It's an empty cup and we've got some hot tea being chucked in here. So we need to write ourselves an equation of Q lost equals Q gained. So let's try to figure that out here if we can do it. So Q lost equals Q gained. So who's losing energy? Who is getting cooler? I hope it makes sense that the tea is going to get cooler as it meets the cup, and the cup's going to get hotter. So we're going to say this is going to be Q of the tea. It's going to sound like QT, QT. But it's going to be QT equals Q cup, I guess we could say. That's how we're going to set it up, because the tea loses energy, the cup gains energy. And if we can set it up like this, now it becomes a lot more straightforward. It's just a matter of bookkeeping. It's annoying, but it's doable. So let's figure out what happens with the tea. With the T, it's an M, T, C, T, delta T, T, which I know if you heard just what I'm saying, it sounds insane. But it's the mass of the T times the specific heat capacity of the T times the change in temperature. Same with the cup. So we're going to go like this, M cup, C cup, and delta T of the cup as well. So because of this then, how do we actually figure all this out? We can actually now start putting in the values. So the mass of the tea, let's see, it was, is it 200? No, this is 200 grams, which is 0.2 kilograms. Always put proper units here. So 0.2 kilograms times the specific heat capacity of the T, which is 4186, times a change in temperature of the T. Now here's the sneaky part. You got to think, we're going to have, delta T really means one temperature minus another one. So which one's going to be the largest, which is the smallest? We have to sort of figure that out. That's the only sort of sneaky part here. So we have a larger temperature minus a smaller temperature. Which is the larger or smaller? In other words, we're going to have an unknown T. We're just going to have a letter T we're going to try to solve for. Is the unknown, does it go here first or does it go second? Hope it makes sense. It goes second because that's going to be a smaller number here. That's the unknown. The bigger one is going to be the 95. That's because we know that when it reaches equilibrium, it'll be less than 95. So that's how we know it's 95 minus T. Now we can set it up on the right side. We can say M cup. So the mass of the cup is 0.15 kilograms. We have the specific heat capacity of the cup, which is 840, times delta T. And think about this now. Which value is largest? Hope it makes sense that now the T is larger. The equilibrium temperature that we're going to be solving for, that's going to be larger than the initial 25 degrees Celsius. So that, again, that was the sneaky part, I thought, was just notice this one and notice this one. One came first, one came second. You do have to figure that out because the equilibrium will be lower than 95, but the equilibrium will also be greater than 25. So we just do that to keep the numbers positive. Now it's just a matter of putting in the numbers and multiplying with our calculator. So I'm going to get out my trusty calculator here, and I'm going to do 0.2 times 4186 times 95. I end up with, this is a really ugly question, so 79534 minus, and I have to do 0.2 times 4186 times negative T. So that's why I'm going to have 0.2 times 4186. So I'm going to have minus 837.2 T. That's going to equal, this is really annoying, 0.15 times 840 T. So that's going to be 126 T minus 0.15 times 840, which is the same thing I just had, times 25, which in this case is 3150. So because that was a 3150, now I can, let's see, I can move all the different values, all the different terms with T on them. I'm going to put them on the same side. T as in this letter T. So I'm going to take this one and move it over here, and I'm going to take this one and move it over there. So then I'm going to be left with, let's see, 79534 plus that 3150, and I end up with 82684. I'm really annoyed by this question already. Equals, and I'm going to have 837.2 plus 126. So that moves over, becomes positive. I have this number, T. And then finally, to get T itself, then I'll do those two numbers divided by each other, right? Because I want to divide it out. Boy, this is really annoying. So I have 82684 divided by that answer. And I hope I get something that's correct here. Let's see. I get 85.84. Let's look at significant figures. How much am I allowed to use? I can use 2 digits to write this. So I'll say, therefore, the temperature is going to be 86 degrees Celsius. That's my final answer. So ugly question, yes. But the way to solve it, remember, is first think about what is losing temperature, what's gaining temperature. And you set yourself up a separate, Q lost equals Q gained equation. And when you do that, then you set up a Q equals MC delta T for each of them. And in case there were other players in here, just whoever lost energy, put them on one side, do a Q equals MC delta T for that one as well. So you might have had, Q equals MC delta T plus another MC delta T equals another MC delta T. So you can have basically all the terms that are gaining or losing temperature, just put them on the gaining or losing side, add up all the different Q's basically, and then solve for whatever you need to solve for. A specific latent heat is just related to a phase change. So what I mean by phase change is something changes from solid to liquid or gas or vice versa. That's why I actually love that little joke there, solid, liquid, gas. They all matter. Get it? Because they're all forms of matter. So we have the formal definition of it. So specific latent heat is the energy per unit mass absorbed or released during a phase change. So we have an equation for it. I'm going to write it down for you here. That's going to be really important, I think. So we have Q equals ML. So just like for a specific heat capacitor, we had Q equals MC delta T. Here we have Q equals ML, where Q is the heat. Remember, that's just the energy, isn't it? So energy, so that's measured in joules. M is the mass. Mass is measured in kilograms. And the specific latent heat is this property, right? It's the energy that's absorbed or released during a phase change. So it basically tells you how much energy is needed to change phases, or what's happening within a phase change, because maybe it can release energy as well. So the specific latent heat, in order to know the units for it, again, just try to figure out, if I get L by itself, to do that I have to get Q divided by M. So that would mean then I would have, let's see, joules per kilogram. There we go. That's it. Whenever you're working with these kinds of situations, so if you've got a question where you're supposed to solve, you've got a phase change happening and you've got things changing temperature, then all you would have to do is add a term, Q equals ML, for any phase changes. So for example, let's say you had T being put into, like we talked about in another example, T being put into a cup, but maybe that cup also had water in it, or maybe it had ice in it. So maybe it actually had ice. But then because of that, you'd have to also have an ML because it's phase change. So what you would do, you would have the T, you'd have the cup, you would have ice itself has to change phase. You'd have energy related to that. That's the Q equals ML. And then once it's changed phase, you also have that water then. So you have that sort of Q of that water. It has to also change temperature. So changing a temperature sort of costs in Q, and changing phase also costs in Q. So that's why we have a Q equals ML as far as that goes. I don't think I really need necessarily that example there, else it's going to get, maybe I'll leave it. So let's say we do a graph here. We're looking at a graph of the temperature of a substance versus the amount of energy that you add. So as we keep adding more and more energy, the temperature usually just goes right up, doesn't it? Not quite. That's the whole point of this. I'm going to show you this. So let's just say we do this in, maybe we'll do it in red. So when it's at really, really cold, so really negative temperature in Celsius, of course. In Kelvin, it'll be 0, right? But in Celsius, let's just say we start off really, really cold, and we add energy to it. We add heat. By adding heat, when it's already a solid, let's assume this is water. Let's assume this is H2O in solid form. So in this case, in this ice, like this dumb example here, like this dumb joke. So solid, we have ice here. The ice itself, if it's super cold, all the energy being added is going to go towards raising its temperature. In other words, it's going to go to, a Q equals MC delta T. That's for specific heat capacity. Okay, this one right here, though, that's the important one here for latent heat. So all the energy is going to be used to just raise its temperature until it reaches, the magic number is 0 degrees Celsius. So let's just say, so it goes up like this, and then it's going to remain constant. That's going to be a weird thing. I'll explain that in a second. After that, it's going to go up again. It's going to keep going up. And after that, it'll be constant again. And after that, it'll go up again. Now, the actual length of these things and the actual heights of these things, those depend on different factors, like what material you're using. In this case, if it's water or H2O, then it's going to be something like this. And this one, by the way, keeps going up forever. Not quite forever, but really high at least. So what this really means is here, the energy is using to actually heat. So you're actually using the energy to actually change the temperature. Do you notice? Energy being added, temperature goes up. But what happens right here? This is the important part. Right here. Why is it flat? You're adding energy. Why isn't the temperature going up? Well, that's when it's changing phase. So this is the important thing here. When it's changing phase, in this case right here, we could say it's melting, isn't it? So it's melting. So that's going to be really important here. Then, by the way, let's maybe, and up here then, it's going to be all liquid. After that, over here then, it's going to be boiling, you could say. Of course, we could reverse this process, couldn't we? But in this case, well, let's just talk about boiling that way. So that's what's been going on. And maybe I'll also put in sort of what is actually happening, like what kind of materials are we looking at here? Like what kind of phases do we have? So right here we have just solid. Right, we just have solid water, solid ice, I mean. Melting, we have solid ice plus water. because as it's melting, right, we have solid ice plus water. Here, though, at this point right here, again, so it basically, what's going to happen is this. As you add energy, the energy is used to raise the temperature, that's true, until it starts to melt. And during this melting, that's when you have a Q equals ml here going on. You're changing phase. As you change phase, the energy, before the energy was being used to excite those molecules. In other words, that energy was being used to raise the kinetic energy. Remember that's making those molecules go faster, and faster molecules means higher temperature. So that's what was happening here in this raising the temperature phase. When you're actually doing the melting, the energy is being used to break bonds. So you're still adding energy, it's just being used to break those bonds apart. So that's where the energy is going. It's not being used to raise the temperature remains constant. It's that the energy is being used to break bonds. So that's why you have solid plus ice. Solid ice plus water. Then what you have is over here, you have all water, don't you? Because it's above 0 degrees, but it's below 100. So here it's just water. Again, water then, the energy is being used to just raise the temperature of the water. In other words, it's being used to excite those water molecules, make them go faster. And remember, temperature is kinetic energy. So the faster they go, the higher temperature. And again, we reach a point here where we break phase, we change the phase again because we're breaking bonds again. So here we have water, we could say plus steam. That's the form for of gas for water, isn't it? So we have water plus steam. And of course, once you have all steam, then in other words, that's a gas, right? There we go. So what's being used after that? Again, the temperature is going up because the energy is being used to raise the temperature. And this goes up really, really high. That's why steam can be extremely hot. You ever seen like really bad movies? Sometimes they have someone get hurt by steam. I remember, what was the movie? I think it was called Commando with Arnold Schwarzenegger. It's a really bad movie. But I remember near the end, there's a bad guy and there's some steam that goes on his face. It sort of, burns his face. Yeah, steam can burn because it can be way hotter than 100 degrees. It can be many, many hundreds of degrees. But if you're going to deal with these kinds of questions in an IB format, you're probably just going to need to think about, which one changed phase? Add a Q equals ml to that side of the Q lost equals Q gained sort of equation. And then there you go, you got it. Ideal gases and the gas laws are really important for your exams. You could literally be asked for the definition of an ideal gas, and very often you're asked for questions relating to the ideal gas law. By the way, I just love this picture of this dog. I don't know why I find it so funny that he has no idea what he's doing. He's doing chemistry. I don't know why I find that so funny. Anyway, let's talk about an ideal gas. In physics, we love to take something really complicated and reduce it to something really simple because it's a lot easier to work with. So in this case, if we have a gas contains a bunch of different molecules going around. We're going to assume an ideal one is one where there's no forces between them. Because in real life, of course, they attract or repel each other and all sorts of things can happen. But ideal gases, we'll just say, nah, there's no forces between them. We'll just assume they just bounce off each other like billiard balls. And of course, we're going to assume that it works for all pressures and all volumes and all temperatures. So this is the sort of main definition. If you're asked what is an ideal gas, say something like this. This would be really good. That's the definition. Now, as far as the kinetic model of gases, it's a pretty straightforward idea. This idea that these molecules in the gas, they're just these little billiard balls, like I said, just sort of bouncing around, and they're just going along. And what happens, of course, they might bounce into each other. They might also bounce into the wall. So remember from the definition of temperature, that temperature is the average kinetic energy of those molecules. Remember, kinetic energy contains a speed. So really, the faster they move, the hotter the gas. Right? Because as they get faster, that's V gets bigger, and V squared is obviously still bigger, and then you have kinetic energy then goes up, and that's the temperature. So faster particles, hotter gases. Slower particles, cooler gas. How slow can they go? They can go to 0, and that's why it's at absolute 0 in that case. So that's the temperature. You also have to remember about volume. That as the volume itself of this box gets smaller, let's say you took that volume and you made it smaller. What's going to happen? The pressure is going to increase. So it maybe helps to talk about pressure. Pressure is just a force divided by an area. Okay, that's what it is. So pressure is just force divided by the area. That's sort of that's a definition of pressure. It's even in your data booklet. So this definition then, what this tells you, by the way, pressure is, we'll talk about, that's what this is right here. Pressure is just a force. So what happens divided by an area? So what happens is these molecules, as they bounce off each other and they bounce off the wall, when they bounce off the wall, they change momentum. And because of that, that means they're gonna impart a force to that wall because of that definition of impulse. Right? As you change momentum, there's an impulse, and an impulse is a change in force. Well, it's a force times a change in time, but so basically you're gonna have a force. They're gonna push against that wall, and depending on the size of that wall, then that can tell you about the pressure. Obviously, if there's less area, then the pressure will increase. So that hopefully is gonna make some sense to you. So that's really important, I think. Now let's go to the definition. Ooh, boy, I need to change this here. This is not number of molecules. I just realized I have a mistake here. I don't want that. So it's a number of, I just got to change this here because it's really important here. It's a number of, not molecules, moles. There we go, that should look a lot better. There we go. So the ideal gas law goes like this. The equation is as follows. It goes PV equals nRT. This is the equation you need. This is on your data booklet, so you don't have to memorize it, but it's really important. So first we'll talk about each of the different players in here, right? So the pressure, do you remember what units we use for pressure? So P here is pressure, it's not momentum, like from mechanics. This is pressure, which is in pascals. Then we have the volume. A volume is length times width times height, so that's in meters cubed. N is just a number of moles, and we'll talk about that in another video, what exactly this means. But this is a number of moles. It relates to the amount of material you have. Then R is just a constant. This big R is just a constant number. You don't have to memorize it. You can look it up. It's this. And finally, you have temperature. And temperature can be measured in degrees Celsius, or it can be in Kelvin. That's all you need, really, for all this here. So this is the ideal gas law. You could be asked there's lots of examples of questions that go like this, and the good news is they're not so bad. It's usually just fill in whatever numbers you need. Like they'll say like, okay, you have a pressure of this and a temperature of this, what's the volume? As long as you know how many moles there are. Or they'll tell you the moles and the temperature and the volume, say what's the pressure. So in this case, these are fairly straightforward seeming, but it's still really important to think about. And actually, I have a true story to tell you. You might find this funny or gross or I don't know what, but it's a true story. At some point, I used to be in the military, and then we were doing our pilot training, and they would put us in this big giant box to simulate high altitude. So what they do is they'd put us all in this box here, and they give us oxygen masks, so we're sort of connected to some O2. So we're all getting oxygen here, so we can breathe. And what they would do is they would simulate going up at high altitude. And to go to high altitude, what they would do, they would lower the pressure. So imagine then they took the pressure, made the pressure go down. And they would sort of see how you can do, and they do all these funny tests. Like they would have us play patty cake with each other, for example, and test our hand-eye coordination. So this is all really funny stuff. But the thing I noticed that struck me the most is the moment I stepped into this room, I thought, God, it smells like, it's like someone just like had an accident in their pants. Like, it smelled like the worst farts ever. And I thought like, what happened in this room before me? What's really funny is that as soon as they turned on this machine to simulate high altitude, I knew exactly what had happened. And I sort of forgot about this equation, right? I was just worried about, passing my test. So I wanted to get through all this, right? So it turns out when you lower the pressure, if the temperature remains the same, lower the pressure. Do you know what happens to volume? Volume goes up. And you're made of gases. You have gases in you. So imagine this. They lower the pressure in the room. Of course, your ears pop and all these weird things happen, right? So you sort of, you kind of adjust your ears. But as they lower the pressure, all the gases in you want to go out because the volume wants to expand, right? If pressure goes down, volume wants to go up. So that meant as soon as they turned on this machine and they lowered the pressure, I was burping and farting like crazy because all your gases want to go out. So now I was like, now I know why this machine stinks so bad. So I thought that was pretty funny. By the way, it looks like it says cork, and I don't mean cork here. Oh God, what have I done? I just meant to say C or K. So PV equals nRT, yes. Now we have the gas laws. These are ones that are not addressed as often, but if it comes up, it's really important to know this. So constant volume, we have a gas law for this. If you have constant volume, that means V equals constant, right? And now I'm just going to remind you about that equation, PV equals nRT. So if V is constant, look carefully at this equation then. If V is constant, that means we essentially make it 1, or we leave it the same. You can see then that P, because we ignore the N and the R, they're just constant numbers as well. So V is constant, N is constant, R is constant. You can see that P is just proportional to T. So I'm going to say that P is proportional to T. That means if I did a graph of pressure versus temperature, then I could get, it depends on the temperature, if I graph this with Kelvin or Celsius. So that's going to make a difference if I graph this in Kelvin or Celsius. Let's assume it's in Kelvin. That means I can have 0, right? I can have 0 temperature here. So in this case right here, let's just say it'll go something like, if it's proportional, it'll be a linear graph. It'll be something like that. So what that means is, as temperature goes up, what happens then? Pressure goes up. Right? That's the important thing here. I think this is a key thing. So yes, temperature goes up, pressure goes up. Charles's law, which is where something is, the pressure is constant. I mean, in thermodynamics, we have special rules for all these. Here we can say this is isovolumetric, and we can say this is isobaric, and this is isothermal. But I mean, it's what you really need for the IB is just you need to know that pressure is constant. And if the pressure is constant, let's look at this same equation. If P is constant, that means you can see that V is proportional to T. So the volume is proportional to temperature. So that means I can do a graph of volume and temperature in Kelvin, and I could have something like that. So again, as temperature goes up, I'll just put arrows, right? V goes up. So that means higher temperature means larger volume. Finally, we have Boyle's law where T is constant, because see, we're making each of these 3 main players here constant. So if the temperature is constant, let's look what happens. You make T constant, that means P times V is some constant. If that makes any sense, what you can do then, you can take P then is going to equal 1 over V, well, some constant times, something times it. Right? Because I get P on its own, that means I got to divide the V. So what I can say then is the pressure is proportional to 1 over the volume. And that's going to be a little bit weird. So this means that if I do a graph of pressure versus volume, I'm not going to get a linear function. Do you remember what the graph of 1 over x looks like? It goes like this. So that's the graph. So that's a weird one. Okay, so just so you know, that's what happens with these these are called isotherms. In thermodynamics, we call these isotherms. But just so you know, this is the main theory that you needed from the gas laws. Okay, I'm going to talk to you about moles and Avogadro. First of all, I love this joke. What do chemists use to make guacamole? Avogadros. Because of course you need avocados. Oh, okay, so let's talk about moles and Avogadro first of all. What is a mole? A mole is the amount of a substance. So I mean, in chemistry it becomes important to count different amounts, and this is what we use in chemistry. But of course in physics we steal from chemists all the time. So there we go. The equation we're going to need for this is in your data booklet. It goes N equals capital N over N with a little a. This is the equation you need. Luckily, you don't have to memorize it. It's there for you in your data booklet. So what this really means, the N is the number of moles. This is the important thing to be counting. You're trying to count these things. Capital N is the number of atoms you have. And Na, this N with a little subscript a, that's 6.02 times 10 to the 23, which is known as Avogadro's constant. That's the amount of atoms in 1 mole of a material. So hopefully it makes sense then that there's this many atoms in 1 mole. If you have 2 moles, you must have double the number of atoms, So if you have like 2 Na over Na, then you'll get N equals 2. So basically this Na tells you the number of atoms in 1 mole. This tells you how many moles you have. I hope that'll make some sense. What I'll do is I'll show you an example, one that showed up on an exam that doesn't seem quite so simple, and that's why I wanted to give you this here. So we have an example here where you have 8 grams of helium gas, and helium has a mass number of 4. You might remember that from atomic physics. Remember helium? Helium is, let's write it like this. He, which is 2, 4. It's got 4 nucleons, we say, and we know it has 2 protons, so we know it has 2 protons and then 2 neutrons. In any case, it's got a mass number of 4, and it's sitting there at a temperature of 20 degrees Celsius. It's at a pressure of, it's a bit awkward how I typed it out. Let's put maybe a comma there. Right, it's a little bit nicer to see. So it's 100,000 pascals. what's the volume of the gas? Now, of course, we can use the ideal gas equation. Remember that one? PV equals nRT. You can look that one up if you need to. And from that, then we could get the volume pretty easily, right? V then equals, let's see, it's nRT, and I would just divide by P. Awesome. Okay. Here's the problem, though. I don't know N. You see that I know everything else. I need to know N. So this is my issue. Is what is N? I'm not told how many moles I have. So that's why I've got a little trick for you. There's a trick it really helps to know. I've seen this show up a few times on exams. It's a nice trick to know. If you have an element of mass number A, in this case 4, then it's going to have a molar mass of 8 grams. What that means is that 1 mole of that material will be 4 grams. So what you can do then, you can use this idea. Because what I'll maybe do on the side, I'll say, fine, that means N equals, let's see, we have 8 grams of the material. And we know that it normally, how's this? 1 mole of this material is going to be 4 grams. So I know that I'm actually sitting there with 8 grams, right? Let me just maybe make my mole a little bit nicer to look at because I just hate how I wrote it. See that? There we go. 1 mole equals 4 grams. So if I know that 1 mole of this gas of helium weighs 4 grams, I shouldn't say weigh, has a mass of 4 grams, the fact that I have 8 should tell me how many moles I have. And I hope this makes sense, that then I get N equals 2. You see that? I have N equals 2 moles. So again, just to make sure this makes sense, because of this trick, it tells you that this mass number of 4 tells you that 1 mole of helium is going to have a mass of 4 grams. That's the definition, right? A molar mass. That means a mass of 1 mole. So because helium has a mass number of 4, it's got a molar mass of 4 grams. That means 1 mole is 4 grams. I've got 8 grams of it. 8 is double 4. So that's how I know I have 2 moles, if that makes any sense. I've got double the amount of the molar mass. So now I know that N equals 2, and from there I can then plug in and say, okay, let's actually put it all in. So then V equals N, which now I know is 2, times R, and I can look that up. It's 8.31, I just gotta look it up here. What is it? 8.314, yeah. We have the temperature, which is 20 degrees Celsius, but what we need to do is put it in Kelvin. We always need the Kelvin temperature for this. So in this case here, we'll say 20 plus 273, because that's 0 degrees Celsius is 273 Kelvin. So because that, I have to put that in there and then divide that by the pressure, which is 100,000 pascals, or I could say it's 10 to the 5. So I put all that into my calculator, and let's try that out. So we'll do 8.314 times 2 times 293. I get that. I divide that by 100,000, and I end up with a volume of 0.04938, something like that. Let's look at how many decimals I should use. I should use 2. So I could say the volume is, say, 4.9, let's say, times 10 to the negative 2 meters cubed. Like I said, that's my answer for my volume. Now, how many atoms of helium are there? Luckily, that's really easy now, because we can just use this equation that N equals capital N over Na. The number of moles equals the number of atoms divided by Avogadro's number. In this case, I want to solve for N. That's the number of atoms. Remember that from before? N is the number of atoms. This one right here. So because of that, I just get N equals little n, the number of moles, times Avogadro's number. So the number of moles, remember, we found was 2. So I put in 2 there. And I get Avogadro's number was 6.02 times 10 to the 23. And I end up with a grand total of, oh, that's a big number, isn't it? This will be 1.2. I'm only allowed 2 digits, right? So it'll end up being 1.2, because the other decimals won't matter, times 10 to the 20, in this case 4, because 2 times 6 is 12, so that adds 1 more. So 1.2 times 10 to the 24 atoms, which is lots, but it should make sense that 1 mole, I mean, it's got more than 1 mole. So there you go. That's how you can use a kind of sneaky one, right? The sneaky part was knowing this trick here, that the mass number A has a molar mass of 8 grams. Simple harmonic motion is something that's seen by students as not so simple. That's why I have that dumb joke there from Austin Powers, right? Simple harmonic motion, so simple. It's a kind of motion that is a little bit difficult to describe for many people. First of all, people think that it's just something that repeats. But there you're confusing periodic with simple harmonic motion. Something that's periodic is something that sort of the motion repeats, that's true, like a clock face or something like that, or like your heart beating, but doesn't necessarily make it simple harmonic motion. So we're going to use this short form SHM for simple harmonic motion, and we have a definition for it. And we say this. This is actually a really important definition. I'm going to put it in green. We're going to say this. If, now watch carefully what this here means here. This right here. This means the acceleration. Remember what this alpha symbol means? It means proportional to, and it's going to be negative x. This is going to be what we need here. Now, what does this mean? It means that the acceleration is equal to some number times x. Right? That's what the proportional means, and it happens to have a negative there. Let's first define a few things here. Make sure we remember what acceleration is measured in. Do you remember the units for acceleration? Hopefully you're screaming at the screen right now. It's meters per second squared. Displacement from equilibrium is in meters. So let's maybe, as an example, maybe I'll just talk about something like, one example could be a pendulum. So imagine that you have a pendulum. So can you imagine this pen right here? There's my pendulum. Get it? It's a pen. Oh, I'm really proud of myself for that one. That wasn't planned at all. But imagine that I take my pendulum and I have it going back and forth like this. This right here, obviously if I do it right now, it's not going to work because there's a lot of friction from my hand. But imagine it's going back and forth, okay? As the pendulum swings back and forth, it's going to undergo simple harmonic motion. So there's a few things that are going to be really important, okay? First of all, maybe we can even write it down here. Well, let's say here, the acceleration, I'll put it maybe in blue. So we'll say the acceleration is proportional to, this is going to be important here, okay? And proportional to the displacement, that's true. That's just because it's linearly, it's proportional. In other words, the more displacement you have, the more acceleration you have. And I'll explain this in just a second. This will be more important. But it's also, let me say this. The acceleration is also proportional. Actually, no, let's say this. I can say the acceleration, I can say acts in the opposite, let's put this down, opposite direction to the displacement. I think this will be a really good definition here if we do it this way. Displacement. So I'll put this here around. This is sort of the words version of what this here means. There's two pieces to this, right? A is proportional to x, and also A is, negative. So what this is going to mean, maybe this will first of all be nice to show you a graph, and then I'll explain it more in context here. So what I'll do is I'll show you with a graph here how this graph goes. This is an equation. If it's proportional to, do you see you can put some number in front of it? So we can say A equals some constant. I'm going to put a negative in front of it. It's going to be some constant times x. It's going to have some number there. Now it turns out if you're an HL, you're going to learn that constant is something called omega squared. It's just a constant. Now keep in mind that square doesn't make it a quadratic. This is just a number squared. Okay, so it turns out, you don't have to know this for SL, but for HL you do. For SL, you just say A is equal to negative some number times x, which you don't know. In HL, you have to know, oh, it's called omega squared, and that's what's beside it. So what does this mean? This looks like a linear graph, doesn't it? That means it's a straight line graph. It goes through the origin because there's no plus or minus anything here. And it's got a negative slope. So what that means is it's going to be a graph that goes something like, let me see if I can draw it. Oh, I hope I can. There we go, there. That looks great. So this would be an example of this equation here. That acceleration is proportional to negative x. That means it's a linear graph, but it doesn't go up. It actually goes down because it's got the negative in front of it. Now, what in the world does that mean? I think it's really important to understand. First of all, this graph that I just showed you, that is the most common thing you're asked about, especially for the physics SL portion here. This is the most common thing they ask you. It's often a definition about being proportional to displacement or acting in opposite direction, or it's going to be literally just which is the graph for SHM. You're like, oh, that one. If you remember the definition, that tells you the graph, or vice versa. The graph tells you the definition. So to think a little bit more about it, let's look at this. Let's imagine then that I've got my pendulum. Let's talk about this a little bit more. So remember, an acceleration is related to a force, isn't it? Because of Newton's second law. So if you have a force, you have an acceleration. So watch this carefully. As I pull this right here back, think about this now. Right now, as I pull it back, I've displaced it that way, right? There's a displacement going this way. Which way is the force going? The force is going to act that way, isn't it? Because gravity is sort of acting that way. So even though I've displaced it that way, force is acting opposite in direction. See that? And the more I displace it, the more force there will be. That explains, hopefully, on this graph, for example, why when you have a positive x, displacement, you have a larger acceleration. Remember, acceleration is related to force, right? The more force you have, the more acceleration. Conversely, if you go in the negative direction, so let's just say you go the opposite direction, that means in this case I'm going negative x, then my acceleration is in that way. It's always acting opposite to the motion. So I think that is one good way to sort of think about this. So that's SHM. What I'm going to show you then is another basic definition, really important. I like this SMH. Isn't that supposed to be shaking my head, right? But it's like SMH, isn't that simple harmonic motion? No. Let's do a simple example here. A mass on a spring that moves back and forth. I figured it would be good to not just do pendulums. So imagine then you have this mass. So you have that something, it's sitting on a frictionless surface, we'll assume, and it's got springs on both sides. And what you do with it, you take it, you stretch it, and you let it go. Can you think of what motion it'll do? It'll hopefully, if you think it right, it'll go like this, right? It'll go back and forth and back and forth. So it's going to have something called equilibrium. And we're going to call that x. Remember we said x was the displacement from equilibrium. So in this case here, we're going to state then that x equals 0 at this point. Over here at maximum displacement, as far as it goes, keep in mind it's symmetric, so it also does the same on the other side. Let's say we can say here x equals max. Now let's think about the potential energy here for both cases. In a spring or some sort of situation like this, can you think about this? Is there any potential energy, you think, when it's sitting right at its equilibrium? I mean, potential kind of means like stored energy. In this case, it doesn't have any stored energy when it's right in the middle. It's happy, perfectly happy, so we could say it's 0. Whereas the potential energy, in this case right here, where it's at maximum displacement, is also at maximum. It's because we have an equation for this, right, for the energy of a spring. Now we can also talk about the velocity at both of these cases, because it is a dynamic situation. I've drawn a stupid drawing here, but it actually is something that's moving. So if you imagine it moving, think about this right at this point, right at equilibrium, right in the middle, as it's passing by and going back and forth. What is its speed right as it's passing that middle point? Is it at maximum or at 0 as it's going like this, back and forth? Hope you can see it's at a maximum value. So we're going to say V is max here. And if V is max, did you know we can also do EK, kinetic energy, which is half mv squared. So if V is at a maximum, then the kinetic energy is at a maximum. Conversely, let's look at this at its maximum displacement over here. It stops, doesn't it? So right there when it stops, that means V is 0. And if V is 0, since EK, the kinetic energy, is half mv squared, and that's also 0. So this is all you really need. This idea, this understanding right here, this is how I can generate each of these two graphs here. And I'm going to show those graphs. You need to know those as well. So let's talk about these graphs here. Let's do a graph for energy versus displacement. Okay, so we'll consider the energy on the y-axis, displacement on the x-axis. That means that it's going to be limited. It's going to be bound in displacement, won't it? It doesn't go forever, because this displacement actually goes to a certain value and then a certain value. We normally call that displacement, the maximum displacement, usually x0 we call it, the maximum displacement here. We call that x0. Which is weird because you'd think that that's not when x equals 0. Which is what we call maximum displacement, or the amplitude. In this case right here, as this thing goes along, let's think carefully about the energies. Let's deal with potential energy first, maybe. At x equals 0, so at 0x right here, it's got a potential energy of 0, so I'm going to draw a dot there. Okay, good. At maximum displacement, it has a maximum potential energy. So in this case, that means at one maximum, I don't know, I'll pick maybe right here. Let's just say I'll pick that right there and that right there. The point will actually go maybe up here to some maximum. And because it's symmetric, it also does that. It has a nice smooth curve, so it'll be something like this. And I'll label it E, P. Now for the kinetic, it goes very similarly, only opposite. Let's look at this. The kinetic, that one is at a maximum at 0. So at x equals 0, it's at a maximum kinetic energy because it's moving as fast as it can. And at maximum displacement, kinetic energy is 0. So you can go here and here, right? Because it's symmetric. Again, it's a nice smooth curve, so it goes like this. So that's, oh, I drew that poorly. I'll try to do it again here a little bit better. There, that's better. EK. There we go. We have kinetic and potential. And do you remember how we have an equation for total energy? Remember that total energy is just the kinetic plus the potential? So if you think about that, that means that if you add up like 0 plus 1, whatever this unit is, that you have a point here. And if you add 0 plus 1, you get this. And 0 plus 1, you get this. And even half and half. So you end up with, if you do it right, you end up with a straight line going across total energy. And you can see the total energy is conserved. It's the same. Thank goodness that's how it's supposed to work. So this thing is actually bound. What if we did this same kind of graph, but this time with time? That means now we sort of let it go and see what happens. Now it does depend on how you decide your time is 0. In other words, do you decide that the kinetic is 0 at t equals 0, or do you decide that the potential is 0? It depends on when you start your timer. Imagine as it's going back and forth. Do you start your timer right at when it's at a maximum? You know, click, and then you go like this. Or do you start it when it's at its equilibrium? Let's assume we did it at the maximum. Okay, let's assume at t equals 0, you're at maximum displacement. So let's see what happens then with the different values here. So let's do potential. At t equals 0, you're at maximum displacement, which is up here. So what's your potential? Your potential is maximum, some maximum value. Of course, at some time, it's going to be down to 0, right? And then it's going to go back up again. So over time, it's actually going to do some sort of, curve like this. I'm drawing it poorly there, but it'll be something like this. It'll oscillate like this. This will be the graph for potential. The kinetic will do the opposite. And hopefully that makes sense, because if this at maximum displacement, the kinetic energy will be 0. So that means at t equals 0, it's 0 here. And of course it goes up and down and up and down. So it does the opposite. So it goes basically like this, like this, and like this, and like this, and continues forever. Well, until it stops moving, I guess. That's EK. And good news, and remember, this one does go forever. Like both of these graphs actually do go as far as you need them to go. And we can do the same thing with total energy. Total energy is this nice straight line that goes right across the top, ET. This is all the information you need to be able to solve any of the physics SL questions about simple harmonic motion. If we're going to talk about properties of waves, it's important to know the wave equation. First, I really like this joke here. Calculating frequency, it's so easy, it hurts. Actually, I've heard another one too where it says it mega hurts, right? But okay. So we'll do the wave equation. Oh wait, I have another joke for you. Here's a really bad joke. Ready? If you saw a light wave, would you wave back? So we'll do the wave equation. Normally it's written as V equals F lambda, but I think it shows up as C equals F lambda in your data booklet here. Either way, it's V or C equals F lambda. So we could also write it with a V here. It doesn't really matter. It could also be a V. So if we say V equals F lambda as well, that's also the same thing. What does this mean? Well, speed, that's V. So if we talk about the speed itself, what's speed measured in? That's in meters per second. And if it was light, right? If it was light, then do you know what the speed of light is? Do you hopefully know that? You should know that C is the speed of light. And it is really fast, right? It is, do you remember? You don't have to remember, you can actually look it up, but it's 3 times 10 to the 8 meters per second. That is pretty fast, right? That means it goes, let's see, we can put it in kilometers. That would be times 10 to the 5. So that would be 300,000 kilometers in 1 second. So that is pretty quick, yeah. If it's a speed of a wave, like a water wave or whatever, then just put in V equals F lambda. If it's light, then put in C equals F lambda, just because light speed is that value, C. What about the frequency? The frequency, which is something we haven't quite talked about yet, but the frequency is measured in hertz, like that awesomeness there. They're so easy, it hurts. Or it can be in seconds to the -1, because that's really what it is. A hertz is 1 over a second. It's supposed to be like cycles per second. Think about your computer. The speed that your computer actually does calculations. Don't we do it in hertz, like gigahertz? Right? That means in billions of calculations every second. So this idea of hertz and megahertz and gigahertz, that's really important, isn't it? So this is actually pretty important to know about. Then this is a Greek symbol lambda. Lambda is the wavelength, and that's just measured in meters. So this is the wave equation. It's actually pretty straightforward. There's nothing really much to it. You'll be given, sometimes you'll actually have to use this. It's this really nice converter though between frequency and wavelength and vice versa. So if you start with frequencies and wonder what the wavelength is, or wavelength and want to know what the frequency is, then this is a really good way to do it, I think. Let's go here to features of graphs. I love this hipster dog here. This dog is so hipster, right? My favorite frequency is 50,000 hertz because that's what dogs can hear at. And of course, that's a frequency that we can't hear. That's why he's like, you probably never heard it before. What a douchey hipster dog. So, oh, that's just a cute dog. He's probably minding his own business, and his owner probably, or his person probably just put that around him. Don't want to trigger anyone with the word owner. It's true, you don't technically own, but there we go. Features of graphs. If we're going to do displacement against position, and I'm going to do another graph of displacement versus time, they're going to be different. So I'll do a graph. Let's see here. Let's draw ourselves a nice displacement versus position sort of graph. Something like this. Now we could have a number of features that we could actually try to measure. First of all, we could measure from the middle of the graph to the top of the graph, we could measure something we call the amplitude. Okay, the amplitude, and that's going to be measured in meters because we're measuring a length. Keep in mind that's also the same as this. That's also the amplitude. Right? So it's the distance that you go from the middle of this wave to the top or the middle to the bottom. That's the amplitude. And if we measure this distance across here, this distance from a peak to a peak, for example, like that distance right there, in this case right here, because it's position, we're measuring an actual length, then we know this is going to be lambda, which is the wavelength. That's the thing we need to know about. And that's measured in meters. So this is really important. Now keep in mind, you could also measure the length right here. The length of the wave can be done from the bottom to bottom here, what we call a trough to a trough. It can be a crest to a crest. It can be from the middle here to the next middle right here. It can be also here. This is also the wavelength here. There's a lot of ways of measuring, the period, as we call it, of a wave, or in this case, the wavelength. So there's a lot of ways of doing it. This is just one way. We can also look at displacement versus time graph. So here we have a totally different thing. Maybe I'll just draw another wavy looking wave though, just to be sure. And it goes on forever. And what we can do, of course, still, the height is still the amplitude. So that hasn't changed. So this right here, still the amplitude. Okay, with amplitude. Still the amplitude there. But this time, the length that you're measuring here is something very, very different here. This length right here that you're measuring from here to here. Think about it. That's a length that you measure in units of time. That's why we call this the period of oscillation. It'll be measured in seconds. So the period is going to be measured in seconds. So that'll be like the time it takes to do a full cycle. Or it could have been, remember, from a trough to a trough or from the middle to a middle. It'll still give you the period. So these are the main features you need to be able to do with graphs. You need to be able to look at a graph and tell what happens. And I actually want to bring up a very typical kind of IB question, actually, now that I think of it. They love to give you one of these graphs, especially with position, and they would say something like, it's not formally asked here. I didn't do it as a formal question, but I think it's really important. Imagine you have a wave like this, and what they'll do is they'll tell you, you have some particles that are sitting along that wave. So let's just say you have some situation like this right here, and you have a wave that's going like this, but they'll tell you the wave itself, the wave is actually traveling that way. Okay, and then they'll say, all right, you have a particle that's sitting right here, for example. What will that particle's motion be right here at this point? So what this means is that it's not allowed to move left and right. Okay, we're fixing the position here in this case. We'll fix the position. This will be displacement in meters as well. So what happens is, imagine this particle here. As this particle is just sitting right there, imagine it's sitting right there. And what happens is this wave moves, but the particle stays in the same x position. So in order to stay on the wave, let me see, can I actually copy this thing here and then move it? Let's see here. So I take this wave now and I take it and I make it travel. Good, this is good. Imagine that it moved a little bit. Now where is my particle? Can you see my particle is no longer here? It had to follow the wave. So now, do you see my particle went up? So can you see that? Does that make any sense? And as this wave moves over, my particle has to go up in order to follow that wave. So the question could be, which direction is that particle moving? And you can see that particle goes up. Had the question been reversed, actually, let's do something different. What about if we started with a particle like, we could do it over here, for example. As the particle goes, we'll do it over here maybe. Like this. Let's just say it was a wave just like this. We started like this. This was the initial starting condition. And we say, this wave moves to the side again like this. What happens to that particle? Can you see that this particle, as the wave goes to the side, can you see that the particle has to actually drop down to stay there? That particle would have to drop down. So that's why in that case, that particle will be going down. I think of this as if I'm like, trying to surf or something in the water and a big wave comes and hits me. If I'm just sort of bobbing in the water, I, for the most part, will stay still. The wave will come and make me go up and down, but I won't move. Unless I'm obviously surfing, then of course, then I'm actually moving with the wave. A different story. I just mean if you're swimming in the water waiting for a wave, you decide you don't want that wave to hit you. You don't want to ride that wave, I mean. So you decide to just sort of be just part of the water. So that's actually a pretty typical kind of question you might be asked on IB exams. So that might be pretty important. I'm just going to see if I can delete this. All right, now we have a frequency equation. This one, luckily, is really easy. It goes like this, and this one is in your data booklet. F equals 1 over T. This is the definition. Really important, data booklet. There you go. And we just have to remember what the frequency is measured in, just to remind ourselves again. It's always good practice to do this. Frequency, look at this. It's 1 over, let's do period first. T is a period, so that's in seconds. It's the amount of time, right? It's the amount of time you're measuring here. That's a period. Frequency then, if you look, frequency is 1 over period. That's why it's seconds to the minus 1, which is otherwise known as hertz. So you could do hertz or second to the minus 1. Well, there we go. That was okay, wasn't it? Very last thing, just a very minor piece of information. I think it's important. We have transverse waves. That's where the direction of oscillation is perpendicular to the direction of travel. What does that mean? It's an example just like what I showed you, with this water wave, for example, going like this right here, right? So what that means is that the oscillation is going up and down. Your little particles themselves, let's say you're a little person sitting in the water, your direction of oscillation will be up and down, and yet the actual wave will be traveling, in this case, maybe in that direction. So I'll say that's the direction of travel. So the travel direction might be that way, but your oscillation is up and down. Do you see they're 90 degrees to each other? That's why they're perpendicular. Same with light. Light does the same sort of thing. So for example, I could draw it here. So I could have light like this. Now light is an oscillating electromagnetic field. So we could say maybe it's the magnetic field that's oscillating. This is the oscillation. Keep in mind it's also in 3D. So there's a magnetic field and there's an electric field. And then those whole things are traveling, let's say, in that direction. In this case, let's say to the right. So that's the direction of travel. There we go. Longitudinal waves, by contrast, that's where the direction of oscillation is parallel. So these are the key words here, is perpendicular and parallel to the direction of travel. How does that work? That's a little bit harder. It's maybe a bit more abstract. But sound, for example, works this way. Right now, the fact that I can speak to you means in this room where I'm recording, it's kind of weird to think about when my throat is creating these standing waves, which is really weird to think about. And those are actually vibrating some molecules of air. And those molecules of air are actually going into a microphone that I have, which is being picked up. The vibrations in the molecules are being picked up by a microphone, which is then converted to a digital signal, and there you go. But the direction of oscillation is parallel. So what that means, you have all these particles, let's just say. All right? We have a whole bunch of particles like this right here, and now I'll draw a whole bunch of other particles like this. What's happening is, it's kind of weird to see, but it's actually a direction of oscillation like this. So your particles themselves, like the air molecules in this case, the air molecules are actually going to be going, let's say it's going this way. So they're going to be going like this right here. The air molecules are going to be vibrating this way. They're oscillating left to right. And because of that, the direction of travel of the wave is also left to right. So that's why I said they're parallel. So for example, this right here, then that would, maybe that's the direction there of travel of the wave. That's actually how sound waves work. And that also explains why you need to have a medium in which to have sound. That's why in space there is no sound, because there's no molecules to vibrate or to make them move back and forth. There's nothing there. That's why you can't have sound in space. Sorry, but you can have light, because light, electromagnetic field, that can exist in a vacuum, no problem. That's why you have light in space, but you don't have sound. Sorry, space is really quiet. Sorry, space movies. In this video, we're going to be talking about intensity and amplitude. That's why this word intensity reminded me of this awesome t-shirt I once saw there. This camping is intense. So we have intensity here, and we have a definition for it. Well, at least not a definition, but at least how it's related to amplitude. And we have that the intensity is proportional to the amplitude squared. What does that actually mean? That means that you can say the intensity is proportional to, remember we use that sort of alpha symbol, to the amplitude squared. That's the equation we could say here. That is one actually on your data booklet, so there you go. What it really means, if you just want to sort of break it down here, what it really means is that the intensity of a wave is going to be related to the amplitude of the wave by some constant. And I don't know, maybe you have to find that constant or something. Or maybe if you're dividing two different things, maybe that constant disappears. This idea, though, that there's some number times a squared. We also have the intensity is inversely proportional to the square of the distance. And that's one we use a lot in astrophysics and also in topic 8, for example, this idea about this 1 over r squared law. So that has to do with it right here. It's usually because you're doing it over a sphere, and the surface area of a sphere is 4 pi r squared. That's usually where it comes from. But we'll just write it down like this. So it's I is proportional to 1 over r squared. Usually it's just 1 over 4 pi r squared, but you know we can just write it like this. That's good enough. This here is also an important one. So this is all you need really for intensity and amplitude as far as for IB questions. They show up often enough actually on exams. This is still really important, this idea here, because sometimes they're really sneaky with some ratios or things. So I've got one example just to show you how to deal with a ratio here. So we have an example. At a certain distance away from a source, we have an intensity of sound heard. We're told it's 75 times 10 to the minus 4 watts per meter squared, because that's a power over a surface area. Power over an area. And then we have a farther distance out, the intensity of a sound is now this. So it's smaller. I hope that makes sense, because if you've got the sound from some place, the farther away you go, the sound should, intensity should go down. It should make sense. But we want the ratio of the amplitude of each of the waves here. So the amplitude at at 1 and the amplitude at 2. So can you see, we can just use this equation that we have here, this idea that, and you should always show your examiner you know what you're doing, so you can say, I'm going to use this fact that intensity is proportional to amplitude squared. You sort of show them that you know what you're doing. So let's actually start to just write out what we know. Very often when they ask for a ratio like this, you just need an equation for this, an equation for this, and you're fine. Or what you can do is you can set up one whole equation on the top, another whole equation on the bottom, and just divide the equations, and lots of stuff will cancel out. In this case, I think that'll be the way to do it. So let's look at this. So we have I1. I'll fill in the numbers only later. So I have I1 over I2. Let's see. Well, I1 equals sort of, I could call it a k, couldn't I? Some constant times A1 squared. Because isn't that the equation? I1 equals k times A1 squared. And then I could divide this whole equation by I2 equals k times A2 squared. See where it came from? It's because I1, by itself, you could say I1 equals KA1 squared. And you can say that I2 equals KA2 squared. Because of that, you can divide the two whole equations. You can say I1 over I2 is KA1 squared over KA2 squared. Because that the k's cancel out, which is good, they're supposed to. And we're left with this. So keep in mind, and now I can maybe put in my numbers. If I put in the numbers, let's see, I've got 75. Now, good news is, maybe I'll just write it all up just so you can see everything here happening. 75 times 10 to the minus 4, and 3 times 10 to the minus 4. All right, all that equals A1 over A2. And since they're both squared, I can say just whole thing squared. I can do that. Good news, because they're both times 10 to the minus 4, that cancels out. So you just got to think, what's 75 divided by 3? Well, it's just 25. So I have 25 equals A1 over A2 squared. Therefore, to get A1 over A2, what do? I take the square root. Technically plus or minus, but in this case I'll just care about the positive value. So in this case here I could say it's 5. So this would be my final answer here. Okay, that the amplitude 1 over amplitude 2 is going to be equal to 5. So see how you deal with these kind of questions? You can often deal with ratio questions by just literally just write an equation on the top, the same equation on the bottom with whatever's been changed. Sometimes they'll say like it's been moved twice as far, or they'll change something. They'll say the amplitude has been doubled. Fine, you put a 2 there, but 2 squared will become a 4. So you have to be careful with powers. But really, this is the way you do it. In this video, I'll be speaking to you about reflection and refraction. And the good news is reflection itself is super easy. It's so basic, in fact, there's really not much to say except for when something comes into a surface like this, if it reflects, it means it bounces off. And the good news is the angle that it comes in at is the angle that it leaves at. So the one important thing though to remember though with reflection is that we define our angles, sort of coming in and the angle coming out. We define the angles from the normal. So what I mean by that, the normal is if this is the surface right here, the normal is going to be at 90 degrees to it. And so we define our angles, so, theta 1 and theta 2 like this right here, as from the normal. So in this case, in reflection, it's super easy. Theta 1 just equals theta 2. Whoops. So it's just, that's the rule for reflection. Pretty straightforward, not much else to say. So we'll move on to refraction. That's more important, I think. This is actually just a bending of the light. So actually the light, it actually speeds up or slows down. It doesn't have to be just light, but actually maybe I'll be careful here. I'll say, so it speeds up or it slows down. So this is the key thing that goes on here. So it could be for light, but it could also be for water. It could be for anything. So in this case here, it's going to speed up or slow down depending on a difference in optical density, we can say. So this is this n, this index of refraction. This term right here, n. So for example, for air, n would be 1. And then for water, n would be, I don't know, greater than that. I can't remember. I think it's something like 1.3 for some water or something like that. Let's just say it's that. So what happens is this. As light comes in, its frequency remains the same. This is one of the key things actually from all of this. You have to know that the frequency of the light that comes in is the same as the light that leaves. So the frequency doesn't change. The speed can and the wavelength can. And that's actually going to be really key here. So we have an equation for it. And the good news is you don't have to memorize this one right here. It's nicknamed Snell's law. But it goes like this, n1 over n2, and this is how it looks in your data booklet, equals sine theta 2 over sine theta 1. Notice here the n1 over 2, but everything else goes 2 over 1. I just want to make sure I have it exactly how it looks here, and it's v2 over v1. This is the equation that you get in your data booklet. So basically it defines this index of refraction in medium 1 and 2. 1 would be what it is initially in, and 2 is what it enters. The angles right here will be important, so we'll see what happens with the angles, but also the speed. So for example, what's going to happen here in this example right here that I've shown you, you're going to see, how shall I say it here? You're going to see this ray right here coming in at this theta 1, because it's going from something from a smaller number to a bigger number, okay, smaller to a bigger. That means in this case right here, it's going to have to be something with sine theta. This right here is going to be bigger and smaller. So what's going to end up happening is your angle right here, your angle of refraction, we call it, is going to be, in this case, if it goes from smaller n value to larger n value, then the angle itself is actually going to get smaller. So in this case right here, I could redraw it. Let me just attempt to here. Draw an arrow. So maybe it'll be something like, that. So something where the angle, can you see this angle theta 2 here that I'm trying to draw here? See, theta 2 is smaller than theta 1. So what's going to end up happening is it's going to slow down as it goes into this material. Now, what I love about this picture here is this girl here smiling. I mean, that's refraction obviously happening in the water there. And I love this one. This picture actually made me LOL. I actually laughed out loud when I saw this. It's a dog in a swimming pool, but just with the way the refraction looks, it looks like he's got huge legs. I love how we call it Dogosaurus Rex. So the key thing to know is that, of course, you can use this equation, but pretty much when you're asked this on an exam, they kind of never really ask you just this. They almost always ask you for the wavelength. So an extra piece to know, maybe to try to add to your memory, is this, that the wavelength in medium 2 over medium 1 as well. So do you notice how it works? The n1 over n2. So if the n's are 1 over 2, everything else is 2 over 1, 2 over 1, 2 over 1. So if this is the part you see, then you can use that to remember, oh yeah, I can use lambda 2 over lambda 1. So frequency remains the same. That's how you can have a v equals f lambda, basically, sort of going on right here. We have something called a critical angle. That's when the refracted angle is 90 degrees. So we could see that right here. So you could have, your angle right here like this. It could be coming in. And the refracted angle then will be 90 degrees. Anything then that comes in, at a, let's say, a larger angle than this. So anything that's larger than this, theta c, for example, if it comes in larger, then actually the ray is going to bounce back in on itself. It's going to reflect. So we call that total internal reflection. So that's going to be an example of that. So this right here is total internal reflection, is something there like that. So I think that's most of what you need for refraction. Let me give you an example. This is an example, a really sneaky one that showed up in a recent exam. It sounded actually kind of sneaky, but hopefully it's not so bad. It was phrased slightly differently. I've tried to make it a little bit simpler looking, but it was, we have air, which is n equals 1. We have water, which is n equals 1.33. This time, though, your ray comes from the water and goes out to the air. So remember I said that if something goes from a medium where it has to slow down, like from a 1 to a larger number, like n equals 1.33, it's going to slow down. In this case right here, it's the reverse. Do you see that? It's reversed. So now it comes up from the water and goes out into the air. So the outgoing ray, well, it's going to be the opposite. So what's going to end up happening is we're going to have, so I can draw that here with an arrow. So whatever this angle right here was, the outgoing ray, instead of going smaller angle right here, so towards the normal. Remember, the angle is always defined from the normal. In this case, it's going to be bigger than it. So it's going to be something, where theta 2 is going to be bigger than theta 1. So now the angle here, oops, I should probably name it theta 1, put a little subscript on it. So that's really important. It's going to end up at a larger angle right here. Now, how will the wavelength change? Whatever the wavelength of a light was here, if you remember this equation right here, it says that whatever happens with n1 over n2, so if it goes from smaller to larger values like it did here, smaller to larger when it went down this way, then the wavelength went the opposite. So this became larger to smaller. So in this case right here, let's look at it. This one right here then, it's going to be, let's see, we have n, let's say 1 over n2. Let's compare those numbers. So n1, we could consider that 1.33 over 1 in this case here. So we have this right here. That's going to equal whatever the wavelength right here is supposed to do. So in this case right here, the wavelength, remember what's going to happen here. Remember I said over here the velocity is going to get smaller as it goes into here. Because of that, the wavelength will get smaller as it went this way. In this case right here, it goes opposite. So I could even say, what's that? I could say it's going to get larger. In this case right here, we could say that V2, whoops, not V2. Come back here. Let's say lambda 2. It's actually going to be larger. I think that's maybe a simpler way. Instead of trying to see it from the equation, maybe we can just do it from a conceptual point of view. Maybe that's a little bit simpler. So our wavelength is going to get larger because the angle got larger. Okay? And that's because the ends went smaller. Remember, the ends do opposites to what everything else does. So whatever the ends do, the angles and the speeds and the wavelengths do opposite to that. So maybe that's a simpler way. So the wavelength will get larger. I'm going to speak to you about diffraction. And diffraction is actually pretty straightforward. The idea is that when waves go through some sort of aperture, some sort of opening, they spread out. That's the main thing from diffraction, at least from a physics SL point of view. So this is the key word here is spread out. Okay. So if we look at this right here, let's take a look at an aperture. An aperture is a hole. In this case here we have D. Can you imagine this here is a solid wall? So we have a solid wall right here. We have a little hole in between it. And we have some waves that are coming in. These could be light waves. These could be water waves. In fact, let's maybe consider them as just water waves. So let's take a look at this then and see what to do with this. If we look at these as water waves, what I've drawn right here are actually the wave fronts. That's what these are here are. These are places where, the wave has the same intensity. So maybe it's like the crest of a wave or it's the trough of a wave. In this case here, these are places, that's how we can, you ever flown on an airplane, for example, if you're looking down at the water, sometimes the waves really do look like this. They look like these lines. That's where you can tell, that, where the next wave starts. From that, then, we can actually tell the wave length, can't we? If these are here are places with a similar, let's say, peak and a peak, or a trough and a trough, we can define that as the wavelength. And this right here represents the direction of travel. So we call these right here the wave fronts. That's the word we use for these ones right here. And this here would be the direction of travel. That would be the direction of travel. Sometimes we could call these rays. So the rays are the ones going in the direction that the light goes, but the wave fronts are perpendicular to that. Sometimes you'll see sneaky drawings where they ask you, they show you one thing or they show you the other. So the direction of travel, those are these rays. Rays could be directions, you know, like little arrows going that way. But the wave fronts themselves are actually going across. So in this case, they're perpendicular. So we can take a look at that, and same situation right here, right? Same exact thing right here, still the wavelength. These are still the wave fronts over here on that side. So that's all the same. These are still the rays. This is still the direction that they travel. Now what's really interesting to see is what happens with the size of the aperture. That's what we're trying to look at here. In this case right here, if we look at the size of the aperture here, D, maybe I'll write it down here. I'll say that if the size of the aperture, so this D, is greater than the wavelength. Can you see that that's actually what we've got here? You see that that's actually what we're looking at here? That if the D, the size of the opening, is bigger than the wavelength, then we have one situation going on. And here what I'll say is, you can see there's not much diffraction will happen. That's the answer here. There's not much diffraction. So what I mean by that, if I try to draw these, it'll be a little bit hard, but let me just try here. They shouldn't change wavelength. They'll just bend a little bit. They'll bend just a little bit. Like that. So not that much. I'm just trying to draw something that's not bending much. Just a little bit of bending like that. So these things right here will go through it and they'll sort of spread a little bit. So they will spread, of course, but not much. So that's maybe the key thing is here. If you have D is greater than the wavelength, we can say not much diffraction. In other words, not much spreading. But conversely, if you look at this one right here, what if we have D is, in this case here, D is less than, or it could be equal to the wavelength? That could be another situation. And you're probably already knowing what's going to look like. We're going to say more diffraction, we're going to say. So it diffracts more. In other words, it's going to spread more. So what that means is this. If I'm actually going to draw it now, I'm going to draw it with, say, because look at this D here. This distance now, this aperture is much smaller than the wavelength. If it's comparable to the wavelength or less than the wavelength, then you'll have these diffraction effects. So this right here will, for example, it'll curve a lot more like this here. It starts to be the same wavelength. Okay, there's something like that. I'm just trying to draw something. So it's going to spread out a lot more as it, of course, goes out. Remember the direction of travel. Now it's going to go out in all these different directions. So this is a good example of diffraction. This happens in everyday life, right? This is why you can hear sounds around a corner, because the sound will actually diffract and go around. This is why corners aren't exactly sharp. If you look at, for example, a wall and the sun is shining on that wall, if you look at, the place where the shadow and the light is, it's not exactly a straight line. It's a bit fuzzy. That's because some of the light actually diffracts. Some of the light actually goes a little bit around. So that's why, corners and shadows aren't super, super sharp. Not always, at least. This is a perfect example. This is just a satellite image. I think it's a satellite image, or maybe it's just an aerial image. It's a great example of what we have near our summer house where my wife and I live in Denmark. We have a nice little house up near the water. And this is actually kind of what it looks like. There used to be an older picture on Google Maps that showed it really well. But the problem is they updated their picture, and when they took that picture, there was no wave, so you couldn't really see it. I used to show the actual picture near our summer house, but here's an example of one. So what's going on here is exactly this. You've got these waves here. It's hard to tell exactly, but can you see? You might be able to guess. This could be a wave front, so could this. It's a little bit hard to tell. It's something like this. And these are coming in this way. That's the direction of travel. They're coming in that angle. And what happens, of course, they pass through this small aperture. And do you notice this aperture here is roughly the same size or smaller than this? So that means now, can you see that these waves are now spreading? Can you see that now they've spread? They've diffracted. So that means they go out that way and that way and that way. Isn't that cool? So this happens in real life. But the kinds of IB questions you'll have will be related to diffraction. You might actually be asked to just draw something like this, or something related to this. But basically you just got to remember that things go around corners and they will spread a little bit. So in other words, they won't just be straight, they'll bend a little bit. And the smaller the aperture is compared to the wavelength, if the aperture is close to the same size as the wavelength, in other words, if d is equal to wavelength or less than, then more diffraction happens. In this video, I'll be speaking to you about interference. Now, I like this joke. It's actually going to be really a little bit later on, you know, and people without kids tell me they're exhausted. I like how the guy's laughing. That's going to have to do with noise cancelling headphones, actually, because I have kids and I can say that, be glad you don't have kids in that sense, because they certainly are a lot of work. Of course, they're wonderful and all this good stuff, yes, but it is pretty exhausting. All right, let's talk about interference. The general definition of interference just says that when two waves meet, it's like a love story, right? Like when two waves meet, what happens? In this case, you can imagine like a wave like this and a wave like this, and when they meet, what happens? So in this case, we can have the two extremes. Of course, everything else can happen. I'm just talking about the two very extremes. So one is called constructive interference. That's when the two waves are exactly the same and they meet exactly in phase. So what I mean by that, let's just take a look here. I'll try to label them a little bit here. So we'll have wave number 1 here and wave number 2. And let's assume that wave number 1 is going that way to the right and wave number 2 is going to the left. You can imagine that we have these two waves that are meeting like this. Same size waves, and they're meeting. Of course, they're going to actually meet in the same place right here, and they're going to actually cross and go through each other. So that's actually what's going to happen. In the same place, they're actually going to go right through. So that's why at the end right here, if we look at sort of before, during, and after, afterwards, wave 1 will have gone right through. So this will be wave 1 going that way, and wave 2 will be going that way. However, what happens in the middle is really interesting. The rule is for superposition of waves. That's when two waves are right on top of each other in the same place. You just add up the intensities. You add up the heights of each of the waves. So in this case right here, we would want them to be, I'll just draw a dotted line. Like, you know, the first wave would probably be like this, but the second wave would also be like this. So you can imagine like 1 plus 1, that'll equal 2. So it'll be something, you know, a lot higher. In this case right here, it'll look something like this. So it'll be something like this right here. So right here when they meet, this is constructive interference. They actually added up to be double the size of the wave, just when they meet. After that, they just keep passing through each other. So it's like, whoa. I like my sound effects. I guess they don't go woo. So this is constructive interference. That's the one extreme. The other extreme is destructive, where they cancel out. So in that same sort of model right here, let's have wave number 1 going to the right. Wave number 2, however, is inverted, and it's going to the left. And of course, what happens when they're done, remember, even though they're sort of opposites, they'll pass right through each other. So in other words, later on, 1 is still going to the right, 2 is still going to the left. They've just passed through each other. But again, what's interesting is what happens when they meet. Right where they meet, what's going on. So there you could draw a dotted line for wave number 1, but you could also draw a dotted line for wave number 2. If you think about it, at this point, you have to say, you know, plus 1, minus 1, so they cancel out. And over here, maybe plus a half, minus a half, they cancel out. So the end result is actually really interesting. It gives you nothing. That's why it's called destructive interference. It's because it literally, you know, destructs. So the wave is not there at that exact moment. This is something that's actually pretty important all over the place in real life, especially. We can even do some of the geometry and some of the equations you're going to need. So the reason why this happens is that when something is emitted, it has to actually travel somewhere. This wave literally has to get there. So what that means then is if I'm going to try to draw this, maybe I'll draw it in light blue, let's just say. So I'll draw just a straight line. So let's say light, or it could be any other kind of wave. It could be water wave, but let's just say light. Let's say it came from this point right here, and I went right there. Let's just say, so light came across, went that point right there. This is the point we're looking at. Whoops. God, what have I done? There we go. So let's just say, so this right here is the magic point we're looking at right now. So we're looking at this point right here. Now, this wave has actually reached it by going that certain path. Can you see that wave actually had to travel from here to get there? However, we might have a different wave that reached it from the other extreme, the other end. So let me just try to draw a straight line doing that for this color here. Let's see if I can do it. Yeah, there we go, like that. So you can see there's two different waves that have reached that point. If those two waves went exactly the same length, you know, then we know that they're going to be constructive interference. But what if they just cancel each other out? They have to actually be off by half of a wavelength, it turns out. But we'll talk about that in more detail in a second. So what I'd like to do then is show you this right here. So the distance that this first one traveled is this. Now the distance that the second one traveled might be, this, basically from here to here. Can you see this distance right here? This one right here, from here to here. That is what we call the path difference. That's what's really important here, because this, from this point right here, from this bottom one, sorry, it's actually traveled the same distance the top one went, except this extra bit. So we call that the path difference. It literally had to travel further. So it's had more time to do its waviness. So you don't know how the waviness is going to line up with things. That's sort of how you can see it working out. So in this case right here, let's look at this equation here. You get this equation in your data booklet, it turns out. If the path difference equals n lambda. In other words, now keep in mind, n can be 0, can be 1, can be 2. It's basically any whole number right here. That's from 0 to 1, 2, 3, 4, like this. So we don't do decimals here. We just say n. So in other words, we could say that the path difference, if I put PD, for example, path difference could be, let's see, 0 times lambda, that could be 0. If it's 1 times lambda, it's just lambda. If it's 2 times lambda, it's 2 lambda, or 3 lambda, or so on. This is the case here. So if this path difference is equal to n lambda, then you have this right here going on. You have constructive interference. I hope it makes sense, because the two waves are lined up. And if it's done one whole extra wave, they're also lined up again. So this is an equation you get in your data book. You don't have to memorize this, but it helps to sort of know how this works. In a different way, you can see if the path difference is equal to, now to have constructive interference, they have to be off by an amount. And if you think a whole wave does this sort of shape, like, let me show you. Whole wave does this sort of shape. If you want them, and you have another wave right here that's lined up exactly the same way, right? If you have these two waves right here that are totally lined up, actually I probably shouldn't have done it this way. I probably should have done, hold on a second. Let me do undo. I'll try to do something a little bit clever here. Do like this, I go like this, and I'll say copy, and then I'll go like this and say paste. Yeah, there we go. So here's what's happening. If you have these two waves right here, they have two different waves that are meeting in place. I mean, they could be meeting like this, they could be on top of each other, any which way, these two waves. Remember, they have the same wavelength, so that's why they do line up initially. What happens is if they line up exactly, that means they're off by none. That's off by this. What if they're off by exactly this amount right here? They're still going to line up with each other. That's why it's 1 lambda and so on. But to make them destruct, you have to have them off by, like this. You have to have them like this so that they're going to, the top one's going to cancel out the bottom one. That's why they're off by half of a wavelength, if that makes sense here. This is the whole wavelength. It's that whole length there from here to here. Half of a wavelength is just that. So just to try to explain then how this might work, I'll just put it over here. So this one right here then, if the path difference is half of a wavelength, or, well, we'll write it like this. I'll say it like this. I'll say n plus a half wavelength. That's actually how we do it. So this one right here then, it could be off by half of a wavelength. That's true. It could be off by more. So let's see what this n does. Remember, n can still be, n is still equal to 0 or 1 or 2 or 3 or 4, ... Right? There's a whole bunch of different possibilities. But they will destruct if, let's see here now, if the path difference is equal to, let's make n 0. 0 plus a half is just a half. So that means it's lambda over 2. If I make n equals 1, 1 plus a half, that's 2 halves plus 1 half, that's 3 halves. So we could say 3 lambda over 2 and 5 lambda over 2 and so on. So you can see how this right here actually works. What I want to do then is explain a little bit about noise cancelling headphones, because it turns out they do exactly this. It's kind of magic, and this is where it relates to that picture I put about kids. I've actually got a pair of noise cancelling headphones here, so it's Bose that makes them. I really love these ones. They're amazing. They're active because they have a little switcher here you turn on. That means they need a battery here. What's amazing about this is this. Let's say you're on an airplane. For example, tomorrow I'm going on an airplane. I'm flying to Dubai tomorrow. And when I'm flying on the airplane, there's going to be lots of extra noises. Could be kids, could be the sound of the airplane. So what I'm going to do is I'm going to put these bad boys on. I'm going to turn on the switch right here. Bang. I mean, you can't hear the difference, obviously, because you're not in it. But what happens is this. There's a microphone on the outside of this. It picks up the signal and tries to draw the wave of what it looks like. Then it says to your ear, hey, I want to take off that signal. So what it does, it calculates what's the opposite signal. In other words, what's the signal that's going to give a path difference of n plus a half. It calculates that signal, and then it basically gives you that into your ear inside. So it gives you that into your ear. That way, although your ear is hearing the outside noise, it's also hearing the opposite noise from your headphones. It's giving you that. And that cancels out some of the noise. It doesn't work for all things, but it works for some really, especially constant sounds. It works brilliantly well. So these are kind of like magic. And maybe let's do one example here. We have an example here where we have two different microwave towers. So can you imagine then we have a tower right here. We can call them, I don't know, we can call it A and B. So we have A and B. These two different places right here. And they're both emitting signals of the same wavelength. So we know that the lambda is the same. And both waves are in phase. That just means they're lined up. At a point away from the towers, let's just say right over here, right here when I'm looking, the two signals interfere destructively and the path difference is 0.5 meters. So what that means is that the signal from this one here received there, signal from this one here right here received there. We know that the path difference, okay, we know this answer now. We're told the path difference is 0.5 meters. So the question is, and we know that it's destructive. So what are two different possible values for the wavelength? Because there's lots, there's an infinite number. But let's just take a look and see if we can do this. Remember what path difference is for destructive interference? For destructive interference, path difference is equal to n plus 1/2 times lambda. This is just the way it works. Now we're told the path difference, so we just need to figure out lambda. Here's the problem. We can play around with n. We can make it whatever we want. So in this case, let's try to just guess at a value of n. Let's just say n equals 0. Let's see what we get. If that's the case, we get 0.5 equals 0 plus 1/2 times lambda. So that means we get lambda over 2. Therefore, we get lambda equals, let's see, 2 times 0.5. That's 1 meter. Okay, that's one answer. What if we made n equal 1? Then we'd have 0.5 equals 1 plus 1/2, so that would be 3 lambda over 2. Then we would multiply our, because we want to get lambda by itself, so we'd say that lambda is, let's see, we could say that 3 lambda equals 2 times 0.5, which is 1. Therefore, lambda must equal 1/3, so we could say 0.3 meters, if we're just using one decimal to write it. And so on and so on. You can see all these different combinations. So this is how we can work with path difference and constructive and destructive interference. Let's now talk about slit diffraction. Now this happens when light is entering not just one hole or aperture, but multiple ones. So can you imagine laser light or some other light is coming in from the left, it's coming in this way, and there's a hole here for it to go through and another hole. Now, remember we've learned before that depending on where that light goes, there could be a path difference. Like imagine if this light went, for example, to this point right here, and this light went to this point. You notice there wouldn't really be a path difference, and so we might have constructive interference where those two, light waveforms, those patterns, will actually add up. Whereas you might be, a little bit higher up. Maybe at this point, for example, maybe the distance that this light has to travel compared to the distance that this one has to travel, remember we call that the path difference, maybe it is such that it's destructive interference, so you have a minimum here maybe. So basically, depending on how you go along here, along this axis here, you might have different places where the light is more intense, or the intensity here. So what I'm going to do then is I'm going to try to draw what this might look like. Imagine this right here is, we're going to sort of overlay on this axis right here. Imagine this axis right here has been turned and now it's this way. So this x-axis, that sort of represents what this one would be if it was sideways like this. So what I mean by this is that this right here would be, for example, x equals 0. That would be right here. Well, at x equals 0, we would expect this one right here, the path difference, to be such that, the path difference is 0 probably, according to this symmetry. So that means it should probably have a maximum intensity. So maybe it starts up here. And at some distance away, maybe we say x is this way, for example. Maybe up here then, the path difference is such that it's a minimum. And then after that, it's going to be a maximum again, a minimum, and so on. So if you can guess what the pattern would look like, it would be something like, I'm not perfect at drawing this, but some sort of sketch that's supposed to look like the same heights here. I'm just not the best artist in the world here, as you can tell, but I'm trying. There we go. Something like this. This should be roughly the same height here. And furthermore, I can get this distance right here. We can tell what this is. So let's start defining some of these different features here. We've got d, lowercase d, which is this slit separation. That's the distance between your openings here. Now keep in mind that will be in meters. All right, so we've got that size. Then we've got the distance between those fringes. These are these top things right here. We call these fringes. So this right here is a fringe. And this right here would be another fringe. Okay, so the idea here is that we've got this fringe separation here. So we've got these fringes here. This one and this one are fringes. Well, we've got a fringe separation. That will be this S. Okay, S is the fringe separation. So that's also in meters. That's the distance between your maxima, let's say. So that could be that. Now, of course, your slits and your screen are separated by some distance. That's why we call that capital D here. That's this distance right here. So at least that one's easy to remember because that one's a larger distance. Usually this distance is way larger than these. So the larger distance is the capital D. Now we have a formula for this, which is really nice. And it just goes like this. It goes S equals lambda D over D. That is at least a version of it. I like this version right here. It's the one you get in your formula booklet. But I really like this one because it just puts this together really nicely. You can basically figure out what your fringe separation depending on your wavelength and the distance and your slit separation. Which is really nice because you can start answering lots of conceptual questions. You can start answering questions like, if I want to make S bigger, so if I want to increase the fringe separation, what should I do? Well, to make this bigger, let's see, I can make lambda bigger, I can make D bigger, or I can make this little d smaller. Or you could think the opposites, so you can start thinking quantitatively about this as well as qualitatively. By the way, the wavelength is also in meters. So luckily the units all work out. If you look at this right here, this is, let's see, S, which is in meters, should be equal to something in meters times something in meters. Well, meters times meters over meters, what will that do? Just for the units, notice the meters cancel out, so yay. So that's sort of, it all works out. So there we go. Let's do an example. So this is an example. It looks very much like what you'd see on an exam. So something like, you have laser light of, 633 nanometers. That's what NM means. It's shining on two slits that are 0.25 millimeters apart. How far apart are the fringes on a screen placed 6.1 meters away? The key to doing this, I think, is to first figure out what's what. What are these different values here? Also, I like to suggest to students always watch out for the IB trying to change units. Look at this. This right here is not in meters. So right away, when I see this, I would actually cross this out immediately and say this is 633. Now you have to remember what NM means. This is really cheap how I remember it. I mean, you can always look it up too in your formula booklet, but this is a nanometer, and the way I remember it's a ninometer. It's so lame, but it's 10 to the minus 9. So I remember these are nanometers, so I know it's 10 to the minus 9. This right here is not 0.25 millimeters. We're going to rewrite it as 0.25. And what do we do about millimeters? Millimeters are 10 to the minus 3 meters. So we can put everything in meters. This is in meters, so that one's okay. Now maybe it helps to start writing out what letters are what. So laser light of this right here. See, the way we're going to do this, because we have fringes, we have light, and we have slits, and there's more than one slit, we're going to be using that equation. S equals lambda D over D. So the idea then will be, we need to figure out what is what letter. That's it. This question is merely about solving for which variable is which, or figuring them out. So let's figure out the easy one here, hopefully, 633. Hope you'll see that's the wavelength. So we know the wavelength is going to be 633 times 10 to the minus 9 meters. All right, what's this one? This is the slit separation. Slit separation is lowercase d. So that'll be d. So 0.25 times 10 to the minus 3 meters. And we have, what else? Capital D as well. That's this one right here. It's 6.1 meters. That's because that's the distance between the slits and the screen. So that implies then we must be, if we want how far apart are the fringes, this question then is asking, like, what do we want? This is the question here. We want how far apart are the fringes. We want the fringe separation, which is S. That's what we want. So I don't even have to rearrange this. This is so easy. Look, I just put in S equals, I just say, well, I just put in all the numbers again. So 633 times 10 to the minus 9. All that times 6.1, all that divided by D, which is 0.25 times 10 to the minus 3. I just need a calculator for this. That might help. So I'll just get out my trusty calculator and do this. I'll make a pretty fraction here, and I'll say, all right, so 633 times 10 to the minus 9. All that times 6.1. All that divided by 0.25 times 10 to the minus 3. And my answer then is 0.015445. Okay, I'm going to write that down. So 0.015445. 015455. Is that what I had? 154. No, I said 455. It's 445. See? That's why I checked. I'm always bad with numbers for that. There we go. Now, we can't just put this answer. We have to look at significant figures. We've got 3 here, we've got 2 here, we've got 2 here for significant figures. So I'm only allowed to use 2. That means I can only use these 2 digits. So you could say it like this. You could say S equals 0.15 meters. You could say it that way. That would be the answer. In fact, let me just put a square around it here. That'll be my final answer. I mean, you could say it that way. You could also say, I mean, it depends on how you feel like putting it in. Maybe the question says what it is in centimeters, or what's going on. You can say it's 1.5 times 10 to the, let's see, 1, 2, minus 2 like this. Or you could say it's 1.5 times 10 to the minus 2 meters. You could say it's 1.5 centimeters because that's what those are. I mean, there's lots of ways to say it, right? But I mean, this is your answer in proper significant figures. So see, it actually wasn't nearly so hard as you might think. The key is just to look at this equation, figure out what variables are what, and you're done. I'm going to speak to you about polarization and Malus's law. I absolutely love this joke. Where does bad light end up? In prism. All right, I'm really tired of laughing at my own jokes, so I think that's just the way it is. I love these dumb jokes. So let's talk about polarization. It's defined as the plane of vibration of an electromagnetic wave. So an electromagnetic wave really means light. When we say the plane of vibration, it gets a little bit complicated because we're trying to draw light, which is a 3D object, so to speak, and trying to represent it in 2 dimensions. So I want you to imagine this light coming straight towards you right now. So if you can see me, light coming straight towards you, okay? If light is coming straight towards you, there's going to be an, let's say a magnetic field, let's say going up and down like this, oscillating straight up and down. And there'll be an electric field oscillating, let's say, left and right like this. So as the light's coming towards you, you'll be an oscillating magnetic field and electric field. Now the problem is, how do you draw that? We have to decide on either electric field or magnetic field being polarization. And in terms of what you need for physics SL, it actually doesn't matter which one you choose. We're going to say light is polarized. It's just going to be the direction of oscillation. So instead of seeing it as electric and magnetic fields that are sort of perpendicular to each other, just consider just one oscillation plane. Either it's magnetic or electric, it actually doesn't matter. So I'm going to try to draw this. This is always really hard to do for me because I'm a lousy artist. So I'm going to try to actually draw, okay, this is light. You could say this right here is some sort of wavy thing. This could be light. And I would say then that light is traveling in this direction, to the right. So I could say, all right, the direction of travel, that's that direction. As it's traveling that way, it's going to have like an up or down or sort of left or right polarization. In other words, the direction of its vibration will be in some direction. So I'm going to try to draw this. Of course, it's going to be really bad, but I'm going to try to draw, for example, like, something like this. What that means is that each of them is going to be angled at some angle. That is a little bit difficult to see because this is in 3D. But like I said, just imagine it's light coming straight towards you. Let's just say we define the polarization as like this, for example. And another photon might be, polarization like this, or like whatever angle. So this angle of this plane of vibration of the light, that is what the polarization is. I've got a key thing right here to tell you is that, maybe I'll say this right here. So light from the sun, maybe we'll need this right here. So light from the sun is usually unpolarized. So for the most part, light from the sun is not polarized. So what that means is that each photon you get is sort of randomly polarized. One photon, if it's coming straight towards you, maybe one of them is, straight up and down, up and down, we'd say it's vertically polarized. The next photon could be one that's sort of left and right. So we could say that's horizontally polarized. The next photon could be like this. So to see how the plane of polarization of each of these photons is pretty random. That's what we mean by unpolarized. So now if something is polarized, it means, if like all the light is polarized, that means every photon that's reaching you would have the same plane. Let's say it's all vertical or horizontal or whatever. So let's look at this Malus's law and what it means. What I like to do is maybe draw you and attempt to draw this idea here of light coming in. So we're going to have light of intensity, in this case right here, I0. So light has an intensity of the incident light. We're going to call it I0. And by the way, it's got units of, let's see here, it's in watts per meter squared. Intensity of a transmitted light, we're going to call that over here, but I'll just put in the units here. Watts per meter squared. And the angle, of course, is going to be theta, just to get all these units here. So we're going to see this here. Incoming light is going to have an incident intensity. We're going to have the transmitted light. So when we're finally done, we're going to have this intensity of the transmitted light. That's going to be what's going to come out. And what happens is this. The light coming in is initially randomly polarized, or we say unpolarized. So that means that the direction could be anything. But now what we're going to do, we're going to throw in this polarizer, and let's just say this first one, let's say it's vertically polarized. Does that make sense? Like the light coming in now has to pass through this vertical polarizer. I've once seen the explanation for this. It's like, imagine like a hula hoop, and you're trying to fit that like in the slats of a fence. Imagine like, you have a fence and you try to fit the hula hoop through it. That kind of works, but it doesn't quite work, because it turns out light, let's say the polarizer is vertically polarized. What that means is that only the vertical component of the light is allowed to exit that vertical polarizer, number one, for example. So that means that light could be polarized like this, or like this, or like this, or straight up and down. It's not just that the only straight up and down one will come out. It's that if it's at an angle, there's going to be a component. There's going to be a vertical component. That piece will also get through. So this idea of using hula hoops instead of going through fences doesn't quite work. I think it's better to say it's the vertical component. Remember, because we can break up anything into vectors, a vertical component and a horizontal component. So it's the vertical part that gets through. But the good news is the kind of light that exits this thing right here. Okay, so the light that exits this right here, we're going to say it's a vertically polarized. Okay, and that's because only the vertical part came out. So that should hopefully make sense. So now that means light which is initially unpolarized or randomly polarized passes through the polarizer, and there's a reason why we call it that. It's because only light now, the only light that can pass through this polarizer to come out is going to be vertically polarized. In other words, now all the light coming out of polarizer 1 is light that's polarized straight up and down. That's it. Then you have polarizer 2. And what you do with that one, you have a random angle. So here, it depends on how you want to do it. But basically, do you see how this first one, the polarizer, let's say it's vertical? Maybe polarizer number 2, maybe it's at some angle. So see how we can define the angle between like the first one and the second one? We can define that angle theta. That's the theta that's here in Malus's law, like this. So what it really tells us then, we're going to have an equation that we actually have to write down the law, don't we? So it goes like this. I equals I0 cosine squared of the angle. This is an equation on your data booklet. Really important. That's Malus's law. So that's it. So what it tells you then is that the intensity of the transmitted light is going to be equal to the initial or the incident light's intensity times a cosine squared of the angle between them. I want you to look very carefully at this. Do you remember what cosine of 90 is? Just for fun, do you remember what cosine of 90 is? It's 0. So this tells you something really, really special. Check this out. If the angle is 0, imagine you have a polarizer that's vertical and the second one is also vertical. Can you see that? Then the angle between these two is 0. That means only vertically polarized light comes out of the first one, and that means out of the second one, also vertically polarized light comes out. In that case, if the angle is 0, cosine of 0 is 1. So that means the transmitted, incident light is going to be the same as the transmitted light. So that means, everything goes through. It's not quite true because things are absorbed and reflected, but in this case, it's pretty much this. As far as physics SL, at least, and HL is concerned, this is good enough. What's interesting though is, what if it's 90 degrees? Let's do the other extreme. What if the angle between those two polarizers is 90 degrees? Imagine one like this and one like this. That means only the vertically polarized light comes out of the first one, but the second one is horizontally polarized. None of the vertically polarized one has a component in the horizontal direction. So in this case, if the angle, this is an important thing right here. We'll put this down maybe. So if theta equals 90 degrees, I equals 0. This is like a really important thing right here. Okay, so if the angle between the two polarizers is 90 degrees, then you're going to have nothing come out. Right? This is going to be, opaque, we say. So there's some really cool examples of this. So we can have fishing glasses. So let's say you want to actually see the fish in the water here, and there's the sun in their way. The sun's light actually will do something like this, right? The sun's light will sort of, bounce off this right here and create what we call glare. So in other words, you're trying to look at the fish. You're attempting to see the fish here. So you want to see the fish in the water here. But the problem is, you're trying to look in the water, and the glare, the sunlight is, it's really hurting your eyes. You can't see the fish. So what you do is you can use this fishing glasses, they're called, so polarized fishing glasses. What happens is this, there's a really cool property that if light reflects off a surface, pretty much all of it is going to be horizontally polarized. So in other words, it's going to be parallel to the surface. So if the sun's light, which is initially unpolarized, if it bounces off the surface of the water, or like, let's say the surface of your car or something like that, like the car hood, if it bounces off of it, most of the light then will be horizontally polarized. So what do? You wear some glasses that are actually vertically polarized. Why do you want them vertically polarized? So they'll remove the horizontally polarized glare from the sun. That way then, boom, you can see the fishies. You can always tell two different sets of polarized fishing glasses, because if you take two polarizers, just turn them 90 degrees to each other and you shouldn't see anything through them. So you can, go to Walmart or something, and if there is one in your town or your country, and take two sets of, fishing glasses, take two sets and just rotate them 90 degrees and look through them. You should not be able to see through them. Then they're polarized. Now the windows on Qatar Airways flights, that's also really interesting. When I rode one of their flights, what's really interesting is that you can actually choose to dim your window. And basically the way this works, you've got two polarizers. You've got window, with a polarizer this way, and you got a window behind it with that. And then by pressing little buttons to basically change the angle of the second polarizer. You can essentially make your windows pretty much see nothing or really clear. It's kind of magic. Now let's do an example. The example is we have unpolarized light is incident on a vertical polarizer. So maybe before starting out, I'll just actually draw this. So now I have some sort of vertical polarizer here. So that means, here we go, a vertical polarizer. And I've got my light coming in this way. What happens? It enters a second polarizer at an unknown angle to the first. Okay, so there's my second polarizer here. And I don't know the angle of this one right here. I don't know the angle of the second one. So I don't know. Question mark. Don't know. If the intensity of the transmitted light, this is the important thing right here, the intensity is half the incident intensity. So what that means is that I equals I0 over 2. It's exactly half the incident intensity. We're supposed to write an expression for the angle theta between the two polarizers. Well, we can use good old Malus's law, right? We can use our good old pal. Remember, it goes I equals I0 cos squared theta. And that means then, if we plug this in, so we put this in so that the examiner knows that you know what you're talking about, then you take this and say, all right, well, I replace I with I0 over 2. So if that makes any sense, then I can say, all right, that means I want I0 over 2. That's what I is. That's what the transmitted intensity is. Equals I0 cos squared theta. Now, do you notice something? The I0s cancel out. So now I have 1 over 2, I'll just write over here, 1 over 2 equals cos squared theta. Now how do you get theta by itself? Do you remember what you do? You take the, well, first of all, I could take the square root of all this, couldn't I? So I could say that cos theta equals the square root of 1 over 2. Technically it's plus or minus, you got to watch out. It's actually technically plus or minus. But remember, the square root of 1 is just 1. So I could rewrite it then as cos theta is just plus or minus 1 over square root of 2. And if I want to take theta by itself, I take the inverse cos. So that's how I finally do it. I do the inverse cosine of plus or minus 1 over root 2. That's technically what I should do. You can take a look and see if you need the positive or the negative, but this is a general expression for it, right? Then you can think about the physics and what's a physical situation here. But I think this is actually really nice to see that this is how you can do it. It starts off pretty simple. The equation itself looks gross, and I saw an example very much like this on a paper 1, where that was one of the choices. You had to know that it was inverse cosine of 1 over root 2. Standing waves. This is something in the older syllabus. It used to be an HL only, but now it's moved to the SL syllabus. And I have this picture here. I have no idea what I'm doing. It's a dog playing the guitar, because we're going to be talking about guitar strings. So what are standing waves? This is a dynamic situation, so I can't really draw it, but you have to imagine in a system that's closed. So for example, in a string with both ends that are actually fixed. When I say fixed, I mean, they're attached somehow. What happens is this: you start a wave that goes one way, and you have another wave that goes the other way. And what happens is they're going to meet, and remember, they're going to have interference and superposition in just such a way so if the frequency and the amplitude are constant, these two waves are meeting in superposition. They're working in opposite directions, and it's technically just two waves that are bouncing back and forth. They're bouncing and reflecting as they do that. And they're both meeting in just such a way as it looks like the string itself goes up and down. Technically, it's two different waves that are actually meeting with each other. But it ends up looking like the string goes up and down. So in this case right here, if we have we'll talk about three different situations here. But the first one here, if we have a situation where it's fixed at both ends. So for example, a guitar or a piano, those actual strings on the piano are like this. They're fixed at both ends. They're held still. These right here then are areas where it won't move. So we have what's called the fundamental, which is like the simplest solution to this. And this almost becomes like a game. I don't recommend you memorize these things. I recommend you just sort of learn how to play the game. So the game is this. What you do is you take your string, for example, and you have to imagine it then going sort of up and down and up and down. It doesn't, technically it's two different waves going back and forth, but it ends up making the wave go up and down. So the simplest solution is something like, I'm not drawing it very well, but something like this. And of course it can go down at the bottom as well. So what this is the string going up and down and up and down. When you first pluck it, that's what it'll do. We call that the fundamental frequency. Sometimes we call it the first harmonic. It looks like this. Let's look at the second one now. So the next one, the second harmonic, it's going to be in that same string. We still have to fit, we have to have this fixed at these two ends right here. It has to be fixed. So does it right here too. Fixed and fixed here. And the rule is this: every harmonic you go up, you just add one of these fixed points here in the middle. So in this case right here, you got to be fixed here and fixed here and fixed here. And these other places then are places of maximum intensity. Can you see like maximum amplitude here? So right in the middle, it goes up and down the most. Right? So if you're actually looking at the string, it will really look like it goes up here. The second harmonic is going to be like this, where you can actually fit something like this. So here it still has to come back in, but then it has to come back in like this right here. That's one. And of course I can draw the dotted line version, because you have to imagine this thing here going up and down. That's why I draw the dotted line, just so you can kind of see it's going sort of, up and down and up and down like this. It's something that really does shake like this. The third harmonic is similar, except instead of having one of these points that doesn't move in the middle, you have two of them. So again, hopefully you can figure out how to do it. It goes up, then down, then up. Oops, I'm not drawing it very well, but there we go. I'll just draw my point there. And we draw the dotted line version, of course, and there we go. And do you see how you can do the fourth harmonic and fifth and sixth and seventh and so on? So the important thing here then is to consider what is the length of this tube here, or in this case, this string. So we're going to define something right here. We're going to call it L. That'll be the length right here. So the length of this right here, because that's the length of your string in this case. And we're going to see a relation between the length and the wavelength. So watch very carefully. Do you remember how wavelengths work? Wavelengths work like this, right? One whole wave could be, I'll just have it like this right here. So to see how one whole wave, there's a lot of different ways of fitting a wave, right? We can consider a wave starting here and finishing here, that could be one wavelength. So could it be from here to here? That could be a wavelength. We could start from here and finish here. That could also be a wavelength. A lot of different ways of looking at it. So let's look here then. What fraction of a wavelength do we fit inside L? In other words, if you look at this equation right here for L, okay, or not this equation, but this situation here, this string, we need a relation between L and lambda. And take a look at this. L, if you look at it, you see how it's actually half of a wavelength? In other words, this part that goes up like that, that's only half of a wavelength because you need another half to make it work. I always imagine you copy and paste this again. If you copied just this piece and you pasted it again, it would go like this. That's not a wave. That's how you know you didn't do it right. If you copy and pasted it though, and it does give you what you need, then that's a wavelength. So for example, this right here, it's only half of a wavelength. So I'm going to say lambda over 2. This is the sort of key equation you need for this one. I just draw them. I don't memorize these. I just draw them. I think it's easier. Second harmonic, take a look at this then. What fraction of a whole wave do I have? Well, see, it goes up and then it goes down. Imagine if I copy and pasted that piece, this piece right here, and then I put it back in again on itself like this. See how it would continue the pattern? That's how I know that this is actually, or you can see it 1 up, that's lambda over 2. So this is 1 lambda over 2, 2 lambda over 2. So that means I have L equals lambda. So here, the length of the string is equal to the wavelength. Let's look at this one then. Let's count by these lambda over 2's. This one I have 1 lambda over 2, 2 lambda over 2, 3 lambda over 2. That's why I think this becomes easier to count it that way. That's how you deal with this one. Let's play a similar game now, but instead of fixed at both ends. Oh, by the way, don't forget this. If ever you need to convert between velocity or speed, or frequency or lambda, or the wavelength, you can always use this. Let's do the 2 other examples here. Open at one end, closed at the other. For example, a clarinet, trumpet, something like that. That's something where it's open at one end, closed at one end where you're blowing on it, open at the other end. So here's what happens. We were learning these rules before. It has to be fixed sort of at this end. So this end right here on the left is going to always be a fixed point. But where it's open, that's where we're going to have maximum amplitude here. So it has to be sort of flappy going up and down. Imagine that. That means this one is going to go like this. Something like that. Oops, I drew it really poorly. Try that again. Something like that, and then dotted line goes like that. In other words, it goes sort of up and down like that. The second one is going to have a point in the middle here where it doesn't move, so that means it has to go up, and then it has to go back down to this one, and then it has to go like that. And this one here will go like that, up here and across. Second one has 2 in the middle. Sorry, the third harmonic. So that means it'll go up and then down and then up and then sort of flappy, so to speak. Same idea here. This is sort of what you need to be able to draw pretty quickly. And remember, this whole thing here is L. This whole length right here, right? That length right there is L. So is this, so is this. So let's do the equation again for this. How does this look? Let's see here what we have here. L equals what fraction of a wavelength? Look carefully here. We've got from here only going up. That's not a whole wavelength, is it? Can you imagine if I had another one of them, like another length, that would be that, then another one would be this, and then another one would be this. So I've only got 1/4 of a wavelength. Can you see, like, sort of going from the middle to the top is 1/4, top to the middle, middle to the bottom, bottom to the middle again, and that makes one wave. In other words, I'm looking at lambda over 4 here. Look at the second one here. If each of these sort of quarters is a quarter wavelength, then let's count in quarters here. Here I've got 1/4, 2/4, 3/4. So I can say L equals 3 lambda over 4. What fraction of a wavelength do I have here? Let's see, 1/4, 2/4, 3/4, 4/4, 5/4. So that's why L equals 5 lambda over 4. Again, you don't have to memorize these. Some people do. I just like to draw them, then you can figure it out. Let's go again to the last page right here of the new stuff here. Open at both ends. For example, a flute. You know, it's got a tube or a pipe that's open at both ends, and you blow across the top of it to make that standing wave. So this one right here is a special case. Well, it's got to be sort of flappy at both ends. So we're going to have this point right here in the middle. So it's going to go like this, sort of like that. And then this one's going to go like this. That's the fundamental or first harmonic. Next one's going to have two of these bad boys in the middle. So of course it goes down and back up again. And then like this. And the third one's going to have three of them. So it's going to go down, then up, then down. And like this. There we go. So let's look at then again, this is L, remember? This is L, so is this, so is this. Let's look at what fraction of a wavelength we have here. This is maybe not so easy to see, but look carefully at this piece right here. Do you see this piece right here from here to here? So from a top to a bottom is really what we have here. Do you see how we actually technically have half of a wavelength? Because if I had two of them, can you see that that would be a top to a top? It's not so obvious. This is actually half of a wavelength. Because if you had two of these, and one and then two of these, if you copy and pasted, you know, sort of this whole thing, then you would see that you would be able to continue this whole path here. So this is a whole wavelength here. So if each of these things, sort of top to bottom, is a half wavelength, let's look at this. This second harmonic goes from top to bottom, that's 1/2. Then bottom to top, that's 2/2. 2/2 equals lambda. Does that make sense as a whole wavelength? I hope so, because see, you're starting off here, you're going down like this. That's one wavelength, isn't it? You can say that's 1 lambda. This next one then, top to bottom, is 1/2. This is 2/2. This is 3/2. That's why it's 3 lambda over 2. That's how you do these. So again, knowing how to do the drawings and knowing the rules of this game can really help you out. Let's do a real example here. So we have an organ pipe, and it's open at one end and closed at the other. Before anything else, then I'm just going to start by drawing myself that. There we go. There's my organ pipe. And I know it has a fundamental frequency of 16 hertz. What does that mean? Remember, let's just draw the fundamental frequency of this thing. That's fixed at this end, flappy at the other end. Therefore, it goes like this, or it goes like this. And before anything else, remember, we can still, this is how I do these. I just right away just start drawing this thing. I just draw the whole thing. What fraction of the wavelength do we have here again? Do you remember? You don't have to look it up. We'll figure it out again. So L equals, let's see here. What fraction of a wavelength do we have? This is a quarter, isn't it? Because it goes from middle to the top. I would need a top to the middle, middle to the bottom, bottom to the middle to make a whole wavelength. That's how I know I have lambda over 4. Let's see how this is going to help me. I know that the frequency of this is 16 hertz. Okay, I'm not sure what to do with that one. We have the speed of sound in air is 330 meters per second. And the question is, what's the length? That's what we're looking for. What's the length? So I hope you see it's actually not so hard at all to do. Because we already know the drawing here and we figured out this relation, this is actually the key to solving, is this L equals lambda over 4. So what I'm going to do, I'm going to use, remember this handy dandy equation here, V equals F lambda? I'm going to need that one. I'm going to use that equation, V equals F lambda. Oops, maybe my F looked a little bit gross here. F lambda. I'm going to use that because, do you see I have F and I have V, but I need lambda. So I'm going to get lambda by itself, so of course that's V over F. So in this case, V is 330 meters per second. We could say, right, over seconds here. And we have frequency of 16 hertz, but a hertz is a 1 over second, and if we're doing 1 over second, the seconds come on top. That's why they disappear, and we have a length in meters, so that'll work out. Let's see, what is that? That's 330 divided by 16. I just get out my calculator, and I end up with 20.625 meters. That's a pretty long wavelength, isn't it? 20 meters long, imagine that. All right, what do I do with this right here? Well, I can take this number then and do what? I know that L is lambda over 4. So I just literally do that. So L then equals this lambda, which is 20.625 over 4. So I'm going to do that. I'll divide them. Divide by 4, and I get 5.15625 meters. So what do I do with my final answer then? How do I deal with it? I have to look at how many digits I'm allowed to use. I'm allowed 2 here. I'm allowed 2. So I'll use 2 digits. So I'll say 5. In this case right here, we'll round it up to 2, I guess. This will be my length. 5.2 meters. That must be a huge organ then. But there you go. That's how it works. I hope that makes sense with standing waves. We're going to do an introduction now to electric charges and electric fields. I think that's something that a lot of people really struggle with, so that's why I wanted to show you some tricks. I do love that joke there with Tesla. I was making joules before. It's Coulomb, so let's start off actually with Coulomb's law. Now, Coulomb's law is the force between two charges that are a distance r apart. Now, this force can be attractive. If you have a negative charge and a positive charge, those two charges will be attracted. So this could be the force of attraction between them. It can also be a force of repulsion. For example, let's say they're like charges. So if they're both negative, then they're going to repel, or if they're both positive, they're going to repel. So this is really important to keep in mind. This is not just an attractive force, this Coulomb's law. It can also be a repulsive force. It just depends on the nature of the charges. So I'm going to start by just writing you the equation here. So it goes F, most people know it here, equals K Q1 Q2 over R squared. This is what I'm going to say it's like here. There we go. I'll just put a little square around it, because this is something you get in your data booklet. So what does it mean? I mean, first of all, it means that F is the electric force. And do you remember the units of force? I hope you do. I'm just going to change the color here. Electric force is measured in newtons. That hasn't changed. Now, K is just a constant. You can actually look it up, so you don't have to worry about that. You just look it up on your data booklet. Then you have Q1. That's one of the charges. Again, that could be positive or negative, but we're looking at the nature of that charge. So let's put in the units of that charge. Do you remember the units of charge? It's Coulomb. And then charge 2, of course, is also in Coulomb. And R is the distance between the charges. So in this case here, that'll be in meters. And what it does is it tells you, it characterizes this force, which is, of course, it's proportional to the charges themselves. So the size of the charges, bigger charges will be a bigger force of attraction or repulsion. But it also tells you about the distance. Did you notice it's a 1 over distance squared? In other words, you could say here that, let me just write it down here like this. So we could say, for example, that the force is proportional to 1 over the distance squared. So what that means is, as the distance, let's say, doubles, let's just say so these two charges then were, double the distance apart, then 2 squared is 4. So that means the force will actually go down by 4. And they love to ask these kind of questions on NBA exams. That's why it's really important. And by the way, you can also say that this K here can also be written here as 1 over 4 pi epsilon 0, where epsilon is just the permittivity of a vacuum. You can just look that up. But I don't think that's actually that bad. I think that's possible to solve questions with it. So here we go. We have an example. So we have 2 point charges, and they're located on a straight line. So you can see this is point charge Q1, and this is point charge Q2. Notice Q1 is plus 20, and these are MC, so that'll be millicoulombs. That'll be 10 to the minus 3 coulombs. And then we have Q2, which is negative 10. You have to think about that. Now we're going to draw a vector to represent the resultant force on a positive particle. I think the key thing here is going to be this positive particle. And it's placed at point A. So what it helps to do then is just split this up into 2 separate, completely separate problems. So in other words, I try to just imagine, I just sort of hide one of them and just look at the force between 2 of them. And after that, then I would, hide the other one and look at the force between the other ones. That's how I like to do it. So let's see if we can figure that out. So we don't have to put in numbers. Do you notice? Even though they gave us these numbers right here, I think what's important is that 1 is positive, 1 is negative, and it's important that Q1 is twice as big as Q2. I think that's the key part. So let's see if we can do this. I'll do this maybe in light blue here, and I'll maybe use some arrows. Maybe that'll be nice. So let's just deal with Q1. Let's ignore that Q2 even exists, because we're going to add up to 2 vectors here. So if there's Q1, and remember it's a positive particle. So A is a positive particle. Oops, I shouldn't have done that. So A is a positive particle. Do you think a positive then will be attracted to or repelled by Q1? I hope you know that like charges repel. So it's going to go away from it. Now, I don't know how big to make it. I'm going to just choose sort of a random length. I'm going to make it going away. And maybe I'll make it like sort of that long. If that makes any sense here. I'm going to sort of draw it like that. So this is the force based, this is the force on A caused by Q1. But we also have another force. Right? We also have another force that's caused by Q2. So let's think about that one. It's going to be a positive charge is attracted to a negative charge. So it's going to go towards it. And how strong will it be? Can you see that they're both roughly the same distance away? So the distance hasn't changed, but the charge has changed. Can you see that? It's half the value. So because of that, if you're trying to draw a rough idea of a vector, I could maybe draw myself a vector that's maybe half as long. So whereas, the other one was maybe this long, I have to make it, I don't know, maybe half as long, maybe something like that. So these are the two different forces. And do you remember how we actually add up forces? We actually add up vectors by doing exactly this. So watch this. This is what's really cool about this, what I can do here. I can kind of cheat here. I'm going to grab this one right here. Let's say I just put it right here. And let's just say then I grab this one. Remember, this is how you can add vectors head to tail. So I can say, I don't know, maybe the vector will be something like, I'll draw it in a different color. There we go. And I'll draw an arrow. So we go from the start to the finish. It'll be something like this. I don't know if that made any sense. So here's the resultant force here. I'm going to maybe label it here. This will be the resultant force. Let's say the net force. Right? Because a net force is when you add up the two vectors. You have one vector, you have another vector, then you have to add them up. So this is a rough idea of what it could look like. It's not perfect. If we had the distances, we could actually figure out the exact length of the vectors here. But we didn't need that. We just had to sort of characterize it. So see, although it might look kind of weird, this really tells you this one really will have a net force this way. That means it really will accelerate in that direction. It'll go flying that way because it's repelled by this one a lot. It's attracted to this one a little bit. So that's why instead of going straight back, it's going to go a little bit that way. Now, another thing we do is we can draw electric fields. Now, when we draw them, it's where it's arbitrarily defined. It actually doesn't matter. We could have chosen them to be negative. And in fact, we reversed everything in the universe and then nothing actually would change here. So it's the direction that a positive test charge would go. That's sort of the definition of electric field line. So if we're going to draw them, this is sort of based on Michael Faraday's, his sort of idea about drawing vectors, drawing these arrows to characterize what goes on around something. So I imagine these are here are pinned. So there's like 4 different questions here. Imagine I have a positive charge that's just actually been pinned there. It's stuck there. You can't move. Now my question is, where would a little test charge? What I mean by a test charge, I just imagine I picked up a little positive charge, I just placed it somewhere, and I just sort of look, where will it go? So in this case here, just imagine then, I've got a little test charge. And it's sitting in my hand right now, and here it is. And I'm going to place it right here. Where will a positive go from a positive? Do you see it's going to be repelled by it, so it's going to go straight away? And what if I placed it right here? Can you see where it'll go? It'll go to the right, and then it'll go to the left and down. In other words, these will be field lines going radially outward. This is how we define them. So we actually define this right here, this electric field, like this. This is how we actually characterize them. What about this one right here? How could I draw this one? It's a little bit sneakier. Now there's 2 charges. You've got a positive and a negative charge. So what would I do here? Imagine I placed one, I don't know, maybe right here. A positive. Remember, it's always a positive test charge. Positive will be repelled by this positive. It wants to go away, but it's also attracted to this one, so it'll probably go like that. And if it's this way here, it'll want to go away, but then it gets attracted this way, and then this way. And you can keep drawing these arrows, right? You can draw an arbitrary number of them, but they go kind of like this. This is the electric field lines around this, which means if you really had these sort of positive particles, they really would follow this path. They really would go away from this. They really would travel in that direction. How about this one right here, a positive and a positive? It wants to go away from this positive, but also away from that one. That means it's going to go sort of going to curve upwards and away because it wants to try to get away. These are going to be asymptotic here, like this. And of course, we're still going to have arrows going away because they always want to go away here. So something like this. And look at this one. Now I have 2 charged plates. I have a positively charged plate and a negatively charged plate. If I drew just a random point right here, where will it go? To see, it'll be repelled by the positive, so it wants to go down, and it's also attracted to the negative. So we can just draw an arbitrary number of these lines here. Don't forget the edge effects here. Don't forget to draw the curvy ones over here. They're going to kind of curve that way. I guess you could draw, really big curve one like this. There you go, something like that. That's how we can draw electric field lines. Now, it seems really arbitrary, but it turns out the number of field lines compared to another one, that can tell you that, it's a more positive electric field. So maybe it's a good time then to define what we call electric field strength. This is another equation on your data booklet, and it goes like this. E equals F over Q. So in other words, this right here is the electric field strength. So it's defined as the force per unit charge. So that means we can actually define it right here. So it's the force is measured in newtons, charges in coulombs. And think about this then. If you want to know electric field strength then, what would it be? It would be newtons, that's the units of force, divided by charge, which is coulombs. So it would be in newtons per coulomb. If I really want to be careful, I should actually draw my vector symbols here. I should draw a vector here and here. If I really want to be careful, let's go back actually. I should probably draw my vector symbol here, because force is a vector, right? The direction actually matters. So I hope that helps. Then you can actually see an idea how we can actually deal with this. And again, if you want electric field strength, it's just the force per unit charge. So just divide out one of the charges. That's it. I'm going to show you a few really important definitions from electricity here. So, I like this one here from The Office. This electricity joke's shocking. I don't know if you ever saw that show. That's Dwight, at least from The Office. It's an older show, and it's actually an American copy from a British show. But either way, I thought his character was amazing. So let's do some important definitions. And one of them is when we talk about moving charge. So we've talked in the last video about charge itself, how it's, well, charge itself, it's just a quantity. It's a quantity that different particles can have. And we know that charge is something that's conserved. And that's going to be really important later on when we're talking about circuits, that, you know, these charges themselves, these coulombs of charge, don't disappear in a circuit. They just move around. You'll see we're going to do an electricity analogy. It should make more sense then. But when we talk about moving charges, this is really what we have here. I'm going to give you some definitions first, and we're going to use them later in an analogy to show you how circuits can actually work. And one of the really important definitions then is about charge itself. So we're going to define something called I, and we're going to say it's just delta Q over delta T. This is the definition we're going to use here. So this is for this. I equals delta Q over delta T. And maybe then it's a good idea to actually define what everything is. So we're going to define I as the current, which will be measured in, as in English people say amperes, in French we say ampere. Either way, so it says I. This is not just one, it's supposed to be an I. Maybe I'll make it a little capital I like this, it'll be more clear. So we'll say I is the current. Okay, so I is the current, it's measured in amperes. Then we have Q, which is the charge. You know that one before. That's measured in, do you remember the unit? Coulombs. And time, I hope you know, is in seconds. So this is just a definition. It's just current, it's just coulombs per second. And that's why I wrote it down over here, that the current is just the number of coulombs going by per second. So just like, you know, just counting the coulombs every second. That's what you do. This is the most important one. You might need to know this extra one here, that if you have a wire, this wire, you have these little electrons in them. You know, you have little electrons that are sort of drifting along here. We call this here the drift velocity. So we're going to define then the current here. Let me just write this. Maybe in green would be a good idea here. I'll make the current with little like that. I think it'll be simpler here. And we'll talk about the current then. Again, I'm just giving you some basic definitions here. You're going to see it's going to make more sense later in context when we put everything together. This right here represents the cross-sectional area, because if you look at a wire from the side, now you rotate it and then put it right in front of you. Can you see that there's going to be like a circular part of the wire if you cut it? And that's what we call it a cross-section. And that's this area right here that we can actually measure then. So we can find out the cross-sectional area of a wire. You know, if it has a radius r here, you could actually get the cross-sectional area. So that would be this area here. Now remember, the area of a circle is going to be pi r squared. Remember, I'm trying to draw it from the side, so you see the perspective there. But you know, if you put it really right in front of you, it would actually be a nice circle. So let's define then these different variables just to make sure you know them all. So remember what I is. I is the current, which is measured in amperes. N is the number of electrons per unit volume. So what this is, you have to consider then the units. So this will be just, well, unit volume. Volume is in meters cubed. So because it's per unit volume, it's meters to the -3. because it's like 1 over meters cubed. Then we got A is the area, that's the cross-sectional area that is passing through, so that's meters squared. We've got drift velocity of electrons, which is in meters per second. And finally, we have the charge, which you know now is measured in coulombs. And if you're just looking at the units, just to make sure all the units work, I think sometimes that's a good idea, just for practice, just to play around with them. Let's just say we have the units here. So let's look at the units. We have the units for N. What are the units for N? It's 1 over meters cubed. I'm just putting in the units here. A has units of meters squared. Then we have V, which has units of meters per second. And finally, we have Q, which is in coulombs. And look very carefully what happens here. The meters squared times meters, those give you meters cubed. Over meters cubed, they all cancel out. And you're left with coulombs per second, which is exactly what we're supposed to have here. We're supposed to have it in coulombs per second. So just so you know then, another unit of current then, just keep in mind, could also be coulombs per second. You know, that could also be another unit. Right, because it's number of coulombs per second. So I hope that makes a little bit more sense just with this equation. I haven't seen them ask this very much on exams, but it could easily show up. Potential difference, I think, is the hardest one for students to understand because it's the least intuitive. So I mean, to move a charge around, you need to do work. This is the key thing. If you want to take a charge and actually shove it, from a place to a place, work has to be done. Remember, we have an equation that work done is just the applied force times the displacement. And so the potential difference is the work done per unit charge. So we're going to actually have a definition. Again, you get this one on your data booklet, and it goes like this. The potential difference is W over Q. You get this. You're given this. You don't have to memorize it. I think the key thing is to remember what each of these things means. First of all, we have V. That's a weird one, right? V is called the potential difference. And we're going to measure it in volts. Do not call it voltage. See, this is how I say never use the word voltage, especially on IB exams. Don't use the word voltage, use PD instead. In other words, potential difference. The IB will often use PD like this, or just potential difference. Do not say the word voltage, even though it kind of is, but don't use it. But it kind of is, but don't use it. Work done. Do you remember what that's measured in? Work is a form of energy. So work is joules. And charge, of course, is coulombs. So you could say another unit then for volts. Instead of volts. So the potential difference could also be measured in what we call, let's see, it would be joules per coulomb. So that's another way of writing it. See, just so you know, that's another unit of it. Now keep in mind, this isn't very intuitive. A lot of students really struggle with this. And also, by the way, the path taken doesn't matter. In other words, the way that you got there actually doesn't matter when you do your work. It just matters the total work done divided by the charge. There you get this thing called potential difference. It's going to make more sense, I think, when circuits are involved. But at least this is just a general definition. And finally, I think the most interesting one, and this can be an IB question, I've seen this show up many times, something like this. What's the kinetic energy of an electron accelerated across a potential? So what we're going to say is, imagine we have two plates. Can you imagine I have like a charged plate here and a charged plate here? And because of that, an electron is going to be accelerated. So the question would be like, maybe the question is, how fast is that electron going by the time it's done accelerating? And this is the very definition of this word electron volt. And this shows up in other topics as well. So when we're talking about particle physics, if you do the option called relativity, if you're looking at atomic physics and this famous equation E equals mc squared, we often put the energy in terms of electron volts. And you'll see why in a second. So on your exams, they don't actually give you what 1 electron volt is. So we have to think very, very carefully about this. So I'm going to show you a little trick here, and this trick is awesome. I'm going to start off by saying 1 EV. So 1, if I want EV, I want 1 electron, right? So that means I want 1 charge of an electron, so 1 charge, times 1 volt. So we're going to write this down now. Actually, maybe what I'll do is I'll cut this piece right here at least. I'll just say E times V. In other words, the charge times the potential difference. And it turns out this right here is a unit of energy. This right here is. This is an energy. Although it looks like I just wrote like a hipster mustache here, but I mean it to denote the energy here. So this is a form of energy, E times V. That's the one thing you sort of have to know. What I like is that the definition of electron volt sort of comes into its word. 1 electron times 1 volt. That's what I love about it. And remember, we know something that's measured in energy. We know the kinetic energy of something. We can say it's half mv squared. So this is the kinetic energy of, so this is, I could say, Ek of that electron. So if I knew the charge of that electron, I knew the potential difference, I knew the mass of the electron, which I can look up, then I can tell the speed of it. Or I could be asked, what's its energy? Then I would just, E times V is the energy. But maybe I want to find the mass of an object or the velocity of it. So this is much more powerful, this one equation here. I think this is the really key equation here to try to look at, is EV equals half mv squared. Now, what is actually 1 electron volt? This is actually really awesome. Watch this. If I take 1, maybe I'll do a different color here. I'll do it, we'll do the blue here. So I take 1 electron. This is what I have this time. 1 electron across 1 volt. If that makes any sense. Well, then I have to look up the charge of an electron. And if I look at my data booklet, I can see the charge of an electron, little e, is 1.6 times 10 to the minus 19 coulombs. That's just 1 electron charge. And this thing right here times 1 volt. And it turns out you can just multiply this. Now look very carefully. What do I end up with? I end up with 1.6 times 10 to the minus 19. But I have coulombs times volts. We need another unit for that. And it turns out a coulomb times volt is also a joule. You'll see that back here. Look, we've sort of proved it back here. Look, didn't we say that 1 volt right here is a joule per coulomb? Can you see that? So that means a joule is, if you imagine this joule right here by itself, you know that this is like a joule divided by C, right? That's what this really is looking like. And that means if I want a joule by itself, I could put the coulomb over there. So see, a coulomb volt is equal to a joule. I don't know if you believe me, but it is. So it turns out 1 coulomb times 1 volt is a joule. So watch very carefully, and this is the sort of magical thing that ends up coming from here. So you can see that 1 electron volt is just, again, 1 electron times 1 volt. Now remember though, E is actually a number. So E is a charge of an electron. It's the elementary charge. Remember, charge is quantized. So all other charges you find in nature are multiples of this. So all I have to do is say 1 eV equals 1.6 times 10 to the minus 19, which is the charge of an electron. But because of the magic of the units here, a coulomb volt equals a joule. So this is like my conversion factor here. This is what I need in order to convert from 1 electron volt to 1 joule. You either multiply by this magic number or divide, depending on what you want your units to do. Awesome! Welcome to Circuits. Today's circuits joke is brought to you by Futurama. I like this one. I'm not sure if V is for velocity, volume, voltage, viscosity, or frequency. Because frequency doesn't have a V. Oh, I like it. All right. So let's talk about circuits themselves. I think a lot of people really struggle with circuits because I don't think we have any intuition for them. If you imagine we're looking at something being launched in the air, I sort of understand that because I've seen things fly through the air, right? We understand waves in some senses. So we have some intuition about these things, but circuits, a lot of people it's just gross. People just don't get it. So I'm trying to show you an analogy here that I think is going to help. But like analogies, I mean, all analogies are just that. I mean, it doesn't say exactly what electricity is. We're going to say it's what it's like. It's like kind of this. A lot of analogies that teachers use, for example, is like with water. Water flowing down a hill is like what it is. But I don't think that really is a very good one. At least it's not good enough. So I've modified one that I read about that I actually really liked. So I'd like to show you this with chocolate. Not with real chocolate, unfortunately, but with imaginary chocolate. So this analogy is going to require a few things, and clearly there'll be some places where this analogy fails as well. But what I think it really does is it gives us a sense of intuition. I think that's going to be important. In fact, we're going to try to sort of derive Kirchhoff's laws. We're going to see how it goes here. So let's see how far we get. So first of all, in this analogy, what I would normally do in a classroom, I would actually get all of the students standing up, and it's okay, everybody arrange yourselves in a circuit. And a circuit just means, in some sort of way, like some sort of path for them to follow. And now in this analogy, so can you see that that's actually why I've got these little dots, for example, in here? Those represents the students that are just sort of arranged in this sort of square or a circle or whatever. So in this analogy, the students are going to represent in the real circuit's land the coulombs of charge. So the students themselves are coulombs. So you have to think of that first. The good thing is, I think that that's going to help you to know that they're conserved. Because if you imagine you have a circuit and it's moving around, the number of coulombs don't change, right? You don't like kill students. Well, hopefully not. That'd be messy. So they're conserved. They stay the same in the circuit. No matter what's going on, the coulombs themselves are fixed. They're conserved. They don't change. Now we're going to have, now you have to imagine this. You have to imagine a student that I designate the battery. And that student's job is a really nice job. Their job is just to give out chocolate. So imagine if I'm the battery, I just have a bunch of chocolates here, and if you pass by me, I'm just going to give you a piece of chocolate. So that's going to be the rule of the game. So every time a student passes in front of the battery, that battery gives chocolate. In this case right here, the battery, what it's going to give is electric potential. In other words, it's going to give 1 volt. So let's just say we say 1 piece of chocolate equals 1 volt. Remember, I'm not going to say voltage, so I'm going to say potential difference. Or it has an electric potential. So if we measure something, we're gonna see later on why we call it a potential difference. It'll make more sense in just a second. So we're gonna, that's the quote unquote voltage. So just remember, 1 chocolate equals 1 volt. Now the ammeter. By the way, just before that, so this right here would be the rule of the game. So these coulombs would actually just travel around the circuit, just like these coulombs right here will travel around this real circuit. I'm going to skip a little bit ahead and tell you about the rules of the game. First of all, the rules of the game is that the coulombs have to be smart. What do I mean? I mean, clearly they're not sentient coulombs. So in order to understand this analogy, this is where it fails a little bit. You have to sort of suspend some disbelief here, but that's the point of an analogy, right? It doesn't say, of course, coulombs aren't chocolate. It's just a way for us to help understand it. But to do that, you have to imagine that the coulombs, they're smart. They can see what's ahead, so they can act accordingly. They can plan. And they've got to use up all their potential. In other words, they've got to use up all their chocolate before they come to the battery. And remember now, the battery gives chocolate to each coulomb as they pass by. So what that means then is, and by the way, you're not allowed to hoard. You're not allowed to save up. So in other words, if I got a piece of chocolate, so I pass by the battery, I got my piece of chocolate. As I go around the circuit, I have to eat it. And the important thing is eating chocolate. This is going to be the important thing, because when you eat chocolate, you're sort of losing, you're gaining energy, but, you could say that the chocolate itself is losing. There's chocolate being used. In this case right here, as you go around a circuit, you have to use electric potential. In other words, in this world's dumbest circuit here that doesn't actually do anything, can you imagine if you're a coulomb, you pass by the battery here, and it gives you 1 piece of chocolate. In other words, 1 volt. That means as you go around the circuit, then you must lose 1 volt. And remember, electric potential is related to energy, so you're literally losing energy. And this energy lost is really important. This energy lost, in fact, is lost often through heat. So that's why circuits get hot. So for example, this really boring circuit right here, this real circuit though, is what we call a short circuit. Because can you see the coulombs themselves? They can just pass around right here, and then they just come right to the battery. They don't really do anything, but they're going to have to eat up their chocolate, like in this analogy here. So that means if you walk around, remember, you'd have to eat your chocolate before you can get to the battery in order to get another one. You're not allowed to hoard and save up. So by that analogy then, if we look at real circuits, that means that you're going to have to use up energy. And when you do that, it's lost through heat. That's how it's lost. So this is why circuits get hot. This is why, your phone, for example, my little phone right here, if I'm, doing a lot of really tough things for my phone, like, on YouTube or whatever, and the phone gets very, very hot. That's because you've got a lot of circuits going on and things are really heating up because they really are losing energy in the form of heat. Now we're going to have some detectors we need to bring into this situation. We've got someone called an ammeter. This would be a student in the class who I would designate as the ammeter. Their job is the worst job. Their job is actually to just sit in the circuit. So part of the circuit is going to be key here. So that ammeter is actually going to be connected in, we're going to say, in series. What does it mean to be in series? It means you have to be part of the actual circuit. So you have to be, you have to have the coulombs actually passing right by you. I would have that student actually stand there with their arms out. It's the worst job in this. They would stand there with their arms out, and then as a student passes by, they have to spin. So if you imagine them, they're going to just sort of spin. And think about, they're counting students per second. Well, if you're an ammeter in this case, if you're thinking about what's a student, it's a coulomb. So if you're an ammeter, you're measuring charges per second. You're measuring coulombs per second. And wait, if you're measuring coulombs per second, isn't that the current? This is why this is the case here. So we basically sort of talked about this ammeter here, literally in this sense right here, right? So it's measuring coulombs going by per second. So that would be connected directly in series. I like to think of it as like if you go to an amusement park, sometimes you have to pass through this like little gate. You have to sort of like turn this little turnstile, it's called. So as you walk by, a little thing has to turn around you. Imagine that happening in a circuit. The ammeter has to be part of the circuit in order to turn it to count people per second. It has to be part of the circuit, so the coulombs have to pass right by it. By contrast, we have someone called the voltmeter. That would be someone in the class who's really tall. Let's say it's really, really long arms. And I would tell that student, your job is to use your arms, and put them around something. So what you're measuring a difference in chocolate. So what I mean by that is, what if I connected my voltmeter right here? Can you see that? If I did that, I would put my arms around this. And think about this then. If you're coming in this way, by the way, in the IB, it's not really so important which way the current actually goes. Because there's something called the electron flow current, there's something called conventional current. They go opposite directions. It's not so important to know the direction. It is important to define opposite directions to each other, that's true. But, when we're doing circuits later on, I'll show you that when it's important. But just to know that they're opposites. In this case right here, this is fine. It doesn't matter which way it goes. Imagine that if you're measuring a difference in chocolate here. That means, imagine you're going around the circuit in this way over here in a clockwise direction. That means, you gained a piece of chocolate here. That means you had to use it up and eat it while you passed by the circuit. That means when you come back to the battery, you've got no chocolate. So can you see the voltmeter's arms? Their job is to measure across something. That's why it's measured in parallel, we say, because that's measured across. It's not part of the circuit. It's sort of measuring a piece of the circuit. And if you measure across it, this right here will tell you something really important. It'll tell you difference in chocolate. So what do I mean by difference in chocolate? I mean, coming in, you'd have 0 chocolate. Leaving, you'd have 1 chocolate. So 1 minus 0 is 1. So you'd have a gain of 1 chocolate. In that same way, the voltmeter here measures a difference in potential. Remember, chocolate was potential. So in other words, that's why it's called a potential difference. It literally measures, the volts. So if you're going to measure the volts, you're measuring, amount of chocolate. You're measuring difference in chocolate. So in this real situation, you're measuring difference in voltage. Potential difference is what it measures. That's actually why we call it a potential difference for a reason. Because there's a difference in electric potential from before and after. So I think this is something that's really important. In another video, I'm going to define a lot more just to make it make a lot more sense. In continuing with this circuits analogy, I'm going to just review again. Remember what a voltmeter does? A voltmeter measures the potential. In this case right here, in the analogy, it was a difference in chocolate. In real life, it measures a difference in electric potential. So we call that 1 volt. And remember what the ammeter does? It's connected directly in the series, whereas the voltmeter is connected in parallel. Let's now continue this to add some more devices to it. So we've talked about the rules of the game before, so let's add now what I would, in the analogy, I would call them, I'll just bring in some chairs. Not call them chairs, they are chairs. I'd bring in some chairs, so that's what I've tried to draw here in my crappy drawing. Can you see you can see I'm not an artist. No one's ever invited me to art school. You can see why. You can see a little chair right here. So what I would say is that if you're going to, cross something like this here, you'd have to, eat chocolate in order to cross a chair. I don't know if that makes sense. So before, when we didn't have anywhere to cross, you would just come from the battery and just sort of eat some chocolate on your way out. But in this case right here, if we've got the chair there, I hope it makes sense to you that if I was going to walk across here, can you see you'd eat your chocolate when you pass over the chair? So in this case right here, chairs are going to represent resistors, because chairs are going to cost you chocolate. Resistors are going to cost you potential. In other words, V. Like if it's a 1 volt. So let's just say again, if at the battery I gain 1 volt, in other words, I gain 1 piece of chocolate, then I have to use up 1 piece of chocolate. So in this case, I'm going to draw a resistor as a little square like this with an R. And that means that it's going to cost me maybe, in this case, if it's 1 volt here, I'm going to eat 1 volt of potential here. So So now I'm mixing the analogy I know in the real circuits, but this is how I like to do it. So if you look at it, you gain one piece of chocolate here, you gain 1 volt. That means as you cross the chair there, you lose 1 volt. So there really is sort of a gain and a loss. And I think now we can start actually looking at a series circuit. So we're going to define this. First of all, we're going to define resistors. So resistors themselves, we're going to say that they have a unit of ohms. So that's why resistors, they're actually, that's maybe a key thing right here. We'll just say, so the units of resistance, so we'll say R equals resistance, and this is measured in a unit we call ohms. It looks like, well, this is a Greek capital omega. So this is the unit we use, so it's called resistance. So this is the value of this. In the analogy, it would represent like the height of the chair, if that makes any sense. So that way, as I'm passing along, maybe I have 2 equal-sized chairs. So what I want to do now is, this is given, by the way, so you're given that the total resistance, what that means is that the equivalent resistance here is given by just the sum of all the different resistances. So this is really important. First of all, you get this on your data booklet, so you don't have to memorize this. Series circuits, the equivalent resistances is just add up all the resistors. So that's what we have here. So what I hope we're going to be able to do is kind of derive from intuition the results of Kirchhoff's laws. You know, this Kirchhoff or Kirchhoff, I've heard them called different things. I'm not sure how to pronounce it right, but I'll just say Kirchhoff, and hopefully you'll forgive me if I say it wrong. At least I'm going to be equally wrong. I'll at least be self-consistent. So what I'm going to do then is I'm going to show you the result of Kirchhoff's laws. We're going to have a separate video showing you how to do them. There's something called loop law and the junction law. But the results themselves, I think, are more important. And I think that's where a lot of students don't have intuition. Here we're going to get intuition from it. So we're going to kind of come up with the result of this, hopefully. So imagine now I've got real circuits here, but I'm going to still use the analogy to help me. Can you imagine here, this is a battery. Imagine it's a 1 volt battery. So it's like, you know, you get 1 piece of chocolate from the analogy here. So as you're a coulomb of charge, you pass by here, and everyone has to follow this circuit, right? Everyone has to go around. You don't have a choice. So as you go around here, imagine you had 2 equal-sized resistors. In other words, 2 equal-sized chairs. So wherein before I was, you know, crossing here, it was clear if I gained 1 volt, you know, if I gained 1 volt, here, I would then lose 1 volt. What happens when I have 2 chairs? If they were equal height chairs here, does it make sense what I would do? I mean, most people have intuition here. Think about it. If you gain 1 volt here, you know, so 1 piece of chocolate, let's just say, how much chocolate are you going to eat in order to get over both chairs? And most people know it's half. Wouldn't you eat half here and half here? Because you know intuitively, without thinking about it, that the amount of chocolate you gain, remember, it has to be used. So because it has to be used up, that means, you know, in this case, I would eat a half and a half if they were equal-sized chairs. So you already have some intuition about this. Now think about this. What if one of the chairs was taller than the other? Would it make sense to you then that maybe I would eat, I don't know, like 0.7 and then 0.3, something like that maybe? So, you know, taller chairs or bigger resistor values means, you know, you might need to use up more or less of the potential. But you still somehow know through intuition that the sum of them has to equal that amount. So this is why I'm going to write down what I think is really, really important, that V total. So what does this right here mean? That means the total sort of potential right here across the battery. When I say total, I mean across the battery. So we could say VT. Some people call it V0. What this means is that you can redraw this whole thing as if the battery, see, it thinks there's only 1 resistor. The battery's going to act like there's just 1 resistor. You could redraw this as just 1 resistor whose resistance is just the sum of these resistors. You'll see that in more context, that'll make more sense. In this case here, if I look at V total, then I hope you're okay with this, that that'll be equal to V1 plus V2 plus ... So what do I mean by that? What I mean here is that, look at this here. If, notice I'm not drawing all my different detectors everywhere because that would get really annoying. I mean, I could. Right? I could have a detector. I could say, all right, I'm going to measure the voltage, or sorry, the potential difference right here across this. Can you see that? So remember, if they were equal sized chairs, can you see here I would measure a drop in one half of a piece of chocolate. And over here I would measure a drop of one half of a piece of chocolate. So you have to imagine your little voltmeter sitting across all these things. And if over here it would measure V1. If I placed it here, see that? It would measure V2. And so on. So this here would be V2, this would be V1, this here would be VT, would be measuring it across the battery like this. And just to show you how it would be plugged in. Of course, that makes the circuit messier. That's why I'm trying not to mess it up. Of course I have, so it's a bit ironic. So do you see how if I had a whole bunch of them, I would just have to add those values up? So maybe I had 3 resistors that are equal size. And can you see you do like 1/3 plus a third plus a third? Because you know it kind of has to equal that whole amount. So you already have intuition. By the way, this is the loop law result of Kirchhoff's law. We have another one for current as well. Imagine I put an ammeter right here, right by the battery. Can you see that? Right by the battery if I put one there. Imagine how many coulombs per second I'm counting here. Or in other words, students per second in the analogy. Imagine I compare it to right beside R2. I could call that I2 right here. And maybe right beside R1, I could call that I1. And can you see how the number of students per second wouldn't really change? I'm not allowing students to separate and go different paths. So in this case right here, I hope you can see that my IT, in other words, the total current here, will be equal to just the current in, current near I1 plus the current in I2 equals ... In other words, as many different currents as I have. There we go. This, by the way, these are the 2 results of Kirchhoff's laws here. This is really important, that you can have some intuition for this. Next, then, I hope this is going to make even more sense then. We can go a little bit faster, maybe. Parallel circuits. First of all, we have an equivalent resistance here. So the battery is going to act as if there's one resistor, but it works a little bit differently. This one's given on your data booklet again, because 1 over R total is 1 over R1 plus 1 over R2. So that's how you deal with parallel resistors. So if we look at parallel circuits here, let's look at this here. If we're going to look at this, imagine then I'm looking at the potential. In other words, the voltage values here. So this one right here, VT, if I'm measuring that right there, compared to V1 right here, and compared to V2 right here. If I was going to measure those potentials here, this difference in potentials, imagine this. You have to really think about which path you take. For Kirchhoff's laws, it's important to think about what loop you take. Imagine you're a little coulomb right here. Can you see where I'm pointing on the screen here? Imagine you're a coulomb right here and you go around and you choose to go this way. Wouldn't that make sense? You could do that loop. If you do this, and then imagine you're a different coulomb might take this path, like it might take the big loop. So can you see here there's 2 loops? There's 2 different paths you could take, either this small one here or this bigger path. But if you're 1 coulomb, you have to think about the analogy here. Remember, imagine you gained 1 piece of chocolate here at the battery, so 1 volt. That means as you go along here, what are you going to eat when you cross this chair here? In other words, what are you going to eat right here before you get back? Does it make sense? You're going to eat 1 whole volt here? And what if you did this path? What if you did you started off this, you did the big path right here? Wouldn't you also eat 1 volt in order to get back? So I don't know if this will make any sense to you. I hope so, but then it means the total potential difference here at the battery is going to equal V1 equals V2 equals ... So in other words, the potential differences here will be the same in parallel. Because remember, you just have to think about the intuition. I think it'll help you. And let's do it for current. Imagine your little ammeter right over here. Let's say you're measuring all the students per second here. That would be IT in this case. IT. And now I'm going to measure, compared to, imagine a little ammeter that's like sitting right here beside R1. We'll measure I1 here. Does it make sense we don't have so many students per second? Because some of the students per second might have gone this way. Some of the students per second are this way. So if you're measuring right here beside R1, you're not getting all the people per second. Not compared to this. But can you imagine that the people per second here plus the people per second in R2 here, so I2, those would be equal to this. So in this case, that's why these ones right here, they add. So the currents add. And these, by the way, are the results, again, of Kirchhoff's laws. So if you actually work out Kirchhoff's laws carefully, for the loop law and the junction law, this is the result. This is what it leads to. So you somehow need to be able to have some intuition here. I think that will really, really help. In the last video for our circuits analogy, congratulations, by the way, for making it this far. We've now defined a few things. We've talked about the rules of this game. We've talked about detectors, ammeters, and voltmeters. We've even intuitively come up with the results of Kirchhoff's laws for series and parallel circuits. How amazing! Now let's put it into practice. So here's an example. It's a combination of kinds of things that show up often on exams for IB, not only paper 1, but also paper 2. So I've sort of combined a few things into one sort of potentially nasty question. But when you understand this stuff, these kind of questions can be super easy. And that's the goal. So in the circuit below, find the total equivalent resistance at the battery. We have a 10-volt battery. And if you notice then, if you're a coulomb of charge here, imagine which path you're taking. Remember, it depends on which loop you take. So watch this. You go along this way, you go along this way, and then, you have a choice. You might go down and take that loop. Or you might go and take this loop where you go up and across. But you'll have to still consider. So there's one of those two loops. First of all, we want the total equivalent resistance at the battery. What that means is, what is the battery acting like? The battery is going to, act like there's just one resistor. In other words, you can redraw it as just one resistor. And maybe actually that'll be one way to do it. Sometimes I like to solve these questions by just redrawing it. So can you notice right now, this looks really gross, right? So maybe I can make it easier. Watch this when I'm going to do this. Maybe you're going to like this. Oops, like this. What I'm going to do is attempt to redraw it as, do you see these two resistors in series with each other? If I just concentrate on this section right here, there's two resistors in series. And what do we do with resistors in series? Remember, the total resistance of that little piece is just add them up. So in this case right here, I can redraw it as, instead of R and R plus R is 2R. So I'm going to replace it with just one resistor of value 2R. And this one's still 1R. I'm going to redraw it one last time. Watch this. I'm going to redraw it now as if it's just one resistor now. See, this is what we wanted. The total equivalent resistance. This is this value here. How do I deal with that? Can you see I've got two resistors in parallel now? Can you see in parallel circuits? If you got a place with a path, the coulombs can go in one path or the other. That's what I have here. So I can say 1 over R total equals 1 over R1 plus 1 over R2. I'm going to use that. So in this case here, I'm going to say 1 over R. In this case, I like to put P for parallel. I'm going to put that little parallel part here. Well, it's going to be 1 over R, that's this bottom one here, plus 1 over 2R. And you just have to be very, very careful with your fractions. So if we look at this, then let's see. That means 1 over RP equals, I just like P for parallel. Let's see. I need to make them both the same denominator. So I'm going to make them both over 2R. Luckily, the second one is already over 2R, so that one can stay. However, I have to multiply R by 2 to get it to be 2R. So that means the top has to also multiply by 2. Therefore, I can say that 1 over RP equals, let's see, 2 plus 1 is 3. So the answer is 3 over 2R, right? No, wrong. I just wanted to allow you to think about the wrong answer. This is 1 over RP is 3 over 2R. Therefore, RP, you could think about, you could flip the equation. If you see my hands are here, you can actually flip the equation. You can actually, you go like this. Some people call this cross multiply and divide. I call it just do algebra. It was in my mind, look at this RP. It comes up to the top here, but that means you have to bring this one over here to the top. This one goes to the bottom. So either way, you end up with RP equals, let's see, it's going to be 2R over 3. That's going to be the total resistance here. That's going to be, it's going to act like there's just that resistor right here. It's going to be 2R over 3. It's going to be like one resistor that's a value 2R over 3. That's what the battery is going to act like. That'll be the total equivalent resistance at the battery. All right. That was actually the hard part. Turns out the potential difference across A and B, sometimes these questions are amazingly easy. Think very carefully about this. This is, you can think about it using Kirchhoff's laws, or you can think about it using this analogy that I've shown you. Imagine then you pass by the battery. You're a coulomb of charge, so you're getting a piece of chocolate. I'll use the analogy. You're getting 10 pieces of chocolate, and then you go through it and you pass by here. Right, through that path there. If we're going to consider A and B, we've got to consider that path. Think about this then. If I want the potential difference across A and B, that means I would place it here and here. What would I measure? Can you see how here you've gained 10 pieces of chocolate? That means if you measured across here to here, remember if you've taken this path, that's everything. So that means if you've gained 10 pieces of chocolate, does it make sense here that you would lose 10 pieces of chocolate? That would be the potential difference here. You just say V equals 10.0 volts. In other words, it would be the same exact voltage. Same exact potential difference. Isn't that amazingly easy? Oh, by the way, let's just ask, what if it had been, what is it across this R right here? What would you say it was? Remember, these are the same R values. This is R, this is the same R. Does it make sense? This would be, because they're the same height chairs, you could say in the analogy. Does it make sense that you'd have to eat up your 10 pieces of chocolate evenly by going over them? So do you see this one is 5 volts? This one is 5 volts. What is it across this one? Imagine then you cross over this one here. Do you see this one here would be 10 volts? So this one here would be 10 volts. This would be 5 volts. This would be 5 volts. If that makes any sense. Because look, if you go across this right here, you got to go 10 has to equal 5 plus 5 if you do that little loop. If you do the outer loop, you only pass through one. That's why you have to eat all 10 volts here, all 10 pieces of chocolate. I hope that helps to make these circuits way easier. It's time to talk about Ohm's law and resistance and power. I love this join the resistance in Ohm, because it's like people are praying. So let's see if this makes any sense here. First of all, we're going to define Ohm's law. And I love this one right here. It's a nice little pun even involved in it. But the equation that you get in your data booklet actually goes like this. R equals V over I. That's the one you actually get. I prefer it to look like this. I like it better, V equals IR. I like it better that way. But I mean, this is the same, right? V equals IR, it's the same. So let's look again at what are these different values again? Let's just remind ourselves. What is resistance measured in? It's actually the Greek capital omega. And I love that because it's like omega. See, it's like, oh my God. That's a bad joke, sorry. Then we have V equals the potential difference. Remember what that's measured in? Volts. And I is the current. What's that measured in? Amperes. I hope you're yelling at the screen. That's good. So I'm just going to fix it up here so it looks a little bit prettier. There we go. What I want to show you though is you can linearize this bad boy. What do I mean by linearize? I mean, what if I rewrote this like this? This is going to look a little bit dumb. I'm just going to say R times I. Isn't that the same thing as V equals IR? The reason I'm doing this is I'm going to look at this and see it as a linear graph. Watch this. If I graphed this as the Y value and I graphed I as the X value. Do you remember your equation? Like, doesn't it go Y equals MX plus B? Isn't that the equation for a straight line? Look, that means any junk in front of the X value, that's the gradient. So watch carefully. That means if I graph V versus I, see, Y versus X, then any junk in front of it's going to be the gradient. So that's why this right here is the gradient, or the slope if you prefer that word. So that means that this should be a straight line and it should pass through the origin because there's no plus anything, right? So it's not shifted up or down. That means then if I draw it right, it should look like, let's see if I can make it look nice and pretty here, something like that. Where we know that the slope, or sorry, the gradient, this is going to be important, the gradient is going to equal the resistance, which is measured in ohms. That's again because the gradient, if you think about the gradient, then it'll be delta y over delta x. So the gradient will be v over I. And hey, look, that's the definition of a gradient, delta v over delta I. So you can see it all hopefully makes sense. This is called Ohm's law, by the way. We say that if something is linear, see if the relation between the potential difference and the current, if it's a straight line like this, we say this thing is ohmic because it follows Ohm's law. It's possible that it's a curve, and if it's a curve, we say it's non-ohmic. That's how it works. It's nice and simple. Let's go with one other thing now. We're going to talk about resistivity in a wire. This doesn't show up so often. I think it's just good to be aware of it. So if you have a wire right here, we could find the resistance in the wire. So we're going to, of course, let's just make sure we know the units here. Resistance is just ohms. This is a property. It's called resistivity. You can actually, we'll talk about its units in just a second. The length of the wire, that'll be in meters. I hope that makes sense. That's the length of the wire right here. That'll be in meters. Cross-sectional area A, that would be this area right here. That would be this A. So that would be in meters squared. So if you think then about the units for it, if I wanted resistivity by itself, wouldn't I do R times A, because I'd have to move my A up here, I'd divide by L. So look at the units then, it would be ohms, if we do the units for it. It would be in ohms times A, which is in meters squared. Divide that by the length, which is in meters. So what happens to the meters? They cancel out. I end up with resistivity's units is ohm meters. So that's why this is in ohm meters. So you don't have to memorize it. Just figure it out as you go along. It's actually a nice simple equation. There's not really much to it. I want to get to what there is more to it, which is power. Power dissipated is an energy lost in heating up. This is really important. Resistors themselves, they will heat up. So there will be a loss of energy, you could say. Because remember, we have this trick right here. I just wanted to show you this one. Remember that power is work over time. And if work is a form of energy, then it's energy over time, which means the units for power could be in joules per second. That's 1 unit. But we also use the unit we use for power. Do you know what we use for units for power? It's awesome. What's the unit for power? What's the unit for power? It's a watt. That's a really dumb joke. So the unit for power, we call it a watt, but a watt is also the same thing as a joule per second. So this is a really important trick, I think, is knowing this right here, okay? This is really, really important. This will make your life a lot easier in the IB, very often. In fact, if you get really complicated questions where you're mixing different topics, like topic 2, like mechanics, for example, that's being mixed with this kind of thing, then this becomes really important. This is how you can mix, like, I don't know, you have a motor that lifts up something in a certain amount of time, and so you could figure out, see the energy that you've used to do that. Then they would say, what's the current in this thing? And you think, how do I link mechanics with electricity stuff? This is how. Because you can get to this energy. And once you know about energy over time, that is the same thing as power in watts, which means that's the same thing as this one here. So the power is normally just written as I times V. So it's the current times the potential difference. But if you use V equals IR, see that you could replace for I. So what if you got I by itself? Could you see that I is also equal to V over R then? So then instead of I, you would replace I with V over R. Can you see that? So if you replace this I with V over R, you'd have V times V over R. That's why you get V squared over R. And if you used this one right here, but instead you replaced V with IR, so where every time I see a V here instead, I replace it with an IR. So I have I times IR, so that's I squared R. That's why this formulation and this one with I squared R and V squared over R are actually, all three are the same formulation. It just depends on which value were you given. Because remember, in Ohm's law is the way of finding out the third thing. In other words, if you know in a circuit the potential difference and the current, then you can find resistance. Or if you know resistance and current, you can know the potential difference. And if you know the resistance, potential difference, you can know the current. This is like your conversion factor. This is how you get, if you know 2 of them, you know the third one. So this is why it's really important, and you have this version of power that has any of the 2 pairs of values that you know, whatever is most suitable for you. So P is the power, and like I said, we measure in watts. That's it. That's all you need for power dissipated. So dissipated really means energy lost. Now let's do an example. So now we have a circuit below. We're supposed to find the power dissipated in the entire circuit. So my goal then is to find out what's the power right here. If that makes any sense, like the power sort of at the battery, that's taking into account all this junk here going on. And this should be easy then. The power is just I times V. So do you see that if I just knew the current here, or I could call IT, let's just say. If I knew that, wouldn't it be easy? I would just do 8 times that current and I'd have my answer. Great. Okay, what's the current? I'm not sure. Or, remember, I could have also, what if I knew the resistance here? If I knew the resistance here, then I could also do it because I could use P equals V squared over R. Or I could do I squared R. I guess it depends on which one I feel like doing. But do you see I'm missing one of these stages? I find a lot of times in the answer keys it's not clear what you should be finding. This is why I'm trying to show you the intuition for it, the logic behind doing it, or maybe illogic, I don't know. So do you see how I need one of these values to do it? There's a number of ways, of course, of solving these. You could figure out the power dissipated in each of them, that's sure. Sure you could. But just for fun, let's just use this analogy stuff that I've been showing you before, and let's see if this can make sense. By the way, this is supposed to be 2.0. Just realized it almost looks like 20 here. So 2.0, 4.0, and 4.0. So we could consider this. I could redraw this circuit. But I always like to redraw them. That's how I like to do them. So I'm going to redraw this circuit because can you see I've got a parallel circuit that's in series with this thing. So I'm going to try to just redraw because I love to do that. I'm just going to say 2 ohms here. I'm going to try to redraw it as just this. I think it's going to look a lot easier. So now I got to figure out what's this result. In other words, what do I do about this? I can say 1 over RP. I like to call it parallel resistance. And if you remember your rule for parallel resistors, 1 over R equals 1 over 4 plus 1 over 4. Because I have a same denominator, I can say then it's 1 plus 1, which is 2 over 4. So my answer is RP equals 2 over 4, right? No. RP, this is 1 over RP is 2 over 4. Therefore, RP is 4 over 2. So if that makes any sense, then 4 divided by 2 is just 2. So it's 2 ohms. Good, then that's how I get this. Now I've redrawn it as this. So now I've got a circuit. It's a lot simpler already, isn't it? So now I just look at it like this. Do you see I can take one step further? I can say, all right then, let's take one step further and draw it as just one single resistor. Does that make any sense? Now I'm just saying it. Now there's 2 resistors in series. And instead of series resistors, I like to draw it. Remember the rule for resistors in series? You can just do the sum of them. So 2 plus 2 equals 4. So this is like one single 4 ohm resistor. So if that makes any sense now, I know this value right. Watch this. I know this value right here. That value is 4 ohms. So now, I got to make sure that looks like a 4, don't I? So this right here is everything I needed. Remember, I needed the 2 of these 3 quantities. So if I'm not sure, remember, look, I've got the potential difference, I've got V, and I've got R. So let's look at an equation for the power. If I've got V and R, it goes V squared over R. So all I have to do now is go right here. I'm just going to change the color here. That means now I finally have power is just going to be V squared over R. So in this case, remember my V is 8. So I put in 8 squared, divide that by 4. Now 8 squared is 16, right? No. Remember, that's what a lot of people think. 8 squared is 8 times 8, which is 64. 64 divided by 4. If you're not too sure about that, you can always reduce it. You can always divide them both by 2, let's just say. So that's 32 over 2, which hopefully that makes it more clear that it's 16. So finally, my power then is 16 watts. That's the unit of power. Do you see I could have also done it by calculating the current? I could have done that. There's a number of ways of doing it, right there. So you could have actually found the current and done it that way. There's lots of ways of doing it, but I think this is one really good way. And I hope you see that it's not actually so hard. I'm going to show you how to use Kirchhoff's laws, even if you don't really need them, because I showed you this analogy. But I think it's a good idea just to know them in case you're asked. I love this picture. Basically apply Kirchhoff's laws with this big mess of wires. So we have a loop law, we have a junction law. And again, remember I said with this analogy that I gave you, it's kind of the same thing here. It's all the same. So let's look at a loop law. What does that mean? That means that if you go around in a loop, in this case, consider this. If this here's my battery, and I have 2 resistors here, I could do one loop. You see, I could do a loop that goes, let's say, this way. But can you see I can also do a loop that goes this way? There's different loops here. In this case, we've got 2 different loops, 2 different ways that coulombs could travel, right? Either the small one or the big one. Either way, in a total loop, this is the rule right here. You're supposed to say that the sum of all the potential differences, is 0. This is the first one you're supposed to do. This is called a loop law. I hope it makes sense. We learned this before, that let's say you came out of this battery, let's say with 10 pieces of chocolate, this analogy that I use, so 10 volts, let's just say, then that 10 that you gain here has to equal a total 10 lost if you do this little loop here. So that way, in this case, the sum of R1 and R2 have to add up to 10. Because whatever you gain, if you gain 10 volts in this case, 10 pieces of chocolate here, then maybe this is like 5 and 5, or 8 and 2, or 1 and 9. As long as they add up to 10, you're fine. And this big loop, same thing. So that means that's why in this big loop, if you gain 10, then it means you have to lose 10. So here you'd be at 10. This would be 10 volts across this resistor R3. I hope that makes some sense. So that's just the loop law. And the junction law says, in this case right here, that the sum of all of the currents also equals 0. This is called the junction law. Now there's another way to look at it. Sometimes we look at sort of current in and current out. So just the way I've drawn it here, let's just say, I could consider those. Maybe I'll do them in a different color here. Let's just say here I have it coming in right here, and I could call this I0, and here I could call this one here I3 going that way. I can consider them this way right here, I2. This is a junction. What that means, if I was to zoom in on that junction, then I've got this happening. You can see I've got currents going in and out. What it really means is your currents in have to equal the currents out. In this case right here, if I drew them like this, then what's going in this case it's just I0, then the current going in has to equal the currents going out. So this would be I2 plus I3. That's it. I don't think it's that hard actually. So what I'm going to do then, I'm going to consider then a really complicated looking circuit. This is one that looks almost impossible to solve because there's two batteries. There's two sources of potential. So you can see we've got a battery here that's 1.5 volt battery going sort of this way, doing this sort of loop or this sort of loop. And then I've got another battery doing this sort of loop or this sort of loop. So you could consider a bunch of different things, but if you keep it nice and simple, it'll be fine. For example, if we want the current in resistor 1, and you can consider this Kirchhoff's laws and say, all right, well, let's consider this, maybe this loop right here going this way. If we consider just that loop, if we know this is a 1.5 volt battery, because there's only one device to go across, you know that the gain in volts should be the loss in volts. So in this case right here, if this is 1.5 volts coming from the battery, then here you have to use 1.5 volts to go across this. So already I know, see how amazingly easy that was? Again, I don't really use Kirchhoff's law. Well, I kind of use it for a loop. I like this analogy better, but it still works. So I could say, so V1 then, so V across this one right here will be 1.5 volts. The reason this is helpful is because if I know that V1 is 1.5 volts, I know R1, can you see I can solve it now? Don't we know that V equals IR? So if I want current, can you see that I can say I1, the current, you know, maybe right here, or maybe right here, right before it or after it. I1 I could say is V1 over R1. You see that? I've got the first potential difference divided by the first resistance. In this case right here, then I have 1.5 over 1. So that means I have I1 is just 1.5 amperes. That's it. That wasn't that hard, was it? And then look at this, the power dissipated by each resistor. You're like, oh, that seems really hard. But actually, if you just look at this carefully, we just found, keep in mind, that I1 is equal to 1.5 amperes. This would be helpful because I can use that for another loop. Watch this. What if I do a different loop? What if I do maybe this loop going around like that? That loop. If I just consider this one right here. If I know that this right here, this V value is 9. So in other words, this one here coming around in this loop right here. This one here is 9 volts gained at the battery. Look at this carefully. Didn't we figure out this is 1.5 volts lost here? So what do you think this one right here has to be? I don't know if this will make any sense, but we can figure out V2. In other words, we can figure out the potential difference across this one, because we know that the voltages have to add up, or the potential differences. So in this case then, 9 volts has to equal 1.5 plus something. Because remember, your gain in volts has to equal your loss in volts. So 1.5 plus what gives you 9? And I hope you can see that's 7.5 volts. And if I want to be really good, I can also find I2. Because if I want to find the current here, you have to be careful. It's not quite just 1.5. You have to be really, really careful if because the loop law is the one that told me about the potentials. In other words, the voltages here. In order to get I2, remember that V equals IR. So if I want I, it's equal to V over R. In this case right here, then again, I can say fine then that I2 then is going to be equal to V2 over R2. So in this case, let's see, V2 is 7.5 volts. Divide that by R2, which is 2, so half of 7.5, and that is 3.75 amperes. Now, why is that helpful? That's because now I can figure out what goes on here. Look carefully here. If I want the power dissipated by each resistor, can you see that for around R1? Remember, I've got my equation for power dissipated. Remember, it goes, where is it? Power dissipated is P equals IV. So in this case right here, then I can say fine. Around, so the power in 1, this resistor 1, is going to be I1 V1. So in this case right here, then I'm going to say fine. I1 is, I know that number. We found it before, right? It was 1.5 amperes. So it's 1.5 times V1, which is 1.5 volts. So I have to do 1.5 squared, and that gives me 2.25. And remember what's the unit of power again? It's watts. So that's why I could say that P1 is equal to 2.25 watts. And I'm doing it to 3 significant figures, so we're fine. There we go, that's the first answer. And for the second one, around R2, I can say then that P2 in the same way is I2 V2. And let's see, what's I2? I2 is 3.75 times V2, which is 7.5. So 3.75 times 7.5, just using my calculator, and I get 28.1, let's just say. So I could say that. I could say P2 is 28.1 watts. Whoops, I made a bad W there. Let me just fix it up. So this is again to 3 significant figures. So you can see how you can either use Kirchhoff's laws or just be careful with this electricity analogy I showed you, but you can actually solve these kind of questions. So they don't have to be as crazy as they seem. You just really take your time, think about different loops, and you can do it. We have something called internal resistance when you have circuits. This is because they're real life circuits. Oh, maybe we'll look at the little meme here. This is again from The Office, but voltage divided by current. Resistance is futile. That's something, there's a lot of things here. Resistance is futile, supposed to be from Star Trek. Have you ever seen The Next Generation, the original versions? There was people called the Borg. But then, of course, Dwight Schrute from The Office, he says, wrong, superconductors, because the resistance is 0. Anyway. We have internal resistance. That's because real-life batteries aren't ideal. They're not perfect. They have their own internal resistance. And the way I like to think of it, it's almost like it eats away some of the volts. Of course, we shouldn't say voltage. We should say electric potential. That's why I put it in quotations. So here's the thing. If we zoom in on a battery, normally we draw the battery, with a little short little stick and then the tall stick. If we zoom in on it, you can really draw it as this letter epsilon, and with a little r. So this little r is going to be the internal resistance of the battery, and let's make sure we put in proper units here. That should be in ohms, that's a resistance. And this is the really weird part here. We have an epsilon, which is the electromotive force. And you might think, oh, a force, that's in newtons, right? Nope, the EMF is not a force. It's a little bit misleading. The EMF is actually a potential difference, which means it's measured in volts. That's the key thing right here. It's measured in volts. The way I like to think of it, the EMF is it's like what the battery's trying to put out. Can you imagine, you're actually trying to give this much potential? It's like, in this analogy, it's the amount of, chocolate it's trying to give out. It's trying to give out, let's say, 10 pieces of chocolate. But the problem is there's an internal resistance there. It eats up some of the chocolate, so to speak. So just imagine, it's like in everyday life, right? You want to, give out chocolate to the people who are passing by you. In other words, you want to give out electric potential. The problem is there's sort of a middleman, someone who's, hey, sir, I'll help you out. I will help you get your 10 pieces of chocolate to your customers. But of course, as they take the 10 pieces of chocolate, they just sort of eat a little bit. And then, hey, look at that, it's a 9-volt battery. No, it's supposed to be a 10-volt battery. Nope, it acts like a 9-volt battery. That's because the internal resistance sort of ate some of the chocolate. Remember, we're using chocolate and volts sort of interchangeably here. But this is the key thing here. It's like a middleman that just takes their cut of the profits. So let's maybe look at this equation right here. We have one for you. This is one that shows up directly in your data booklet. And it goes like this, that the EMF, that's this E, this epsilon, is equal to I. If you look, it almost looks like, doesn't it almost look like V equals IR? If you look at it, because remember, this right here is, that's measured in volts, isn't it? And this right here is a current, which is measured in amperes. And this right here is just a sum of 2 resistors, because there's 2 resistors in series. This because here you'd have a whole circuit. You'd have this thing right here plus your little resistor here. This is your inside the battery sort of zoom in. And then maybe you'd have a whole, like an actual resistor sitting in the circuit here. So this is a more realistic circuit, right? You have your EMF here. So really it's V equals IR. This is your voltage, so to speak. So, well, it's trying to be at least. So it's going to be like a V equals IR. That's sort of how it works. I hope that's going to make some sense. So what I'd like to show you then is this. If you want to see how the battery or how the circuit actually acts, I like to actually sort of break open this equation. This is the one you get. So I'm going to just rewrite it as epsilon equals, I'm just going to multiply these out. So I have I times capital R plus I times little r. And then what I'm going to do, I'm going to isolate for IR by itself. So that means I have to move my minus IR over to the other side. So you can see I have E minus IR equals capital I times capital R. Or can you see I've rewritten like this? So this is the same equation here. You see that's just this one, just written just the other way around. What I like is that this I times R, like the R of the whole circuit, that's sort of what you get. In other words, that's what the circuit actually acts as. Whereas this is the EMF, that's like what the battery tries to give you. Remember, it might be trying to be a 10-volt battery, but there's some voltage lost by the internal resistance of the battery. You know, there's some electric potential that's lost here. So that's why I really like to see it this way. It makes more sense to me. It's like it's trying to put out this, but it's losing this amount of V here, volts here, which means then you end up with actually getting this. So I like this because they're all in terms of V. They're all values with potential differences here in volts. And maybe let's do a real example. I love this picture. Electronic circuit. How does that work? That's how I think a lot of people feel with these questions. So let's look at this. So we have a circuit, and it consists of 10 identical 5 ohm resistors. So already, can you imagine that now? I've got a whole bunch of them, and they're all connected in parallel. So I don't know, maybe I have my circuit like this, and I have a resistor here, and then another one here. I don't really feel like drawing 10 of them, do you? Dot, 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 dot. Huh? I feel sad already at doing this. I don't feel like drawing the whole circuit diagram. I think you get the idea, right? There's 10 of them. So first of all, what's the equivalent resistance of the 10 resistors? Because I don't feel like drawing this. Let's just redraw it as one giant, well not giant, but one resistor. I'll call it RP. You know, like I'll just redraw it as one resistor. So what do I do with parallel resistors? Do you remember the equation for parallel resistors? You can look it up. But the equation goes like this. It goes 1 over RP, you know, the parallel resistor is 1 over R plus 1 over R plus dot, dot, dot. You have to keep going. Well, how many do I have? I have 10 of them, don't I? So in this case, I have 1 over RP equals 1 over, let's see, the resistance is actually 5 ohms. I have 5 plus 1 over 5 plus 1 over 5. Can you see I've got 10 of them, and they all have the same denominator? So are you okay with this? Watch. I'm going to go 1 over RP. I'm going to set that equal to 10 times 1 over 5. Because I got 1 over 5 plus 1 over 5 plus, I've got it 10 times. So I can just say 10 times 1 over 5. It's easier. Which is equal to 10 over 5, which equals 2. So you could say then that RP equals 2 ohms, right? No, remember again, this is 1 over RP equals 2. Therefore, RP equals 1 over 2, which is equal to 0.5 ohms. This is my equivalent resistance. So now, this thing really acts as a 0.5 ohm resistor. I hope that made some sense here. This is hopefully how it works here in your brain. Hopefully you're following. Now, we have an internal resistance. So what we've really got now, I can redraw this battery now. I can redraw it as this thing, then a little internal resistor, R, and then my one battery, my one resistor now, that is 0.5 ohms, if that makes any sense. This is a lot simpler to look at than this mess. So you have internal resistance of the battery, which is 0.1 ohms, and I have the EMF is 6 volts, so this is what it's trying to be. That's epsilon here. Now, what is the circuit current? Any ideas how to do this? You may want to look at this equation right here we just looked at. Epsilon equals I times R plus R. If you're not sure, just start with an equation you know. Isn't that how you get marks on an exam? It turns out it is. So I'll solve this. So I'll say fine, then I have epsilon equals I times R plus R. Well, I just want I. So can you see that I can just get I by itself? It's just going to be epsilon divided by. Now remember, I right now is multiplying the r plus r. That means I can divide them together. So it's like a 1 unit. So I'm going to divide both sides by that. So I end up with this. So the epsilon is 6 volts, right? So I have 6 volts divided by 0.1 plus 0.5. Maybe I'll write them down. So 0.5 plus 0.1 ohms. So that equals 6 volts divided by 0.6 ohms. I don't need a calculator for this. 6 divided by 0.6. I hope you can see that the answer then is going to be what? 6 divided by 0.6 is 10. And 10 amperes. So there we go. There's the circuit current. And finally, what's the potential difference across the terminal? How in the world do I do that? Across the terminal, that just means, like, remember, this is the terminal right here. This is the whole, this is the battery here, across this. So what we're really asking for is what's the V here? Well, don't we know that V equals IR? Isn't that what it's supposed to be? Remember, I even showed this little sort of short form like this. This is like what you get. This is the potential difference. You could say across the terminal. You could say it's that. That would be like across here. That distance right there. So the potential difference across this, let's see, what is it? It's just I times R. Do I know the whole circuit current? I do. The whole circuit current is 10 amperes. Do I know the whole circuit resistance? I do. What can I say here? The circuit resistance is 0.5. Can you see that? That's actually what the circuit is acting like. It's a 0.5 here. So I can say 0.5 ohms. Because remember, we're not caring about the internal resistance now. We're caring about the result here. So just I times R, which is just 10 times 0.5. So that just makes it 5. So finally I have 5.0 amperes. Oh, not amperes. Wrong units. Come on, Mitch. V is in volts. So you can see we've taken a question that might have looked really complicated, and we've simplified it, I hope you can see, immensely. So hopefully now you no longer feel like that little girl going, like, how does that work? Maybe you're like, maybe I know a little bit how it works. Now it's time to talk about magnetic fields. I like this picture of Tesla. He's feeling underappreciated again. So we have magnetic fields, and we're going to define the lines that we're going to draw, because we're going to learn how to draw magnetic field lines, and then we're going to quantify them with some equations. But we define it as the north on a compass, like where it would point. You know what a little compass is? It's usually a little thing that sort of spins around, and it depends on the magnetic field, and it points somewhere. So if you imagine you had a little compass, don't you see them? Don't they look like this? Like if nothing else, if you're using even like Google Maps or something like that, even with that, they usually draw it like this right here, you know, and this right here is sort of shaded red. You know, isn't that sort of a little compass like that? It's supposed to point north. In a real life, you know, you might actually have an actual compass that you carry around. I know when I've been in the woods, for example, we carry around a little compass like this. It's a little thing that's allowed to spin, then it can rotate. It tells you which way is north. Then you can use that to navigate. So if we have a magnet, so let's just say we have a magnet here, we define things as north and south. So conversely, you know, with charges, we had a positive and a negative charge. And what's interesting is charges can exist on their own. In other words, you can have a positive charge by itself, or you can have a negative charge by itself. But for some reason, you can't have a north by itself. So there exists a statement that says that there's no magnetic monopoles. It's really interesting. If you have like a compass like north-south and you go and start cutting it, it's still going to be north-south, still north-south. And then to the atom, the moment you cut it, boom, it becomes north-south, north-south. You can't have a north by itself. It's really weird. So imagine you have a bar magnet like this right here. Imagine that I place my little compass right here. Maybe I place it right here. Where would it point? Do you know that a north and a north, they don't like each other. They're going to repel. So it's going to go away from the north. But if I placed a compass right here towards the south, you can see that it would actually be attracted to the south. So then I could draw my magnetic field lines. I don't know if you see this, but you can actually go like this. You can draw them going out like that. And then out like this right here. Like that. And of course you can draw more lines. And more lines. You can draw as many as you feel like, right? Go along forever. So it looks kind of like an apple core, I guess, or whatever you want to draw. So it looks like this. This is how the magnetic field lines work. Now, have you ever seen people say that Earth is kind of like this? You can say, yeah, the Earth can be sort of looked at as a bar magnet. So you could say that it's like the Earth has a This is a very careful thing. Watch this carefully. It's technically a south here and a north here. And this is the part that's really weird to people. They say, no, we call it the North Pole. Yeah, we do. It's technically then a magnetic south. Because don't we agree that north on a compass would never point towards the north? A north, is away from a north. So watch carefully. This is actually the Earth. If we draw the Earth like this, it's just a minor little thing. But technically, the lines should go like this. This is actually how it looks on Earth. We still call this the North Pole because it is the direction that north would point, but it's technically a magnetic south. Some people get really bothered by that, so don't worry too much. If that really makes you upset, don't worry. You can say fine. It's still a north. Oh, wait a second. I drew one of my arrows wrong, didn't I? Look at this. This isn't this way. That one should be that way. I just want to make sure my drawing looks okay, right? I don't want to give you the wrong information. There we go. So this is how it's drawn. Now we're going to quantify things. So we're going to have a moving charge in a magnetic field. So imagine I have a magnetic field, I have a charge, and I move it along within it. We have an equation that's from your data booklet, and it goes like this. It goes F equals QVB sine theta. This is the equation you need. I don't know why I'm making sound effects, but there you go. So this is a vector, so is this. So let's maybe define a few things here. It's important to define them. So what's a force? In this case, it'll be a magnetic force, you could say. It's going to be the force that's acting on a charge. So force is measured in newtons. Do you remember what the unit of charge is? Q is a charge. So that's in coulombs. V is the speed of this particle, or this charge. So in this case, speed is in meters per second. Interestingly, here we have the unit of magnetic field strength. I just want to draw it nicely here. Draw a better S. So magnetic field strength. This is a new unit. Okay, this is something that we haven't talked about at least yet. We measure in a unit called Tesla. That's why I put Tesla here. He's underappreciated in a lot of science. There's a resurgence for him. But anyway, magnetic field strength measured in Teslas. That's why it's named after him. Also the car company, no big surprise, is named there. Then we have the angle between B and V. So the angle between the velocity, or you could say the speed, in this case right here. And the angle could be in degrees. So this is it. This is just the angle between them. What happens if the angle is 90 degrees? Then sine of 90 is actually 1. So then away you go. You can figure that out. That comes from, look at this graph here. Graph of sine of x. It goes like this, doesn't it? And this right here is 360 degrees. This is 180 degrees. So this right here is 90 degrees. And the sine of 90, in other words, if they're perpendicular, sine of 90 is this is x equals 90, this is the y value, and that's 1. So sine of 90 degrees equals 1. Just so you know, this is sometimes a nice to know. Just remember that one. Actually, I'll write it like this. I'll say if theta equals 90 degrees, we know that sine of 90 equals 1. This is maybe a good sort of trick for you. So nice little thing to try to remember. That's it. That's not so bad, is it? Then we have another equation. What if we have a wire in a magnetic field? So this is another equation you get. And this one looks a little bit like the other one, except instead of going QVB sine theta, this one goes BIL sine theta. So we'll define these things. So what are these? Maybe I better put the vector symbol on that. So F is a force. It's a magnetic force still. So that's still measured in. Let's think. What kind of units do we have for force again? Newtons. Magnetic field strength, we know that now. It's Teslas. Current in the wire. What's that? That's measured in amperes. L, length of a wire. What do you think length is measured in? Meters. And finally, theta is the angle between B and I. So that would be measured in degrees. And again, remember that if they're perpendicular, that sine of 90 degrees is 1. So that way they sort of work out. That's not so bad, is it? What I think is really neat, then you can start solving some questions. This is like what the IB loves to have questions about ratios. Things where you have something that changes by a certain factor. And the sooner you get used to those and see them as something to smile about, the better off you'll be. Because they show up a lot in paper 1 especially. I know that, for example, if you do astrophysics option, these kind of ratio things show up all the time there. Not all the time, but lots. So let's see. We have a wire that has a current I running through it, which is in a magnetic field B that is perpendicular to the current. What does the word, let's just break it down here. What does the word perpendicular mean? Hope you know that theta equals 90. That's going to be the key here. So it feels a force F. So right away, before starting anything else, I usually then just like to write an equation for F. So F equals, now we have a wire with current running through it. So can you see we would use this equation for a wire, which is BIL sine theta. One of my students was like, oh yeah, that's Bill. And this one you just call it QUV. Because that doesn't really work very nicely, but that's Bill. So we have F equals Bill sine theta, of course. The vector symbols. But we know that theta is 90. And remember we learned that if theta is 90 degrees, what do we get? We have sine 90 equals 1. Therefore, we could state that F equals, it's nice and easy, it's just Bill without any sine theta. That's kind of nice. So F equals Bill. Maybe I'll just take away the vectors just to keep it nice and easy. So F equals BIL. This is what we're going to use. Now we have a new force. What do I mean by new force? I'm going to write it maybe with different letters here. New force, maybe we'll call it F2, just like it's another force. So I'll write it down. So F2. That also goes Bill, except the current is I over 8. So instead of I, I'm going to say I over 8. Has the same length, I guess, so I'll put an L. And instead of B, what do I put in? Let's say magnetic field strength is 16B. So watch, I just put in 16B. That's not so hard, is it? You see down on F2, I could just simplify this at least. What's 16 divided by 8? Hope you see it's 2BIL. And here's a trick now. If you want a new force, a good way to do it is to do this. Do a ratio. This is the key here. You can use this sort of tool a lot in IB physics, SL or HL. This is very, very common. This is really, really common. And the good news, they're really easy. What I like to do is just say, fine. I don't say fine, but what I say is, I'll do F2 divided by F1. And you can literally divide in a whole equation. So I can say F2, which is equal to 2BIL, divided by F1, and F1 equals BIL. The reason I do this is I want F2 as a function of F1. Oops, and I actually don't need to call it F1. I can just call it F. That's what we named it. So can you see that it's really, really obvious on what cancels out? These BILs right here, they cancel out. So can you see I end up with F2 over F equals 2? Therefore, can you get F2 by itself then? And you move the F up to the top here. So you have F2 is 2F. So what does that mean? That means that making the magnetic field change by 16 times stronger, but at the same time making the current 8 times weaker, will end up still giving you twice the magnetic force. So this is sort of how you can use this. And this kind of stuff is very, very useful. I mean, in everyday life, you've got particles flying around. So if the particle is entering a magnetic field, then that particle will curve because it'll feel a force. So it'll actually deviate because of it. And that's used to explain things like mass spectrometers, because then you have unknown particles, like you don't know what kind they are. But it turns out if you know their velocity, which you call the velocity selector, you pass into a magnetic field, they're going to curve. And the radius of the curvature is going to be dependent on the mass. That's why like in CSI and these kind of shows like that, when they play cool music, whatever, what they're really doing, they're putting it into a machine, this material they don't know, and it tells them the mass. That's why it's called a mass spectrometer, because you're breaking up the mass in almost like a spectrum of masses. And just like with QVB sine theta, I like this Bill sine theta, for example. People who fly anti-submarine missions, so people who are in the military, they're looking for submarines. Turns out if you have, for example, at the back of one of these planes, they have something called a MAD boom. It's called a magnetic anomaly detector. At the back of the plane, it's got this big thing. What it's doing is it's measuring force and current and length. Because it turns out if you know the length and you know the current you're running through it, you can measure the force, or you can do the opposite, right? But it turns out as you pass over then a disturbance in the Earth's magnetic field, like, oh, I don't know, a big ass piece of metal in the water, turns out that's going to cause a disturbance in the Earth's magnetic field. So which means if you were actually flying in your airplane, let's just say, this is actually really cool here. So you're flying in your airplane, here's the water here, and here's your airplane. I'm really a bad artist, as you can see, but your airplane has this big, big thing called a MAD boom here, this big thing sticking out of the back of it. This thing is going to detect, then, a disturbance in the Earth's magnetic field, and that's how they can know that there is a submarine that's actually hanging out under the water here. So that's how they can say, aha, So I know that, then they can say, okay, I have a mad contact, and to turn around and start looking for them. So there's a lot of practical aspects, both good and for bad, because humans do terrible things as well to each other, like submarines, which have nuclear weapons in them. So we have to have airplanes that can find those submarines in case, I don't know, someone goes crazy and wants to launch all these things. So there's some sort of scary things there, but the science is just science, right? You can use it for good or for bad. Like I said, so for good, like in mass spectrometer, or maybe for bad things like, I don't know, finding submarines. Welcome to hand rules. Here we're going to be learning some tricks for determining the directions of magnetic fields and currents and forces. Now, like this, maybe that feeling you get when you finally understand electromagnetism. Like, yes! So let's see if I can get you to think that. And I hope you'll pardon the dumb pun here, but electric and magnetic fields, they go hand in hand. Get it? Because actually when you have one, you have the other. They're related. In the past, we used to think they were separate fundamental forces, electricity and magnetism. And now, because they're so closely related, we call them electromagnetism for a reason. So this is why. So there's 3 different hand rules I'm going to show you. 2 of them I'm going to show you ways you've probably seen before, but the last one I'm going to show you something that may change your world. I don't know, we'll see. I'm going to use Star Wars as an example. So first of all, let's do wire with a current. So what we do is we define, there's left hand rule, that's what LHR stands for, not London Heathrow as the airport, but left hand rule or right hand rule. And this is because it depends on if you're considering what we call a conventional current or electron flow current. And the IB has decided that we should have a current such that we should always use right-hand rule. So because of that, good news, we will ignore a left-hand rule current for this. So there will be no left-hand rule current for a wire with a current. And normally the way we do this, we normally use our thumb like this. So it's going to be a little bit hard for me to show you, but watch me. So you can see we actually use our thumb like this. So here, can you see like the way my hand is like this? So this is how I'm going to attempt to draw this exact thing. You're going to see I am not an artist, and no one has ever claimed that or accused me of, that I should be an artist. That's because I'm a really, well, you'll see it. So hopefully you'll see that this is that's supposed to be a hand. I don't know what happened to that thumb, but I'm trying to draw a hand with fingernails. I'm trying to draw, you can see the fingernails on my hand. If I'm drawing it like this, you can see them. So this is what I'm trying to draw here. So now what I'm going to say then is this. I'm going to say, all right, then the fingers, so the thumb, I'm going to say, thumb is going to be the current. That's the thing. So my thumb is the direction of the current. And my fingers, they're going to curl. You notice, your fingers, if you look at them, they curl in a certain direction. So because of that, I'm going to say it, maybe I'll do it in green, maybe. I'll say, I'm trying to loop it like this. Can you see the fingers that sort of curl around like that? I'll say fingers. Those are going to be in the direction of the magnetic field. And what is a magnetic field? We call that B, right? That's in Tesla. And current, let's do it with a proper notation here. So we'll do current I, which is measured in amperes. Ampere. There we go, that's how we use it. So it sounds really easy, right? And I think it kind of is. So let's see if we can do an example. So here you have a wire with a current directed out of the page. Now here's the problem with these hand rules. You're trying to draw something in 3 dimension, and yet you have a 2-dimensional sort of plane, right? Like your screen or your piece of paper. So you have to imagine that we have directions like up, we have left, right, and we have down, but we also have out of the page, like stabbing you in the face, and we have into the page. So that's sort of how it works. So you have to sort of try to consider this. So if it's out of the page, into the page, or up, down, left, right. So the way that we normally draw by convention, things being out of the page, this is supposed to be in 3 dimensions. It's supposed to be stabbing you in the face here. Can you see this thing? We normally draw it with a dot. That's because if you imagine like an arrow being fired at your face, like what part would sort of stab you? It would be the point of the arrow, wouldn't it? So we draw that. If something was going away from you, we would draw with a cross, even though I know that arrows are usually not, the fletching on the arrow is usually not a cross. It's usually like a triangle, isn't it? But it doesn't matter, right? So just imagine that's the part you'd see going away from you. So that's the notation we use. So in this case, we have a wire. The current is directed out of the page, which means it's coming right out of the page, right into your face. So what you should do then is draw the magnetic field lines around the wire. So this is going to be hard. So I want you to take your hand, your right hand, and you're going to, like this right here, and you're going to put your thumb out of the page. So in this case, can you see, like for me, for example, if the page for me is the screen, you can't see it, but the screen, which means to me, I'm going to have my thumb pointed towards my face, like, like that. Can you see which way your fingers then curl? Can you see that they curl? In my case, that would be counterclockwise. So in this case, just be really, really careful whether you try it yourself. Okay, so put your fingers, so have your thumb right now on the screen right here, have your thumb sticking out of the page right into your face, and hopefully you'll see that your fingers curl in this direction. Do you see how your fingers sort of curl in that direction? And this is how you can actually draw then the magnetic field lines. So this right here, this would be magnetic field lines. They would go like this. Let's try another example. You have a wire with current. This time the current is directed into the page. Do you see that's why I drew this X here? In which direction will a compass point at A, I mean. So let's, again, use our right hand rule. So here we go. I take my trusty right hand. I'm going to this time, I'm going to put my thumb into the page. Can you do that? So take your thumb, point it into the page right now, because that's what this arrow shows you, into the page. Do you notice which way your fingers curl? If I do like this here, my fingers curl that way. So to me, that's counterclockwise, clockwise. So see if that works for you. You should have something like this. They should be curling that direction. So I can draw different field lines like this. So here, right, this is B. So be very careful. Watch this. How do I figure out what happens at A? Look at this. What if I draw a field line that just passes through A? Which way is it pointing? Can you see which way it's pointing? The magnetic field lines through A. Can you see they're going to the left? If that's the case, then I can state without any doubt then that that is the way a compass would point. Because don't we draw the magnetic field lines, don't we define them as the direction that a compass would point? That's why we do this. It's awesome. So that's how we can figure this out. Had the compass been over here, let's say at this point right here, the compass would point up. Can you see that's the way these are going? Had I put it right here, the compass would point down. Over at the top here, the compass would point to the right. So it all depends on which different directions, but that will be the case here. That's hand rule number 1. So we draw like this. Thumb is the current, fingers are the magnetic field. Now, let's do rule number 2, which is with a solenoid. Solenoid is just a coil of wire. So, like we're going to do an example, like look at the next thing. So we're going to have a thing right here, like how do magnets work, aliens. We're going to have a solenoid, so some sort of piece of metal with some wire coiled around it. So in this case right here, it's a coil of wire. And again, we don't have a left-hand rule. We're just going to have a right-hand rule. That's the good news. Now I'm going to attempt to draw my thumb like this, sorry, my finger like this, or my hand, I mean like this. So can you see, I see my thumb, but I don't see my fingernails. Like to you at least, you can't see my fingernails. So I'm going to attempt to draw that right here. I don't know if I can. Well, let's just see if I can here. So I'm going to attempt to draw this. So it'll go like that. And I guess 2, 3, 4, something like that. Or I can see my nail here. Well, that's a big thumb I have, but there you go. You get the idea. Here, however, it goes opposite to what the other one did. So where the other example, we had the thumb being the current, the fingers are the magnetic field. This time they get reversed. This time the fingers are the current. So I'm going to draw them sort of curling. Can you see my fingers? You know, they sort of curl around. Look at my fingers. They're curling around that way. So your fingers are going to curl around. And those are the current. Which is I, which is in amperes. So it doesn't help you to calculate the value of the current, but it helps you to calculate the direction. Or not calculate, but to figure out, to determine. And your thumb, that is the direction of the magnetic field lines. In other words, it's also the direction that a compass would point, because doesn't that make sense? Like this would become the north. Because if I put a north here, wouldn't a compass want to point away from a north? So that's why it also is where the north is pointed. In this case, you could say that would be north. Let's see if this is going to help us with our example. So now we have an example that says, which way is north on the electromagnet? Again, the direction of the current isn't important, whether it's electron flow or conventional current. In the IB, it's not supposed to matter unless you're looking at diodes. But other than that, you can kind of reverse. I know I'm being really sloppy with the directions, and it's okay. You could draw it one way or the other way. The point is, let's just assume the current goes this way. It goes this way around this. Can you see? So the current goes up, then down, and then behind this thing, and then around, and then behind it, then around. So in this case right here, that's the solenoid rule. So use your trusty right hand. It's a solenoid, so you know you have to do it. And I want you to curl your fingers. For you, it'll look kind of like this right here, I guess, right? Like this. So curl your fingers going out and behind that object. Okay, so I'm going to do that with me. So I'm going to take my hand, I'm going to curl my fingers behind this. Can you see that if I do that, I end up with, can you see my hand ends up actually pointing like this right here? That's the only way I can do it. So my fingers are curling behind, just like the current goes front and back like this. If I had reversed my hand, in other words, if the hand was a mirror image, it wouldn't work, because then the current would be coming from behind and out. You can see the way it's drawn here, this current going this way, means it must go behind it and then forward and behind it and behind it. So that's why I know it for sure has to be oriented this way. So my fingers are the current. So which way is my thumb pointing? To the left. So that's how I know that's a north. That's going to be a south. Therefore, not so bad, is it? So the final video, I'm going to show you the third hand rule, and this is maybe going to be the most interesting one for you. Now it's time for the last video for hand rules. I'm going to show you the third hand rule, which I think is going to hopefully be something new for you, or maybe you've seen it this way. But the third hand rule, this is when you're supposed to be using, it's for a moving charge or wire in a magnetic field. Most people have learned it like this. This is how I learned it, like this. We're taught like FBI and this kind of things, but I never quite liked this. And I'm such a nerd. I love, and I mean that in a nice way. I really like being a nerd. Isn't it the time of the nerd? Nerds sort of rule the world now, so I'm really glad for that. So this is true story, actually. When I started dating Inge, who is now my wife, when we first started dating, I mean, she knew that I was a big old nerd, so we sort of had this rule that, you know, we each had to teach each other things from our own lives or from our own sort of backgrounds and interests. And so I had her watch Star Wars, the original 3 movies. So if you remember, these are the ones that came out in the 70s and 80s. So the last of those movies is called Return of the Jedi. And in that movie, so she and I were watching this, and this is a true story. Imagine I'm trying to impress this Danish girl. We're just sitting and watching this movie, and I remember I was teaching these classes during the days, and then, you know, I see Inge at night, so we're watching this movie. We're sitting down on the couch, we're watching it, and sure enough, we see this scene near the end of the movie. Can you see this right here? This is this sort of mean emperor here, and he's shooting out sort of lightning bolts from his hands. And I remember this is so ridiculous. I actually stopped. I was like, hold on. I pressed pause. I went and wrote some things down. And Inge was like, what are you doing? I was like, I've just changed how I teach physics. And what I'm going to do is I'm going to show you this trick. So I'm going to use Star Wars to help explain the hand rules, because I don't like this way at all. So I'm going to show you a different way. This way it's sort of inspired, literally, by the emperor here. So this sort of evil emperor, and he's mean and he's ugly, because ugly people are often the bad guys. At least in the old movies they were. Now it's, you know, ugly people can be also the nice people. And so it's really weird how they used to, you know, make movies and how they do it now and how things change. But let's just take a look at this right here. So this evil emperor, he was sort of shooting out lightning beams from his hands, right? So that's why I'm going to hopefully blow your minds here. So this one, there is a left-hand rule and there's a right-hand rule. And that's because you could have a charge that's moving in a magnetic field. So imagine it's a little charge, it's zipping along. Or it could be current. So it could be a wire. In other words, here I'm going to say current. So if you have current that's in a magnetic field, then that's also going to be the case. So there will be a left-hand rule and a right-hand rule. Now this is going to be really silly here. So I'm going to say left-hand rule, that's for negative charges. So that's the only thing that we use for left-hand rule. Everything else we're going to use the right-hand rule for. So this will be for positive things, and I'm going to say or current. So if you have a current going on, you do this. At least in the IB, you use your right-hand rule for this. Okay? So that's because you're using the conventional current, so it's the direction of positive, so that's why. So either positive particles, or if you have current in a wire, it's going to be the current. Okay, so positive particles or current. Here it's negative particles, and that's it for left-hand rule. This is really lame. Now, keep in mind, this is how I remember them, is I use my left hand, because I call them, this is so dumb, I'm so embarrassed, I nickname electrons. See, instead of electrons, I call them electrons. That reminds me to use my left hand. That's so dumb, I know. Because I think the image is reversed when you see me. So this is my left hand. I'm holding up my left hand, but I think you'll see it that way. So anyway, my own left hand, that's how I would do it. So the way I learn this is, the way I like to use these hand rules is, hold your hand like this. This is how we're going to do the hand rules, like this. Okay? And hopefully that's going to make some sense. So let's see actually how you do it. So first of all, I'm going to attempt to draw a left hand just like this. So I'm going to try to draw my hand like this. I'm going to try to draw a right hand like this. Okay, so watch carefully my amazing, awesome artistic powers here. You're not going to be impressed at all, but basically there's my hand. I'm trying to draw fingernails here. No, the pinky shouldn't be the longest finger, but oh well, that's my hand there. And then this one here is this one here, same thing. Okay, so you can probably draw it better than I can, so there we go. So I'm still drawing a thumb, and I can see all the fingernails. Can you draw it better than me? I hope so. But basically draw this, or sort of draw it looking like this for you. Okay, so draw so you can see the fingernails and the thumbs. If you've done this, then here's how we're going to define things. So this is going to be really awesome here. This is how I do it. From now on, this is how I draw things. So I have totally abandoned this stupid trick like this. I don't like it. Now I just think of Star Wars. And the reason is I'm inspired by that evil emperor. He's shooting out lightning beams from his fingernails, right? Or his fingertips. So I'm going to draw these right here are going to be magnetic field lines. So the fingers are going to be magnetic field. See, just like him sort of shooting out these lightning bolts, I imagine him shooting out these arrows. See? That's a little bit lame, I know, but there you go. Next, we have to have something with a force. Don't they use the word force a lot in Star Wars? Especially in the original movies. They're always like, use the force, Luke. So that's why there's a force involved here too. So the way I think of it is this. If I want to push you away from me, wouldn't I sort of force you away from me with my palm? So I think about the palm is the force. So I force you away from me by using the palm. Now, how do I draw the palm here? The palm is actually sort of into the page. So what I'm going to do here, I hope it's okay with you. I'm going to draw maybe in red. I'll draw it with an X, because X means, you know, sort of into the page. So here I'll draw X like this, and I'm going to say palm, because it's not so obvious. Say palm is the force. Same thing here. Palm. Oops, I shouldn't put it here. I should put it on this side. Oops. I should put it here. I should say palm is the force. So again, you can force something away from you by using the palm and forcing it away. Then finally, I'm going to have my direction here. So in this case right here, that's my thumb. My thumb is the direction of the velocity of these particles, so either that way or that way. Or in the case of a current, it's the current. So if you have, remember I said in positive particles, then it'll be the velocity of that particle. Or if it's a current, it'll be the direction of the current, only for your right hand. For your left hand, it'll just be the direction of the negative particle, like in a leftron. So I hope this makes sense. You're just going to use these hand rules right here like this. Just use your hands, and let's see if we can apply them to some situations here. So now I've got some examples for you, okay? You ready? Here we go. First, we have an electron, and it moves to the right in a magnetic field that's directed into the page. Draw the electron's path. So you can see I have my little negative particle here, and it's moving to the right. I have my magnetic field lines, which are X's because they go into the page. So think very carefully. Do you use left or right hand rule? I hope you remember because of my dumb little trick. It's a leftron. So this is my left hand here. So use your left hand. Okay, so get out your left hand. And what I want you to do is place your fingers into the page. So if this right here was the page behind me, for example, you would use your left hand and you would place your fingers into the page. Now, where do you place your thumb? Your thumb goes in the direction of the velocity. So in this case, my thumb has to be to the right. Does that make sense now? So now, for you, it would be like this. Fingers into the page and thumb to the right. Which way does your palm point? Can you see your palm has to point downwards? So because of that, do it on this page here, on this image now, okay? So do it right here. So you should point your fingers, left hand, fingers into the page, your thumb to the right, and hopefully you'll see that means your palm has to point downwards. So because of that, your path of your particle, in this case your electron, is going to curve downwards. It's going to actually curve in a circle. This is actually the process when you have this mass spectrometer I talked about in another video. This is exactly what's going on. You have an unknown particle, in this case it's negative, and it's got a magnetic field there, then you just know it's going to curve. And the radius of curvature, it turns out, will tell you the mass of the particle, in case you didn't know what it was. But in this case, this electron will curve downwards. It'll make a little circle. Cool, huh? Now let's look at this. Now we have another situation. A proton this time, which is positive. It moves to the right in a magnetic field, and the magnetic field lines are directed upwards this time. Draw the path of the proton. Think very carefully. Do you need left or right hand rule? because I'll be like this. You should use your right hand, shouldn't you? So use your right hand. So get out your trusty right hand. Here's mine. And now I want you to place your fingers are going to be upwards. So can you see actually for me, the fingers are going to be upwards. And my palm should be to the right because that's the direction of my proton. So like this. What is your, not palms, or my thumb. So fingers upwards, thumb to the right. That's the velocity. And can you see my palm is pointing out of the page? Try that here on this diagram right here. So now watch the screen. So this one right here, watch my drawing here, my pencil. So can you see this here is my positive particle here. It moves to the right. You place your right hand so that your fingers are pointing upwards, so that your thumb is pointing to the right. And can you see your palm points out of the page? The problem is, how do I draw that? I can't. I'll just say curves out of the page. That's all I can say. It's going to curve out of the page. So because I said it curves out of the page, I can't really draw that, can I? Imagine this. I mean, if you look at it like this, it's going to go like this. It's going to curve out of the page like that. I mean, that's why you can't really draw it, but you can describe it. You can say it's going to curve out of the page. It's going to lift up out of the page and curve around. So that's an example of how you can describe it without actually drawing it. And finally, I have another example here for you. A neutron, let me just see. I think that was the last example. Yeah. So a neutron this time, it moves to the right in a magnetic field. This time the magnetic field lines are down. Draw the path of the neutron. So try that yourself right now. And I'm waiting. And you might wonder, which hand rule do I use? Do I use the left or the right hand rule? And I hope you'll see it's a neutron. Think of it carefully. This is a trick question. Does a neutron have a negative charge, so I'd use my left hand rule? No. Does a neutron have a positive charge, so I use my right hand rule? No. What does a neutron have? No charge. So I don't use a hand rule. It's a trick question. This neutron is going to move through undeflected. It's just going to pass like this. Undeflected. That's because it has no charge. So that's how you can deal with it. That was a sneaky trick question, wasn't it? So do you see how you can deal with a lot of these things? And if you have currents going through, then your thumb is going to be the current. You could figure out the force acting on things in magnetic fields just by using these hand rules from Star Wars. Your fingers are the magnetic field lines, your thumb is the velocity or the current, and then your palm is the force. So just think, use the force, just use that. Is that awesome? I'm going to start by explaining to you about angular speed. But in order to know angular speed, I think it's important to look at the contrast, which is linear speed. And with a lot of students, I think with angular speed especially, it seems a little bit wacky. So it reminds me a little bit of like, have you ever seen the movie The Matrix? It's an older movie about Neo. He's like, how does this even work? He had to bend the spoon with his mind. It's related to reality. So let's see if we can do this. In order to understand angular speed, I think it's important to understand linear speed. Now, you know how linear speed works, I hope. We could normally say that speed, we could say maybe a linear speed like this. Isn't it just distance over time? Isn't that normally what it is? So think about this now. What if you're going around in a circle? So you're traveling around in a circle, a radius r, and we're talking about linear speed, so like at this key point here. Or maybe it's, here. Maybe it could be that point right there. Whoops, it'll be exactly left, not this way. I drew it really poorly, actually. There we go. Should be exactly to the left. Or it could be here. I hope you get the idea here, right? So this is linear speed, could be wherever. So this actual value, you have to think about a speed. Speed is a distance over time, true. How do you do this distance if you go all the way around a circle? Do you remember that? To find the distance all the way around a circle, it's called a circumference. Do you remember how it goes? It's 2 pi r. That's the circumference of a circle. And so, I hope it's okay with you, then we're going to define the linear speed as this. The linear speed is going to be the distance traveled, which is 2 pi r, that's the distance to go around one whole circle, divided by the time it takes to go around a whole circle, which we call t. This is normally what we do. So we would say this right here, this is your linear speed, and we'll define that in meters per second. We're going to say this here is your radius of the circle, that's r, which is measured in meters, and t is going to be the period. That's going to be the time it takes to go all the way around one circle. So we'll call that the period t in seconds. So this is how we can deal with it. It's the linear speed. Now in a similar way, let's do the angular speed now. This time you're again going around in a circle of radius r. This time we're going to define the angle is going to be the important thing. So this distance is going to kind of be like this. So imagine this, and usually with this we would make it a circle of radius r equals 1. So that's just why it becomes, if you look, it looks an awful lot like 2 pi r over t, doesn't it? Except what if you made your radius 1? What if you made a unit circle? Do you see that it looks like it's just 2 pi r over t, where r is just 1? So this is why you can get this one here. So this is going to be a weird thing because we're going to define this thing. It looks like a W, but it's not. It's actually omega. Omega is the angular speed. So I'm going to write it down in units now. This angle is not going to be in degrees. It's going to be in radians. You might have seen that in math class. Maybe not, but it's in radians. So it's going to be a speed. So that means it's got to be radians per second. Right, so that's actually, we're going to say rad. We often say radians times, seconds to the -1, because that's how we say radians per second. T is the period, that's the time it takes to go all the way around, so we just have that, that's in seconds. And we're going to define a frequency. I'm going to show you that. That's in hertz, or we could say it's in 1 over seconds. So how does this relate? First of all, this equation doesn't really show up in in this topic, but it does show up in a different topic, so that's just why I've put it there. So this is the omega here. This is the angular speed, and again, it's in radians per second. Now you might want to know how to convert that to frequencies. So do you remember we have an equation for, I'll put it like this here. So do you remember we have an equation, maybe I'll do it light blue, there we go, for frequency. Frequency is 1 over the period. So watch very carefully. If I had omega, which is 2 pi, and over t, are you okay with me just writing it like this? 2 pi times 1 over t, that's the same thing as this. The reason I'm doing that is because that'll be more apparent. 1 over t can be replaced with f. So you see I can say frequency is 2 pi f. So this might be useful for you as well. So in case you need it, you're not given this on the exams, but I think you could still use it. Right? So it's either 2 pi over t or it's 2 pi f. So this is how we define the angular speed. Sounds complicated, but it's not actually nearly as bad as you think. Then finally, we have a relation between the linear and the angular speeds. Okay, so we can define this linear speed, which remember the linear speed is in meters per second. Angular speed is in radians per second. And we have the radius, which is obviously in meters. So we can actually relate the two. And this is in your data book. That's why I'm putting green with a big square around it. This is given. So this is how you can compare between linear speed and angular speed. It all depends on the radius. So that's how you can do it. And surprisingly, that's all you need to do. It's actually not so hard at all. I hope you'll see that at least, that it's not nearly as bad as you might think. This stuff may look really weird, but I promise you it's okay. You can actually do this. So this will be doable. We can use these in other videos right here, but really you don't need actually that much with these. You just need to know these definitions. And they can ask you something really, really simple, like, I don't know, this thing goes around, what is its angular speed if they give you the frequency. That's the only way to be a little bit sneakier. I'm going to speak to you now about centripetal acceleration and force. What it means to be centripetal is center seeking. So we're going to talk about this. I like this EO one here, the circular motion problem in physics. It really threw me for a loop. So we're going to talk about this, what it means to go in a circle and what it does. So I want you to remember though that acceleration, the very base definition of acceleration. We actually write it like this, right? We could say that acceleration, let's just get a pen here. We could say the acceleration, which is a vector, is going to be given by the change in velocity over time. This is how it is. Now keep in mind, look at this very, very carefully here. This is fundamental. Because remember, acceleration is a vector. And something that's a vector has a direction and a magnitude. So we're here saying you have to change your velocity in some way. Now, we're used to changing the magnitude. In other words, we're used to seeing questions like from mechanics, where you've got a speed actually changing, so you go from 100 kilometers an hour to 5 kilometers an hour. That's like the length of that vector has changed. But it turns out So of course, so yes, if that changes, you do accelerate. But we can also say that if you change the direction of the velocity, you also accelerate. And this is the case with going in a circle. So that's why I'm saying here we change the direction here. So for example, if you look at this, the change in direction, that's a constituted change in velocity, so there is acceleration. And a lot of you have trouble sort of understanding that. So I want to try to give you this sort of way to visualize it. Imagine you had a ball, like a sphere, and it's on the ground, it's on a nice level surface, and you just push the ball in a line. And do you see it's going to go in a straight line, as long as it's not a really wobbly one, or as long as it's all nice and even and spherical? It should go in a nice straight line. Think about this. If you're only allowed to give it short little pushes, you can sort of apply a little impulse, we would say, right? That makes it change its momentum. So let's say you just apply a little push, a little force. So you kind of boom, you just sort of hit it lightly. If you wanted that ball to go in a circle, how would you do it? Imagine this. This ball is going straight up, let's say. You could give it a little tap that way to left, and then maybe another tap that way, and then another tap that way, another tap. Can you see each way you tap it? Imagine which way you have to hit it. Think about which way you'd have to hit it. You'd have to hit it, this way. Then it would be going that way, and then you have to hit it that way and that way. Look at which way your force is. Isn't your force always acting towards the center? That's why we call it centripetal. Centri means center seeking. That's what this means. This is center. All right, the American style with the ER like this, center seeking. That's what centripetal means. This is because as you go around in a circle, there's technically a center force. And if there's a center sort of directed force, do you see there's also a center acceleration? Or maybe that's better to put the acceleration. So you're going to have an acceleration inwards. It doesn't seem like it, but you're actually going to have a center pointing acceleration here. Okay, and that's because, again, you've changed your velocity. So even though your value of your speed stayed the same, so imagine you have just, v here. So the actual length of that vector stayed the same at all points in this thing that here's motion. That's assuming you're going to the right, like this, counterclockwise. You could say that, well, the value of the speed doesn't change. Maybe you're going 8 meters per second all the time. But your direction is changing. Because of that, you have an acceleration. And the good news is, excuse me, you don't have to memorize this. You have an equation for the centripetal, see the center seeking, acceleration. It goes like this, A equals V squared over R. So again, don't have to memorize it. There it is. What does this do for you? I like to label it with a little C. C for centripetal. It's technically a vector, but we'll leave it like that. So acceleration is in meters per second squared. Linear speed, I hope you see, is in meters per second. And radius is in meters. So hopefully you'll see that if you do linear speed, which is meters per second, you square it, you get meters squared per second squared. And then you have meters on the bottom, so then this becomes meters per second squared. So the units work out. Let's look at centripetal force. To do the force, you just use Newton's second law on the acceleration. And remember, the acceleration was acceleration was v squared over r. Well, isn't Newton's second law, one of the formulations, of course it's with a change in momentum. You could say that F is it's related to a change in momentum. But in this case, let's use the other form, probably the more common one, which is F equals ma. That means all you have to do to get the force, you just multiply the acceleration times the mass. So in this case right here, then, does that make sense then? I would say then, fine, F equals ma. So that means I would multiply mass times acceleration, which would be mass times v squared over r. So that's why I end up with, very, very simply, F equals mv squared over r. So you just take your acceleration that you had before, v squared over r, and you just multiply it by an m. That's not that brain busting, right? I hope not. So there we go. There's our equation. And again, just to make sure we know, centripetal force. This is the force acting towards the center. It's measured in newtons, mass is in kilograms, speed is in meters per second, and the radius is in meters. Just so we have all the right units. And what I like is this. You can see this. Because from before we have v equals omega r. In other words, we have the angular speed is related to the linear speed. Here we've been talking about linear speed, right, in meters per second. So because of that, look, we can replace. We can say F equals M. Instead of V squared, we put in omega R squared. Do you see that? This is V, according to this. So because of that, I have M and then V squared. So that's omega R. So therefore, I have F equals, let's see, leads to F equals M. And look at this. I have omega squared R squared over R. And if I have R squared divided by R, that one cancels out that one. So I'm left with just F equals M omega squared R. Hey, look. And remember that omega is your angular speed, which is in radians per second. So do you see, actually, it's not that bad? Now I have an example for you. Maybe that's a good one to have. So we're looking at here, we have a radius. And we have the radius of the Earth. So it's 6.4 times 10 to the 6 meters. Okay, so that's important. So maybe I'll just write it down. So R equals this. I just didn't really like the notation of the font I'm using, so this is more clear, right? Maybe not. Actually, my 6 looks terrible. There we go. I'll make it better. 6 meters. What's a centripetal acceleration? Do the spinning Earth experienced. Oops, I should have really made it experienced, shouldn't I? I'll just fix that right now. Hold on a second here. I just don't want to be too many spelling mistakes, at least. There we go. So what I want to do here I need to sort of figure out, kind of what to do. So if I have the centripetal acceleration, I can actually figure this out. I can find the acceleration itself. We have an equation for it, don't we? We have the equation right here. Acceleration is v squared over r. So we're going to put that in. So we're going to have, so fine. We have the acceleration then. I'll use this equation here. Acceleration is just v squared over r. Now I know r, which is really good, but I don't know v, do I? But it turns out I kind of do. You can kind of figure it out because you can say that v is a distance over time. Remember, v is your linear speed. So because of that, v is your distance over time. But dist over time. And remember, if you go all the way around in a circle, what's your distance traveled? It's a circumference of a circle, which is 2 times pi times r. All that divided by, usually we say t for the period of orbit. So in this case, then it becomes v squared, which is 2 pi r over t. That's v, and then square that divided by r. So it may not look that nice, so we can figure it out again. So a equals, let's see, 2 squared is 4 times pi squared times r squared over t squared. I divide that whole thing by r. Now some people like to write this. I can write it as a fraction. So just so you can see, that means when you divide by a fraction, what do? You multiply by the reciprocal. I'm just trying to make it more obvious to see what happens. Some people really struggle with this and putting the r on the bottom. So that's just why it becomes like a 1 over r. So you can see this r cancels out that one. So I'm left with acceleration is just equal to 4 pi squared r over t squared. Now this equation, this 4 pi squared r over t squared, turns out we've sort of re-derived an equation that's actually in your formula booklet. So I mean, you didn't actually have to do all this work right here that I did. You could have just looked this up and said, oh, a is 4 pi squared r over t squared. Fine. Now remember, this is for someone who's sitting on Earth, who's basically rotating around the Earth like this, right? So what do we do now? Well, we need to know the period for someone on the Earth, right? We need to know how long does it take to go all the way around the Earth. And you might know that number, so maybe we'll do this in a different color here. So let's just figure this out here. So how long does it take to go all the way around the Earth? Do you know that value of t? I hope you do. It's 24 hours. But now we need this in seconds, so what do? We use a trick that I learned in chemistry. So I just want to get rid of the hours. So I'm going to put hours on the bottom. This way they're going to cancel out. But I need to think about what will this do for me? I need to know something per hour. In this case, I know there's 60 minutes in 1 hour. So now I know, that's why I put the minutes on top, because there's 60 minutes for 1 hour. And if I do 24 times 60, then I'm going to get my answer in minutes. But I don't want it in minutes, I want it in seconds. So you can use the same sort of trick here that, the minutes are here. You're going to have, minutes here. So the minutes will cancel out, and then you'll have seconds. So then in the end, you're going to end up with this right here, which is 24 times 3600, which is 86400. Technically, you should use a sidereal tape, but good enough. This here is in seconds. So this is my t. So what I'm going to do now is put all this stuff into the equation. So finally I have a equals 4 pi squared times the radius, which is 0.4 times 10 to the 6. All that divided by this number. Right, so it's 86,400 seconds. That thing has to be squared. And I'm going to get my answer. So let's see if we can figure it out. So I'm just going to do that. So 6.4 times 10 to the 6. All that times 4 times pi squared. I get that answer. I divide that by, in brackets, 86400 squared. I end up with an acceleration of 0.0338, something like that. So how many significant figures can I use? Can you see I use 2? So I'm going to say, therefore, that my A equals, I guess, you could say just 0.03, for example, meters per second squared. You can say that's your answer. So think about this. This is very little compared to what we feel on Earth, right? By gravity. So this is, yes, there's a slight acceleration inwards, but it's not very big, is it? We feel the acceleration due to gravity a lot more. But that's actually pretty interesting to figure out what happens. So this is how we can deal with a question that might seem really hard, but it turns out we can solve it by just doing a little bit of algebra and a little bit of magic. And like I said, you can actually save a lot of time if you're worried about this whole piece right here by just starting off right away with A equals 4 pi squared r over t squared. You just had to know the period, how long it takes to go around the Earth. I'd like to show you an example with that vertical circle, because those are ones that cause a lot of people problems. So here we have a mass m, and it's tied to a string. So can you imagine that? So there's an invisible string here. You're sort of moving it around here. And the string has it goes in a vertical circle of radius r with a constant speed v. So the question is, find the tension in the string at the lowest and the highest points of the circle. So I've sort of labeled them. So we've got highest point and lowest point here. So maybe let's do the lowest point. Maybe we'll start with that one. So we'll say lowest here. Whoops. Hold that there. Here we go. So let's see here. Lowest. What happens at the lowest point here? Well, maybe we could start by drawing the vectors. At the lowest point, what's going on? Well, we've got tension in the string. It's going upwards, right? So we call it T, 1, I guess, for, lowest point here. 1. But acting on it, of course, is the real mass, m, so it's got a downwards force of mg. That's its downwards gravitational force. Remember, because F equals ma? So tension is a force going upwards, and gravitation is downwards. Do you notice I've drawn the tension bigger than mg? There's a reason for that. So here we go. We can do this. Well, then from this, can you see we can actually figure out what's the net force? The net force on something, isn't it just the difference, or you do the vector summation of the forces. So F net, in this case here will be, let's say, T1 minus mg. If that's okay with you, we can just say that because they're subtracted. They're in opposite directions. But remember very carefully, though, if you do F net, remember F net, the net force right here, it's going to be a circle. There's going to be a circular force. So that F net, you're used to saying F net equals ma. In this case, it's not ma, it's mv squared over r. So that's why the F net is mv squared over r, and that's going to equal T1 minus mg. So from there, I don't know if that made any sense, I just set F net equal to the centripetal force. That's the net force. Then I just want to solve for T1. So I get T1 by itself. Let's see, I can move the mg over. So I have mv squared over r plus mg. And this is what I have here. This is, I think, as simple as I can make it. I can, of course, combine the m's if I wanted to, but I think this is good enough. So we'll say this is the tension 1, depending on the mass and the radius. Let's do it for the highest point now. So what happens at the highest? Well, at the highest, let's look at the vectors here, what's going on. If we look at this at the highest point, remember, this thing right here is going down. It's got mg still going down. See, that's still that same mg still acting downwards. Except the tension, if it makes sense, the tension is also acting downwards. Now, this tension can be different. It's going to really depend on the speed. Because do you see that? You could spin it faster and you have more tension. You could spin it slower until the tension becomes 0 and it's or even less than that, and then it actually doesn't make it over the circle. So this T2 can vary. But what I want you to see, though, is that this net force, we can still do a net force like this right here. So net force, in this case right here, won't it just be, it'll just be this T2 and this mg, and they're both going to be in the same direction. So we can just say it's T2, you know, they're both added. They're both in the same direction. So you could say it's T2 plus mg. I mean, you could have, I guess, said they're both negative, but we can just say that they're the same, they're in the same direction. So therefore we can say mv squared over r is equal to T2 plus mg. And by that, then we can say, fine, then T2 equals, let's see, it's going to be mv squared over r minus mg, because I'm going to move that one over. And this is going to be my final tension for T2. So now we got the tension at point 1, we got the tension at point 2 here, and there we go. So let's see what we can do with this. We want to calculate the minimum speed so that the string never goes slack. That may not sound so obvious. What's going on is that it all depends on the speed at which you sort of rotate this thing, right? If you rotate this thing really, really slowly, like I said, tension T2 can technically be 0. Do you see that? Like, it goes slack. It goes slack when tension 2 equals 0. Does that make sense? Or if it's less than 0, then it's slack. Well, this happens exactly here, right? So that means if the tension is less than that, then, you know, it's not even going to make it. If the tension is more than that value 0, then it's going to be a not slack string. So basically, we're going to try to set this right here. So we want, the key thing here is we want T2 to be greater than 0, if that makes any sense. We want that tension to be, you know, more than nothing. So can you see, all we have to do now is we take this equation for T2. You know, we go and borrow that equation again. So from up there, we had T2, which equaled mv squared over r minus mg. We just set that greater than 0. So to see how now I can just do a little bit of algebra with this right here, I can move maybe my mg to the other side just to make it a little bit simpler. So I just want to show you, you can still do algebra with inequality. Some people aren't comfortable with that, but that's fine. Do you see I add the mg to the other side? If I multiplied, I would have switched the sign of this inequality, but I didn't multiply by anything. I just added mg, so that's why the mg goes to the other side. Then it becomes more obvious the m's cancel out. And then I can get v squared is greater than r times g. Does that make sense? I can move the r, I can multiply both sides by r to get it up top. I guess technically then I could say that has to be greater than square root of rg, technically. So you could say something like that. So as long as your speed is bigger than the square root of the radius times g, then the string will never be slack. It didn't seem all that simple, this kind of question. That's why I think it was a really good idea to show you how to deal with a vertical circle. Because certainly the first couple of exams from the IB, they've certainly asked vertical circles, at least in May 2016, November 2016, they certainly have. So I think it's important to be able to deal with them. Welcome to gravity. So we're going to talk about gravitation and gravitational field strength. And I love this hover orcus. I don't think you understand the gravity of the situation. So we're going to talk about Newton's universal law of gravitation. It's assumed to apply everywhere in the universe. Turns out with dark energy stuff, we know that actually it's a little bit different. So we have now put it like an asterisk saying, always the case except on very large scales in the universe, because something seems to be acting opposite to this. But for right now, let's just talk about this. So it's universal law of gravitation. It's assumed that there's a force of attraction between two masses at a distance r apart. What that means is no matter what the mass of one object and another object, those two masses are attracted to each other gravitationally. And it's based on the actual value of the masses, also the distance, so that'll affect it. And it turns out every object with mass in the universe attracts every other object with mass in the universe. So you're attracted to like a galaxy far away. You're attracted to it technically. It's just that, yes, it's got a huge mass, but it's got a very long distance. So that's just why you will see how this works here. We can quantify it. This is what Newton figured out, a very, very clever man. Look at this, F equals G M over R squared. This is the equation we can use here. So this is the force of attraction. So this one right here, and we assume that gravity always attracts. So again, it depends on the different units here. So force of attraction, what do you think the force is measured in? I hope you know it's newtons. G is just a constant, you can look it up. It's 6.67 times 10 to the minus 11. Mass is measured in kilograms. r is the distance between the center of both masses. So it's the center of gravity. And a distance would be measured in meters. So this is it. That's how we use it. So g, you can look it up. And then you just multiply the masses. So you can see that the gravitational force between two objects depends on the masses themselves. So it depends directly on the masses. It's proportional, I mean. But it depends inversely proportional to the square of the distance. So it tells you that, you know, if your distance increased by 2, for example, 2 squared is 4. That means the force would go down by 4. It's one of those inverse square law, we call it. Now we have something more interesting called the gravitational field strength. I like this. It's a gravitational force per unit mass experienced by a point mass. What do we mean by that? There's a nice easy equation for it as well. It goes like this. G equals F over M. This is the equation you get in your data booklet here. And the reason I think it's so amazing is that, well, let's first of all look at this thing over here. There's this thing called the gravitational field strength. We have to be a little bit careful here. So let's look at this and put in units. Gravitational field strength, well, let's see. It's based on a force. Force is measured in newtons. And a mass, which is measured in kilograms. So if you ever don't know the units for this right here, think carefully. It's gravitational field strength. Let's see. It should be newtons per kilogram. So that will be the unit for it. You can also use, because we can also use this equation we just had before, you can say then, here I'll put it down like this, I'll put a different color. So then G equals, let's see, F was GMM over R squared. We divide that whole thing by M. That means we can divide by 1, which is the same thing as saying G equals GMM over R squared times 1 over M. Therefore the M's cancel out. And that's why you end up with G equals GM over R squared. Do you see this is the other equation we get? That's this one right here. So that's the important thing here. I will just put it in green maybe, just so we can see it's really, really important. And good news, you don't have to memorize this. They give you this too. So what this tells you is you can find out the gravitational field strength around any object of mass m as long as you know its distance or its radius r. Now the really interesting thing is this. G, do you notice it looks tantalizingly similar to the number we know on Earth, right? 9.81 meters per second squared. And it turns out that is the case. This G, this gravitational field strength, is the acceleration due to gravity on that planet, which is amazing. That means you can find the acceleration due to gravity on any mass m given a radius r. So as long as you know the mass m and the radius, you can find the acceleration due to gravity around any planet. So that means if you put an m for Earth and you put an r for Earth, you'll get something close to 9.81. I mean, this is theoretical. There's some actualities that are a little bit different. But isn't this pretty amazing? So this is how you can actually do it. And if you're not sure, you can look at the units really carefully. Remember what a force is? A force is, let's just look at the units of this thing right here. If you look at this right here, the units of G. Well, it's got units of force. And a force is a Newton, isn't it? Newton per kilogram. Let's just say. But don't forget a Newton. A Newton is F equals ma, isn't it? And if you remember F equals ma, that means we have a mass, which is also in kilograms, times acceleration, which is meters per second squared. And look carefully, then you've got these kind of units, right? Don't forget you had a divide by kilogram there as well. You still had, that's newtons, is kilogram meter per second squared. But we also had a kilogram hanging out there. That was from the definition. It had to be divided by mass. So we take our kilogram meter per second squared, that's a Newton, divide that by a kilogram, and what do we get? Kilograms cancel out. We have units of meters per second squared. Do you see it's units of acceleration? This is why it's awesome. Okay, so you can use this to calculate either the gravitational field strength if you're asked for that, or if they ask you what's the acceleration due to gravity, same. Let's look at some examples here. So we got this one. I love this, gravity, just a theory like this. So we got, what's the acceleration of free fall? Ooh, what does that mean? For a planet that has 10 times the Earth's mass and a radius 20 times that of Earth. So if we want the acceleration due to free fall, isn't that g? Now you might think, well, isn't it 9.81 question mark? No, not on Earth. Yes on Earth, not on this planet. So it's not that. So we use this other formulation for g. We say g is, again, F over m. which is gm over r squared. We can use that. We can start off with that directly. Now here's the interesting part. Then let's look at this thing for this planet here. So it's g times, and instead of mass, let's put a little subscript e, for mass of the Earth. We'll use those things when we need them. So for example, it has 10 times the mass of the Earth. So do you see I'm going to put 10 me, so it's going to be g times 10 times the mass of the Earth. Divide that by the radius. So I'll say 20 radius of the Earth squared. Do you see I've done gm over r squared? I've just had to put in the numbers that I know. I know 10 and 20. Look very, very careful at this. You can actually take this number out. You can say this is g times 10. Actually, maybe I'll put the 10 in front. So it's 10 gme. Do you see I've just put the 10 in front here? Now I have to think about what's 20 squared. Don't forget the 20 here also gets squared. So 20 squared, and that is all over re squared here, like this. So we can look at this, and what's 20 squared? Well, it's 2 times 2, because you have to do 20 times 20, right? So which is 2 times 2, which is 4, and then you put 2 zeros at the end of it. So it'll be like this. So if you look at this then, that means, let's see, I can do 10 over 400. I can knock out a 0 from both of them. So now I have 1 over 40 gme over re squared. And you might be thinking like, hey, I'm missing the information that I need, right? I'm missing what I need. But it turns out, no, you didn't have to be told Earth's mass and Earth's radius. Look carefully at this. Look. Do you see this gm over r squared? Isn't that g for Earth? Isn't that just gm over r squared for Earth? And we know that number is 9.81. So this is the key part. That means then you can say the gravitational field strength, in other words, the acceleration of free fall on that planet then is going to be 9.81 divided by 40. You see that? Because this is 1 over 40 times that number. In other words, it's 1/40th the gravitational or the acceleration on Earth. So let's just see what that is. That ends up being 0.24. Let's see, that's good enough. Actually, technically, I should round it to 5. So 0.25 meters per second squared. So that's really, really small acceleration, right? There you go. So that's how you can deal with that one. Let's maybe do another example quickly. We have a center of 2 planets. They're separated by a distance r. So we have a planet and a distance r here between them. The gravitational force between the 2 planets is F. Oh, great. So I have F equals gmm over r squared. What will be the force between the 2 planets if their separation increases to 4r? So what I want to show you is, again, I always do these ratio questions like this. I first find an equation for F in general, and then I'll call it F2. That's like my second force. It's going to be the same thing, gmm, except I make my distance 4r squared. And if you want to do it then technically, then you should technically do F2 over F. If you really want to be careful with these ratios. Then you can say, fine, it's gmm over 4r squared, which, by the way, 4 squared is 16, so 16r squared. All that divided by this F, which is gmm over r squared. I should use capitals everywhere. What happens when I divide a fraction by a fraction? I multiply by the reciprocal. So, whoops. So I'm going to say then it's just gmm over 16r squared times r squared over gmm. Look carefully what happens then. Lots of the things cancel out. The gmm's cancel out. The r's cancel out. And I end up with F2 is equal to, let's see, I can put the F over here, so I can say F over 16. This is going to be my final answer. Now, I've done it formally to show you all the painful details. This is how you can deal with any ratio question. And I say ratio because, whenever you see something changing by something, you can always do it in this way. However, if you get a little bit faster at it, you can just say, the separation increases to 4r, and look carefully. The only thing that changed was the r's. So then you can say that the proportionality constant is just 1 over r squared. You could basically, that the gm's are going to all cancel out. So that means then, let's see here, you've got this 4r, so that's why you could just say fine, and also the r's will cancel out too. So you'll end up with proportionality then, it'll just be 1 over 4 squared, which is 1 over 16. So can you see that's how you can kind of know that it'll be, you can say F2 will be equal to F over 16. This is another way to get it faster. If you're not sure though, just do it slowly, you'll get it to work. This is how we can deal with these kind of questions with gravitational field strength. I want to talk to you about orbital motion and a little bit about Kepler's law. Although Kepler's law is not technically needed for the IB, I've seen on exam questions where they actually ask you essentially to derive it just without really being told out. So I think it's slightly unfair, but we may as well show you something because it has shown up twice. So we have the orbital speed. Let's talk about this. If you've got an orbit, you've got a large mass and a smaller mass, and they're technically, I mean, a lot of people think it's the smaller one just goes around the large one like it stays still, but it's not technically the case. Anytime you have an orbit, they're both technically orbiting each other around a central common center of mass. So it's really going to depend on the masses themselves. So for example, you have a really massive thing like the sun compared to us, the earth. Of course, we go around the sun. Technically, the sun moves a little bit, just less than us. So that's something that most people don't necessarily think about. But it's not just the mass going around the larger mass, it's also the larger mass also moves a little bit. So that's a technicality there. But to have a constant orbit, we're going to assume there's no friction from your gases in space or whatever. So there's only going to be gravitational forces acting. Now, what's really important about this is that if we have a gravitational force, then we could say this. We could say then that we have a gravitational force like this, right? Fg. And remember the gravitational force equation is gmm over r squared. But because it's going in a circle, we also, we have a centripetal force. Remember that equation is mv squared over r. You can look these up. And the interesting thing is because there's no other forces, the centripetal force, is caused by the gravitation. That's like the invisible string that's pulling it along. So by that sense, you can say Fg equals Fc. This is often the first part to starting orbital mechanics questions, is set your gravitational force equal to the centripetal force. In other words, let's put it here. So gmm over r squared, that's the gravitational, equals mv squared over r. Good news, the m's cancel out. So now, and also I can move my r up here. Can you see that? Now, if you're not sure, I'll just do it. So r over r squared equals v squared. Can you see that this squared and this r right here cancel out? So now I'm left with v squared equals gm over r. And so that means I can get v by itself. It's technically plus or minus the square root of gm over r. But we'll just count the plus part. So that's where we get this equation from. So what this tells you, this v is the linear speed. It's the actual linear speed needed. So it's how fast you need to go to have an orbital radius r around some object of mass m. So that's actually the orbital speed equation. This is it. This is what you need to do. So it's kind of interesting because you can see what happens here that you can set the different radius and find out what speed you need to have and see how it goes. Now I think what would be really nice to do is Kepler's third law. Like I said, it's super useful for orbital mechanics. I want to read you these little comics here. This is from XKCD, both of them. If you don't know that guy, Random Monroe is his name. It's a great webpage. I can only recommend it. This guy is brilliant. So he actually used to work for NASA, and I love this. He said, how well I understood orbital mechanics. And he said, when I took high school physics, he learned a little bit. That's you, right? Then he got a physics degree. Oh, he understood more. Actual job at NASA. Then he started playing a game called Kerbal Space Program. I can only recommend it. It's awesome. It's such a good game. It's a game where you basically play around with these little Kerbals and they sort of get kills and do all these silly things. But basically you end up accidentally, without thinking about it, learning about orbital mechanics. And this next one here is going to be more important. Well, we can talk about this. Is one of Kepler's laws as well. He says, nice door. How do you keep the floor so clean? It's one of Randall Munro's first ones here. Says, oh, we hired this dude named Kepler. He's really good, hard worker, doesn't mind the monotony. He sweeps out the same area every night. Because if you know Kepler's law, you know that that's one of the things that's supposed to be that the area swept out is the same for a given time. In other words, let's say you're going in an orbit. Orbits are supposed to be ellipses with the sun at one of the focal points, it turns out. And it also turns out if you could time, like in a given amount of time, let's say in 1 day maybe in its orbit, it travels this far. You can calculate that area. And maybe when it's going further out, let's just say, maybe 1 day, maybe it only does this. In other words, 1 day maybe it only moves from here to here. whereas 1 day moves from here to here. It turns out you can calculate that area here and that area, and it turns out in the same amount of time, it'll always sweep out the same area. So the way it's formulated, we always say it's always swept out the same area. And that's why here, see, he doesn't mind. He sweeps out the same area every night. Oh, what a good joke. I like that one. So Kepler's third law, you don't formally need to know it, but I think it's nice to know it. Let's start off with this equation right here. Let's go back to this v squared equals gm over r. Let's look at that one. So we'll start with that. So v squared equals gm over r. This time, instead of v, let's use, we used this before. Let's use that v is the distance over time. But if you go in a circle, the distance you travel in a whole circle, remember, is the circumference of a circle. So in this case, it's 2 pi r, and we'd say time, we'll say is the period. You know, that'll be the time that we use. So instead of v squared, we're going to say 2 pi r over t. That's going to be v squared equals gm over r. If we do this really carefully, we take our time, we square everything, so we end up with a 4, because that's 2 squared, times pi squared times r squared over t squared. That equals gm over r. You see I can move my r over here. So I can say I have 4 pi squared r cubed. And I'm going to move my t squared over here at the same time, so I'm going to have gm t squared. And then I'm going to say, I'm going to get t squared by itself, so I'm going to drop the gm on the other side. So I'm going to say 4 pi squared r cubed over gm. I'm going to have t squared equals that. It turns out this is Kepler's third law. Well, kind of. See, Kepler didn't know the mathematics of it here. He was really, really clever. He figured out this. He said that the period squared of an orbit is proportional to its orbital radius cubed. He didn't quite know the proportionality constant, but that's why when Newton came along with his universal law of gravitation here, this gmm over r squared, then you're able to actually formulate it to figure this out. Because look carefully. You could say t squared equals, and this 4 pi squared over gm, this is the, let's say this is the proportionality constant. That's the number that's in front of it. All that is times, of course, this r cubed. So see, because if it's proportional, you normally you say it equals to some constant times r cubed, right? That constant that he didn't know. See, Newton allowed us to figure out that constant. So this is actually Kepler's third law. And I've seen it where you kind of needed it. They didn't formally ask, hey, derive Kepler's third law. But I've seen it in exam questions where they actually, you sort of needed to know this. So that's why I would say start with your, remember, if you're in an orbit and there's no other forces acting on it, then you got gravitational force equals the centripetal force. So you get gmm over r squared equals mv squared over r. Set them equal to and get as far as you feel like. If you need v, then you get v. If you wanted to isolate for v, you, like I said, if you want to go a little bit further, you can say distance over time. And that allows you to have this time aspect. That's it. That's orbital mechanics. A neutron walks into a bar and asks, how much for a drink? And the bartender replies, for you, no charge. That's such a bad joke, but I love it. So we're going to talk about nuclear physics and energy levels. And it's important to talk about different ways of notation. I think once you understand this, it's going to make all the rest of this topic a lot easier. So first of all, the very simple atom. I put that down because it's just, I mean, it's so ridiculously simple. We know now the atom is not really this simple, but for now it suffices to say this. So inside an atom, there's a central nucleus. That's why we call it nuclear physics, right? We've got neutrons inside and we've got protons inside. So that's what N and P means. And of course, in orbit, we have electrons. We're not going to care so much about the electrons for now. By the way, I've made the nucleus extremely big. Obviously, there's a lot of space in an atom. It's almost all space, right? So just keep in mind, you've got a number of neutrons and protons in the center. So that's in the nucleus. That's the part we're going to be mainly concerned with for now. And it's important to talk about the notation. So this would be some general, whoops, actually I probably shouldn't say A. I should probably actually say X instead. I think it's maybe better to say that. So I'm going to replace it with something like X. This is just like some element. Doesn't matter what it is. So we normally use Z. And this Z, like this bottom number right here, and I'll give you some examples like over here. Normally we write this bottom number here. We call this the atomic number. And the reason we call it that is because it's the number of protons. So this would be the number of protons in the nucleus. This is the key thing here with this Z, or this atomic number. So that'll tell you the number of protons. So for example, this one here, He, that's helium. And you know that there's 2 protons then. This top number right here is called the mass number. And the mass number tells you the number of nucleons. So you might wonder, what's a nucleon? Nucleon is just a particle in the nucleus. In other words, it's equal to N plus P. In other words, the number of neutrons plus the number of protons. So in this case right here, for example, with helium, we've got 2 protons and we've got 4 nucleons. Now 2 of them are already protons, so 4 minus 2 is 2. So that's how we know there are, let's just say 2 neutrons, and we can say there's 2 neutrons in here. Here there's 2 protons. And this is how it works, okay? This is the notation that we use. The important thing is that the element name, for example, helium, and that bottom number, the atomic number, they're redundant. What I mean by redundant is that you don't need them. You could just say helium and you know it's 2. Because this bottom number tells you which element on the periodic table it is. So now we know that helium is the 2nd element. You know, we know that hydrogen is the 1st. And it's this top number that might vary, but not the bottom number. So they're redundant. That's why we often call this helium-4. We don't have to say helium-2,4 because this 2 on the bottom is redundant. Saying helium, we know it's got to be 2. As soon as you make it number 3, it's the next element. It can't be helium, and so on. So we've quickly got isotopes. Those are just a same atomic number. So for example, we can have carbon. That's a nice simple example. So we've got 2 different versions of carbon, which is the 6th element, but different mass number. We can have carbon 12 and we can have carbon 14. So these are called isotopes of each other. You can see that this carbon 14 has more neutrons than carbon 12 does, but has the same number of protons because the bottom number is the same. That was like really, really simple overview, right? The more interesting then is the energy levels. So what happens is in an atom, you've got, of course, those nucleons in the center, the neutrons and the protons, and around it go these electrons. Those electrons are important as far as these energy levels, because what will happen is they can get excited by, maybe they, for example, absorb a photon. Or maybe you apply a potential difference across them. That's what happens in like a lot of those fluorescent lights, for example, in a room. Maybe the room you're sitting in has fluorescent lights in it right now. So if you look at that, what happens is you end up taking electrons and you excite them into what we call an excited state. So I could maybe draw that. I could draw myself like some line like this right here, and another line like this, maybe another line like this. I'm just trying to draw some parallel lines here. I'm doing a bad job of it, but there we go. What'll happen then is these electrons, maybe it goes all the way up to the very top. And what happens is this, when they drop down in energy. So for example, right here. So now it's in an excited state. And maybe now it drops down like this right here, to that energy level. When it did that, it's going to emit a photon. It's going to emit some light. So we normally write that with a curvy line. We could say it's a photon. And that photon will have a very specific energy. This is the key thing here with this. It goes E equals HF. This is the key equation here that you need for this stuff here. This is on your data booklet, so you don't have to memorize it. But it goes E equals HF, where E is the energy of the photon. Now that could be in joules, but we normally do the energy in EV. So of course you can do it in joules, or you can do electron volts. H is just a constant. You look it up. What is it? 6.63 times 10 to the minus 34. So it's called Planck's constant. And what's important is this. Energies that we find of photons, for example, the energy is quantized. What I mean by quantized means it only comes in multiples of H. You can have 2H or 3H or 4H, but it's always a multiple of this sort of magical number, this Planck's constant. Then we have F is the frequency of the photon. And remember, frequency is measured in hertz, or it could be in seconds to the minus 1. That's the same thing as hertz. Now keep in mind, there's a lot of other energy levels transitions possible. So can you notice it could have dropped here, then it could drop down 2 of these, or it could go down here, then it could go down here. Do you see there's a lot of different combinations? It could also drop from, let's just say we kept going here, it could also drop from here to here. It could drop all the way down in one go. So do you see there's a lot of these different energy levels possible? And each of those energy levels, do you see this difference in energy here? You'd have to actually measure it. Whatever that distance is, that's E. So then you know the type of photon you're going to get, because that tells you the frequency of the photon. It's unique. So for example, this one right here will have a very different energy than that one right there, right? Because this one has a much larger energy. And a larger energy means a larger frequency photon. So this is really important. This basically tells you the different colors that are possible, because the frequency of a photon is its color in a sense, even if you can't see it. But I mean, it really tells you that the frequency is related to its wavelength. So if you ever get a question like this, you have to think of all the different transitions possible. So from the top you can go down all the way to the bottom. You can go down until the second last one, like I did. You can go down just that one, and then from here you can go all the way down, or one and one. So this is how it works. I hope this is clear, because of course you can always raise and drop by lots of different things, but this is actually what explains the quantized nature of this light. In other words, you won't have every frequency possible. You only have these specific allowed frequencies. So that's really important. Now, if you want, you can also translate the rewrite this equation, because we have this equation here, E equals HF. But we also have the equation, we call it the wave equation. Some people call it V equals F lambda. If it's light, we say C equals F lambda. So that's the speed equals the frequency times the wavelength. And if we want to do that, we could replace for F. We can get F by itself, so that would be C over lambda. That means then we can rewrite this equation, which when E equals HF, we can say E equals H, and instead of F, we put in C equals lambda. And from there, then we can take lambda, put it over here to the top here, so we can say lambda equals, and it's HC over E. And that's where that equation right there came from. This is just a different version of E equals HF. This is it relating to wavelengths. So if you want the wavelength of the photon, there you go. And a nice easy thing to remember is that frequency and wavelength do opposites. So if you have a large frequency, for example, this transition right here has a very large frequency because it has a very large energy. Well, then it's going to have a very small wavelength because they work opposites to each other. Maybe then that's a good idea to do this example. This is from an exam, so something like this. Electrons in an atom are excited, and they have a following energy levels possible when they go down in energy. Of course, there's other ones possible, but I'm just drawing these four to choose from. So which of the transitions has the smallest wavelength? So if you think about this one now, let's see, what do we want here? Remember, E equals HF. And if we have smallest, you have to remember this, okay? So smallest, we're looking for the smallest wavelength, right? That means it's the largest frequency. This is the key thing to remember here, is that if we want the smallest wavelength, we want the largest frequency. And if we have E equals HF, that means then we want the largest energy. We want the largest energy value. So which one has the largest energy? Can you see how easy it was? It was A. So again, just to explain it, remember, E equals HF, so that tells you the energy of the photons is related to the frequency. They want the smallest wavelength, and frequency and wavelength were opposite to each other. So if we want the smallest lambda, then we want the largest F. And since E equals HF, the largest F is found by the largest E. That's why we want the largest energy. Not so bad, huh? For alpha, beta, and gamma decay, it's important to just know what each of them means. Speaking of memes or memes, I've got this nice little cat here. I love a science cat. Scientists love dinosaurs so much they carbon date them. Do you notice, by the way, someone actually bothered to Photoshop and actually put a little dinosaur there, which I thought was actually so cute. All right, so we got alpha, beta, and gamma decay. This is to do with a nucleus, and it can spontaneously, it can decay. It can just become a new element by itself. There's a few different types of it. This is why we're going to talk about these three types. In fact, mostly alpha and beta. So we'll talk about alpha decay. And this is actually a big one. It's in terms of ionizing power, alpha has the most. In other words, it's got the most mass, so it can cause a lot of damage. It can cause a lot of problems. Let's say you're hit with alpha particles. Bad news for you. And in fact, alpha decay itself, they used to not know what it was. When they were first discovered, they didn't really know what they were called. That's why they were called alpha as a placeholder for, hey, what's this going to be called? But now we know what an alpha particle is. We know that an alpha particle is an entire atom of helium-4. So this is why this is really important right here. One alpha particle is this. Remember, you don't have to say helium-2, you just say helium-4, right? Because this 2 means helium. This is it. So these kind of questions, if they show up on exams, these are some of the easiest ones. And they show up often enough. So I like this question. For example, fill in the blanks for the following alpha decay reaction. Now you don't have to know the periodic table by heart. Notice they don't give you one, but the questions are always phrased such that you don't need them. For example, here you're told that uranium-238, so you know its atomic number is 92, it undergoes alpha decay and becomes thorium plus this alpha, which is helium-4. So the question is on, fill in the blanks. We're supposed to fill in these different numbers of the values here that we don't know. So all you have to do is add or subtract. It's that easy. So we know that something plus 2 has to equal 92. So it has to be conserved. So must be 90 protons needed because 90 plus 2 gives you 92. Same over here, 238. Well, something plus 4 equals 238. So hopefully you see it's 234. This question is that easy. I'm just going to fix the 2 here. So I think those kind of questions almost too easy. That's why we're going to skip right away to next kind, which is beta decay. It's a little bit more interesting because a beta particle, we write it like this right here, or this beta like this. We have two different types. We have this kind, or we have this kind. And we'll talk about the difference here. But this one right here is an electron. That's what's important about this one. This one here is called a positron. It's the antiparticle of an electron. Now it seems a little bit weird because electrons themselves, they shouldn't have any protons. We have this just to make all this the math line up. So for example, electron beta decay, whenever you get this one right here, whenever you get electron beta decay, it's really important that you know that you always end up with this right here. Or remember, that's the electron. That's what this is called. This is called an electron. And you always get something special right here. So this right here is a Greek letter nu. And this right here, that's good, it's a neutrino, haha. And we get this electron neutrino, it's called. This is called an electron neutrino. However, whoops, like this here. For these right here, these electron neutrinos, we need to always have an antiparticle if we have a regular particle. So this, we're going to talk about this later on in the particle physics section, but this one right here, we have to put this right here. So this is called an anti-electron neutrino. So you always get these right here paired up. Whenever you get electron beta decay, you're going to get this. And it's kind of weird because you have to think about an electron doesn't have any protons. Remember this bottom number is supposed to be the number of protons? An electron doesn't have protons. It's not an atom. Remember, if it's an atom, then it has an atomic mass number, and that means it has protons and neutrons in its nucleus. The electron is part of a nucleus. It orbits around it, right, in this smear of probabilities. So the weird thing is that we have to just put a -1 here just to make the math work. And clearly it doesn't have any nucleons, that's why we put a 0 here. I mean, it doesn't have any neutrons or protons in it. It's an electron. But we do this -1 to make everything work out. So let's do this example here. We have cesium-137, and we're told that cesium has an atomic number of 55. Before I do anything else then, I can then write this down. I can say, all right, I know I have cesium. And atomic number 55 means this is the bottom number, and I know now the top number is 137. Do you see I didn't have to know the periodic table by heart? I just had to use the clues they gave me. So if we do this, it undergoes electron beta decay. So now I know it's going to do this right here. It's going to have this barium, and it's going to have plus, and let's see here, electron beta decay. So now I know it's got this little one here, the beta with a -1. I know it's got to have the electron neutrino. It's got to be anti-neutrino. The way I remember it is this little minus right here tells me I need a minus on the top, so to speak. Now we're supposed to write out the rest of the decay equation. So the piece then that's missing is this what goes on for barium here. Now if you look, this neutrino has no numbers. It has 0 and 0. That's the good news. So it has nothing going on here. It doesn't really change things. Not in this terms, at least. Momentum-wise and everything else, yeah, sure. If we look at this, though, we got to have 55 on the left. On the right, we also have to have 55. So I put a 54 here, right? No, 54 minus 1 doesn't work. That gives you 53. I need 56 at the bottom here. 56 is the one that's going to work. I'm just going to rewrite it so it's closer. So 56, because 56 minus 1 gives you 50. And of course, this top number then must be 137. So now I know what makes barium-137. In the same way, we can do positron beta decay. And this is kind of weird here. This thing is called a positron. it's just like an electron, except it has an opposite in every respect. It's an antiparticle, it turns out, of the electron. And what's really weird is this: if a particle and its antiparticle, if they meet and they touch, they actually disappear, they annihilate, and they end up making some gamma rays. So they end up making photons. That can happen. So you don't want matter and antimatter to touch. If you do that, they disappear. So a positron is the antimatter of an electron, which is kind of cool to think about. So because of that, of course, it's got opposite charge, got opposite everything. I mean, sometimes we write the electron, remember? Sometimes we write an electron as just E with a minus like that. And this here would be an E with a plus then. So electron with a minus charge, this is an electron with a positive charge. That's what's called a positron. But we have to also add a neutrino. And we have this little neutrino here, this new E. And then we don't need the antiparticle here because it turns out this is the antiparticle. And through conservation rules, which I'll explain later, that's how you know that the beta particle here is a regular particle. So you need an antiparticle to make all the conservation work. Here we have a regular neutrino because we already have an antiparticle. That's this. This thing is the anti-electron. So that's why we do this. So we have a nice simple example here. Fill in the blanks for the following reaction. So this is sodium becoming neon 22 plus a positron plus an electron neutrino. So what do we do with this? We again just have to do the math. It's almost too easy, isn't it? I love these questions. They're so simple. So 10 plus 1 is 11. So hopefully sodium is the 11th element on the periodic table. And 22 plus 0 is 22. There we go. So we know it's sodium 22. That wasn't so bad, was it? Now we have gamma decay. Gamma is the simplest one because a gamma is just a photon. That's it. And a photon has no protons, has no nucleons. It's just this. So the thing is, we don't really bother with it because it doesn't really change. Imagine if you say, I don't know, some element, X, it undergoes gamma decay. What does that mean it does? That means it goes and it just emits a photon. That means it must have been in higher energy and it emitted a photon somehow, or it could have done some other internal processes. But either way, it doesn't change the element. It doesn't change the atom, I mean. So in that sense, it's not that interesting. When we learn about Feynman diagrams, you'll see photons are immensely interesting for a lot of other reasons. But as far as just this right here is concerned, the exam questions they can ask you are pretty much nothing. They're going to ask you lots of other things about photons, like I said, for Feynman diagrams. But as far as the gamma decay goes, it's pretty straightforward. It's just 0, 0. And that's it. So I hope that explains these different kinds of decays. Okay, you've got alpha, which is a helium-4. We got beta, which could be beta plus or minus. Those are either electrons or positrons. And you got gamma, which is just a photon. That's all you need. I'm going to speak to you about exponential decay. I have another science cat for you here with the radioactive cats have 18 half-lives. Ha! So we're going to talk about half-life. It's going to be related, but I mean, first I just want to explain about decay itself. I mean, inside the atom, remember you've got neutrons and protons, and we've got these electrons with this smear of probability going on. But what the atom can do, it can spontaneously decay into something else. But this act of spontaneously decaying, it's exponential. And what that means is that it follows this kind of curve. And remember what an exponential curve looks like. I'll try to draw one here. Maybe I'll do a poor job. We'll find out pretty soon. So I'm just going to start off with some amount first. So let's just say something down here. And then I'm going to attempt to go, I don't know, something like that. Oops, I didn't do it very well there, but good enough. Actually, I'll do it again. Maybe I can draw it better. Something like that. And the last little bit shouldn't have been quite so raised, but something like this. So if you look at this, then this is the idea is that you start off with a certain number of particles, or it could be a mass, like in grams or kilograms or whatever. It could be something called activity. And activity is just decays per second. So we use that unit called a becquerel. So it could be activity. Either of these, it goes like this. What that means is that you can actually simulate this in a lab. What you can do is you can take a whole bunch of dice, for example. This is something I would do with my students. Let's say you start off with, I don't know, like 100 dice. Let's just say that would be crazy, but let's just say 100 dice, and then you just roll them. And what you do is you keep track of each roll, you put that on the x-axis, and you keep track of number of dice on the y-axis. What you could do is have a rule like anytime I see 6s, I remove them. So basically, can you imagine your first one, you just count the number of dice as 100 dice. Then you roll, boom, and you get a bunch of 6s, won't you? You'll have some 6s. So every time you have a 6, you remove them, and then you plot then the number of dice now. Then you roll again, boom, and you continue this. If you do this, this will give you a nice exponential decay curve. It'll look better than what I've drawn, actually. So this is exponential. What that means then is that there exists this word half-life here, and I'm going to show you what that is. I haven't drawn it very well, but let's say you start off here with whatever this is here, 100 particles, or 100 grams, or 100 becquerels here, because activity. No matter what we start off with, there exists some half, right? We can get to half of it, so we can go like this right here, go across, and then go down. And this right here then will be what we call T1 half. This is the letter we use for half-life. Okay, we call it T1 half. That's the half-life. So this is the time it takes to have exactly half of the original amount. That's why it's called half-life. So do you see it's the time it takes to have the activity or mass or number of particles go down to half their original value. And can you see if we go one more half-life? Let's see if that's going to work out. So if I go half of this height now like this, I should go across, and if I've done it right, it should look roughly the same distance here. That's not too bad. So this would be 2 times T1 half. So after 2 half-lives, you have 25% of the original amount remaining. And you can go 3 and 4 and 5 and whatever half-lives. This is the idea behind it, okay? It's exponential. Now these right here, you could say that these right here, these little nuclei here, you could be counting what are called the parent. What that means is this is the one that's decaying. We're counting the amount of the what we call the parent. But keep in mind, every time you have a decay happening, you make a new thing. And sometimes those are called daughter nuclei. So I'm going to draw you, just in case you'd like to see it, I'm going to try to draw you the curve of a daughter nuclei. So it's going to go like, I'll just try to draw it like this. So yeah, it's going to go like this and then like that. So in other words, you start off with no daughters. So this will be called daughter here. So the daughter particles, like whatever it's making, whatever it's turning into, clearly when you have 100% of the parent, then you have no daughters, right? But then as soon as the parents sort of make something new, well, then you have more daughters, if that makes any sense. And of course, at the end, when you have almost no parents left, then you have almost all daughters. And of course, the daughters can't outshine the parents. Well, I guess they can in real life. But in this case right here, then you know what this right here should be asymptotic to. Those are the daughter nuclei, these are the parents. But the key thing, though, is that this right here still is an exponential decay here. That's the key thing to learn. Now, I love this name, Half-Life. Maybe you've played, it's an old computer game. There's an old computer game actually called Half-Life that I used to love to play. Actually, it was Half-Life 2 they made. They've been saying they're going to make a Half-Life 3 for like 15 years. But really great game, a little bit scary. I liked it because you actually play a physicist. That's about where the physics part stops. Although they do use the symbol lambda, which isn't wavelength actually, it's actually the decay constant. So that's sort of related to a half-life. Either way, let's talk about a real example here. We have an isotope, and we're given the fact that it has a half-life of 20 minutes. So now I know T1 half, right away, T1 half equals 20 minutes. Now initially there are 1,024 grams of this isotope. So that means initially now we start off with 1024 grams. Find the time after which there are 128 grams remaining. Maybe what we can do is consider just look at half-lives and look what happens. So what if, for example, we take this 1024 and we try to maybe split it into 2. So this is originally, right? So this is original. And maybe then what we can do, we can actually sort of consider how much is there actually remaining. So watch this. If I take 1024 like this grams and I divide that by 2, what do I end up with? Well, 1024 divided by 2, it's 512 grams. That's after 1 half-life. If that makes any sense, that's after 1 half-life. After another half-life, let's see what we have now. So now we have 512, whoops, I should go like this. I should say 512 grams, that divided by 2, because I have that further divided. That's 256. Maybe you've played that game, actually. What's it called? Actually, 2048. I think it's an app on your phone, for example, an iPad or whatever. That was a game that was popular a couple of years ago, but yeah, then you learn your powers of 2 really well. That's what these are. So you have 256 grams. That's after 2 half-lives. Is that what I wanted here? Nope. Split that into 2 again. So 256 divided by 2, what do I get? And there I have 128. Hey, do you see how I'm looking for 3 half-lives? Do you see this is what I wanted? I wanted 3 half-lives. So because I know 3 half-lives have happened, this is actually really easy. Because I know 3 half-lives have happened, well, how long is each half-life? It's 3 times 20 minutes. So then I know it's 60 minutes, and that's it. That's your final answer. It's that easy. So this is the case. In physics SL, you're expected to do this with nice numbers of half-lives. In other words, you're going to be finding like times that are multiples of the half-life. If you're in HL, then you have an extra topic where you have to learn how to do it when it's not necessarily a nice number. So that's sort of the difference between the HL and the SL part here. It's not that hard. The idea is the same. It's just that then we'll get an equation. For the HLs, they'll get an equation for how to solve for T. It'll involve this thing called the decay constant, this lambda. But just so you know, this is how we can deal with this. And it's not so bad, is it? This is this nuclear physics here. This is exponential decay. Now it's time to talk about binding energy. I like this picture here. Your radioactive substance has only made me stronger, Erwin. That's relating to radioactivity, but also Erwin. I have a feeling Schrodinger because that's a cat in a box. Anyway, we have binding energy. This is something that's a little bit unintuitive to a lot of people. You would think that when you make an atom, you need to use energy and you need to, you release energy when you sort of blow things up, but it's the opposite. You release energy when a nucleus is assembled from its constituent parts, which means every time a new element is made, there's some energy that's released. That is this binding energy. And we talk about the mass of a left-hand side is not equal to the mass of the right-hand side. So what this means is this. When you have a reaction, for example, the main reaction inside a star, for example, is hydrogen to helium. So it's not just as simple as just, 2 hydrogens make a helium. It's not that simple. It's a few steps process. We actually call it, in astrophysics, we call it the PP cycle, like PP. We didn't mean proton. So what happens is there's a process by which hydrogen can eventually turn into helium. And you have 1 and 1, and then you end up with a 2, 4. Obviously, this just by itself can't make it. You have to have a few different hydrogens, and you have to have the processes repeat. But basically, you end up eventually with ... helium-4. In this process, if you were to add up all the pieces to the left, for example, all the different reactions that happen in order to make this possible, if you sort of weighed one of the sides, let's say the left-hand side, and then you weigh the right-hand side, all the masses before and all of it after, you'll see that they don't add up. There's a little bit missing. So that's why this is called the mass defect. This is the key thing right here. You need to know this is mass defect. And this mass defect is what's important here, because now we have Einstein's famous equation. If I asked you, or even your parents or someone, if I ask just about anybody, what's Einstein's famous equation? Most people know. E equals mc squared, right? Let's write it how it looks like in your formula book. Delta E equals delta E mc squared. Einstein was really clever. He also had an ability to take really complicated things and boil them down to the most beautiful of simple equations. So what this really tells you is this. This delta E here that we're talking about, this binding energy, that's going to be the energy released when you make a nucleus. So what happens is inside a star, remember I was explaining we have hydrogen to helium. Every time you have that reaction happening, you end up with some mass that is missing, right? This is this mass defect. It turns out that mass gets converted into energy. This is the process by which it does that. E equals mc squared, which is really deep, right? Mass can turn into energy. Yep. In fact, think about a star. Think about the center of a star. What goes on, of course, every time this happens, mass gets converted to energy. Energy can be in the form of a lot of things, can't it? Including, light. That's why stars are bright. Heat. That's why stars are hot. So, my little daughter, for example, she sings a song, Twinkle, twinkle, little star, how I wonder what you are. Like, done. It's a big ball of gas, right? converting hydrogen into helium and releasing energy every time it does it. So that's this E equals mc squared. It has to do with any atom being made. So anytime you make a new element, you end up releasing some energy because some mass went missing. So let's talk about this then. It's the binding energy. Remember, that's the released energy. And we measure energy in either electron volts or joules. And we typically use EV or MeV, mega electron volts, which is 1,000,000 electron volts. We have delta mass, which is the mass defect, we could say. And that would be in, now, we can measure it in kilograms, of course, or we can measure it in U, which we have over here, or we could say it's in MeV per c squared. These are different units. Get it? Units? So if we did the mass defect in kilograms, of course we could. And by the way, speed of light, we know that is just 3 times 10 to the 8, and it's meters per second. Now we know the speed of light. So we have this thing called an atomic mass unit, or AMU sometimes for short. That's this 1U. That's this in the red here. So this one atomic mass unit, what that represents, you could define it. It's actually defined based on a carbon atom, but we can actually say this one atomic mass unit. You can get it in kilograms, but I think the more useful thing is to put this in MeV per c squared. And it seems like that's a ridiculous unit. Like, why would we make this atomic mass unit in mega electron volts for every c squared? What? But it turns out, if you do a lot of physics, you realize you get really annoyed by always have to use c squared. If you think about it, you're in the middle of a calculation, like, okay, got a mass, that's in kilograms, I got to multiply by 3 times 10 to the 8, and I got to square that. And you do it so often, you get really annoyed by it. So then it makes sense then to think, can't we have a unit that already sort of just cancels out the c squared? And it turns out this is your magic unit. This is the unit that makes your life a lot easier. And I'll show you how, because otherwise you'd have to calculate your mass in kilograms and multiply it by c squared. Then you'd get the energy, which would be in joules. And then you'd probably have to then convert it to electron volts, which sounds annoying. You have a lot of extra steps. So let's do a real example here. So we have something called radium. And radium is atomic number 88. And you're told it's radium, you have 226 nucleons. Okay, so you're told it's radium-22. And it undergoes alpha decay to give radon. Now look, radium, and this is radon, so you do have to keep them straight. Radon is one with N, radium is one with A. They both technically start with rad, don't they? They're both rad. So let's write the decay equation for this bad boy here. So what do? Well, we start off with this radium. So I'll put radium, 88, and I'll put the 226 here. It undergoes alpha decay. So what does that mean? Well, they tell you here it gives radon, so I'll leave the Rn here. Plus, I need an alpha particle. Do you remember what an alpha particle is? It's a helium-4 atom, and you have to know it's 2. So do you see how this right here, then I've got what I need. I just have to write the decay equation. Oh, I just need to fill in the numbers. So in this case right here, let's see. 88 equals what plus 2? Hopefully you can see it's 86. 86 plus 2 gives you 88, so that's that number. That's the number of protons. So that tells you radon is the 86th element on the periodic table. And then I have to have the top number here. So 226 equals what plus 4? And hopefully you can see that's 222. Because that plus 4 equals 226. So now we can call it radon 222. Now the question is, how much energy is released in this reaction? And you're given the masses of radium, radon, and an alpha particle in terms of atomic mass units. This might seem annoying, but it turns out it's going to make your life easier. Let's do the left-hand side, and let's do the right-hand side. So the left-hand side is just this radium. That's all I need. So this radium's mass is just 226.0254 U. I'd say for these cases right here, be really careful. Use lots of decimals. I usually use at least 4 decimals here. It's one of the only sort of exceptions to sort of rounding things off. Here, leave all the decimals you can. Leave at least 4 for these sort of questions. Now the right-hand side, what do we have? We have radon, which is 222.0176, and we add that, oops, I have to say it's U. That's important. You can't forget that. Then we have plus an alpha particle. An alpha particle has a mass of 4.0026 U. So I'll put that in. Well, then I just look at this here and say, all right, well, what's this right-hand side? Well, of course, I add these up. I end up with 226.0176 019. Oh no. Yeah, I end up with 226 point, what do I get? Oh, that rounds. I did a really bad job here. And it turns out it's 02. I counted the numbers totally wrong, hadn't I? 0202. I just can't seem to add. I can do nuclear physics. Apparently I just can't add. So we have this number right here, left-hand side, and we have the right-hand side. Do you notice they're not the same? They're very close, but a little bit different. So how are they different? Do the mass defect. This is the thing we need to find, is the mass defect. This is this delta M. And if we look at this 226.0254, if I subtract from that 226.0202, let's see, the O2 is nothing that is important. We have a 5.2. So we should have 0.0052 U. This is the number I'm going to need. Now, of course, you could convert this. You can convert this U into kilograms and multiply it by C squared, and away you go. But let's use the easy equation. Let's use the easy version, which is just, you have this delta E equals delta M C squared. Well, then I have delta E, the energy released, that's this, equals, let's see, the change in mass, so that would be 0.0052, 52. And instead of U, I put in actually what a U is. And what's a U? It's 931.5 MeV per C squared. So because I have this many times U, and U is this 931.5 MeV for every C squared. This now is U. But don't I have to multiply M times C squared? So that's why I have to throw in a C squared. Remember, this is the missing mass times U times C squared. So in this case right here, do you notice the C squareds cancel out? That's nice, isn't it? And I end up with 931.5 times 0.0052. So I better do that on my trusty calculator. And I end up with 4.8438. As mega electron volts. Is this way easier? So that's why I prefer to leave things in electron volts, even though it's a unit that a lot of people get scared about. Leave it like this because the C squareds cancel out. That makes your life a lot easier. Now it's time to show you this graph that I really like. It's called binding energy per nucleon. Of course, we have another science cat here. How often do you like jokes about elements? Periodically. Because here we're going to talk about actually nucleosynthesis. And this has a lot to do with astrophysics. That's why I like it so much. I'm very biased. But this has to do with everything to do with stars, it turns out. So let's talk about this binding energy per nucleon. What this is, remember the binding energy, it's the energy released when an atom is made from its constituent parts, which means when you make a new atom, this energy is the energy that's released. That's the binding energy. Now, of course, a larger atom, of course, has larger binding energy. So one way to sort of scale it is look at what's the binding energy for every nucleon. Remember, nucleons at the top number, the neutrons plus protons. So if we consider the binding energy per nucleon, that would be the graph of this on the y-axis, and on the x-axis we'd say the nucleon number. For example, the very first element is hydrogen, so that would be 1, that would be here. The next one would be helium, and so on. You have to know the shape of this graph. Maybe I'll draw it like this, maybe in sort of blue like this. So I would draw it like this. First of all, you have to know that it goes kind of up and then has a peak and then kind of goes down like this. It turns out it actually has a few little spikes there, but it suffices to go something like this. It goes kind of like this. It has a peak right here, and you have to know this peak. You have to know that it's iron. Something like that. So there you go. So it's the iron, which is the 26th element. You have to know it's iron 56. This is something really important to know. That's the peak. That's the top. And then it goes kind of down again. So what happens here? Well, first of all, if you don't know how to remember the shape of this graph, this is going to be really, really dumb, but watch this. Look, I always thought this looks kind of like a whale. So I always thought this is like, the top of a whale here. I'm going to erase that because if I save this PDF, no one's ever going to understand that, okay? But if you want, think of a whale. And there you go. That's why I call this the whale here. So this binding energy per nucleon. Maybe that's really dumb, but hey, I'm teaching you how I remember things. So the important thing to know is this. First of all, reactions will occur naturally, which means in a star. Remember I said inside a star, for example, you've got hydrogen turning into helium. That's a natural process. But they'll happen naturally if they go up in the curve. They have to go up in binding energy per nucleon. So what that means, look carefully here. That means that if I'm looking at, I don't know, something like hydrogen here, and I want to go up on the curve, do you notice that means I have to go right? That means I have to go from a lighter thing to a heavier thing, and we call that fusion. So fusion is this act of going from a lighter element to a heavier element. So this explains why fusion is on the left, because it's more energetically favorable, you could say. Because only by this does it go up the curve, and by going up the curve, then that's what it has to do to be natural. That's why fusion happens to the right until it reaches binding energy maximum here, which is iron. At this point, you notice even if it tries to fuse iron into the next thing, it doesn't go up in the curve. So it doesn't do it naturally. You have to force it to happen. So like I said, here's the problem. Stars can't naturally fuse iron in their cores. So we'll talk about that in a second here. By the way, then I'm doing like the HL extra stuff to astrophysics options. So it very much relates to this. Let's look at this one though. So if you have to go up on this curve to have a naturally occurring process, then that's why it goes up. That's why it goes to the right here. What about on this side? Like what if I had, I don't know, like uranium? That's way over here somewhere, nucleon number, right? That's like 238 maybe. They're like way over here. This one, in order for uranium to do something naturally, do you notice that to go up on the curve, it has to go to the left? So that's why going left means you make lighter elements, don't you? We call that fission. So that's why fusion is on the left side and fission is on the right. So to go naturally occurring, you got to go up on this curve. But then the natural question is, all right, what goes on inside a star? I mean, there's a lot of details for the astrophysics option. But just to explain it here, where it relates here, I think it's really interesting. You've got hydrogen to helium. Stars can form other things. When they run out of hydrogen in their core, they're going to do some weird things. They're going to collapse and expand, and weird things is going to happen. More detail in the astrophysics option. But the end result is, what if you have a really massive star, and it got all the way to iron? Imagine this. So you have a star with iron in its core, right at its very, very center. What's amazing about that is that, notice it can't go up anymore. It can't fuse anything higher. So what ends up happening is the mass of the star, the rest of the mass of the star, of course, it's very massive, right? It has a lot of gravity. So that means that's going to come inside and sort of collapse because it can't push anymore. It's related to something called hydrostatic equilibrium. You don't have to know that for this right here, for this topic here. But I think it's nice to know what happens is that stars can't fuse anything higher than iron. And we think that stars are actually responsible for making the elements. We call it nucleosynthesis. So the very fact that stars are making new elements, what happens as soon as they get iron in their cores, though, they collapse. So actually, it turns out it's really kind of freaky, but like the iron that's in your blood, that is what wrecks the star. That's what makes the star actually not be stable anymore. Because it can go all the way up till iron in its core. If it has iron in its core, it's no longer able to fuse, so that means it's going to collapse. And it turns out it's going to collapse, and through some weird processes, it'll harden and explode into a supernova. And we go into the details in the astrophysics option there. But just so you know, I think it's really cool to know that stars can't make anything heavier than iron. Then they blow up. So the thing you need to blow up a star is actually in your veins, literally. As soon as a star has iron in its core, it explodes. It doesn't quite, it actually implodes and bounces off a neutron core, but those are details for the astro option. Now you might wonder then, how in the world then are heavier elements made? You know, because if stars are the ones making all the elements, which we think they are, other than hydrogen, we think the Big Bang made hydrogen, or actually pair production and this asymmetry between matter and antimatter. But if you look at this, how are heavy elements made? You could say, well, a star can make all the way up until iron. But then after iron, when it blows up, only when it explodes in this supernova explosion is when it has enough energy to then make those. So we actually think that all the elements higher than iron were actually made in the supernova explosion itself from a star. It's kind of mind-blowing, isn't it? Now it's time for what scares a lot of people, which is particle physics. This t-shirt is actually really naughty. Maybe it's the worst thing that I put in here, but particle physics gives me a hadron because it's a play on words. If we replace the R and the D, it's very naughty. But I've actually seen some physicists wear this kind of t-shirt. So anyway, We're going to talk about hadrons, actually. So we got particle physics, and it all comes from a really basic idea, right? You take the atom, you take the pieces of the atom, like a neutron and a proton, or electrons, and you try to break them up into smaller pieces to find out, can they be broken up? Turns out electrons can't. So as far as we know, you can't split up an electron into any component parts, but neutrons and protons, they do break up into other particles. Those particles are called quarks. Those are, I think they have a background, I think it's in science fiction. I think there's a book, I can't remember the name of the book now, but they had quarks in them. So a lot of this is named kind of with a sense of humor. You see, a lot of the physicists here really had a good sense of humor about naming them. So they realized, imagine this is empirical, right? You do this, you split up a neutron, you just smash it together with something else at very high energies. You see it makes these other particles. So they had to give them a name, so they called them quarks. And it turned out there were 6 different basic types of these particles. So we're going to call them, these are the 6 types of quarks. So first we're going to say there's the up, well, we'll write them like this, UCT and DSB. And then I'll name them all. So U is called up. Now these names are kind of arbitrary, although some of them are kind of paired up for different reasons, which we don't quite need for IB. But U is up, C is called charm, T is top, D is down. We have S, which is called strange, which I think is a fun one. And they got B, which is bottom. So this is what you need. So you got up, charm, top, down, strange, and bottom quark. Those are those 6 basic quarks. However, each of the quarks has its antiparticle. Now, antiparticles, they have opposite properties. So, for example, charge, baryon number, we're going to talk about lepton number, and strangeness. So they all have opposite particles, opposite properties. So, for example, there exists something called the, well, we'll write them down again. So UCT, DSB. Except for each of them, we put a line on the top. So that tells us it's the antiparticle. So if you have a up, you have something called the anti-up. And if you have a charm, this is called the anti-charm. I hope you get the idea here. This is anti-top, anti-bottom, and so on. So I think this is actually really interesting because you have these antiparticles. And an antiparticle is really strange because if a particle meets its antiparticle, something very, very special happens. Okay, I'll just make sure I spelled this right. So anti-charm, top, down. Because when I'm talking, maybe there's a big chance I made a mistake. Okay, good. So for example, if you have a particle like an anti-up running into an up, so a particle and an antiparticle, if they meet and collide, they actually annihilate. They make, well, photons basically. So this is really interesting. For example, an electron and its antiparticle called a positron, that was something from the nuclear physics part. If an electron and its positron, they're opposite particles. If they meet, they disappear. We call it annihilation. They make photons. We're going to learn with the Feynman diagrams what that looks like. So basically, you just have to keep in mind there's particles and there's antiparticles. These are quarks. Now, the thing I think that causes a lot of students problems is this idea about this sort of the structure of this, like how they're organized and how they're structured. I think a lot of textbooks just write a bunch of sentences. They'll say, you can make a lot of particles out of quarks. You can say hadrons are made of quarks. You can have baryons are made of 3 quarks. Baryons are also hadrons. Mesons are made of 2 quarks, where 1 quark and an antiquark, and those are also examples of hadrons. I think what I said, by the way, is all true, and yet I think if you write it all in sentence form, it's not very clear. So I'm going to be repetitive to annoy you, but because I'm going to annoy you, you're going to learn the structure really well, sort of how they're related, okay? So this is going to sound slightly annoying. If I'm annoying you, good, it means you know it. So what do we do with quarks? We have the largest scale structure with this is called a hadron, or like this t-shirt, right? Particle physics gives me a So what do we do with quarks? Hadron is a particle made of quarks. So just think of that. There's nothing else needed. You take some quarks and you make something out of it. That's called a hadron. That's it. I like to think about hadrons as heavy. So these like the heavier particles. Now within hadrons, if you're going to make something out of quarks, you can make 2 different types of particles. you can make something called a baryon, and that's when it's got 3 quarks. So again, baryons are just 3 quarks put together. You can have any of them, except obviously not an up, and it's anti-up because those will, annihilate. But as long as you have any quarks, any 3 quarks, or even anti-quarks, just choose 3 out of these 12, so long as there's never like a quark and its own anti-quark together. You can have like an anti-top and an up, and an anti-strange, I guess. You'd have to check for conservation to see if it's possible. You could check the Feynman diagram, but if you can draw it, then it's possible. But if it's made of 3 quarks, we call it a baryon. That's it. So again, baryons made 3 quarks, and of course you made it out of quarks, therefore it's a hadron. So do you see the structure? Make something out of quarks called a hadron. If you make 3 quarks together, that's called a baryon, which is also a hadron because it's made of quarks. See, repetitive. So there are 2 types of particles you need to sort of memorize, or at least know the structure for. You need to know the quark makeup of a proton. So proton is going to be made up of this. It's going to be up, up, down quark. So it's got 3 quarks, right? See, 3 quarks. That's why it's a baryon. And because it's made of quarks, it's a hadron. It goes up, up, down. Now, does the order matter? No. You could say it's down, up, up. You can say it's up, down, up. It doesn't matter. The fact that it has 2 ups and a down, that's the important part. A neutron, however, is up, down, down. So it's very similar to the proton, right? It's only that there's a difference between one of the ups is a down. This is a little bit lame how I remember this, okay? But because you do need to know this. Okay, so I'm going to put this maybe in green here to circle it. So you do need to know this one, and you do need to know this one. Those could be asked. It's implied, at least. You'll need to know the makeup in order to continue. It's kind of lame, but I remember that both of them end in a down. So those are sort of the same. The way I remember the difference between a proton and a neutron, I think like pro means, we kind of use like the word like positive. If you're positive about something, you're pro something. So look at this. You're up, up. It's almost like, you're feeling like up. So you're very uplifted. So it's you're very, very happy. So that's why you're pro. Whereas a neutron, you're sort of neutral. Look, you're up, but you're also a little bit down. You're in the middle. You're neutral. So I remember that the up, down, that makes me think of neutral. If that's really too lame for you, no problem. Just remember these and you're fine. Okay, so those are the 2 baryons you need to know about. And baryons, remember, 3 quarks. And you're also a hadron because you're made of quarks. There's another type of hadron, though. What if, instead of making 3 quarks together, you put in 2 quarks together where one is a quark and one's an anti-quark, but not its own? Remember, because if you put a quark and its anti-quark together, they disappear, they annihilate. So look at this. A meson, it's a particle made of 2 quarks, like I said, a quark and an anti-quark. An example could be the positive pion. You don't have to memorize these ones. You'll be given the quark makeup of these things. But for example, there's one called a positive pion. That one, its quark makeup is, let's see here, that would be up and anti-down. Do you see? There's only 2 quarks together. There is a particle and an antiparticle. So this is a meson. This is a real particle. You can actually find this in nature. Some of them are very short-lived, for example, but this is a positive pion, it's called. So this is really important. Again, remember, if it's made of a quark and an antiquark, then it's a meson. And remember, mesons are hadrons because they're still made of quarks. So this is how we can sort of break it all down here. So we've got other particles as well called leptons. These are, because remember, we've got these basic fundamental particles, these quarks. Remember, we've got these 6 and the anti-quarks. We've got other types of particles called leptons. I try to think about the lighter leptons, just like I think of the heavier hadrons. That's what I think about. So lighter leptons and heavy hadrons. There are 6 types of leptons as well. So let's put those down. These go as follows. There's one called tau. At least we call it tau. I heard there's one of my students, she's Greek, she told me they say it, I think they pronounce it taf in Greek, but I'm going to call it tau. I'll ruin it. Then we have mu, and then we have E, the electron. So this is the tau. By the way, these all have a negative charge. I'll put a little minus to the top right here just to make sure we know. So this is called the tau. Some people call it the tauon. This is the mu particle, so some people call it the muon. This is the electron. Hey, that's a particle we know. Then we've got something else. Here, you got these neutrinos. That's why we use the Greek symbol nu. Isn't that clever? Neutrino. And we have these little subscript. We're going to have 3 different neutrinos. It looks like a V that's had one of its branches sort of blown away. Looks like a lot of wind has been blowing on this one, sort of bending. So we put a little subscript. We have a subscript tau, we have a subscript mu, and we have a subscript e. Do you see? In other words, we call this the tau neutrino. Okay, that's what we call this one. We call this one here the mu. Whoops, I should say the mu neutrino, or the muon neutrino, some people say. And this one here is the electron neutrino. Now, of course, we have the 6 antiparticles as well. So we have the anti-tau, the anti-mu, the anti-electron. We have the anti-tau neutrino. We're going to put the anti-symbols on top of them in a second here. So what happens here? We have this on top, this on top, this on top, this on top, this on top. Those are the antiparticles. Remember, this is the anti-tau and so on. So I hope you understand this. Keep in mind, though, this particle right here, remember, it has opposite charge. So if this had a negative charge, you could technically say this is, you could also write it like this, couldn't you? You could say it's a mu plus. That's also another way of writing this. Just like this, you could write it instead of the electron with a minus charge, you could also write it like this with a plus. By the way, this one has a special name. That's called a positron. So see, we have this electron and its positron. Those are the antiparticle pairs. And of course, it's called the anti-tau neutrino. This is the anti-mu neutrino, and so on. And very finally then, I think we have a nice way we can represent the particles. If we write sort of a line like this right here, then we can actually write them all down. So we can say, for example, I like to put the U and C and T, and we'll split them up, and we'll put D, S, B. So these are all the different particles we know of. This is like our zoo of particles here. These are the quarks, aren't they? So these right here, these are the quarks. And remember, if we put things together, if we make things out of them, these are called hadrons. Remember, I'm just trying to put everything together so we remember them, hadrons. And remember what kind of hadrons we have? If we have a baryon, remember what that is? That's 3 quarks. And if we have a meson, remember that's 2 quarks, where one is a quark, one's an antiquark. And on the top here, we're going to have our, instead of hadrons, we're going to have our leptons. Those are the other basic particles. Remember, we can split those up and we can say, all right, we have the tau, mu, and electron, and then we have these 3 right here. These are the different neutrinos. I'm just putting them all down right here just so we can, and I'll put little negative charges maybe on them, just like this. But these are the actual antiparticles here. And these right here have a little tau, and mu, and electron. These are all our different particles. So this is it so far. These are all the particles. I think it's a nice way to represent it this way. I actually saw this on a movie called Particle Fever, and I really loved how they described it. I think it's a lot better than the ways a lot of other people show them. So that's why I use this. For particle physics, now we can look at conservation rules that allow us to find out what's possible and what's not. Well, like this one here, I don't always understand particle physics, but when I do, I don't. That's how a lot of people think. So conservation is the idea that a property must be conserved. So it has to be same before and after. So for example, these are the 4 main properties we'll be looking at, especially in IB. It's going to be charge, baryon number, something called a lepton number, and something called strangeness. Now the strangeness is not always having to be conserved. So did you see to the side here I say the weak interactions, and we'll talk about this later, the ones with the W plus minus bosons or the Z bosons, those don't have to conserve strangeness. They're allowed to violate it. But the strangeness will be conserved for electromagnetic interactions, so things that involve photons as your sort of wingman particle, as I'll talk about. So main thing is that this right here, these 2 tables here are given on your data booklet, so you don't have to memorize these. And look, if you look for your quarks here, you got the UCT. Look at this. You have your charge for UC and T. So the charge is to the left. But for DSB, the charge is different. It's minus 1/3 E. Remember, E is the elementary charge. So you got charge then figured out for quarks. You got charge here. So UCT, there's the charge. DSB, there's the charge. And just for your leptons, your electron, muon, and tau, your charge is -1. And for your neutrinos, it should make sense. Charge is 0 because they're neutral. Then we've got baryon numbers, something called baryon numbers. So in this case, UCT, they all have a baryon number of 1/3. DSB also have 1/3. That's good news. We'll see why. Leptons, by the way, they don't have a baryon number, so they have a baryon number of 0. So if you're one of these particles here, your baryon number is 0, if you want to look at that. Conversely, lepton number. Do you notice there's no lepton number written for the quarks? Good, they're not leptons. That's why, so their lepton numbers are 0. But leptons all have a lepton number of 1, except antiparticles, so the anti-electron has a lepton number of -1. Remember I said antiparticles have opposite properties. Finally, we have something called strangeness. This is a little bit weird. So they're going to say that all quarks have a strangeness number of 0, except one called the strange quark, oddly enough, that one right there. It has a strangeness of -1. See, that's what makes it strange. Why isn't it +1? Because it's strange. What I find interesting is not on the data booklet is that antiquarks have the opposite sign for baryon number. So if you have, it's just nice little things that you might want to know. So for example, if I'm looking at an anti-up, it has a baryon number of -1/3. The anti-strange quark, of course, if the strange quark has a strangeness of -1, then I hope you understand that the anti-strange will have the opposite. So it'll have a strangeness of +1. I love these words, strangeness. And of course, like I said, antiquarks have the opposite charge, etc. So there we go. We're ready to apply the conservation rules. So now let's just do a bunch of examples. So let's look at the charge of a proton and a neutron. Do you remember the quark makeup of a proton? Maybe you remember it already, but you need to know it. So the quark makeup of a proton, let's see. Well, I remember that they all have 3 things and they end in a down. I remember the neutron is like, it's up, but it's also a little bit down. And the proton is up, up. It's very happy. So there we go. Let's look at the charge for this bad boy then. So if we have U, U, and D, let's see here. I have U. U is 2/3 E. So I'm going to have 2/3 E plus 2/3 E minus 1/3 E, if that makes sense. Because that's the D. So I'm going to say 2/3 E plus 2/3 E minus 1/3 E. What do I get here? Well, here I get 2/3 plus 2/3 is 4/3 E minus 1/3 E. So what do I get? 4 minus 1/3 is 3/3 E. So that gives you 1 E. Good news. It's supposed to. A proton should have a charge of 1 times the elementary charge. See, it worked. Let's see if the neutron really gives us neutral. It should be none. Let's see what happens. An up is 2/3 E. And a down is negative 1/3 E. So watch, I have negative 1/3 E and negative 1/3 E because I've got 2 of them. Remember, I got up, down, down. So this is up, down, down. If you look at this ends up being 2/3 E. I'll just show you all the details here, but you don't have to do it all so detailed. So do you notice that gives you 0? Good, a neutron's supposed to be neutral. So it should have no charge. So good news, this is all supposed to work out. Let's look at the baryon number for UCT. So this would be, well, actually I'm going to leave it for now. Let's just look at this, something made with 3 quarks here, U, C, and T. So let's look at this. U, C, T, don't they all have a baryon number of 1/3? So if you look at that then, I'm just trying to get you practice just so you can deal with these. It means I have 1/3 plus 1/3 plus 1/3, all 3 particles. So the baryon number should be 1. Good news. Baryons should have a baryon number of 1. That's why they're called baryons. So good news, right? Look, remember what a baryon is? It's something made of 3 quarks. See, 3 quarks, baryon number of 1. Good news. It's like a little switch it turns on. Yep, it's a baryon. And remember, a baryon is a hadron because it's made of quarks. Let's look at this thing. I wonder if it's a meson. It's got an up and an anti-down. Let's look at the baryon number for these. Well, up has a baryon number of 1/3. But the anti-down, let's see, down has a baryon number of 1/3. So the anti-down has negative 1/3. All right, so now we do minus 1/3. And good news, it's 0. Good news, it shouldn't have a baryon number of 1 because it's not a baryon, right? It's a meson. Remember, because it's made of 2 quarks, where 1 is a quark, 1's an anti-quark. And remember again, something that's a meson is also a hadron because it's also made of quarks. Just so we know everything here. Oops, here, I've got a real mess here. What happened here? Oh, God. Let me just, oof. Boy, it's going to be messy. I just got to actually temporarily grab these things here. I'm just going to try to grab them here because I'm going to have to move them. I'm going to have to move these particles here. I'm going to have to move everything here away. Ooh, it's going to be messy here. Sorry about that. Because my question got a little bit messed up here. There we go. I'll just move these over here. I'll move this back up here. Let's see if I can fix everything now and put them back in here. So I've got this right here. Oh no. At least this one here I can fix. This is that particle. And let's just put it down here. I'll just rewrite it then. Maybe that'll be simpler than trying to move it everywhere. Antiparticle of the pi plus meson. And we have the breakup here. It's pi plus equals u anti down. There we go. So then I don't need to worry about these over here. So we'll just ignore those. So what's the quark content of the antiparticle of the pi plus? Well, you're told that the pi plus is up, anti down. So because of that, the antiparticle of this, you see that? It would be called a, in this case right here, I would call it a pi minus. It would have a minus charge. And let's see what that would be made of. Well, it would be the antiparticle here. So it would just be an anti up and a down. I'm just trying to get you used to this. This is really simple, right? Let's do the baryon number, strangeness, and electric charge for this particle. Anti-strange, anti-strange, anti-strange. Let's look at that. So baryon number of an anti-strange. Let's see. Well, the strange is 1/3. So the baryon number will be minus 1/3. So let's see here. So for baryon number, it'll be minus 1/3, minus 1/3, minus 1/3. So in that case right here, it'll be minus 3/3. So baryon number will be minus 1. All right. Then we have strangeness. Let's see how strangeness works. Well, remember strangeness, you can look it up right here. You don't have to memorize it. Strangeness is, let's see, strange quarks have a strangeness of -1. Does it make sense then that anti-strange will have a +1? So because we have 3 anti-stranges here, it'll be +1, +1, +1. So in other words, the strangeness number will be 3. Seems weird, but you can just calculate these things. What about the charge? Well, we have 3 anti-stranges. Let's see. Well, the charge of a strange is minus 1/3 e. So I'm going to have, as the anti-strange will have plus 1/3 e, won't it? So it'll be charge will be 1/3 e plus 1/3 e plus 1/3 e, which is 3/3 e, which is just e. So I hope that right there made sense to you. This is how I can solve these. And I have a final question for you right here. So we have a positive pion. So we're told this pi plus here. It's a meson consisting of an up quark and an anti-down quark. Can you see we have it right here? We're given that. Now a student suggests that the decay of this thing is represented by the following. So pi plus, and remember the pi plus is really made of an up anti-down here, leads to this particle right here plus that particle right there, right? I'm just rewriting with a u anti-down. And they say, is this possible? If not, what's violated? So let's look if we can figure this out. So let's see if we can look at maybe charge. I'm just going to maybe suggest that we sort of look up all 4 of these things here, just to be safe right here. So let's do, we can do charge, we can do baryon number, we can look at, lepton number, and we'll look at strangeness. Let's look at all of these, just to be sure we know how to do this. It's good practice, I think. So this right here, we have to look at the left side versus the right side. What's the charge of an up? You have to look it up over here. So charge of an up is 2/3 e, and an anti-down is going to be 1/3 e, right? Because it's opposite of this. So up anti-down is going to be 2/3 e plus 1/3 e. All right. So charge will be 2/3 e plus 1/3 e. So that should give me 1 e. That's on the left side. We have to look at the right side. The right side is an anti-mu particle. Let's see what that is. That's see, because it was a mu plus. Remember, mu normally has a minus. So the mu plus actually has a charge of plus 1 e. So we look at that. So here we have a plus 1 e. And of course, the neutrino has no charge. So look at this. See this right here? It's conserved. It's the same left and right. Let's look at the baryon number for this. Up has a baryon number of 1/3. And an anti-down has a baryon number of minus 1/3. So that gives me a baryon number of 0. Let's see if that's the same as on the right side. This right here is a lepton. So that has a baryon number of 0. And this is a lepton as well. So look, this is conserved. Let's look at lepton number though. Let's look at this. So the left side here, the up anti-down, well, they're both baryons. They're both quarks. And quarks have a lepton number of 0. So the left side is 0. The right side, let's look at this. We have an antiparticle. Remember, this is normal particle is mu minus. That's the regular particle. So this one right here, this mu plus, is actually an anti. This is really the important thing right here, I think. This is actually an antiparticle we're looking at right here. So the antiparticle, let's see what its lepton number is. Remember, leptons have lepton number of 1, except for anti-leptons have a lepton number of -1. So let's look at this. So that means this one right here will have a lepton number of -1. And this anti-mu neutrino, let's see what that one has. A mu neutrino will have a lepton number of 1. But because it's an anti-mu neutrino, it'll have a lepton number of -1. Therefore, look carefully here. That means here we have -1, -1. So do we have 0 equaling -2? Nope. This is violated. That means we know, is this possible? We could say no. Why not? Which quantity is violated? Lepton number is violated. By the way, we look at strangeness, but the thing is there's no strange quarks anywhere here. So because the strangeness equals 0 both sides. So we have 0 equals 0. So that's why those are not violated. Because there's no strangeness going on. There's no strange particles. So you can see which one is violated. That's because this is impossible. And if you look at it, it's because we have an antiparticle plus an antiparticle. That's the problem. See? So this is how you can sort of take a look and see if something is actually allowed to happen. Just be really, really careful and look at your conservation and check for charge, baryon, lepton, and strangeness. Well done for getting so far within particle physics. Not giving up yet. So now we're going to talk about the fundamental forces and bosons. So when an interaction occurs, there's particles that mediate the interaction. And this is the kind of weird part here. Whenever you have particles sort of playing with other particles, so to speak, you have these fundamental forces involved. And there's 4 main fundamental forces, and this is actually from your data booklet. So we've got the 4 main fundamental forces, which are right here. There's the gravitational, there's weak, there's electromagnetic, and there's strong. The strong one is the one that's a short range, but it's the one that's involving the nucleus, actually. This one right here is a really important one here. This is the one actually keeping the nucleus together. Because, I mean, if you think about it, inside the nucleus there's a bunch of neutrons. Charge-wise, they don't do anything. But the protons, they're going to repel, aren't they? We say there's a Coulomb repulsion. Because if you have a bunch of protons in the center, in the nucleus, protons all have positive charge, and the positive charges repel. So there is a Coulomb repulsion, because of their charge. So, you might say, oh, that means that the atom should be falling apart because the nucleus shouldn't be stable. However, there's a much stronger force that's winning big time. That's why that's called a strong nuclear force. It's right in the very center of the, the nucleus here. So this is the very, very strong one. It keeps everything together. It way overpowers the Coulomb force. We've got electromagnetic. This is anything to do with photons. We're going to talk about this in a second. And then we've also got something called the weak force. This is something that sort of it involves these lighter particles. And then we've got gravitational, so anything to do with mass. Then we've got all the particles that experience this. Now we're going to say that we've got particles mediating this, and this is what's really important here. You've got different particles, and I think a way to explain it is a brilliant physics teacher that I know. His name is Ivan. He's teaching at Avogadro Gymnasium in Denmark. Absolutely brilliant guy, and he actually explained it in a really neat way. I love how he explained this. He saw these particles mediating almost like having a wingman. Like, if you're going to go date someone, let's say I see, I don't know, a girl or boy, somebody across the hall, and I'm too shy to go talk to them. So rather than me go interact directly with them, I would send my wingman or wingwoman, so to speak. So I'd send someone, my wingman, to go and talk to them, to help to mediate this interaction. So I need one of these helper particles. I'm going to call it a wingman. So you've got different wingman particles here, okay? So your wingmen, those are the gravitons, those are these particles here, we'll talk about in a second, and these ones. These are your sort of wingmen. That means that when you want to have an interaction, you have to send your wingman over to help you with that interaction. And that wingman can do a couple of things, right? They can just go and do what you ask them to do. maybe they sort of talk you up. So this explanation could be taking, you know, a step further, and maybe they, you know, are really positive to talk about you. Like, oh, you shouldn't date that Mitch guy. He's really terrible. You should date me instead. If the wingman said that, that's a pretty negative sort of effect, right? So they've affected the outcome. Whereas they could be really positive. Hey, you should really talk to that Mitch guy. He's really nice. Da, da, da. So in that sort of analogy sense, how a wingman can affect the outcome, one of these wingman particles, these are called these bosons, okay? And in fact, they're often called gauge bosons. So these here are your different bosons. These are your wingman particle. There's these ones, these ones, these ones, and these ones. So first of all, we have particles that are involved in the electromagnetic forces. So things to do with electricity and magnetism. So in this sense, the wingman is a photon. That's just called a photon. So that's a nice, easy one. Then for the weak interaction, we've got these different kinds of bosons. We call them W plus, W minus, and Z. This should be a W. They should have actually had a W minus here. Should be a minus here. So we have a W plus, a W minus, and a Z, which is neutral. So if you think about it, these ones have to do with charge. So the Z has no charge involved with it. The W minus has a negative charge, and the W plus has a positive charge. So this is how these ones work. They mediate this weak interaction. Like I said, those will be like lighter particles, things like quarks and leptons. So to be honest, when we're drawing these things later called Feynman diagrams, they're mostly going to be relating to these ones. However, we can also do them with these. So these are your W plus, W minus. That's why I put them right here. So W plus and minus are called the W bosons. Then you got your Z0, that's a Z boson. You've got your photon, right? That's another kind of boson. Now we've got something that's really fun. The things holding the nucleus together are called gluons. Those are things that are gluing the nucleus together. I love that name, gluon. And then we've got these other particles called gravitons. And these aren't quite we're not quite sure about gravitons yet. I mean, theoretically they should be there, but it's really hard to actually detect them. So I didn't put them here because we're not quite sure about them. We should find them. You know, if there's particles meeting, we should find gravitons. So these are what are called the four main bosons. These are going to be your wingmen, right? So I'm going to call it that. So these are your wingman particles. So if you're going to help mediate an interaction, you need one of these helper particles, either this, this, or this. And the main ones you're really going to be looking at are, actually, especially these and these. These will be the main ones we're really going to look at. Now we have an even more important thing, but also newer and a little bit less known, is the things called the Higgs boson. So Higgs actually predicted this quite a long time ago. He predicted that, well, if this, what's called a standard model, if that's the case, then there should be a particle that's responsible for mass, for everything. It's been nicknamed the God particle because it's how everything gets mass. And we have something called the Higgs field, and as you pass through the Higgs field, that's sort of how you have mass to carry you around. It's not so simple. And luckily for the IB, you don't have to know the Higgs boson in detail because, to be honest, we don't know it in detail. Good news, it was discovered just a couple years ago, so it was for sure confirmed. A big part of the reason for the existence for this Large Hadron Collider, this LHC as it's called, that's all about particle physics, isn't it? So it was all, a big part of it was to detect the Higgs boson, and luckily they found it. So that's why we've got the Higgs boson, which is responsible through these interactions for mass. And all of these have mass. All these particles do. So that's why I love this joke then. Right? This joke is a Higgs boson walks into a church. The priest says, hey, we don't allow Higgs bosons here. And the Higgs boson says, hey, but without me, you can't have mass. Ha, 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 ha. So yeah, there we go. So this is, I think, really important way to sort of look at it. I think now then we can represent all the different particles and everything we have. So this is like a final nice review of everything we've been looking at here. So again, let's put together here. We've got these things called quarks, right? And we can also call these right here, well, if we make things out of them, we call them hadrons. So we're going to put those there. And up here, we're going to have the leptons again. Okay, we're going to put those there. So I'm just going to repeat this. It's going to sound repetitive, but there's a reason. There's a method to my madness here. So we're going to have these different particles. We're going to have U, C, T, and D, S, B. Those are the different quarks, right? Up, charm, top, down, strange, and bottom. And remember, of course, we have the anti-versions of each. And remember for hadrons, hadrons are made of quarks. And remember the definition of a baryon, just to make sure you remember it. Baryon is made of 3 quarks. Good. So that's 3 quarks. So if you have 3 quarks, you're a baryon, and if you're made of quarks, of course, you're a hadron. And remember what a meson is? A meson is made of 2 quarks, where one is a quark, one is an antiquark. Finally, we have the leptons. Remember, we have the tau, we have mu, and we have the electron. I'll put little minus charges on them. So the little charge goes to the top right. We've got these different particles here. And of course, we've got the neutrino versions of each. So we've got the tau neutrino, the mu neutrino, and the electron neutrino. And those are all these particles. So now we've got all the leptons. What's interesting, you might wonder, like, what is the type of particle that's made of leptons? We haven't seen leptons make anything. They seem to hang around by themselves. So quarks can combine, right? 3 of them make baryons, 2 make mesons. But leptons don't combine. We don't have particles made of leptons. They're just leptons. They just fly around. Now, what I want to do now is put in these fundamental bosons here. So these ones right here, these main ones are here that we're going to use. So we'll talk about the gluon, which you write as a G. We could have the W plus. We can have the W minus. We can have the Z. We can also have the photon. These are the main ones here. Notice I've sort of put them around here because they can interact differently with different things. And then finally, so these are here, by the way. Those are your, we can write these are here. These are the bosons here. Right, these are the bosons in this ring. And then finally, in the very, very center, we have the sort of God particle. This is the Higgs. The Higgs is responsible. All these ones right here get mass in some way. They all interact. So this Higgs particle is right in the middle. And I like this representation. I think it shows these, as far as we know, here's all the particles. Here's everything you need to make everything in the universe, so far as we know. Unless we end up like splitting an electron into different particles, then everything changes and we redraw things and physics gets exciting. So this is why I really like this stuff. I think this is a nice way to represent everything, especially with these weird wingman particles, these bosons here, like the gluon, like the W plus, minus, Z, and the photon. Now comes my favorite part from particle physics, which is drawing Feynman diagrams. The reason I like them is, well, they come from my favorite physicist. I mean, if you could have a favorite physicist, I have one. His name is Richard Feynman. He was amazing. If you've never read the book, Surely You Must Be Joking, Mr. Feynman. I think it's Surely You're Joking, Mr. Feynman. He actually wrote it himself. It's totally crazy and awesome and really funny. There's no math in it. You don't have to get scared of that. It's just sort of written like, and then one time I did this, and then I did this. It's awesome. So he had a really good sense of humor, and he was looking at all these particles here and how it worked and trying to figure out the probabilities of things happening. He developed, it's almost like a game. That's why I said that here's the rules of the game. So it's going to make more sense here, this joke right here, because we have neutrinos first, then they say who's there, then they say knock knock, because some neutrinos go back in time, but they don't really. So it's sort of a play on that. So we're going to talk about the rules of the game here. We're going to consider left to right is going to be the time axis. Okay, so going that way, that's going to be time. But up or down, that's going to be sort of position or space or sort of x coordinates. We're going to talk about vertexes here, so vertices. We're going to have an arrow in and an arrow out. So for example, maybe I have an arrow coming in and then maybe an arrow coming out. So this here would be a vertex. That's what it's called. Now we've got quarks or leptons. Remember these basic particles from our sort of wheel of particles. Remember we learned this sort of wheel here, all the different quarks and leptons that go here, all the values that are on these outside here, the leptons and the quarks, they all go here. So any of these ones, they get solid lines. So an example could be an up quark, or I don't know, a electron. That's a lepton, right? So all these ones, they get solid lines. But exchange particles, remember, these are like your, I'll put it like this, these are your sort of wingman particles. Your wingman, like the W plus, the W minus, and the Z, those get curly lines. Oh, by the way, I forgot to also put in the photon as well. Okay, so plus the photon, so don't forget about that one. So for example, we could have something like, you know, that would be a photon. Or we could say a W plus, something like that. Wait, I shouldn't draw it that way. I should put it over here on the right. For example, a W plus. So there's lots of different particles that we could have. So just to show you. And then curly, that'll be a gluon. In case you need it, we actually draw it like this. That's a gluon. So this is how we'll draw these. Then we're going to have arrows from right to left. This is going to seem a little bit strange, okay? But if we draw arrows that are right to left, those are going to be antiparticles. So for example, if I had wanted to represent, for example, an electron, it'll be like this, see, left to right. But if I want the positron doing the same sort of thing, in order to make all these rules work, in order to conserve all these different properties we have to conserve, technically we put it to the left. Now, that does not mean it goes back in time. It's just to make all this work, okay? So really think about going to left to right. So still a positron doing something, because right is, time. So a positron still does something. It's just that you have to draw the arrow to the left instead. So any antiparticles, those are arrows from right to left. Seems backwards, but that's how you can have this situation where you have a neutrino. Well, it'll have to be an anti-neutrino technically. Let's say an anti-electron neutrino. It would move to the left. So since time goes that way, you could say, it looks like these neutrinos go back in time. That's why this joke. See, neutrinos, who's there? Knock, knock. It's like they went back in time. They didn't. That's just for Feynman diagram's sake. Now, whenever we have junctions, and here's the important rule, junctions have to be linked by a line representing the exchange particle. In other words, whenever you have a junction, like a vertex like this, you can have an arrow in, an arrow out, and finally you have to have an exchange particle, like a wingman. This is what we look for. So every time you have an interaction happening, you need to have a particle going in, like an arrow going in, an arrow going out of that junction, and you need to have a wingman. So you need to have either a photon or a W plus, W minus Z, or a gluon. This is the rules of the game. So let's see if we can do a few of these here. So try to draw the Feynman diagrams for these. So I'll help you out here. So we'll do some. Let's do an electron emitting a photon. Well, an electron starts off, so maybe I'll draw it going sort of down and right like this here. So I'll label it as E with a minus. That's an electron going that way. It emits a photon, but to conserve momentum, I'm going to draw it going back up like this. So it's almost like it's sort of like, it's going a certain direction and it sort of bounces the other way. Because remember, this is time, this is position. So it's like it's going down, and after this it goes up. Let's see, it's going up in that way. So now we have the rule. We have a look at this junction right here. We have an in arrow, we have an out arrow. That's good, but we need a wingman. We need a particle. And what kind of particle is it? In this case, it's a photon. So we've drawn this correctly. This is our Feynman diagram for an electron emitting a photon and still being an electron. We can do this when a positron emits a photon. Same sort of thing. We have a positron and emits a photon. So still going to be a positron here. And then we have the photon here. However, look at the arrows. I just want to get you practice with this. The arrow goes to the left because it's a positron. It's an antiparticle, and it's an antiparticle. Time still goes left to right, though. So still a positron, time goes to the right. So it's still a positron that still becomes a positron. It's just that the arrows go left, that's all. Maybe we can do this one here. A photon produces an electron and a positron pair. This is called pair production, and it's really exciting. This is the means by which you're probably here, because this is the means by which, after the Big Bang happened in the universe, we had all light. This is how you went from light to particles. How did light turn into solid matter? Here's how. Watch this. This here was actually just predicted just by drawing Feynman diagrams. So we have a photon. Let's say I just draw it to the right, so I'll label it photon. And now it makes an electron and a positron. Well, what's an electron? It's a solid particle because it's a solid line, because it's a regular matter. But I have a positron. Remember what a positron is? It's the antiparticle of an electron. So because of that, it goes that way. Look at this junction. See, it still follows this rule. At this junction, I have an in arrow, an out arrow, and a photon. So actually, I've got this. This is actually true. Isn't this kind of wild? This is like a photon can actually, think about it. You have light just following along. All of a sudden, it spontaneously makes electron and a positron. But keep in mind, though, this is dangerous because an electron and a positron, guess what they can do? They can meet, boom, they make photons. So that's actually called annihilation. You can draw that Feynman diagram. Right? And that would be really easy, wouldn't it? Wouldn't it be just this right here, electron? You'd have a positron. They come in, left to right here, and they would meet and make a photon. That's called annihilation. So, you can have all these different things possible, okay? You just have to get used to drawing Feynman diagrams. Here's a harder one. It's called beta minus decay, and this is one you should know, that in beta minus, a neutron becomes a proton. This is something you should know for beta minus decay. Okay, you should know this. Beta minus, neutron becomes a proton. This is the only thing you need to know in order to solve the whole thing. And don't worry about the pro tip, I'll show you that stuff later. So first of all, let's break up what is a neutron. A neutron is, let's see, remember the quark makeup of a neutron? It's up, down, down. It's like sort of neutral. And we've got a proton, which is up, up, down. So now the way we can draw this is a little bit of a different way of drawing it here, but let's just look at here. First of all, we have a down remains a down. Can you see like that down can stay to that down? I can maybe say that this up can stay with that up. But really importantly, can you see I'm going to have a down has to turn into an up. That's going to be the key part here. So what I'm going to do in order to draw this, I'm going to draw the up, down, down here. I'm going to draw the up staying to an up first. I'm going to put an up, and that's going to remain an up. So this is going to be really, really boring. An up is just going to remain an up. No problem there. That's this first up and this up here. I have to have a down remaining a down, so I'm going to put it here. A down remains a down. But here, I've just drawn them just in order to see what's going on here. Do you see how I had to have a down turning into an up? That's going to be the interesting one. How does this one turn into this one? How does that happen? This is the important one. How did a down turn into an up? The reason I like doing it this way is because can you see you can combine these ones right here together and you can say that is the neutron. See, the up, down, down is the neutron. Whereas the up, up, down, because remember the order doesn't matter, that is a proton. So the whole idea is how did a neutron turn into a proton? Look at the quarks. You only had to change one of them. Do you notice this up stays to an up, this down stays a down. The important one, or the interesting one, is this down becomes an up. So what do we do here? Here's how we solve this. We can take a look at this down turning into an up and say, let's break down what happens here. This down has to have an interaction. Maybe the interaction will happen right here. So in order to have this happen, we need a wingman particle, don't we? We need some sort of particle here. And how do I figure out which particle it's going to be? Is it a photon? Is it a W plus, minus, Z? Here's my pro tip for you. You know which boson to use by checking the conservation at each step. So what I mean by that, this is going to be really important. Look carefully. I mean, we can ignore the up, up, and the down, down. We don't have to care about charge of those. Nothing changes. Look carefully at the charge of the down. The down one has a charge of minus 1/3 E. Can you see that? So I have to have a minus 1/3 E here everywhere. That means here it has to be 1/3 E. That's why I say left to right. So look, right here, the overall charge of this one is 1/3 E, minus 1/3. That means if I'm sort of scanning like sort of within time, let's say I'm just looking at like right here. What's going on right here? I've got an up. What is the charge of the up? It's 2/3 E. If I'm going to have 2/3 E become a minus 1/3 E, see I have to have that to being the total. What kind of particle could I put here? Do you see it if I had something that had a charge of minus 1 E? Can you see that that would be the same as minus 3/3 E? And look, if I have 2/3 E minus 3/3 E, that gives me minus 1/3 E. So this is what I have to have. I have to have a particle that has a charge of minus 1 E. And this is how I know that I have to have the W minus. Why did I need the W minus? Because I had to have a minus 1 charge. It's the only one of my wingman particles that has a charge of minus 1. So that's why I knew I had to use a W minus boson. See, it's in order to conserve charge. Remember, it's because as I'm scanning, let's say left to right, just this point in time right here. Right here, this point of time, I had a 2/3 E from the U, the up. Because see, this made, it was a down, then it made an up and a boson. So which boson do I have to have again? It's because in order for the 2/3 E to add up to something to make negative 1/3 E, I had to take away 1 whole E. See that? Because 2/3 minus 3/3 is minus 1/3. That's why I knew I had the W minus here. And finally then, we can look at the final step here. It's a nice easy one. What is made? Well, hopefully you can figure that out. Let's see, what do we have to make here? We end up actually, remember it's beta minus, so beta minus, we know it's an electron. So I know I have to make an electron. And if I have an electron, remember what I have to make? Do you remember what you always have? When you have electrons, you always have an anti-electron neutrino, which means goes to the left. Let's look at the charge to the right. Let's look at what this charge is. over here, just to make sure we have everything conserved. Look at the charge here. The U has a charge of 2/3 E. The electron, because remember now we no longer have this W minus boson. This electron has a charge of, oh yeah, -1 E. That's the electron's charge. And the neutrino has no charge. And what's 2/3 E minus 1/3 E? Remember what that adds up to? -1/3 E. Sorry, it's 2/3 E minus 1 E, which is the same thing as saying -3/3 E. That's a fraction. Did you see how charge was conserved here? This is the key part. I think that's the not trivial part, is charge is conserved, here it's conserved, and here it's conserved. That's how you know which particles you had to make. So that's how you can do a hard example of beta minus decay. Now it's time for more fun with Feynman diagrams. I like that meme there. Want to know why they call me Feynman? Because I'm fine, man. So I want to show you something that's actually pretty interesting. It's not necessary for the IB, but it's really good practice, I think, to do this. I'm going to then give you a question that then is good practice. Okay, so we'll figure all this out. So first, just a little bit of fun with it. I want you to start with an electron emitting a photon. We're going to draw the Feynman diagram for it. After that, we're going to rotate it. We're going to rotate, in this case here, counterclockwise by 90 degrees, and then we'll take that and rotate that answer. So just to see what you can do with these things, you can actually rotate them all the way. But let's just do it once, twice. So we'll start off by just doing that. We'll see how it goes. So we'll start with an electron. I'm going to draw an electron, remember, with a positive, not positive, but a solid line. So there's my electron. I'll label it E. There we go. Negative charge, but it's a regular particle. And it emits a photon, so that means I'm still going to have my electron, except now I have my photon. This is my Feynman diagram. Remember, left to right is time. This is electron coming in, still making an electron, except it also makes a photon. There we go. Now let's take this now and rotate it counterclockwise. So what I mean by that is, imagine this whole thing now. Just imagine it rotated that way by 90 degrees. So can you imagine doing that with this right here? That means I have to take this E right here, and this ends up going to the left like this. It ends up like this. Except, watch very carefully though, this one here, which was an arrow kind of pointing to the right, now it ends up, if you think about it, it's sort of, look, it starts off like this, like, and then what it does, of course, it rotates 90 degrees, it goes that way, it points that way. That means it's going to be that way. This right here, let's say this one right here, it ends up going sort of down like this right here, so that means it's like this. Ends up making that one, and of course then I have this one right here, which is still a photon that it makes. So this right here is still making a photon. So what is this doing? This is, let's see, what's an arrow that's to the left called? It's no longer an electron. That's a positron. And this right here is an electron. So can you see, actually this is annihilation. This is a pair annihilation. So do you notice, by the way, if you took this thing right here, and you could, of course, you could work out all the conservation rules. So you can say, for example, that the charge of this thing right here is a positive. And if you look at the charge, and look, the charge of a electron is -1. The charge of a positron then is +1. So if you look at this and the charge is conserved, you can do the same thing with all the other quantities. But I think it's really fun to show that you start with electron emitting a photon, you rotate it 90 degrees, you end up with a whole other thing called annihilation. And what if I take that then and rotate it another 90 degrees? It might seem a little bit weird, but then I'm going to end up with, let's see, this thing is going to go that way. I'm going to have this one right here, a photon, and I'm going to have that one right there will go like this. It'll be that way. So this right here, I've got, of course my photon has to go to the right though. So what does this mean? I've got a photon, I've got an arrow going to the left, so that's a positron, and I've got another positron. What is this? This is, you could call this positron scattering. In other words, if you look at this, you could see that it's a positron, remember, going to the right, so right is time, so right is time. It's a positron going in time, and what happens is a positron meets a photon. It's like a photon bounces that positron. Imagine you're a positron just driving along, all of a sudden a photon hits you like bang, so it makes you sort of change direction. So that's actually a positron scattering. Just trying to show you, you could then take this thing, of course, and you could rotate it again, and you could rotate it again, and hopefully then you'll end up back the way you are. I think it's just kind of fun to take these things and rotate them. So that's one fun thing to do with Feynman diagrams. Let's now reward you by doing an exam question here. So it's not at all related to this. I just thought it was a neat thing you can do to rotate the Feynman diagrams. But you can still good practice to try to figure out how to draw them. Let's actually do this exam question though. Draw the Feynman diagram for pion decay. Luckily you're told what's going on. So you have a pi plus becomes an mu neutrino and a mu plus. The key thing to remember though is this right here, mu plus. Remember, look, normally the regular particle of a mu is a negative charge. In other words, that regular mu particle has a negative charge. So if we're talking about a mu plus, what that really means, this is the antiparticle of a mu. And remember what this is. This pi plus, well, you don't have to remember it. You look it up, and they will tell you this in this case. So it's u anti-down. So what we're going to do, we're going to try to draw this as a Feynman diagram. So I need to draw u and an anti-down. How do I draw that? I'm going to start off by using a sort of neutron and proton trick. I'm going to put this together. So I'm going to have a u coming in, let's just say. And I'm going to have an anti-down coming in as well. So these two things are going to meet. But remember, it's antiparticle, so the arrow has to go left. This is my anti-down. What I like to do then is you can take this and say, this together is called the pi plus. So do you see how you can see that initially you have the pi plus, but I like this kind of notation because then you break it down into its quarks to really figure out what goes on. And what's going to happen then? Well, we have to figure out then what's going on here. We're going to have a wingman particle here. We're going to have some sort of boson here. And let's see what kind of boson we need. Remember this trick about looking for conservation here? So let's look at the charge of each of these things here. So what's the charge of the up? The up has a charge of 2/3 e. Then the anti-down, let's see, well, down normally has a minus 1/3 e, so the anti-down has a charge of 1/3 e. Right, and if I look at that, then what does that give me? That gives me 3/3 e, so that gives me 1 e. So this is my charge on my left side. That means if I'm going to have just this, you remember you have to sort of scan from left to right. What if I sort of move my little scanning thing to right exactly this point in time right here? At this point in time, there's only one particle, and it better have a charge of 1e. Do you know a boson that has a charge of 1e? I hope you do. It's the W plus. That has a charge of positive 1e. That's how you know you have the W plus boson. And now what do we do? Well, now we're going to have these two particles here. So let's try to draw those. Do you see how I just work it out just logically? Then I'm going to have, let's see, a particle goes off this way. Which particle is that? That's this one right here. This is the mu neutrino. It's a regular particle though, so it's arrow going to the right. However, this mu plus is technically an anti-mu. So that means I can draw it like this, or I can draw it, I can draw it like that as well. It depends which format you like. I can draw it like that. But that has an arrow to the left. And remember, it still goes right in time. Let's double check that charge is conserved here, right? So let's just see. So here we had a charge of 1e, so that's why this was okay. What if I look at direct right here? So it's like we're scanning left to right. So over here was that. Over here was in the middle. That's how we knew it had to be 1e. Let's conserve charge here. Neutrinos have no charge, no problem there. And what's a mu plus? Well, it's the antiparticle of the muon. And the muon has a charge of minus 1e. So that means the antiparticle of it must have a charge of plus 1e. Good news. Charge is conserved everywhere. So that's how I know I've done this Feynman diagram right. Isn't that awesome? So this is how you can learn how to actually draw Feynman diagrams of things you don't even know what happens. Just follow the rules, knowing that you have to have a vertex, you have to have a wingman particle. Then I think it's really nice to sort of scan from left to right, so that way you can see which wingman do you have to use, which boson do you have to use. If, by the way, you had no charge, then it would be a Z, right? If you had no charge needed. So you can sort of take a look at what it is that you need to do. This is a good trick, I think. So I hope this helps. Sankey diagrams and energy density are things that are important for exams but are actually not very hard. That's the good news. So for the Sankey diagrams themselves, let's take a look at this and see if we can figure this out. Usually they're drawn like this sort of, structure that sort of comes in, and then you've got some arrows that go out and arrows that go out like this. And what this normally represents, see these width of the arrows, that's the power or the energy. So however wide these ones are, so for example, this width right here, that will tell you actually we could see the energy in, we could say. This could be in joules or whatever. And this one right here then, this here will be what we call the useful energy out. This is what's going to be really important here. Remember, this could also be power or whatever. And this right here, the width of this one right here, that tells you about the losses. So these losses could be due to heat, it could be due to friction, it could be due to lots of other wasteful things. So basically, as long as you know sort of the energy coming in, and you can look at all the energy that was lost and then versus the useful energy out. And so I've got a little example here that I've sort of cut and paste here. So we had the energy input, for example, is 20 little squares. It doesn't even matter what units those were. Let's just say this here was 20 in. So let's just say that was 20. And let's say then this one here, the useful energy out was 6. And then of course we wasted, those have to add up. So this here, for example, will be 14. Let's just say those were the numbers that we'd put in. If we'd put those in, you can say, well, what's the efficiency? This is something that we need to know for Sankey diagrams. This is a way to draw these processes and look at where the energy goes. And the efficiency in this case then is the useful output over the total input. So I hope that makes sense. It's what you get out. So in this case it would be 6 over 20. That's why they put it right here. So that's why it, of course, it would reduce, but you can just do it on a calculator. You get 0.3. So in other words, this particular situation here is only 30% efficient. That's really all there is to Sankey diagrams. They show up often enough, but they're actually really easy. You just got to know efficiency is useful output over total input. In other words, and this could be energy, could be power, could be whatever. All right. Next, we've got energy density. I really like this one. It's energy density is just the energy released divided by the mass of the fuel used. So I love this one here. This is again from xkcd.com. This is a great one here. So if you go there, this is one of the many, many pictures he did. So yeah, like the science tip, log scales are for quitters who can't find enough paper to make their points properly. Because if we look at the fuel energy density, okay, if we look at megajoules per kilogram, do you see? Energy density is all about the energy released per mass used. It's a way to compare different energy sources. So if you look at, how much joules do you get versus how many kilograms do you need of this material or whatever to do it. And that's why you have like sugar is 19 megajoules for every kilogram. And you have, although to like fat, you have coal, fat, gasoline. This is why we use gasoline a lot of the times, because it's more energy dense. The only problem is it's obviously a limited resource, but it's easy to get at. Well, relatively easy. The reason why we use nuclear power is because, uranium, for example, is 76 million megajoules per kilogram. So you could just say, obviously, it's many orders of magnitude. I love how they got like the paper all stacked like this. So basically, this is actually why we use uranium. It's because it's very energy dense. Of course, it has its own issues, like what do you do with some of the fuel after you're done with it, and some of the sort of... the waste products of this have to be well taken care of, but you get so much more energy per kilogram. So this is actually why we use it. So different materials have different energy densities, and surprisingly, that's kind of all you need from this. So this video is done. See ya. Renewable energy, I'm a big fan. How to generate electricity is something that you could be asked for on exams as far as a qualitative idea. They don't really do so much quantitative here. So it's important just to understand the general concept here. That's why I'm going to go over this. So first of all, how do we actually get electricity? How do you actually get it? Well, first you need an energy source. So maybe I'll put that in. So I'll say energy source here. And if we do the energy source, there are lots of different sources of energies, right? There's steam, obviously that's just heating up water. There's fossil fuels like coal or whatever, you just sort of shovel it in there. Again, you heat it up. So this will be in the form of sort of, you're going to heat things up, so will this. Turns out nuclear, although it sounds really complicated, you're just using it for its heat. Wind power, there you're just going to actually, that's just going to be kinetic energy, so EK. Wave power is also going to be kinetic because you're going to turn some sort of fan, and hydroelectric is also going to be kinetic. Well, it's not exactly true because they're all kind of kinetic, in fact, because what ends up happening is, in all of these cases, the goal is to turn a turbine. What a turbine is, just imagine a wheel, with some sort of spokes on a wheel or something like that, and at the end you just put some magnets. This is all you need to do is have magnets. Oops, not magnetics. Magnets. So over here too, and over here too, and over here too. Basically wherever you want here, you just put magnets on the end. And what you do is, as long as they're rotating, that's what this idea of turning a turbine. So somehow you have to turn a wheel. And the reason is, well, in physics SL, you don't really need to know the exact reason, but in HL you do. It's actually called Faraday's law. And it turns out, I may as well just explain it very, very briefly here, because I think it's a shame not to learn how the idea works. Is that, imagine around a magnet, let's just say you have a north, south right here. You got these magnetic field lines. Remember we were learning how to draw them in another chapter, right? So we've got all these magnetic field lines here. And what happens is this: if you have a material, and let's just say I have a coil of wire right here that's being wrapped around this material here, and this right here could go to, I don't know, whatever. It could be a light bulb in this case. But it could just be attached to a light bulb. This is the idea, is that as long as you have magnetic field lines that are crossing this object, we call that magnetic flux linkage, it turns out. But as long as you have these, imagine these magnetic field lines, and imagine that they're crossing this material here. In this case, this little coil of wire that's wrapped around a piece of metal. There's no battery needed in that one. What happens is this: as you have the magnet and it's sitting right there near that coil, if the magnet's not moving, sure, you have these flux lines that are crossing it, but they're not changing, so actually nothing happens. But what happens is this: if you move the magnet around, it doesn't matter how you move it, as long as it moves in some way, then it turns out you induce an EMF. In other words, you induce electricity to flow. This is actually called Faraday's law. It turns out it's formally defined as what we say: the induced EMF is proportional to the rate of change of magnetic flux linkage. Although that sounds really complicated, what it really means is if you have these flux lines that are crossing and changing as they're crossing this object, in this case this coil of wire, as long as they're changing, you're going to induce a current to flow. And then in HL, we learned that if you want to know which direction it flows, you apply Lenz's law, which tells you that it'll flow in a way to oppose the current, oppose the motion in some way. So the idea is this then. Imagine, a simple example is on my bike. For example, I actually have this installed on my own bicycle. So if you imagine on the front wheel of my bike right here, this is the, the fork. You'll see I'm not a very good artist. And I've got my front wheel like this right here. And attached to it, I've got this little coil of wire, basically. So inside, this is basically, it's got a little light right here. And basically I've just got it attached there. And it's just like this. It's just a coil of wire wrapped around probably a metal, maybe like iron or something like that. It doesn't have a battery in it though. What happens is this. Attached to this, I've actually attached some magnets to my spokes. So imagine I've got a magnet here, and a magnet here, and a magnet here, and then one that passes right by it right here. Of course I've drawn it poorly, but you get the idea, I think. Actually, I'll draw it further out then. It crosses like this. What'll happen is this: as those magnets pass by this little thing, do you see those magnets are going to end up making this changing, you could say this changing magnetic flux lines here. So we're going to change the magnetic flux linkage, as it's called. But basically the simplistic idea is moving magnets create electricity. But this is the process by which it does it. And it turns out that is what gets you electricity. So all of these ones are just about turning a turbine in order to generate electricity. So all of these actually do this step right here. So think about this. For steam, what do? You heat up some water. It turns into a gas. That gas is going to basically be sent in through a pressurized tube. And it's got a little wheel at the end, like a little paddle wheel. And imagine you turn that wheel. Guess what the wheel has on it? Magnets. And those are attached to something like this. You get electricity. Fossil fuel, what do you do there? You heat, and oftentimes you heat up steam. So the idea is that the fossil fuel is the process that you're going to use to actually heat up the steam. Then you heat up the steam again, pass that steam through a pipe, turn a wheel, there you go. Nuclear sounds really complicated, and it is, the process by which you sort of control this reaction, but it's just being used for heat. You're just heating up water. Again, you pass a tube of water above all this heat, and that water turns into steam. That steam turns a turbine with magnets on it. Then you get electricity. Wind, however, is slightly different. There you have the wind itself is actually coming in here and it's actually impacting these little blades here. Of course, the wind is going to sort of, deflect that way. And because of Newton's third law, that means that it's going to make this thing want to turn. So, as the wind goes down, it's going to push this blade up. And it continues like that. So basically the blades end up turning. Guess what's attached somehow to this? You just threw some gears or something like that. But basically, your whole reason is you're going to turn this thing. Guess what attached to this? Magnets. Magnets turn and you get electricity. Waves, same idea. You could have waves themselves coming in and turning a turbine. It could also be tides. But again, the idea is the same. And finally, you have hydroelectric. And you might think, oh, that's really complicated, right? No, you just harness the power of water. So if you have water flowing down, for example, through a pipe, guess what you attach at the end of that pipe? A wheel. And that wheel turns, has magnets on it. You generate electricity. It's really that easy. So that's really all you need to know from this. As far as nuclear energy goes, I love this picture here, nuclear lunch detected instead of a launch, right? It looks like a mushroom cloud like from nuclear explosions, but it's really just, I think, a pizza that imploded. Awesome. But if we look at this nuclear energy, here's what's really going on here. We'll go a little bit more detail into this. Again, remember we had nuclear energy, which turned into thermal, which turns into kinetic, and again, that's going to turn a turbine. This is the idea here. So let's talk about what's going to happen. First of all, you have nuclear energy. In this case right here, you can actually dig this stuff from the ground. You can actually, do a big digging project, depending on where you look, and you can find a whole bunch of uranium in the ground. Now, the kind of uranium you get in the ground, you tend to get uranium-238, but there's a small proportion of it that's 235. And this is one of the magic kinds that you can use, for example. Of course, it's a very difficult process to actually, what we call enrich. What you have to do is through some really interesting processes, either through some really caustic, terrible chemicals to sort of leach away the 238 from the 235. You basically want to split up the different versions. You can use centrifuges, for example, because as you spin around, the heavier ones will be more on one end and then the lighter ones. So you can use centrifuges to do this. We call this enrichment of uranium. But it turns out you need this uranium-235. So the reaction that happens, there's lots of them. Just keep in mind there's really a whole bunch of them. This is just one of them. But let's just say you have uranium-235 and you add to it, for example, one neutron. Now neutron is 0 here at the bottom because it has no protons. A neutron has just one neutron plus proton because it has a neutron. This, for example, becomes lots of stuff. It could be lots of things like barium barium. There's a lot of other things plus a lot of other things. But very often you end up with, let's say, 2 neutrons. And of course, plus energy, because whenever you do this, remember, anytime you're building new elements, you're assembling them from their constituent particles, you end up with this released energy because some of the mass goes missing. Remember, we learned about this E equals mc squared business, right? This missing mass gets converted to energy. So you end up with energy, which is great, but you also end up with neutrons. So just imagine this then. So you do this reaction here, you get nuclear energy. So you convert nuclear into thermal. Why is that? That's this energy right here that came in. This extra energy is going to be in the form of heat, also light and other things, but mostly it's going to be temperature. So that's why it's thermal energy. It's going to increase the kinetic energy of the molecules. Now, what you do with that thermal energy, you often run water pipes above it. So imagine then you've just got this area that's really, really hot. You pass above it some pipes that just have water in it. And of course, what do you do then? You heat that water in order to, in this case here, pass it through a little pipe. You make it steam. And again, like we talked about, that will turn a turbine and that will end up giving you the energy that you needed. So this is sort of the process that happens. Interestingly enough, though, if you really sort of zoom in a little bit, these fuel rods, which will contain uranium-235 and other things, the way to basically start the reaction, look, you have to kick in a neutron. So imagine then you have your imagine just like a neutron gun just sitting here. You want to start the reaction, so you throw a neutron into here, pew, and what will happen, of course, it'll create this reaction. We call it a chain reaction because, watch this, you start off with uranium-235 plus a neutron. You get some energy, of course, that was the point of it. But you also get, let's say, 2, maybe 3 neutrons from the reaction. Each of those neutrons can then in turn, imagine then, maybe they can fire off and start off something over here, or maybe fire off something within this. So imagine you start with 1 neutron on uranium, you end up with 2 neutrons, and then you end up with 4, and then 8. It goes up really fast. That's what we call a chain reaction. Now, if you want to control this reaction, like in a reactor, you don't want to blow up the whole thing. If you want to make a nuclear bomb, of course, that's the goal, is to make an uncontrolled chain reaction. Just let it happen. In fact, throw things to multiply it. Like you can do things like, there's all sorts of crazy reactions, but it turns out with the new ones, if you had tritium and some of these other things, it's almost like a multiplier effect for these bombs. Those are for fusion, fusion. So it turns out in this reaction right here, fission, we want to control it, right? We want to try to not blow everything up. So what do? We have these control rods. They're usually made of things like carbon, things that are going to absorb the neutrons. And the reason we want to absorb the neutrons again is to control them. Imagine this. If you have too much reaction going on, the temperature is going up too much, what do? Take your control rods and just throw them down within this. Can you see that? This way, neutrons from, within the fuel rods, they might be able to start these reactions, so it doesn't stop it immediately, but at least stops neutrons from flying into other control rods, other fuel rods. Can you imagine that if you have these control rods just slamming down in between everything, they're going to absorb the neutrons and basically control the reaction. So this is really what happens, and you have to be very careful in a reactor that you have really good safety measures. Basically, if anything looks weird, basically the controls should really be to just drop the control rods all the way down in order to stop the reaction. I mean, that should always be the sort of safety thing. Obviously, maybe if they get jammed or they can't go down, obviously that's going to be a problem. It's going to heat up too much, and bad things can happen, like in Chernobyl in the 80s. I remember when I was a little kid, we lived in Germany at the time, and when that had happened, basically the control rods didn't work. There were some other things going on too, but basically it got so hot, the core itself melted through its casing, and some of these really nasty byproducts of the reaction, they ended up going out into the sky and into the clouds, and that was really bad news. For anybody who lived in the area, of course, I think there was a town called Pripyat, I think it was called, that was really heavily affected. You can see really eerie videos of people biking around in the old town, because people just left, obviously. But I remember it affected me as a little kid because we lived in Germany. I remember they told us, because the winds had come west, I remember they told us we couldn't play outside in the sand for a while. They said we actually couldn't have cow milk because they were worried that the cows actually would have been infected. So there's all these weird things that even affected little old me as a little kiddo. Of course, it affected people in Russia in a very, very real way. But anyway, these control rods are really important for these reactions. Now, why do we actually bother doing this? And if they're dangerous, it's because the energy density is so crazy. It's so crazy high that you get so much sort of bang for your buck, kind of. You get so much energy for every kilogram, and that's why we use them. Even if they have their dangers and they have their challenges, certainly, we don't have anything with the energy density, and even close to it. So that's why we use them. I'm going to go over with you some important equations that show up on your formula booklet. You really need to know how to use these. I love this shirt, of course. Watt is the unit of power, because of course we know that power has units of watts. So that's why we use this. So power is measured in watts. And you get this equation here in this chapter, right? So you get power is energy over time. And remember though another unit for energy? Do you remember? Energy is... it's in joules mostly, and this here is seconds. So you could say power is also in joules per second. You could also say that. Okay, so power is really important. If you know the energy going on every second, then that is your power. That's your power in watts. So this actually works for any case. This one, however, you get this equation of power equals 1/2 a rho, that's a Greek letter, times v cubed. Now, you're not necessarily told what everything is, so what I think it's important to know is this one here is for wind. This is for wind energy. So this one here, what happens is this. Imagine you have a wind turbine. Maybe I should draw you one. Well, I'll try at least. I'm not very good at drawing, but here we go. Something like that. Of course, it's attached like this and has a big stand, right? So it's something like this on the ground here. You end up with some wind that's flying towards it. So maybe I have some wind. I'll put it maybe a different color here. You have some wind, and we're going to consider just like some sort of cylinder here of wind, because this is what we're really going to consider here. This wind then is going to be going, to the right here, basically impacting this thing. Can you see that this wind is the piece that's going to sort of impact this? So if we consider this, that's why we have a cross-sectional area of air. That's this. And remember how we find an area? A is equal to pi r squared. That's the radius then of this piece right here, this sort of tube of air that's sort of coming in. What would this be measured in then? What do you think? cross-sectional area should be in meters squared, shouldn't it? Because you have r squared. Density of air. It's going to depend on how dense the air is. And remember what density is? It's a mass over volume. So it's kilograms per meter cubed. That's what density is. It's a mass divided by volume. And then we've got the speed of the air. That's in meters per second. So really, you're going to use this equation to get the power of a wind turbine. We don't say windmill because usually a mill is reserved for selling, sort of grinding up mill and things like that, or to sort of grind up, I don't know, wheat or whatever you're grinding up. Here we mean a wind turbine because, again, remember, we want to turn a wheel, and that wheel is going to have magnets on it, and those magnets turning are going to create electricity if you have a coil of wire near it, through Faraday's law. So this is the idea behind wind energy, and this is the equation you need. So you might be asked for something like, what's the radius of this thing right here? So you could basically solve for r. You could be given power and ask for the speed of the air or the density or whichever. So usually you could just imagine, just use this equation and solve for one of these values. That's kind of it. Another important equation is this one right here. I is power over area. This is for solar. Solar means the sun. Right, so imagine then you have the sun over here that's actually shining here, and we're going to talk about the power of the star. That's an intrinsic property of the star itself. So because of that, this is the power of a star, so that's going to be measured in watts, or again, remember, it's in joules per second. Now we have the intensity of the radiation. I'll talk about that in just a second here. We also have the surface area of a sphere. I'd better explain these. So first we have the surface area of a sphere. It's because where we live on Earth, just say we're over here, we don't receive all of the sun's power. We only receive a fraction of it, because if you imagine its power, it's the sun's luminosity here, as we call it. The sun's power is emanating everywhere. We have to think about then what piece of a circle here do we get? In other words, what fraction do we get here on Earth? And the easy way to do it is you have to just think about the surface area of a sphere. Do you remember what the surface area of a sphere is? So SA. Sphere, it's 4 pi r squared. So this r then is the distance from us to that star. In this case, us to the sun. So this r is going to be the distance. I mean, in this example at least, distance to the star. In our case, it's the sun, so we put in the distance to the sun here. So that's going to be the surface area of a sphere. And do you remember what units we use for surface area? It should be meters squared. Then we have the intensity of the radiation. Well, let's look at this. If we want the intensity, what are the units of intensity? In case you're not sure, look at this. We have power over area. Power is in watts. Area is in meters squared. So we're going to say it's watts per meter squared. Now in astrophysics, we have a word for this intensity of the radiation. We call it apparent brightness, because it tells us how this star will appear from Earth. So this is what we can actually measure. See, the intensity is easy to measure. The power of a star is not so easy to get. If you think about it, you'd have to go there or know a lot about the star to know exactly how many joules per second it's sort of emitting. So that's really important. So I think this is the main equations you need to use. There's going to be some other ones for black bodies, and I'm going to make a separate video for those. See you there. I'm going to speak to you now about black bodies. Now, black body, it sounds like a weird term. It's not at all meant to be racist or anything. We're talking about black as in like perfectly dark, as in this. So we think that stars are black bodies. In other words, a black body is a perfect absorber or emitter of radiation. And you could be asked on an exam to literally say this definition. Okay, so a black body emits and absorbs radiation perfectly. And the reason why we can do this is that, well, stars behave like this. And you experience this if you have like, imagine you have like an old school oven. And, and your stove, So you have a stove, the element on the stove, if it's sort of round, metal-y thing like that. As it gets hotter, do you notice its temperature, its color changes? So that means as it gets hotter and hotter, do you notice it gets a little bit red? For example, we say it's red hot. We think, oh, that's really hot. Turns out actually that's not very hot at all. So we can talk about, for example, that red is actually cooler temperature. If you look at a candle flame, for example, you've got this one right here. Notice the very bottom of the candle flame where it's actually hottest is going to be bluer and whiter. Whereas the top, that'll be redder. So redder is cooler, blue is hotter. I just love this picture. I know it's photoshopped. I just the thought of this guy farting, making flames. I don't know why I like that so much. This is obviously photoshopped. I would guess it's probably like from a monster car, or one of these cars that has like flames shooting out of it or something, one of these jet engine cars. But either way, I just think it's hilarious. So let's actually talk about what it means to be a black body. See, we say that stars are black bodies because they behave like, for example, the element on your stove, which means if we can know the color of a star, then we can say that that star will have the same temperature as a stove element temperature would be at that color. So that's why we're going to define this thing we call T, which is going to be the temperature of a black body with a similar temperature. So what do I mean by that is sometimes we call this the effective temperature. Sometimes we call this the surface temperature. This is what we're going to mean. It's going to be in Kelvin. So let's first of all maybe look at what something right here might look like. So let's do something maybe that's sort of, we'll say hotter. So maybe we'll do something like this. And I'll try to draw you like a black body curve here. It's not going to be perfect, but something like this right here. So what it means that the intensity of the light is not just one wavelength, it's a whole spectrum of wavelengths. But do you see how there exists a wavelength to where there's a maximum intensity? We call that lambda max. Now watch out, it's a little bit misleading because you might think, oh, that's the maximum wavelength. No, it's the wavelength that gives you maximum intensity. I think it's better to call it a peak wavelength. It's the wavelength that gives you the peak intensity of light. So this would be for something that's sort of hotter, let's just say. So something that's why I drew it in bluish. And then maybe reddish, I'll draw something that's cooler. So watch very carefully. If we have an object that's a little bit cooler, something that's sort of like near the top here, it'll go more like this. So watch carefully what happens. The peak right here goes like this here, and then it goes down again. So what's the difference here? Notice what the peak did. The peak went to the right, didn't it? This maximum wavelength here shifted to larger wavelengths. Larger wavelengths are more red. So that's why this one here is going to be cooler. And do you notice also the peak went down? So this is something really important with black bodies. It's called Wien's displacement law, and you have this equation here that relates the maximum, like the wavelength where you get your peak intensity and the black body temperature of this star. So we could characterize this with objects at home, for example, or in the lab that are black bodies. We can find what we call the effective temperature. In other words, what temperature is that object when it's glowing at that color. Then we look at stars and say, all right, well, we can assume that stars are black bodies, so let's look at the color of that star, and from there we get the temperature. Now, some people think that, well, yeah, but the temperature of a star inside its core is millions of degrees. Yeah, sure. We're not counting that. We're saying the effective temperature, or what's called the black body temperature, or sometimes we say the surface temperature. We're basically saying it's the temperature that you'd have to heat up a black body to get that wavelength. So you say, well, the star has that same wavelength. Fine, it has the same temperature. So when we talk about the effective temperature or surface temperature of a star, this is what we mean. We mean the black body temperature here, and it's measured in Kelvin. Then we have this law called Stefan-Boltzmann's law, and that one is really nice. It goes like this. You get this one on your data booklet. It goes P equals, and it goes epsilon sigma a t to the power 4. And by the way, I forgot to put this. There's sigma there. So this is your equation. You get this. You don't have to memorize this. So what does this tell you? This tells you the power of the star. Remember, power is measured in watts or joules per second. All right, make sure we write that down. Emissivity is just a constant. So this one here you just look up. Usually, it's between 0 and 1. And usually, if you're not otherwise told, just make it 1 if you're not otherwise told. This one here, it's a lowercase Greek symbol. It's called sigma. One of my students once was like, the equation with the whistle in it? I was like, the whistle? I was like, oh yeah, it looks kind of like a whistle. Like if you imagine someone's here, blowing on a whistle. There's your lips, I guess. And you're just trying to blow on a whistle so that, it'll make like a noise, right? It looks like a whistle. I thought that was actually really funny. Like a really creepy guy that I just drew. I don't know what's going on with him. But anyway, we got this constant. It's called the Stefan-Boltzmann's constant. You can look it up. What is it? I think it's 5.67 times 10 to the minus 8. I remember because it goes 5, 6, 7, 8, kind of. Then we have a surface area of a sphere. This here will be, again, this will be the radius of the star. So remember how that goes. It's 4 pi r squared. So that'll be measured in meters squared. And we have a surface temperature. We're going to measure that in Kelvin. Again, that's going to be the effective temperature there. That's all we need to solve questions. So let's try it out. So we have a star has a peak wavelength of this. And so it's 500 nanometers, remember? Now, if it has a radius of 7 times 10 to the 8 meters, what's the energy radiated by the star in 1 second? And it might sound tough, like, what do I know about energy and seconds? But do you remember your equation for power? The key thing is to remember that power is energy over time. You got to remember that one. That's really important to know that power is energy over time. So do you notice they're asking for what's the energy radiated in 1 second? In other words, they want the energy over seconds. In other words, they want the power. So that's actually what we're looking for here. We actually want the power. So let's then maybe go hunting for an equation for power. And hey, we just learned one. So we'll put that one in there. So we'll say, all right, so we have the power. Maybe I'll put in green here. So now the power is going to be equal to the emissivity times sigma times AT to the power 4. This is what I need. I'm going to put in the numbers that I know. So emissivity, we'll assume it's 1. We're not otherwise told that. And this is 5.67 times 10 to the minus 8. That's great. A is the surface area of the star, so that we have to put in 4 pi r of the star squared. And we just have to put in the temperature to the power 4. And we even know the radius of the star, don't we? We know this value right here. So we can even go one step further and put that in. But here's the problem. Do we know the temperature of the star? We don't know it yet. So I just want you to see that this is how we can sort of hunt for the right values. We don't have the temperature of the star, but we can find it because they did tell us the peak wavelength. So remember we have another equation. Lambda max equals 2.9 times 10 to the minus 3 over t. So I'll put that in. All right, so I know that lambda max equals 2.9 times 10 to the minus 3 over t. This is in Kelvin. Therefore, I can say that t then is 2.9 times 10 to the minus 3 over lambda max, which is, in this case, 500 times 10 to the minus 9. I'm going to put that into my trusty calculator here. 2.9 times 10 to the minus 3. Divide that by 500, e minus 9. I end up with a temperature of roughly 5800 Kelvin, which is good because that should be the surface temperature of a sun. So I put in everything else here. So I said finally then the power is just going to be this 5.67 times 10 to the minus 8, because this is a 1 here, times 4 times pi times r squared. So I have to do 7 times 10 to the 8. Don't forget to square that. And I multiply all that by 5800 to the power 4. I got to be really, really careful. I'm going to start with a 7 times 10 to the 8 and square that just so I don't forget it. Multiply by 4 times pi. Multiply that by 5.67 times 10 to the minus 8. And multiply that by, in brackets, 5800 to the power of 4. I end up with a large number, of course, which is hopefully making sense. I get 3.95 times 10 to the 26 watts. I was really sloppy with how many significant figures I told you to use, but this is good enough. So you can say something like this. So you can say 3.95, let's just say, and this is about right. It should be around 10 to the 26 watts. So that's pretty close to what we should be getting here. So that's what we know for the sun, at least our own sun. So this is pretty good. So this is the power, which is the energy radiated in 1 second. Maybe we can do one more example here. We have a star. It emits a power per unit area, P. Remember now, right away, I think it's a good idea to write down the equation for power. Remember, its power is emissivity times sigma times AT to the 4th. What we're told here is the power per unit area. What does that mean? That means we're saying P over A. And we know that it's just this right here. It's emissivity times sigma times T to the 4th. So this is the general equation for it. Now what we have going on here, we have a new situation. Now the temperature is now 2T. So what I'd like to do is maybe I'll call that P2, over its area. And let's see, it'll be emissivity times sigma times T to the 4th, except this T changes to 2T to the 4th. And to see how what we can do then is we can divide these two equations, right? So we can say P2, of course, over A, divide that by P over A, and we have the two equations here. We can always divide them. Some people are a lot faster at doing this right here, and they can just skip steps. I'm just trying to show you all the different steps, just so you're sure where everything came from. You notice, by the way, the A's will cancel out, the E's cancel out, the sigmas cancel out. So I end up with P2 over P equals, and let's just check this out here. This is 2 to the power of 4. Well, 2 to the power of 2 is 4. 2 to the power of 3 is 8. That means 2 to the power of 4 must be 16. So we're going to say 16 t to the 4th over t to the 4th. And good news, those cancel out. So I end up with P2 equals, and I can put the P on top here, so it's 16P. This is, again, the IB loves these kind of ratio questions, these kind of questions where you have something changing. If you're really fast at doing them, just look at anything that you didn't change, those disappear, and all you really care about is the 2t. And keep in mind it was t to the 4th, so that's how you knew you had to do 2 to the 4. That's how you know it changes by that much. But that's it. That's how you can deal with some of this black body stuff. Albedo is something that shows up on exams enough to where it's worth speaking about. They often ask it for you more sort of qualitatively, just to describe it. Sometimes it shows up as quantitatively. We have to actually write an equation. But in this case right here, do a calculation. It's really pretty straightforward. It's albedo, first of all, it's the total scattered power over the total incident power. And we'll talk about that. I just like this one of Neil deGrasse Tyson here saying, maybe you should trust a scientist who spent years studying the subject instead of some neckbeard on the internet. These are one of these like climate change skeptics and people who don't think that this stuff is happening. It's absolutely happening. Come on. I mean, there's a lot of really natural processes that can, that are involved in this. So this isn't rocket science here. This isn't that complicated. So we have this thing that we define as the albedo, and this is on your formula booklets. You don't have to memorize this. It's the total scattered power over total incident power. Now you might be not sure, like, what does scattered mean? It means like reflected. So in this case right here, for example, this little diagram that I gave you, this is like the Earth here, and there's some clouds and whatever else. This right here, we could say this is the incident. So we could say this is the incident radiation, so we can call it power if we wanted to. This is joules per second or watts. This here would be what's out. This is what comes out, and this is the scattered power. Is this? So I mean, one other way to say it is you can say it's I out over I in. That's another way to look at it. Now it's the intensity of light that comes out versus the intensity of light that goes in. So this is one way to look at it. Now, what happens is this then, there's a lot of processes involved here in what actually causes the I out to be different than I in. Obviously, the sun's radiation comes in, and we have this atmosphere. It's like this blanket that keeps us warm. And the way by which it keeps us warm, because we have gases in there, those gases can absorb some of the infrared radiation. And of course, those then are re-radiated into the atmosphere, and so that warms the planet. It acts like a warming effect here, which in a way is good. Because without it, the Earth's temperature would be much, much lower. We probably couldn't have liquid water on it. But then as soon as we have the atmosphere, it warms us up. It also keeps pressure such that we could have liquid water. So all these things are actually really important. So the important thing that, as far as albedo is concerned, though, is just looking at what is scattered outwards. In other words, what is I out versus I in. And that's it. So try to think about this then, because a lot of times the IB questions you'll be asked on exams will be something like talking about what albedo would do, or you might be asked about, like, if a lot of glaciers melted, what would happen? So you need to think about first what albedo actually is and does. Keep in mind what a large albedo would be. For example, high albedo, like 1, for example, what does that mean? It means that I out is pretty much I in. In other words, if it was like albedo was 1, this would be, everything reflects back. So this would be like a surface where, imagine there's no atmosphere whatsoever, and it's just like a pure mirror. Then, everything that comes in is reflected out. So that means, you'd have 1 that reflects perfectly. Whereas if it was equals 0, what would that mean? It means nothing is going out. It means everything is going in, so it absorbs. Now, if we think about the color of things, it reflects, that means it's very white, right? If it absorbs things, whereas things that reflect things that absorb are usually very black, and literally in color. So if you see a surface, for example, like we can look out into space, and we can see that there's a lot of objects that are floating out there, things like asteroids and these other objects. And if they're very, very dark, they're very hard to see, aren't they? Because they won't really reflect much of the light. That's why they're actually hard to detect. So some of these objects that are, orbiting around the sun that might be of interest to us because maybe they'll hit us or something like that, they're a little bit hard to find because they might have a very low albedo. Whereas something has a high albedo, well, then it reflects a lot. It's very white. So that's why I said a high albedo is like a nice little trick. High albedo, very, very bright. It reflects lots. So remember that question I asked, said, like, what would happen then, if global warming continues and all the glaciers melted? Try to think what would happen to the albedo. If the glaciers melted, wouldn't we lose a lot of the glaciers? And glaciers reflect. So that means then the albedo would go down. And what would happen then if the albedo goes down? Of course, that means we're absorbing more light. That means actually the temperature would even increase even more. So it's like these glaciers melting on Earth would actually make the temperature go up even faster. So this could be kind of bad. You could also talk about how you could change the temperature of the Earth. I mean, I saw some calculations done by a brilliant physicist. He had actually said, you could actually really help with global warming if you just painted everything on Earth, black or white. So just think about it. If you painted everything white, you'd reflect more light. That means you would raise the albedo, which means you would lower the temperature on Earth. So imagine if you had paint and you painted all the rooftops in the Earth white, for example. That would actually should make a change in our albedo of the Earth. So kind of amazing sort of ideas, especially when people are like, oh, how are we going to curb emissions, whatever. Like, if you just paint everything white, it would solve a lot of it. Well, what if all the roads were white and all the roofs were white? Turns out that would make a big difference. I don't know why people don't do it. I guess it's the cost of paint, but hey, we also want to live on Earth, right? So this is really important stuff. What I think is really interesting about high albedo is I was wondering, what is the highest albedo thing? And it turns out in our solar system, at least, Saturn's got one moon called Enceladus. And that one has an albedo of pretty much 1. It's 0.99. What that means then is that, and this is a real picture of it, isn't that amazing? So we've got, for example, light then that comes in, basically almost all of it will come back out again. So in other words, I in and I out, it's pretty much the same. In other words, it reflects pretty much everything and acts like a mirror. Which is really weird that it's so high because there's a lot of space dust out there. And you would think that if it's out there and it's sort of just going in orbit, it should be attracting lots of dust. I mean, all the other objects in the solar system seem to do that. So this tells us there must be some processes on this moon that are renewing the surface to sort of make it water again. In other words, to sort of clean off the dust or at least cover it with a layer of water, which then, of course, freezes. And if you look at its surface, you can see also it has very small number of craters. These impact craters also tell you something about the age. If you don't see many craters, that means it hasn't been hit by many things. That means the surface is relatively young. So that tells you that there are some processes at work on Enceladus that are actually renewing its surface. And the biggest, most obvious one is there is very likely a source of liquid H2O underneath the icy surface that, through these cracks and fissures in the ice, it's sort of seeping up and sort of basically covering things up, making like we do in Canada in the winter, right? You sort of, put a hose out in the snow, for example, then all that water will freeze and it makes ice and you can go skate on the ice. How Canadian is that? But that's what people really do. So we have that some sort of process like that happening on Enceladus, for example. So albedo itself, pretty important, but not that complicated. You just got to remember that's just I out over I in. And remember that high albedo is very bright and reflects a lot. So if you're asked for these sort of qualitative questions about what would happen, with glaciers, just think, what do glaciers do to the shininess of the Earth? Because, of course, that will affect the albedo, right? If you make things more shiny, you raise the albedo, that means actually the temperature on Earth would go down. So that would actually be helpful. But if the glaciers melt, bad news, because, of course, that would make the shininess of the Earth go down. That means we would actually absorb more, and that means the temperature would increase even more.